our next one is going to be avatar. We'll have a varchar of 200. So this is going to be another scenario where I think we're definitely going to fit into it doesn't matter if it exists. When a user first signs up to the application, you are not required to provide a profile image. And I'm talking about the real Instagram app. When you sign up to Instagram, you do not have to provide a profile image right away. So that's clearly a rule that, well, it is not required that you have an avatar. It doesn't matter if that value exists or not. Obviously, we would like for all users to have an avatar because it adds a little bit of identity to everyone using our platform. But at the end of the day, it is not required for you to provide an avatar. So we would not provide any constraint in this case. Okay, let's keep on going here. So we're going to have a phone. That's a varchar of 25. We're not going to put any constraint on the next three. I'll tell you why in just a second. So we got phone, email, that's going to be a varchar of 40, and password, we're going to make a varchar of 50. And then just really quickly, I'm going to throw in here a status as well of 15. Okay, so let's now take a look at phone, email, and password. We did not provide any kind of not null or default here, so why is that? Well, thinking back to that sign up page, we looked at a screenshot of it very briefly. You might recall that when you signed up, you had the option to sign up with either an email or a phone number. So we don't really want to put on any kind of not null constraints to either of these, because a user might sign up with an email and password combination and never enter a phone. If that were to happen and we had a not null constraint on phone, that user would not be able to sign up because they signed up with an email and password, but we're saying you must provide a phone number. So in this case, we might not want to put on a not null to any of these. What we could do instead is make sure that at least either phone or email is defined. That could be effective. We could say, you know what, if you're going to sign up, you can do it with either a phone or an email, but out of the two, you must at least provide one. Every user must have some kind of identifying or communication identifier tied to them. So to implement some kind of rule like that, we could put in a check constraint at the very bottom. So we might put in a check down here of something like coalesce phone email is not null. Now you might recall discussing the coalesce function. It sounds like it's really fancy. It is not. All it does is return the first argument that it's provided that is not null. So let's imagine a couple of different values of phone and email that we could provide. If we put in a value of null and null for both phone and email, so let's say that we tried to create a user without a phone or an email, then the result of coalesce would be null. Null does not satisfy the condition is not null, and so our check would fail, and we would not be able to insert a user with a null email and a null phone. If we added in a null phone, but a real email address, then the coalesce would result in the email address, and that would pass the check constraint. So that string right there is not null, and we're good to go. So this would be an effective little check to put in to make sure that either phone or email is provided. Now, that of course doesn't really also make sure that we provide a password. So we could do another nesting of coalesce in here. We could coalesce email and password together, essentially do another level here. It's up to you if you want to do that. Alternatively, we could just add in a second identical check on the next line down and say something like, hey, if you're going to provide an email, then you must also provide a password. And you just have to modify this a little bit to make sure that the phone is also taken into account. I'll leave that up to you if you want to try to add that in. Okay, so that looks good. And then finally, our status right here. So you might recall that we spoke about status very briefly. We said that a user can have a status of something like online, offline, busy, away, and so on. And we had said that although we might make that a varchar of 15 for right now, we might come back and pick out some more appropriate data type for it. We are still going to do that. We're going to do that in a future video. We're not going to worry about updating status right now. We are going to come back to this column and address it a little bit later. Okay, so that is it for our table of users. So I'm going to double check, make sure I've got all the commas on the ends of these lines except for that very last one. Once everything looks good, I'll go ahead and run this. And I've got a typo on varchar right there, much better. And there we go. I have now created my table. Fantastic. So if we go into our Instagram database, we can now expand schemas. We can expand public. We can expand tables. And there's our users table. Okay, so that's our first table. Now, I know it took us a long time to put this thing together. Don't worry, all the tables going forward, we're going to get through much, much more quickly. So let's pause right here and continue implementing the rest of our tables in just a moment. Let's get started on creating our post table. So once again, I'm at my query tool. We're going to enter create table posts. We'll start off with our ID. That's going to be of type serial, and we'll mark that as our primary key. We can then put in our created at column and say that's going to be of type timestamp with time zone. And we'll also provide a default value of the current timestamp. I'm then going to copy paste that line down. And the second one, I'm going to update the column name to updated at. Okay, so these are the three columns that we're going to have in a lot of different tables. So let's now add in some columns that are specific to posts. Our first post specific column is going to be the URL. So we're going to say that's a varchar length 200. And then we need to decide whether or not we want to apply a not null constraint to this or even a default value. Well, when we think about a post, the entire goal of a post is to show a photo to other users. So it doesn't really make any kind of sense to have a post without a URL. That means that 100% of the time, we really want a user to provide a URL, or essentially a photo, really, and we're going to turn it into a URL, but we really want a URL to tie to this post. So we're going to mark this URL column as not null. Okay, looks good. Next up is our caption. That's going to be a varchar 240. And then once again, we need to decide if we want to mark this as not null and so on. Well, whenever you make use of the Instagram application, you can absolutely create a post without entering any kind of description or caption associated with it. So without a doubt, a caption is optional. It does not have to be provided. It doesn't matter if it is provided or not. So we're not going to apply any kind of constraint to the caption column. Next up is our latitude of type real and longitude, or LNG, of type real. Now, just so you know, in the real world, in other words, if you look at a globe, valid values of latitudes go from -90 up to 90. So in other words, a valid latitude is between -90 and 90, and a valid longitude is between -180 and +180. Now, this is not valid syntax here. I'm just putting this in as a note to you personally. So these are valid values of latitudes and longitudes. Okay, I'm going to delete that because, again, not valid. Just want to show you how we can have a valid latitude and longitude. Now the question once again becomes, do we want to mark these as not null, default, or what? Well, if we think about providing a location, it is 100% not required when creating a post. When you create a post, you do not have to attach a location to it at all. And even in today's day and age, location privacy is actually a pretty big deal. And so Instagram probably does not want to ever require you to put in a latitude or longitude attached to a post. We should probably not put in any kind of latitude or longitude here, or any kind of not null requirement. However, we still might want to think a little bit about validation. So in other words, if a latitude and longitude are provided, we might want to make sure that we don't get a latitude of something like 500,000 or something like that. So this really begs the question, which we've gone over once before earlier on in the course, about validation and whether we should handle it inside of our database or maybe at some kind of application server level. So we had this discussion once before, and we came up with some of the following rules. Regarding validation at the database versus application level, we had said that if our rules around validating the value are going to ever change frequently, then we were not going to handle that validation in the database, and instead we would handle it at the application level, where it's a lot easier to change validation rules rather quickly. We also said that if our rules for doing the validation are complex, we would handle that at the application level. Finally, we said that if we ever just want to make sure that we've got the right type of value, or the right domain or range of value, then placing that in the database would be a pretty good idea. A good example of this was the users table we worked on just a moment ago. Remember, one rule of our users table was that either an email or a phone number had to be provided. So that was an example of making sure that we had the right type of data between those two columns. Those two columns could contain values of null, but between the two of them, one of them had to be a string. In this case, with latitude and longitude, we really might want to add in some validation to make sure that we have the correct domain or range of value. we want to make sure that the latitude is between -90 and 90, and that the longitude is between -180 and 180. So in this case, we might want to add in a check and say, you don't have to provide a latitude and longitude, but if you do, here are the values it must satisfy. And that's exactly what we're going to do. So we're going to add in a check here. We're going to say that lat is null. So if you're going to give us a latitude value that's of null, that's totally fine. If you're not going to give us anything for lat, totally fine. But, or in other words, or, if you do give us a latitude, then it must satisfy the following constraint. It must be greater than or equal to -90, and it must be less than or equal to 90. So again, this entire check right here is going to say if you give us no latitude, if the value of latitude is null, totally fine, that will satisfy our check. But if you do give us a latitude, it must satisfy this constraint right here. So now we can repeat that same style down for longitude. So I'll do a check, lng is null, or lng is greater than or equal to -180, and lng is less than or equal to 180. Really quick, I would encourage you to make sure that you have lat, 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 and lat, and then lng, 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 and lng. If you mix and match lat and long between these two lines, you're definitely going to end up with some nasty errors. Okay, so that looks good. So now our last column here, the user ID column, which we're going to use to relate a user to a post. We'll put in our user ID. We're going to say that it has to be an integer. Now, when we think about whether or not we have to have a user ID here, without a doubt, we want to associate a user with a post at all times. We don't really want to have any idea of a post that is orphaned or doesn't have a user associated with it. So in this case, we want to always make sure that we store the user who created a post, which means that we probably want to provide the not null constraint on this. So after integer, we'll put in not null. Then in addition to that, remember user ID is a foreign key column. And to set up a foreign key column, we're going to put in references, making sure we get references spelt correctly right there. We then put in the name of the table that we want to reference, and then inside of parentheses, the ID, or the column specifically. In this case, it is ID. That's going to set up our foreign key constraint, and make sure that whenever we add a post, we are going to provide a user ID that actually exists. One other thing we might want to put in when we set up this foreign key column, remember we spoke about on-delete constraints. On-delete constraints means that if we ever delete the user who is associated with a given post, we would delete that associated post. So in other words, if we have a user ID value of 5 and that user gets deleted, we would go and find all the different posts automatically with a user ID of 5 and delete those posts, just to make sure that we don't have any orphaned posts, so to speak. So we can set that up by putting in on-delete cascade. So again, if we delete the associated user, find all the related posts, and delete them automatically. Okay, so this looks pretty good. I'm going to run this. Looks good. Table has been created. Okay, so that's it for creating our post table. So pause right here, move on to our next table in just a moment. Let's take a look at our comments table very quickly here. So I know the last two videos very long. Don't worry, we're going to speed things up quite a bit. So in this case, we're going to create our comments table. So I'll do a create table comments. Once again, ID, serial, primary, key, are created at column of time stamp with time zone. We'll give a default of current time stamp. Copy that line down, update it to updated at, and now we could take a look at some of our comment specific stuff. The first is our contents column, the actual text of the comment itself. We're going to limit the length of this to 240 characters. And if you're creating a comment, you better give us some contents. It doesn't make any sense to create a comment without any contents or text associated with whatsoever. So we're definitely going to mark this as not null. We can then set up our two foreign key columns of user ID and post ID. The first off is user ID. Must be an integer. You must associate this with a user. So every comment must have a user that the comment belongs to. We're then going to be referencing something on the users table, specifically the ID column. If a user ever gets deleted, we're then going to delete all their associated comments. We'll set up an on-delete cascade. After that, we'll also take a look at the post ID foreign key column. So this is the post that the comment is associated with. It's going to have just about the exact same configuration. So it's going to be of type integer. It must be associated with a post at all times. It's going to be referencing something on the post table, specifically the ID column. And again, if a post gets deleted, we're going to delete all the comments associated with it, because there's no way that we would ever make use of these comments in any other way once the post is deleted. We'll do an on-delete cascade. And that's it for comments. Okay, let's run that. Looks good. Okay, so that's it for comments. We're going to take a pause here, and then in the next video, we're going to do 1 or 2 or 3 tables. In this video, we're going to try to knock out the definition of 2 or 3 different tables. So let's just jump right in. We're going to first create a table for our likes resource. So we're going to have, as usual, an ID column that's of type serial, and we're going to mark it as our primary key. Next up, we'll do a created at column. That'll be of type timestamp with time zone, and we'll give it a default value of current timestamp. Next up, a like is always going to be owned or essentially reference a user. So we're going to have a user ID foreign key column. We'll put in user ID, integer, not null, references, user's ID. And if we ever delete this particular user, then we want to delete all that user's likes. We're going to say if that user gets deleted, then we want to cascade the delete and delete all the associated likes. And again, we set that up with a on-delete cascade like so. Now notice that on the user ID foreign key column, we did add in not null. That's going to make sure that every like is always going to reference a user. Okay, next up, you'll recall that our likes table is functioning with a polymorphic association. That means that a like is going to point at either a post or a comment. In this particular case, to implement this, we have 2 different columns, post ID and comment ID. These are both foreign key columns that are going to point at either a post or a comment. And at any given time, only post or comment should be defined. So we'll do a post ID foreign key column. So it'll be an integer. We are not going to put in the not null statement. So we're going to go straight to references, posts, ID, and again, on delete cascade. So if we delete that post, we're going to delete all of its associated likes. We'll also do our comment ID, integer. We're going to again skip the not null and say references, comments ID, on delete cascade. Okay, so why do we skip the not null in both these cases? Well, again, at any given time, only post ID or comment ID is going to be defined. One of these is going to be null. So if we put in not null, that would ensure that both these values have to be defined. Definitely not what we want. So we want to allow one of them to be undefined. And you might recall when we first discussed this style of association, we saw on a diagram back then that there is a certain kind of little trick we can use inside of a check statement to make sure that at least either post ID or comment ID is defined. Only one of the 2. So we're going to write out that check statement right here. We're going to write out the entire thing in its entirety, and then we'll discuss exactly what it's doing, because we didn't talk about it too much when we originally spoke about it. We're going to add in a check. Come on, there we go. And then we're going to do a coalesce. I'm then going to put in 2 sets of parentheses. In the inner set, I'll do a post underscore ID. And then outside of those first set of parentheses, or the inner set, I'll do colon, colon, Boolean, colon, colon, integer, comma, 0. Then on the next line down, I'll put a plus. And then on the next line down after that, I'm going to copy the first coalesce, put it right there, and then change post ID to comment ID, like so. And then finally, I'm going to say that the result of adding that statement and that statement together should be equal to 1. That is our check. So let's very quickly discuss exactly what this check right here does. Remember, our goal is to have either post ID or comment ID defined, and the other should have a value of null. So let's imagine a scenario where post ID is null and comment ID is like 829,000 or something like that. So how would this entire expression be evaluated? Well, first thing to remember is that coalesce sounds like a really fancy function, but it's very simple in nature. All it does is take a list of arguments and give us back the first argument that is not null. That's all it does. So now we can start to think about the value of the arguments inside of here. With null : Boolean, we are trying to turn the value null into a Boolean value. If you try to turn null into a Boolean value, the result is still just null. If you then try to turn null into an integer, the result is still just null. So then the coalesce is going to take a look at the two arguments it's been provided, and it's going to return the first non-null value, which in this case is 0. That entire function right there condenses down to just 0. Next up is the coalesce down here. The first thing that gets evaluated, we're going to try to coerce 829,000 into a Boolean. That's going to turn into a value of true. If you then try to turn a Boolean value of true into an integer, you get back 1. And then coalesce, once again, is going to give us the first non-null argument, which in this case will be 1. So then we'll have 0 plus 1 results in 1. 1 equals 1, that is a truthy comparison, and so we pass the entire check. And that's it. Yeah, I'm going to undo all those. And now I'm back to what we had when we started. Now, in addition to the check, we're going to add in one other option to this table. Remember, we want a user to only have one unique like on any given post or any given comment. We should never allow them to like a post or a comment multiple times. So to enforce that, we're going to add in a uniqueness constraint over the columns of user ID, post ID, and comment ID, all three of them together. So at the very bottom, after the check, make sure you got a comma after the check right there. We'll put in unique user ID, post ID, comment ID. So remember, we can imagine that this will concatenate together all these different values and make sure that the result is unique across the entire table, all the different rows. So this uniqueness constraint right here is going to make sure that a user can only ever like a post or a comment one single time. Okay, so that looks good. Let's run this. All right, create table successful. And unfortunately, we are already at 6 minutes in, even though I said I wanted to get through a couple of different tables. Well, that's just the way it goes. Let's take a quick pause right here and then try to get through more tables in the next video. Next up is our photo tags table. Let's just jump right in. So we'll do a create table, photo tags. We'll throw in the ID of type serial, mark it as our primary key. We'll then put in our created at timestamp with time zone, default, current timestamp. I'm then going to copy paste that line down and update it to updated at instead. Okay, so remember, the goal of a photo tag is to relate a user who was essentially tagged inside of a photo to a particular post. So we're going to have a foreign key that's going to look at a user ID and a foreign key that's going to look at a post ID as well. So first off, we'll take care of the user. I'll do a user ID, integer, not null, because we always want to make sure that we are actually referencing a user that exists. We'll then do a references users ID, and as usual, on delete cascade. We'll also do a post ID that's going to be an integer. It should always not be null because we always want to refer to a post that actually exists. We're going to be referencing something on the post table, and again, on delete cascade. Now, in addition to tagging a user inside of a photo, we also decided that we wanted to store the XY coordinates of that position as well. So we wanted to make sure that we could point to some very particular place on the photo where the given user is actually mentioned. So we stored those coordinates as a X and Y column. We'll put in an X, lowercase, that will be of type integer, and a Y, that will be an integer as well. Now, in both these cases, we definitely want to make sure that if a user is tagged inside of a photo, they are tagged at a very specific place in that photo. So we always want to make sure that the X and Y values are provided. So I'm going to add in not null to both of these. All right, now the very last thing. Chances are we only want a user to be able to be mentioned inside of a photo exactly one time, rather than having a user mentioned like 20 times inside of one photo. Now, this is kind of something that you might not care to do. Maybe you want someone to be able to be mentioned multiple times in a photo, but personally, I think it makes a lot of sense to say a user can only be mentioned one time inside of any unique photo. So if you agree with me, we can add on a uniqueness constraint and make sure that the combination of user ID and post ID are always unique. We can add in at the very last line, unique, user ID, post ID, like so. Okay, so that looks good. Let's go ahead and create that table. Looks like I got a typo there. 2 typos, as a matter of fact. That's better. Okay, that's better. Create table, good to go. Now, before we delete this, let's go ahead and take care of our caption tags table as well. Remember, caption tags was all about tying a post caption, so the text describing a post, to a user who is actually mentioned inside of it. So we're just going to change a couple of values here. I'm going to change the name of the table to caption tags. We can leave the ID column the same. We can leave created at the same. But in the case of updated at, there's not really any idea of updating a mention inside of a caption. Either the caption mentions a user or it doesn't. That's pretty much it. We only had updated at for the photo tags because in theory, a user could kind of drag around or reposition a tag inside of a photo. But in the case of caption tags, nope, not really any such thing. So we're going to remove the updated at column. We still want the user ID that has been mentioned, and we still want to point out to the post that they were mentioned in. However, there's not going to be any coordinates here anymore. There's no coordinates inside the caption or anything like that, so we do not need those columns. And then lastly, I'm going to assume that we can only mention a user exactly one time. Maybe a user can actually be kind of mentioned in the caption with text multiple times, like we could write out at so-and-so, at so-and-so, at so-and-so multiple times, but I think that that should probably only result in one discrete mention being sent over to that user. Otherwise, if we think about mentioning some other user and that actually generating some kind of notification, I would not want mentioning one single user like 20 times inside of a post to result in 20 different notifications being sent to that target user that says, hey, you got mentioned, you got mentioned, you got mentioned. That'd be a little bit crazy. So I'm going to say that even though you can technically mention a user multiple times inside of a caption, we're only going to kind of reference that fact inside the database one single time. So we are going to leave on that uniqueness constraint. Okay, so table caption tags, ID serial, created at, user ID, post ID. Yeah, everything looks good to me. Let's go ahead and create it. And I got another typo here. There. Every now and then, it gets a little bit funky. You got to run the thing twice. Looks like the table was created successfully. Okay, so that's looking good. Now we've got 3 tables left. Let's take care of all 3 of those in the next video. Let's wrap up our table creation in this video. We're going to create tables for hashtags, posts, and followers. So first off, table for hashtags. I'll do a create table, hashtags, throw in our ID, and a created at timestamp. Now in this case, I think that having a created at only is sufficient for a hashtag. There's really no update that we're ever going to make to a hashtag. It either exists or it doesn't. So created at alone is probably good enough. Then we're going to have our title column. We'll say that any given hashtag can only be 20 characters long. We're going to say that the title must always be provided, not optional, has to be provided. This title column is the entire purpose of a hashtag. It gives us some text that says, hey, this is a hashtag for the word happy or happy birthday or whatever else. We're also going to say that the title has to be unique. So the entire goal of this table is to just list out a unique list of all the different hashtags that have been used inside of our application. So I'm going to apply unique on there as well. And that's it for hashtags. So I'm going to run this. Yep, looks good. I'm then going to reuse this same stuff right here, and we're going to update it to create the hashtags posts table. Remember, the goal of this table is to state which posts are making use of which hashtags. So I'm going to update the name of the table to hashtags, so still plural, underscore posts. We then still want to have the ID, but we do not need a created at timestamp. And remember, the reason for that was that we said that the post itself has a created at timestamp on it, and we're just going to assume that that is when the post originally used the hashtag. Technically not true, because we could update a post, and the update could contain some use of the hashtag where it did not previously, but it's a good enough assumption for right now. So I'm going to delete created at, and we also do not need title. So after ID right there, we'll throw in our foreign key column that's going to point at the hashtag that was used inside the post. We'll do a hashtag ID, integer, not null, because we always want to point at a very specific hashtag. We're going to be referencing the hashtags table that we just created, and specifically the ID column. And then as usual, if for any reason whatsoever, we decide to manually delete a hashtag, maybe it's some kind of offensive hashtag, then we're going to want to delete automatically all the posts, or excuse me, all the relations here as well. So we'll do an on delete cascade. We'll then also reference the post, so post ID integer, not null, references post ID. And again, if we delete some given post, we want to remove the record that that post had ever used a hashtag as well. So on delete cascade. And then finally, we probably want to say that a post can use a hashtag multiple times, but very much like those tags we were just discussing a moment ago, like those mentions, even though a post can use a hashtag multiple times, we probably only want to store one record, even given those multiple mentions of it. So we're going to also place a uniqueness constraint on hashtag ID with the combination of post ID. So unique, hashtag ID, and post ID. And that's it. We'll run that. Looks good. Now finally, last table, our followers table. I'm going to start off from scratch this time around because we didn't really save that too much time the last time. So I'll do a create table followers. We'll do our ID, created at, come on, stamp, there we go, with time zone, default, current, time stamp. Then we're going to have two columns inside of here. One is going to point at the user who's being followed. The other is going to point at the follower. So the user who is being followed will be our leader ID. Make that an integer, not null. So we always have to designate some actual existing user that we are trying to follow. We're going to be referencing our users table, specifically the ID column. And as usual, if we delete that user, we want to delete the record of them being followed as well. So on, delete, cascade. We'll also do our follower ID, so exact same settings. And then finally, we probably want to make sure that any given user can only follow another particular user exactly one time. So you can't follow some specific person like 5 times in a row. So to enforce that, we're going to add in another uniqueness constraint and make sure that the combination of leader ID and follower ID is unique. So we'll do a unique leader ID, follower ID. And that's it. All right, let's run this. And that's it. That's the last of our tables. Well, it took a long time to get here, but we've finally got a bunch of tables inside of our database. So to just verify that all these tables were actually created, I'm going to take a look at my Instagram database again, schemas, and then public. I'm going to go down to tables and refresh it. And then I should see our 9 different tables inside there. Looks good. So now all we have to do is start to insert a bunch of kind of fake data into these different tables. Then we're going to start to write out a bunch of different queries and understand some interesting stuff around optimizations and some advanced features in Postgres that you can only really start to dive into when we've got a good number of tables to work with. So quick pause right here, and we're going to start to get some data into these tables in the next video. We've now got the structure of our Instagram database all put together, but right now there's no data inside this database. In this video, we're going to throw a ton of data into that database, and then we'll start to explore some more advanced features of Postgres. Let's get to it. Let's get some data inside there. In the lecture right before this one, hopefully you downloaded that ig.sql file. If you did not download that file, then pause this video right now, go back to that previous lecture, just the one right before this one, and download that file. This is a database backup file. It has a tremendous number of users, posts, comments, likes, and so on inside of it. We're going to take all the data out of that database backup file and put it into our Instagram database. Let me show you exactly how to do that. Once you've downloaded that file, we're going to go back over to pgadmin. We will find our Instagram database that we just created, right-click on it, and then click on Restore. We'll then see a little window like this pop up. The first thing we're going to do is find the file name section right here, go to the far right-hand side, and click on the ... In the window that appears, make sure you find the drop-down for Format on the bottom right-hand side, and we'll change it from Format of Backup to Format All Files. Then go ahead and find wherever you downloaded that ig.sql file to. I've got it right here inside my downloads directory. I'm going to select the file, and then click on the Select button on the right-hand side. Now don't click on Restore just yet. There are a couple of restore options we need to change. On the little window or the tab up here at the very top left-hand side, I'm going to click on Restore Options, and you'll see a lot of different settings inside of here. Most of these settings by default are set to No, but there are one or two at the very bottom that are set to Yes. We are going to enable 4 other options inside of here. Let me show you the 4 options we're going to change. First, inside the Type of Object section, I'm going to change Only Data to Yes. In the Do Not Save section, I'm going to change Owner to Yes. Inside the Query section, I'm going to change Single Transaction to Yes. And then finally, in the Disable section, I'm going to change Trigger to Yes. So in total, there are now 5 options in here that are set to Yes. We've got Only Data, Owner, Single Transaction, Trigger, and verbose messages. Once you've got all those same settings, then we'll go ahead and click on Restore on the bottom right-hand corner. We'll then get a little pop-up right here that's telling us the process of restoring this backup. Now for me, restoring this backup is only going to take a handful of seconds. I have a very modern computer, however, so if you are using an older laptop or older desktop, it might take you longer than it does for me. So it took me 14 seconds to restore all the data inside of here, but it might easily take you up to 1 to 3 minutes, depending upon how old your laptop is. Just go ahead and let it do its thing. After you see the successfully completed box down here, all the data should be stuck inside of our new Instagram database. We can now right-click on Instagram, open up the query tool once again, and then as a quick little test, let's print out the number of users that are now inside of our users table. So for that, we could do a simple select count star from users. I'll then run that query, and we'll see that we've got 5,345 users. Let's do the same thing for likes. I'll do a select count from likes, and you'll see that, one more time, there we go. We've got 752,000 likes, so almost a million. So there's a lot of data inside this database, and it's going to be very clear very quickly that we're going to have to learn a little bit more about the performance aspects of Postgres to write queries that actually resolve in some reasonable amount of time. Okay, so now that we've got all of our data inside of here, quick pause right here and continue in just a moment. In the coming videos and sections, we're going to start to make a lot of changes to our Instagram database, specifically to the structure of the database and some of the data inside of it as well. As you start to go through all these different steps, it is entirely possible that you might accidentally make a mistake. Maybe you're going to accidentally delete some table or accidentally delete some column or something like that. In this video, I want to show you what to do if you ever accidentally start to kind of mess up the structure of the Instagram database. So chances are you do not need to watch this video right now. Only watch this video if in some coming video you accidentally make a bad change to the database and want to kind of revert back to an earlier state. So again, you probably don't need to watch this right now. Instead, just remember that this video exists and that you can come back and refer to it in the future if you need to. Okay, so let's assume that maybe you accidentally just deleted a column or a table or whatever else, and you want to get back to some more starting state. Let me show you exactly what to do. the first thing we're going to do is close down all the open query tool windows. So right now we are looking at a query tool window. So I'm going to make sure I select that window on the top right-hand side, and then click on the X at the very top right. I'm then going to repeat that process for any other open query tool windows that I have. Once you've done that, we're then going to click on the Instagram database, then click on Dashboard. On this dashboard, we're going to scroll down to the very bottom, and we're going to make sure that we only see exactly one entry in this little table down here at the very bottom. Something that says something like pgadmin4 db Instagram. If you see any other rows on here, then click the X to the very left-hand side of that row. Now, the one that you have right here is totally fine. You don't need to click the X on that. It's only if you have any additional rows. Once you've closed out all those other sessions, we're then going to right-click on Instagram, and then click on Delete/Drop. That is going to completely drop or delete the Instagram database. So we'll then click on Yes. Okay, so now we're going to recreate that Instagram database and restore some data back into it from that same ig.sql file that we just made use of. So I'm going to right-click on Databases. I'll go to Create Database. I'll create another database called Instagram once again, and click on Save. We'll then right-click on the new Instagram database that we just recreated and click on Restore. Once again, we're going to click on the ... change the format dropdown to All Files, select the IGSQL file, and click on the Select button. And then once again, we're not going to click on that Restore button just yet. Instead, we're going to go to the Restore Options tab, and we're going to change some of the settings here. Now, the settings that we're going to change this time around are different than what you saw in the previous video, where we initially restored or put some data into the database. So this time around, we're only going to check 3 different options, as opposed to the 4 that we did previously. So this time around, we're going to enable Do Not Save Section Owner. We'll do the same for Queries Single Transaction, and then Disable Trigger. And then once again, we've got verbose messages on by default. That's totally fine. And then very importantly, we're going to make sure that nothing inside of Type of Objects is enabled. Okay, so once we've got those settings put together, we'll go ahead and click on Restore. All right, there we go. So once again, we're going to wait some number of seconds. Depending upon how old your laptop is or desktop is, this might take all the way up to a minute or 2. Eventually, we'll see Successfully Completed. And now if we open up a query tool once again inside of Instagram, we can once again do a select count star from users. And if we run that, we should see about 5,345. And that's it. That's how we are going to restore our database if you ever get stuck at some point in time in the coming videos. Okay, so now we've got this put together. Back on topic, let's start to take a look at some advanced features inside of Postgres. We have spent a lot of time designing our database, and now we've actually got some data inside of it. As I mentioned, we're going to start to take a look at some advanced features of Postgres, specifically some things around performance and whatnot. But before we do, I want to just get a little bit more familiar with the data set that we are working with. So in this video and the next couple, we're going to go through a couple of very fast little exercises. I'm going to give you a couple of queries for you to write. You're going to go ahead and write them, and we'll take a look at a solution together. If you don't want to do any more exercises, if you just want to learn about some more advanced topics, that is totally fine. Just skip to the end of this section and go on to the next one. Otherwise, stick around. Like I said, we're going to go over a couple of quick exercises. So here's the first one. We'll start off fairly straightforward. In this exercise, we're going to try to select the last 3 users from our users table, or put another way, the 3 users with the highest IDs. So if this is my users table, and you'll notice I'm not showing all the columns just for clarity's sake, then I would want to get users with IDs 4, 5, and 6 because they have the highest IDs. Now, if you think you've got a good idea of how to solve this, go ahead, pause the video, go for a solution, and come back to the next one. We'll go through a solution together. Otherwise, if you want a little hint, I'm going to show you one right now. Okay, so here's just a little hint. We could try to reorder the table based upon the values inside that ID column. So we could do a sorting with a order by keyword. You might recall that one. And then we could use the limit keyword to just get the first 3 records, the first 3 rows, after we do that sorting process. So just a little hint. Okay, so go ahead and give it a shot. We'll go over our solution together in just a moment. Let's take a look at a quick solution. All right, so back inside of pgadmin, I've opened up my query tool. If you've closed yours, remember you can always open it back up by right-clicking on our Instagram database and then clicking on Query Tool. So our goal here is to select the users with the highest 3 IDs. I'm going to first begin by selecting all columns from the users table, and then we'll put on some kind of qualifiers or sorting logic. So I'm going to try to order by the ID column, and I want to order by descending order. That means that my highest IDs are going to be at the very top. By default, all the IDs in here are sorted by ascending order, which means we go from 1 to 2 to 3 to 4 and so on. If we do descending, that means we're going to start at the very highest and count down. So we can then do a limit 3, and that's going to make sure that we get just the first 3 rows. So if I run that, I'll see the users with the highest 3 IDs. And you'll notice they are counting down, so 5345, 44, and 43, and so on. Okay, nice little warm-up. Let's take a look at another little bit more advanced problem in the next video. Another quick exercise. So in this one, we're going to join together our users and post table. I want to focus on user with ID 200, so in this case, James 80. I want to find all the different posts that they have created, and specifically, I want to only see the caption of those posts. So for this, we're definitely going to have to do a join, and then we only want to see user with 200, and specifically the posts that they have created. So that would be that post right there, and that post right there, and then only see the caption of those 2 posts. So go ahead and give this a shot. If you want, I'll show you a hint here. So here's the hint. So we can probably do this join based upon the users table ID column and match that up with the post table user ID column. To make sure that we then only see posts tied to user with ID 200, we can either do a where and find where the user's ID is equal to 200 or where the post's user ID value is equal to 200. So a where on either column would work out just fine. Go ahead and give this a shot, and as usual, quick solution in just a moment. Let's take a look at a quick solution. Back over in pgadmin, I'll first start off by doing a select star, and I'll start from users. I then know that I want to do a join with my post table. So I will join posts, and I need to specify my join criteria. So in this case, I want to make sure that I find all the posts and match them up to users based upon where the post's user ID is equal to users.id. I'm going to run this as it stands right now and just make sure that the join itself works. Yep, looks like it ran successfully. And although I can't quite verify that this data is actually accurate or anything like that, well, it kind of looks like more or less, yeah, it's probably right. Now we want to make sure that we only see posts related to user with ID 200. So as I mentioned in the little hint, we can either do a where users.id equals 200, or alternatively, we can do a posts.userid equals 200. Either one is totally fine. If I go with a posts user ID, I'll then see only the user 200 and then posts created by them over here on the far right hand side. So here is the posts that they have created that have been joined into the same row. And there's the caption for all 3 of the posts that this user has made. Now in the original directions, I had said, I only want to see this person's username and the caption. So we should then update the star right there and probably take it to username, comma, caption. So I'll run that. There we go. Now just to double check, I'm going to make sure that we could do that kind of alternate where with a users.id equal 200. And yep, that definitely gives us an identical result. All right, so this looks pretty good. Pause right here. Move on to another exercise in the next video. Let's take a look at one last exercise. In this one, we're going to show each username, so essentially each unique username that we have, and then right next to it, we're going to show the number of likes that that particular user created. As usual, I'll show you a hint here really quick. So here it comes. One way that you could solve this is by joining together the users table and the likes table. Your join criteria would be the user's ID column and the likes user ID column. We could then do a grouping operation based on the username column on users. And then once we do that group, we can then use that count star or even count ID, or essentially count star would be appropriate here, and use that to count the number of rows in each unique group. So go ahead and give this a shot. We'll take a look at a solution in just a moment. Solution for the last little exercise. Let's get to it. All right, so we definitely know that we need a select. I'm not quite sure what values we want to select just yet, so I'm going to leave that empty for now. I'm going to select my users table, and I'm going to join the likes table. And my joining criteria will be likes.userid equal to users.id. So that's going to give us all the different users, join in likes on it. Now we need to do some kind of grouping operation. So I'm going to group by username. So that's going to take a look at all the different unique usernames that we have, set up groups for each one, and now we could do a count for the number of rows that got placed into each of those groups. So at the very top, I'll now do a select of username, and then the number of rows in each of those individual groups. All right, so let's run this, and there we go. You'll notice that the average count for each of these is hovering kind of around 145 or 150 or so. Inside of our data set, we've got about 750,000 unique likes and about 5,000 users or so. And all the likes are evenly distributed among those users. So if we take the 750,000 likes, divide by 5,000 users, on average, each user has about 150 likes. So it looks like my count right here is pretty much matching up with what I would expect. Okay, so that looks good. Well, now we've got a couple of little exercises under our belt to just be more familiar with this data set. Let's start to move on to our first advanced topic in the next video. I am really excited about this section because we're going to start to dive into some really advanced stuff, and this is where we really get into the world of Postgres as opposed to just really SQL by itself. So in this section, we're going to be talking about performance. So a couple quick notes on performance in general. I could give you some quick tips on performance. I could tell you, oh yeah, do XYZ, do this, do that, give you like a little checklist to go through. And that might work to some degree, but at the end of the day, if you want to really have some good performance inside your database, you have to understand what Postgres is actually doing. You have to understand how information is being stored on a hard disk, how it gets accessed, and different tools that we have, and how those tools precisely work to really understand the performance of your database. So this section is not really about performance so much as it is about the internals of Postgres itself. We're going to start to understand how data is actually stored on a hard drive and accessed. We're going to take a look at something called indexes. We're going to understand the internals of indexes and how they are used, how they improve data access performance. And then we're going to start to put those two things together to really understand how queries are interpreted by the database and how they actually get executed. Now, as we start to go through these videos, I'm going to tell you right now, some of these videos are going to be extremely deep in detail. We're going to go as deep as looking at how the information is stored by the database on the hard drive in terms of binary code. So like the actual ones and zeros. So we're going to go to a very, very deep, very low level. And because of that, some of these videos might be really long, they might be a little bit confusing, and they definitely might be boring. So if at any point in time in this section, if you get confused or bored, totally fine. Just pause the video, move on to the next section, and if you want to, at the end of the course, come back to this section where maybe some stuff will make a little bit more sense. All right, so with all that in mind, we're going to take a quick pause right here and start to take a look at the internals of Postgres in the next video. In this video, we're going to take a look at where Postgres stores information on your hard disk. To do so, we're going to first open up our query tool, and we're going to run a very small command here. So just show data underscore directory. We have not seen the show keyword before. We make use of show anytime that we want to pull one individual configuration option out of our Postgres database. I'm going to run that, and then I'll see the result is a path. So this is the folder or the directory on my personal computer where Postgres is currently installed and running from. I want to try opening up this directory inside of a folder explorer and taking a look at all the different files and folders that make up the Postgres database. In particular, I want to try to find Instagram or our Instagram database inside there and find where all the data for that database is stored. So I would encourage you to pause this video right now, open up a folder explorer and navigate to that exact directory. So I went ahead and did so ahead of time just to save a little bit of time. So here's that directory that was just printed out inside of pgadmin. Once you get here, you're going to see a lot of different kind of mysterious looking files and folders. Right now, I want to just focus on understanding where all the data for our Instagram database is actually stored. All the data for all of our different databases get placed inside of the base directory. So I'm going to open up that base folder. And then inside of here, we'll see a collection of different folders, each with a number assigned to them. Each of these different folders contain all the data for a different database running on our local machine. We can understand or figure out what each of these different identifiers or numbers relate to by running another query back inside of pgadmin. So back inside of pgadmin, I'm going to run a different query here. We're going to do a select OID, dat name. And notice that this is DAT name, not data name, from pg_database. That will then list out the name of all the different databases inside of our Postgres installation and an internal identifier that is being used for each one. Now you'll notice that some of these different databases, the names of them look very familiar. For example, validation, that was a database you and I created. Instagram, of course, is another database we created. But you might also see something called template 0 and template 1. We're not going to worry about what those are for right now. We'll discuss what they're being used for a little bit later. So we can find our Instagram database, and it looks like the internal identifier for that database is 22442. Now, if you have a different ID right here, that is totally fine. You should see inside of this base directory a folder with that same identifier. So for me, there is 22442 right there. So I'm going to open up that directory, and inside of here, I'm going to immediately see a ton of different files. So all the files you see right here, these represent the raw data inside of our database. Now, when we look at this, it kind of looks like there are too many files for them to represent the individual tables that we have, and it looks like there's too few for it to be like maybe one file for every row in every table. So what do these files actually mean? What is stored inside of each one? Well, we can print up what each of these different files are being used for by running another query back inside of pgadmin. So back over here, I'm going to replace this with a select star from pg_class. I'll run that, and then we're going to see a really big listing come up here. So each of these different rows contains information about one of those different files that we're taking a look at. Each file, in turn, represents one individual object inside of our database. The objects we have inside of our database are not just tables. We also have objects to refer to things that are called indexes or sequences, primary keys, and a couple of other things as well. Right now, let's just try to find how about our users table is actually stored. So I can take a look at the rel name column, and I'm going to find a row called users. So this row right here represents our users table. The internal identifier that is being used for the users table is 22445. So we can go back over to that directory we were just taking a look at and find a file inside of here with an ID of 22445. And once again, you might have a slightly different ID than I do. If you do, that is totally fine. So here's a file called 22445 right there. So that file, in theory, contains all of the data for my entire users table. We can also take a look at, say, posts. For me, that is the next row down. Looks like that one has an identifier of 22459. So here's 22459 right here. That file contains all the data for our posts table. Okay, so at this point in time, we've established that inside of your hard disk somewhere, Postgres is storing all the information tied to one individual database inside of one folder. That's the folder that we're looking at right now. And inside of that directory are a ton of different files, and each of these different files represent one different thing inside the database. An example of an individual thing is a table. And so we identified two files that store all the data related to our users table and our post table. So now that we've gotten this far, let's take a pause right here and then go a little bit deeper in the next video. I have now identified file 2245 as being the file that contains all the information about my users table. So we're now going to start to investigate how information is actually stored inside that file and get a better idea of how it eventually gets accessed as well. To start to investigate that file, we do have to understand a couple of different pieces of terminology. Some of these different terms are going to sound a little bit scary, but at the end of the day, they're all referring to things that you really already understand. So our first piece of terminology is heap or heap file. This is a file that contains all the data related to one particular table. So in our case, or I should say in my case in particular, because your ID right here might be slightly different, file 22445 is a heap file. It contains all the information related to my users table. File 22459 is also a heap file. It contains all the information related to my post table. Now, if you've ever studied data structures before, you might be familiar with a data structure called a heap. A heap data structure is very different than a heap file. So we don't really want to be thinking about a heap data structure at all when we're thinking about these heap file things. If you are not familiar with a heap data structure, that is totally fine as well, because again, it's not really relevant in this case. All right, our next term is tuple or tuple. You can pronounce it either way, or item. So tuple, tuple, item, they are all referring to the same thing. These are referring to individual rows from one particular table. And then finally, we've got a block or a page. Again, block or page referring to the exact same thing. A single heap file is divided into many different blocks or pages. And then inside of each block or page, we have many different tuples, items, rows. Now, because these different terms have a lot of different kind of like alternate ways of referring to them, I would just want to show you a quick little diagram to help you understand how these different terms are really related together. All right, so here is a diagram of file 22445. The entire file itself is referred to as the heap or heap file. The file is subdivided into many different blocks or pages. And then each block or page stores some number of tuples, items, rows. Each block or page can store no items, so like no users whatsoever, or it can store many different items, and anywhere in between. By default, each of these blocks or pages are 8 kilobytes in size. So we might have one block right here. Regardless of how many items are inside of it, it is always 8 kilobytes large. The next one, regardless of how many items are stored inside of it, it is always 8 kilobytes large. Now at this point in time, we kind of have an idea of what a heap file is. Okay, it stores some information. It is divided into a block or a page, and each block or page is 8 kilobytes large. But why? Why is anything like this? Why is each block 8 kilobytes large, regardless of how many items are inside of it? Why are there blocks at all? Why don't we just store some number of users inside of here? Well, these are some really important questions, and they're going to help us start to narrow down to one of the first big lessons around Postgres performance that we really need to understand. So we're going to take a pause right here. We're going to come back to the next video, and we're going to start to really get a good idea of what these block things are all about, why are they 8 kilobytes large, and why they exist at all. We've now established that inside of a heap file, there is a collection of different blocks. Every block is 8 kilobytes large, and inside of each of these blocks are our actual user rows, the actual data that we're trying to store inside of our table. In this video, we're going to go one step deeper and really understand what is going on inside of this block. Now, quick disclaimer, this video is going to get a little bit crazy because we're going to go to a very fine level of detail. We're really going to eventually understand how this block is physically stored on your hard drive. If at any point in time during this video, this information seems boring or useless or anything like that, if it's too confusing, don't sweat it, just pause the video and continue on. Okay, so we're going to take a look at another diagram to help you understand a little bit more about that particular block. All right, here we go. So on the left-hand side, we are still looking at file 22445. Inside that file, there is a collection of different blocks. Each block is assigned a number, starting from 0. So the first block is called block 0, then block 1, block 2, and so on. As we mentioned just a moment ago, each block is 8 kilobytes large. We're going to take a look at block 1 in particular. So block 1 has this kind of structure. Now when I say this kind of structure, and you are looking at these kind of boxes on here, you might be a little bit curious, like, what do these boxes actually indicate? Well, when we are thinking about block number 1, we are really talking about some information that is being stored on the hard disk of your computer. your hard disk stores information as binary, so zeros and ones. So as we are looking at this structure right here, we're essentially talking about what different zeros and ones inside this block are actually being used to store what piece of information. So when you are looking at this diagram right here, we can kind of imagine that behind the scenes, we are looking at some collection of zeros and ones. So maybe the first set of zeros and ones right here at the very top, they like these right here, are being dedicated to store some very particular type of information. Maybe the next couple of zeros and ones are being dedicated to store some other kind of information. And then eventually maybe the zeros and ones at the very bottom are dedicated to storing yet another kind of information. So right now, as we're looking at this diagram, this is kind of a representation of the actual physical data being stored on your hard drive and the purpose of every little 0 and 1 in there. So as I mentioned, this is a very low-level lecture that we're going through right now. Okay, so inside the block, we have some collection of zeros and ones at the very start of the block that are made to represent information about the block itself. The next section of zeros and ones contain information about the actual data that is stored inside this block, so information about the actual rows. This does not actually contain information for the rows themselves. So in other words, there's not necessarily any IDs or usernames or anything like that inside of here. These are just little pieces of information that say where you can find the different rows that are stored inside the block. After that, we've got this big gray area in the middle that is dedicated to free space. So by free space, I just mean to say there are some collection of zeros and ones that are not actually being used by the block right now. So that is information or free space that can eventually be used to assign some kind of actual user data or whatever else we're trying to store inside of our table. And then finally, at the very end, is the actual data itself. So at the very end, we've got some collection of zeros and ones down here for information about tuple 2, perhaps, and then maybe some information about tuple number 1, perhaps. So again, when we're looking at this diagram, we're really thinking about the raw zeros and ones and the goal of each section or segment of zeros and ones. Now I want to pause this video for right now. We're going to come back to the next video. We're going to take a look at an actual block that is stored on, in my case, my hard drive, but it's essentially going to be a lecture that could be just as easily applied to some block that is stored on your hard drive as well. And we're going to actually take a look at those raw zeros and ones and understand the real goal of each of these different sections. All right, my friends, I want to repeat this little disclaimer, especially for this video. You almost definitely do not need to watch it. So I highly recommend, unless you are very, very curious, that you just pause this video right now and skip on to the next one. In this video, I'm going to show you how we can actually map out and understand how Postgres stores information at the binary level on your hard drive. So this is extremely specialized knowledge that you probably are never really going to need. I'm only putting it inside the course because it does really give you a much better idea of the amount of engineering effort that has gone into Postgres. It also just gives you a little bit of a better, well-rounded picture of what is going on. So again, I really recommend you just skip it unless you are very, very curious. Okay, so what are we really going to be doing? Well, we are going to take a look at a documentation page. So we're going to pull open this address right here inside of a new browser tab. I'm going to do that right away. Here's that page right here. So this page is all about how Postgres stores information in one individual page. And remember, a page is 8 kilobytes large, and a single heap file has many pages inside of it. So this documentation page explains how information is laid out at a binary level. So it's actually talking about bits and bytes inside of here. So we're going to take a look at the raw binary of our database file, the actual heap file that we're working with, so that actual user's file. And then we're going to map out the raw bits and bytes inside there and understand the purpose of the vast majority of them. So it should be a lot of fun. It is going to be a very long video, so of course feel free to pause at any given time. And if anything gets too confusing, or if I'm just going off the rails, this stuff seems useless, just pause the video and continue. Okay, so the first thing we're going to need is to be able to view the raw binary that makes up that heap file. To do so, we need a hex viewer, also known as a hex editor. Now you can do a quick Google search and download a hex editor if you want to. Alternatively, if you make use of Visual Studio Code, you can get an extension that allows you to use a hex editor directly inside of Visual Studio Code. That's what I'm going to be doing, so let me show you how to do that. Okay, I'm going to open up Visual Studio Code. I'm going to go to the extensions menu. So here it is right here. I'm going to search for Hex Editor. Here's the very first result. It is an extension created by Microsoft. And just go ahead and click it and then hit install. That's pretty much it. So now to make use of this hex editor, I'm going to go and find that heap file that we've been working with. So for me, it is file 22445. Remember, this particular heap file stores my entire user table inside of it. So I'm going to open up that file inside of Visual Studio Code by just doing a simple drag and drop. I'm then told that this is some kind of binary file, and it's not going to print out too nicely. I want to open it up anyways. So I'm going to click on the little link right there. And then right away, I'm going to be presented with a lot of gibberish. Now there's definitely a lot of weird characters inside of here, but you'll notice that there's also some information that looks like it is related to our users table. So that is probably a username right there, Gene76. I also see what looks like a phone number. I see the offline status. A little bit lower, I see what looks like a biography. Here's a couple of URLs. So it definitely looks like this has the correct information inside of it. But right now, we can't really interpret a lot of the different symbols inside of here. So we're now going to open the same file inside the hex editor. To do so, I'm going to press Command-Shift-P or Control-Shift-P if you're on Windows, and then search for hex editor open file. I'll then hit enter, and there we go. This is a hex viewer. I'm going to assume that you might have not used a tool like this before, so let me first begin by giving you a very quick overview. The primary interface that we're really working with here is the kind of bolded table in the middle. So all the different values, it looks like it's pairs of numbers and letters. These are hex values. Each hex value represents 1 byte of information. If you click on any of these different values and then zoom out a little bit, you'll see a data inspector appear on the right-hand side. Take a look at the very first row. It says 8-bit binary. So those are the raw ones and zeros that constitute the hex code A8. So A8 we can think of as being kind of like a shortcut for this particular pattern of zeros and ones. So when we look at these different hex code values, they are really shortcuts or an easier way to read and interpret binary code, like raw ones and zeros. So we are just making use of this stuff in binary or in hex just because it is easier for you and I to visually understand. At the end of the day, it is actually binary or ones and zeros that is actually inside this file. So this is just something to make it easier for you and I to understand what is going on. You'll notice that this entire table of hex codes appears to have 16 columns going across. In reality, the information inside this file is not laid out in any kind of table. It is only being presented in a kind of table format here, again, just to make it easy for you and I to understand. Next to this main table right here, you'll also see this other column called decoded text. The information being presented inside of here is a result of if we took this raw binary and tried to read out all those binary values as text characters. In the vast majority of scenarios, a lot of this information over here inside the decoded text column is not really meaningful to us in any way. Only if this binary is actually meant to store some actual text values does it actually get useful. So if you scroll down just a little bit, you might see that same kind of Gene76 right here or some username right there. And offline, there's another username, there's a biography, there's a URL, and so on. So decoded text is really, once again, just for convenience. Okay, so I've got my big text table here. There's a ton of different rows inside of here because this file is about 44 megabytes large. So there's a tremendous amount of information inside this file. If we scroll up to the very top, we are looking at the start of page 0 right here. So all the stuff that I'm looking at right here, this is page 0. If we counted off 8,096 bytes, so if we counted off like 1, 2, 3, 4, and then all the way down, we would eventually get to page number 2. Because remember, every page is 8 kilobytes, and inside of 8 kilobytes, there are 8,096 bytes. So if we counted off 1, 2, 3, 4, and so on, and eventually went down 8,096, we would end up at page number 2. So right now, we are looking at the first page inside of this file. All right. So next thing, really quick, I took a screenshot of that file and put it into this diagramming tool. So it's the exact same data that I was just looking at inside that hex editor. we're going to start to take a look at the meaning of almost every byte inside this file. And as we do, I'm going to put a couple of boxes around these and describe the purpose of all these different sequences of bytes. So let's try to go through this and understand what these different hex values really mean. So to do so, we're going to first go back over to that documentation page. I'm going to go to table 1682. This is the overall page layout. And you'll notice it's essentially just describing the same thing I told you in the last video. There are really 4 meaningful sections. We're just going to completely ignore special space. So 4 sections that we care about. There's the header, item ID data, which is kind of like the pointers to all the different actual items inside this page, a free space section, and then items, or the actual tuples or row data itself. So we're going to first try to map out the first 24 bytes of information inside this page. The first 24 bytes of information represents the page header. So this has data about the page itself. So to get some more information about what info is actually contained inside these first 24 bytes, we're going to scroll down a little bit more to table 68.3. So this table right here describes the purpose of this first 24 bytes of information. Let's first get started by just kind of locating these 24 bytes inside of our hex editor. So the first 24 bytes, we would scroll all the way up to the very top. We would start at the very first value right there. So that is byte number 1. Then we would start to count off 24 bytes in total. So we'd go 1, 2, 3, 4, and so on. There's 16 bytes on a row. So there's the first 16. Then we move on to 17, 18, 19, 20, 21, 22, 23, 24. So these first 24 bytes of information are all about that header row data. Or excuse me, the page header data. So those first 24 bytes represent these different pieces of information right here in this exact order. So the first 8 bytes, the purpose of those 8 bytes are for whatever that is referring to. The next 2 bytes are for something called a page checksum, then some flag bytes, and then some offset to free space. So to just kind of map along here, I'm going to put on a couple of boxes here. So we know that the first 8 bytes right here are all about that very first value that they call PDLSN. So the very first bytes, I'm going to kind of put a little box around those first 8 and say this represents PDLSN. Now, let me increase the font size there just to make it a little bit easier to read. There we go. Then the next 2 bytes, if you're still looking at that table on your computer, the next 2 bytes are all about a value called PD checksum. Then the next 2 after that are about some other kind of value called PD flags. And then the one that we are going to focus on first are the next 2. Let me make sure these things are all lined up. The next 2, which are called PD lower. So these 2 bytes right here, the first set of 2 bytes that we're going to really focus on and understand what they're doing for us. We're going to take a look at the documentation. It says here PD lower is a 2-byte value. It is an offset to the start of free space. So what does that really mean? Well, we're going to go through the process of understanding what this description is talking about. We're then going to calculate the value of PD lower by using our hex editor, and then try to actually interpret the information inside there. So first off, what is PD lower? Okay, quick diagram once again. So let me swap here. Here we go. Here's our block. Okay. So remember, we've got these 4 different sections. We've got the header. We've then got our list of item IDs at the very top. We've then got free space and the actual data at the bottom. The PD lower value indicates the number of bytes from the start of the page. So like right here, if we count off the number of bytes from left to right, so like 1, 2, 3, 4, blah, and so on, it's the number of bytes from the start to the start of the free space section, which would be right here. That is the goal of the PD lower value. So let's try to actually look up the PD lower value inside of our hex editor and then count off the number of bytes. And that number of bytes should leave us at the actual free space section for block number 1. Okay, so back inside my hex editor, I'm going to find the PD lower value. So that is in the very first row at 0C and 0D. So these 2 bytes right here represent an integer value. So I'm going to click on just the E4. I'm then going to zoom out until I see the data inspector on the right-hand side. And then I'm going to look at the int 16 row right here. So int 16 says 228. So what does that mean? Well, that means that if we start off at the very start of this page and then counted off 228 bytes, that would take us to the very start of the free space section. Let's try counting off 228 or 228 bytes right now. Now, of course, we're going to use a little shortcut for this. I'm going to open up a calculator. I'm going to take 228 and divide by 16, and that gives me 14.25. So the goal of that 16 is, remember, every row has 16 bytes inside of it. So if I count off 14 rows down, and then an additional quarter of a row, that should then leave me at the start of the free space section. So I'm going to do that right now. Here's row 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So that right there, that's the first 14 rows, plus an additional quarter of a row, which is 4 bytes. So there's an additional 1, 2, 3, 4. And the next value is the start of the free space section. So for me, my free space section starts right here in column 04, row E0. Now, if I actually look at these different values, you'll notice that they are all zeros. And that definitely sounds like some free space to me. This is information or space that is not being used at all right now. So it looks like this is definitely some free space. Okay, so I'm going to flip back over to my diagram and just kind of label that out. Okay, here we go. So I'm going to scroll on down here. So here is row E0. There's 1, 2, 3, 4. And then the next byte after that, that is the start of free space. And then we can kind of visually inspect this and say, okay, it looks like all these zero values are probably part of that free space stuff. So I'm going to just kind of expand this free space section to what I think the free space actually is. It's probably like all the way here, all those values, all those, and then probably the next one up to the first actual defined value. So it's probably like to right there. So there is our free space section. Okay, so that looks pretty good. So we've now gone through the entire process of identifying one of the values inside of our header and understanding what it's actually being used for. So let's now repeat that process just very quickly, just to reinforce it. It looks like after PD lower is another value called PD upper, and that is the offset to the end of free space. Okay, so that means that right after PD lower, the next 2 bytes are referred to as PD upper. That is also going to be an integer value, and it's going to be the number of bytes from the start of the page all the way down to the end of free space. So in theory, it'd be the number of bytes to the 26 right there for me in particular. Okay, I'm going to go back up to the very start of my page. I'm going to find all the way over the E400, that was my PD lower. The next 2 bytes are my PD upper. So I'm going to click on the 28. I'll get my data inspector again. Now if I look at my int16 or uint16 in this case, it doesn't make a difference in this particular scenario. It looks like it's 296. That means that if I count off 296 bytes from here all the way down, that should tell me where the end of my free space section is. So we can again do that same little trick. I'll do 296 divided by 16. So that gives me 18 and a half. So I'm going to count down 18 rows. There's 1, 2, 3, 4, 5, 6, 18. So there's 18 rows. And then an additional half row, which will be 8 bytes. There's 1, 2, 3, 4, 5, 6, 7, 8. And sure enough, the next value is that 26. So that is my end of free space right there. So that matches up perfectly with that right there. So there's my free space. So we've now identified our PD lower and our PD upper. Now hopefully you've kind of got a sense of how we can interpret the different values inside of here. Now let's finish off with the header. The rest of the values inside that header are not super interesting to us. So we don't really care about the special space stuff. We don't really care about the page size or version and that other stuff as well. Regardless, I am going to diagram it out here. So on that next row, we get 2 bytes for a value called PD special. The next 2 bytes after that are for PD page size version. I'm going to put a little space in there just to break it. And then after that, we get an additional 4 bytes, again, I'm just referring back to the table that we just looked at 2 seconds ago, and the remaining 4 bytes are for PD, Parun, XID. And that's it. There's our entire header section. So now we move on to our next section. The next section, I'm going to go take a look at the documentation again. If we want to, we could refer to that diagram at figure 68.1. So this is essentially an array of item IDs. Once again, these are not the same IDs that we have inside that ID column inside of all of our different tables. Very, very different item ID. So we can take a look at the documentation and understand what the real meaning of these item ID things is. Like, what is this really telling us and what is the goal of them? So for that, I'm going to scroll up just a little bit. And right underneath table 68.3, you'll find a paragraph that says, following the page header are item identifiers. So this is what we care about right now. So each item identifier is 4 bytes long. That means that if we count off after the end of our header, so here's our header right here. I'm going to zoom back in for you. Here's our header, the first 24 bytes. So then every 4 byte section after that represents one individual item ID data. So there's 4 bytes right there. There's another 4, another 4, another 4, and so on. So you can see that in total, from the end of the header all the way down to the start of our free space, right about here. Let me zoom out just a little bit. So these are all item ID datas. Each one is 4 bytes long. So now that we've identified these, let's figure out what information they actually contain. So back at the documentation, it looks like each item ID data has a byte offset to the start of an item. In this case, remember, an item is a tuple or a row. So the byte offset to the start of the item essentially means the number of bytes from the start of the page to the start of an actual item, or a tuple or a row inside of this block. It then relates the length of that individual row or item in bytes, and then some other information that we don't really care about. So in reality, these item ID things, item ID datas, are telling us the byte offset to the start of item and its length in bytes. So when we look at this diagram right here, and even the diagrams that I've shown you, they're not super accurate. It's really just saying, hey, this item ID, or this diagram is just saying, this item ID is pointing to this item, when in reality, this item ID is pointing to the start of the item and the length in bytes for that item as well. So the number of bytes inside of this page that is occupied by this particular item. And that's all being encoded inside of that item ID. So let's try to take a look at the actual data inside of a particular item ID and try to pull some actual data out of it. Okay, so once again, back at my hex editor, I'm going to find the start of my free space section, which for me is about E0. So right before that, those 4 bytes at the start of the row right there is the last item ID data. That's the last little kind of pointer right there. So we're going to take a look at the information stored in this one in particular. Now here's the kind of tricky part. Actually understanding how the data is stored, like that offset value and the length of data inside of this little thing right here, is actually kind of tricky. And this actually took me a while to actually figure out. So this is where taking a course like this actually makes life a little bit easier, because I'm going to show you how those 2 values are actually stored inside of here. Okay, so here's what I'm going to do. I'm going to open that data inspector again. I'm going to click on the 28. Okay, so there's the start of the item ID data. I'm then going to go over to the next value, the 81 in this case. So on the 81, the next value over, the second one, I'm then going to go up to 8-bit binary right here, and I'm going to copy only the last 7 digits. I'm going to ignore, extremely important, I'm going to ignore the first digit inside there. Okay, so I'm going to ignore the first digit. I'm going to take the remaining 7. I'm going to copy them. We're then going to take that over to Google. I'm going to do a search for binary to decimal. So we're just going to find a little converter to convert a binary value over to a decimal value. I'm then going to paste in that value that I just copied. So at this point in time, you should be able to count out and make sure that you've only got 7 digits right here. Make sure you've only got 7. Okay, so then after that, we're then going to go back over to the 28 for the first value inside that column. I'm then going to take the entire, so all that binary right there, all the zeros and ones, I'm going to copy all of it and then paste it back over here after the number that we already pasted in. So I'm going to put it after, like so. I'll then click on Convert. And that right there is our offset. That is the number of bytes from the start of the page to the first item. In this case, the first item. So it is, find our diagram really quick. The offset, or the number of bytes from the start of the page right here, down to the start of the item that this particular item ID data is referring to. The number of bytes from right there, all the way down to this particular item right here. Remember, each item ID is actually referring to an individual or different item inside the data section of our page. So it just ever so happens that the one that we just looked up is 296 bytes from the very start down to right there. So we can count off those 296 bytes. So this is actually the exact same calculation as the free space. So we should be able to count off 18 rows and then half a row. So again, there's one row right there. We can count all the way down. That's 18 rows right there. And then another half a row. And that leaves us at the 26 right there. So that is the start of our very first item out of the entire big list of items. So on my diagram, I'm just going to mark that down really quick. So here's the end of the free space. And here is the item that we just looked up. So I'll say 296 bytes to this item. Now, once we've located the start of the item, we can then calculate the length of the item as well. So to calculate the length of the item, we're going to go back to that item ID data that we were just looking at a moment ago. So find your free space section. There's my free space. And then we were looking at the very last item ID right before that. So there's the 21 and the 81 that we were looking at just a moment ago. Now to calculate the length of the item, in this case, we don't have to do any tricky math like we just did a moment ago where we had to copy paste the different parts of the binary value. In this case, we can just click on the value inside the third column. So for me, it is AC. And then we can look just directly at the int 16 value. So it says 172. So the 172 right there is telling us the length of data for this first item. That means that our very first item, if we kind of take a look at it in more abstract form, it means this item right here, 172 bytes worth of information. So in theory, if we kind of counted off 172 bytes from the very start, that would give us all the data. But one little catch. The 172 value that we just looked up is the amount of data for our item itself, like the actual data that we are storing. The actual ID and the created at and the username and the URL and so on. But there's actually some other information stored along with an item as well. To figure out what that is, we're going to take another look at the documentation. So the documentation, I'm going to go to 6861, and we're at table row layout. So this is information about how an individual item is put together. So for an individual item, this is the tricky part, there's actually 23 bytes worth of information at the start of the item, then some other information after that, and then finally, after all that filler stuff, is the actual user data, like the actual ID that we care about, the created at, the username, and so on. So in other words, back to the diagram really quick, the start of this item is actually the start of the header for the item. Only after about 23 bytes, plus or minus some additional amount, do we actually get to the data that we really care about. So if we counted out 23, so we got 8 right there, plus another 16, and then take up one short, so there's 23. So there's 23 bytes right there. That is just for the header by itself. And then there's some other filler immediately after it that we just saw inside the documentation. So there's the 23 bytes. I just highlighted that. Then there's some other stuff inside there. And then finally, somewhere after all that is the actual user data. Now in this case, let's just kind of cut to the chase here and find some actual meaningful information. So back at my hex editor, I'm going to zoom in on that first item. So here's my free space. Here's that first item, or the start of the first item. We can then count out those 23 bytes for the header of the item. Then there's some filler information, which is basically about that right there. And then right after that is the actual user data, the actual information that we are trying to store. And if you actually look really closely at the right-hand side, you'll notice that, hey, that actually does look like our actual information. There's my username, the phone number, and the offline online status. Now, if I take a look at the very first defined value inside of here, for me, it is CB. So if I click on CB and then get my data inspector back up, you'll notice over here for int16 or uint16, I have a value of 203. That value in this case, this very first number right here, this very first value, is actually the ID of this row, like the ID that you and I are storing inside the ID column. We can actually very easily verify that as well if we just go and write a query that tries to find inside of our user table the user with a username of Gene76. So I went ahead and did that in advance. So here's a query to find all the information about the user with username Gene76. And sure enough, there is an ID of 203 right there. And there's Gene's username. So that right there is the start of the actual true user data for this particular row that we're looking at, ID 203. So then all the following values after that are related to, say, probably right here, that's probably something about the created at, and then maybe the next little bit is maybe the updated at, and then after that, clearly that's the username. We then have some phone number stuff, and then we've got the online or offline status. So there it is. So from right about there, there's the header for this item. And then there's all the row data, pretty much probably like right around there or so. And that's it. So that's how we finally get down to the actual data for some particular row inside this file. So now if we wanted to, we could repeat this entire process over and over again using all this different item ID header stuff. So remember at the very top up here, at the very start of our page, is the item ID list or the array. So we could take a look at some of these other 4-byte values. We could pull out the offset to the start of the actual item and then the length of the item as well. So we can repeat that over and over and over again and look up all the additional records that are stored in this particular page. Okay, so we've been focusing on just the very first page of information inside of here. But remember, there are many pages being stored inside this one file. So if we were to scroll down a really good amount, so if we scrolled, we could eventually get down to the second page. I'll tell you right now, the second page is at row 2000. So you'll see these kind of numbers and letters over here on the left-hand side. If you scroll all the way down to 2000, that's where the second page is. And there we go right there. So here's 2000. There's the start of our page. So once again, we've got a page header. We've then got all the individual item ID datas, probably to about right there or so would be my guess. Then we've got our free space. So probably about right there. We've then got the first item that is stored inside of here. So there's the header for the item. And then eventually somewhere inside of here, probably like right there, I would guess, is the ID of this user, and then all the other data associated with them. And then we could keep on going down. If we go down to row 4000, that is the third page. So we could go, and eventually get to row 4000. Here we are. There's 4000. There's the start of our page. There's the header for it. Right there, there's all of our item ID datas. There's our free space. And then all the actual rows or tuples themselves. Okay, that is it. That is how information is actually stored inside of an individual file. So you've now seen the collection of the collection of pages or blocks. You've seen the header for every page or every block. You've seen the free space in between. And then we've kind of more or less gotten a sense of how all these individual item IDs eventually refer to one of the actual items or rows that is stored inside the page as well. So where do we go with all this? Well, as I mentioned, there's not necessarily any immediate need to have this information. It is going to actually be really useful once we start to take a look at another topic inside of Postgres called indices or indexes. So we are going to come back to this entire kind of data layout stuff very soon. But again, at the end of the day, remember, this is really just about saying, hey, this is kind of interesting. This is how Postgres really stores information. So I apologize, of course, for the very long video, but I hope that at least was interesting to walk through a hex editor and see how information is stored at a very, very low level. So naturally, let's take a pause right here and continue in just a moment. We've now seen how Postgres stores records inside of individual blocks inside of a heap file. So now the big question is, who cares? What's the difference? Why does it make a difference at all? Well, in this video, we're going to start to walk through a query. We're going to understand how it gets executed by Postgres and start to understand some performance characteristics of it. All right, so I want to imagine that we've got a heap file that looks like this right here. We've got two blocks. Inside of block 0, we've got a user with a username of Nancy, a username of Alf, and then a username of Gia and Ryan in block 1. So let's imagine what would happen if we ran a query like this right here. So we want to take a look at all of our different users and then find only the users with the username of Ryan. Now the important thing to keep in mind is that when data is inside of a heap file on your hard drive, Postgres cannot really just examine that file in place. In other words, in order to take a look at the different users, we have to first load these users up into memory. So step number 1 for a query like this would be to take a look at all of our different blocks inside of the heap file. We would extract or load up all the different users into memory. And then once they are inside of memory, we could start to do some further querying or filter on this data. So in our particular case, we might walk through every single one of these users one by one until we found some that had a username of Ryan. Now, anytime that we are loading up information from our hard drive over to memory, that has a relatively large performance cost. So wherever possible, as database engineers, we try to minimize the amount of data that is being moved between our hard drive over to memory. This is a really big drive when it comes to performance, and we're going to spend a lot of time to understand how we can limit how much data is being taken out of a heap file and placed into memory. Now on top of this, once this data has been loaded into memory, we then have to execute a search record by record. So even once this information is in memory, we then have to walk through each individual one until eventually we find some number of rows that satisfy this criteria of having a username of Ryan. Now, anytime that we are loading up a ton of information out of a table and then iterating over those records one by one, we refer to that as a full table scan. So a full table scan is whenever Postgres has to load up a ton or even possibly all the different rows out of a heap file into memory and then execute some kind of iteration over those rows to find some number of records. You're going to see references to full table scans in a lot of different blog posts, articles, and so on around Postgres performance. A lot of blog posts and articles will say that a full table scan is always 100% of the time going to be a very low performing type of query. So in other words, anytime you run a query that does this kind of full table scan thing, a lot of blog posts are going to say that is bad. But in reality, you do not always run into poor performance when you are doing a full table scan. There are actually some scenarios where a full table scan is kind of desirable over any alternative, and we're going to take a look at those different scenarios. Regardless, at the end of the day, full table scans, generally anytime that we see that Postgres is doing one, we want to do a little bit of investigation and figure out whether or not there is some way that we can somehow search for this data in some different manner. In other words, anytime we see a full table scan, it warrants some investigation. So in this case, we are looking at a query right here that would result in a full table scan. So we would want to investigate this and figure out whether or not there was some more efficient way to execute this query. And that's exactly what we're going to do in the next video. We're going to take a look at a different way to tell Postgres to run a query over our table of users to perhaps find the user that we care about, in this case Ryan, without doing a full table scan. So let's take a look at the alternative to a full table scan in the next video. In the last video, I kind of made it seem as though there was some way that we could load up some particular records out of a heap file without having to first load them all into memory. So how would we actually do that? How would we somehow figure out that we want specifically user Ryan right here, for example, without having to load up all these different records? Well, maybe if we had some kind of outside tool of sorts, something that existed separate from the entire heap file or the table, that could somehow tell us exactly where every user was located inside the heap file. So for example, if we issued a query like this, and we fed it into this tool right here, if we asked for user Ryan, if that thing could just tell us directly, oh yeah, user Ryan, I know where user Ryan is. User Ryan is in block 1 at index 2. If we had some kind of tool like this, then we could get Postgres to go into that heap file, find just this block right here, maybe load up the entire block. Who knows what's really going on behind the scenes. Technically, it does load the entire block up, by the way. So we could load up just that block by itself, get just user Ryan out of there, and there we go. We loaded up our user without having to worry about fetching any other extraneous information, such as block 0. So it would be great if we had some tool like that, right? Well, naturally, we do. It is implemented in Postgres as something called an index. An index is a data structure that very efficiently tells us exactly what block and index a particular record is stored at. So if we fed the index some kind of query like this, the index could tell us, oh, user Ryan, I know where Ryan is. Ryan is at block 1, index 2. And so we could use this index right here as a sign that we should only load up block 1. That's what an index is all about. It is an external record of sorts, record book of sorts, that tells us exactly where some records are stored inside of a heap file. Now, to really understand how an index works internally, I think it's generally easiest if we kind of approach this from understanding how an index is initially created. If you see the kind of behind the scenes on how an index is assembled, I think it generally makes it a little bit easier to understand how the index works, and also helps you understand about some of the pros and cons of it as well. So let's take a pause right here and take a look at how an index is assembled in the next video. Let's take a look at how an index is created. Now, the series of steps we're about to go through is not exactly what occurs inside of Postgres, but the series of steps I'm going to show you is close enough that it's going to help you understand some of the inner workings of an index, how it works, and some big caveats around them as well. So let's get to it. So for step number 1 in creating an index, you and I are first going to decide exactly which column we want to have a very fast lookup on. So let me tell you exactly what I mean by that. Just a moment ago, we were talking about writing a query like this, where we wanted to find some particular user with a very specific username. So whenever we create an index, we create it on a very specific column. That allows us to do a fast lookup on our table of users whenever we are doing some kind of filtering logic on that same column. So in this case, we would want an index on the username column in particular, because that would allow us to run queries that involve username very quickly. So in our case, we are doing a fast lookup on username. Now we can technically have an index that takes into account the value in multiple different columns for each row, not just one, as is the case right here. But we're going to worry about just an index over one particular column at a time for right now. Okay, so on to step number 2. In step number 2, we're going to take a look at our user table, or really our heap file, and we're going to look for every single row. We're going to extract just that one property that we want to create the index for. And then when we extract that property, we're also going to record the block and the index that we found that property at. So in other words, we're going to take a look at block 0. We'll start off with Nancy. Nancy's username is Nancy. So we will extract Nancy, and we will record that we found that username at block 0, index 1. So we'd end up with something like that right there. Next up, we would extract Elf and record that we found Elf at block 0, index 2. And then repeat that same process for Gia and Ryan on block 1 as well. So notice that in all this data right here, this is the information that's actually going to go into our index. And in this information, we have not recorded, say, the ID of Nancy, or Nancy's created at or updated at. We have not recorded Gia's bio. We haven't recorded Ryan's avatar URL or anything like that. So inside the index, the only information that we have about every user is their username, and that is it. Okay, let's move on to our next step. So we're now going to take a look at all the different values that we have extracted and sort them in some meaningful way. So for strings or text, which is what we have right here, we would sort these in alphabetical order. If we had numbers, we might sort them from least to greatest or greatest to least. For dates, we might go from the earliest date to the latest date and so on. So when we do the sorting, we can go from in ascending order or descending order. And there actually is good reasons to do either one that we'll talk about in due time. So in this case, we're going to sort all of our usernames in alphabetical order from A to Z. So we get Elf, Gia, Nancy, and Ryan. Okay, so there's our sorted users. All right, now the next step is going to be a little bit more intense, but we'll get through it. So we're going to take that list of records right there, and we're going to organize them all into a tree data structure. Now, if you are not familiar with trees, that is okay. I think the diagram is going to get you through enough to help you kind of understand more or less what the tree is doing for us. When we insert these records into the tree, we're going to distribute all the records evenly among these different leaf nodes that we have inside the tree. So I'm going to take first elf, and inside of this tree, I'm going to put it at the leftmost position of a leaf node. I'll then take Gia, put it right next to elf. Next is Nancy. And then finally, oh, sorry about that. Finally, we've got, oh, come on. There we go. Finally, we've got Ryan. There we go. Now notice that I preserved alphabetical order here. So if we look at all these records from left to right, they are still in alphabetical order. So we've got Elf, Gia, Nancy, Ryan. Okay, so now, last big step, we're going to add some helpers to the root node. Well, let me explain exactly what that means. You'll notice that inside this root node thing up here, we've got two white boxes. Inside these white boxes, we're going to put in some directions to say whether or not someone who's trying to execute a query or find some particular record should go down to this leaf node. Put another way, I'm going to list inside of here what set of values exist inside of leaf node, this one on the left-hand side, by using an inequality. I'm going to say that you should go this way if the string alf is less than or equal to, when sorted alphabetically, the username that you're looking for, and username is less than Nancy. So if you have a username that you're looking for, and that sorted value of that username is greater than or equal to elf, but also less than Nancy, then you should go to this leaf node, because chances are the username that you're looking for is inside of this node. Otherwise, go this way if Nancy is less than or equal to the username that you're looking for. So if you have a username that you're looking for and it's equal to Nancy, or your username should be sorted later than Nancy, then go to this leaf node. And that's it. There is our index. Now let's take a look at how we would actually use this thing. So we would imagine that we would come to this index and say that we're looking for a user with a username equal to Ryan. So we would start off at the root node. We would then try to evaluate this inequality right here. So is our username, when we're considering alphabetical order here, is it between Elf and Nancy? Well, in this case, no, it's definitely not. We've got Ryan, which is definitely greater in value when we're considering alphabetical order than Nancy. So we'd move on to this other side over here. We would then evaluate this inequality. Well, Nancy is definitely less than or equal to Ryan. So we'd go into this leaf node, and then we are guaranteed that the user we are looking for is listed out inside of here. So in this case, we would find Ryan right there. We'd find that Ryan, the complete record for Ryan, is stored in block 1 at index 2. And so that would be a sign that we should go into our heap file, find block 1, go to index 2, and there's Ryan right there. All right, so now there's something really important I want to point out here around this index. When we went through this sort operation, we were able to find the exact record we were looking for without having to load up the vast majority of records inside of our heap file. So we did not have to access block 0 inside the heap file. In addition, when we were walking through this tree right here, we never had to visit the leaf node over here on the left-hand side. Instead, we just did that initial evaluation up here at the root node, and that told us exactly which leaf node we should go to. So we were able to skip a huge portion of this entire search operation by just using the inequalities that we had set up ahead of time. Okay, so that is, in essence, what an index is doing for us. It allows us to find some particular record very efficiently inside the index, and then once we do that, we are pointed exactly to where that record exists inside the heap file. So we can load up just that block right there and no other extra information. Okay, so now we understand the theory behind an index. Let's actually create one in the next video. We've now got a pretty good idea around the theory of an index. So let's actually create one inside of our Instagram database. We're going to create an index for our users table, specifically for the username column. So we're going to create an index to serve the exact same purpose as what we saw in the last couple of videos. This will speed up any kind of query on the users table that involves that username column. Okay, so to create an index, we're going to write out just a very short little bit of SQL. We're going to write out create index on. We'll then put in the name of the table that we want to create the index for. And then inside of a set of parentheses, we'll put in the name of the column that we want to create the index on. So in our case, we're trying to create an index on the username column. I'm then going to run that, and that's pretty much it. That is how we create an index. So notice that in the last video, we went through that whole process of extracting values and inserting them into the tree. That all happens behind the scenes for us. When we want to create an index, we just run that command right there, and that's it. No other input required. So to take a look at that index and just verify that it was created, we can go to our left-hand nav, expand Instagram, go to schemas, go down to the table section. We can then expand users, and then finally, we can find indexes right there. Now you might have to do a right click on indexes and click on refresh. And then we can see the index that was created appear. So the index that was created was automatically given a name of users, username IDX. IDX being short for index. Whenever you create an index, if you do not provide a name, one will be assigned for you automatically. The name that gets assigned is always going to follow this naming convention. It's always going to be the name of the table, the name of the column, and then IDX at the very end. If for some reason you want to apply a manual name to your index, you'll put it right between the keyword index and on. So we could have manually assigned a name by writing in something like users username IDX. We could also put in something like username index. You can name it whatever you want, but the naming convention is exactly what was automatically generated for us. The naming convention is the name of the table, the column, and then IDX. Even if you manually name the index, I still recommend that you always follow that same exact naming convention. It just makes it a lot easier to remember the name of all your indexes without having to look them up on this side navigation bar. Okay, so that is how we create an index. So now in theory, queries on our username column inside that users table will be rather quick. Before we test that out, however, I just want to show you how you can easily delete an index. So I'm going to comment out the create index, and then right after it, I'm going to do drop index users username IDX. That is how we delete an index. Drop index, and then the name of the index itself. Now this is why we like to use the naming convention. I don't really have to remember the exact name of the index. I can just remember that if I want to delete the index on the users table for the username column, I will always write in users username IDX. That's why we use the naming convention. We don't have to manually go back over and figure out exactly what we named our index. Okay, so I'm going to run that. Now in theory, index has been deleted. If I do a right-click refresh over here, now indexes is empty. Now, of course, we actually want to test out this index quite a bit, so I'm going to comment drop index, uncomment create index. I'm going to run that one more time, and I've recreated the index. Okay, so let's take a quick pause right here. When we come back to the next video, we're going to run 1 or 2 queries on our users table, and we're going to do a little bit of benchmarking just to see what the impact of adding in this index really is for running some kind of typical query. Well, we've got our index in place, but does it actually speed up any query? Well, in this video, we're going to do just a little bit of benchmarking. We haven't really discussed benchmarking inside this course before, so I'm going to give you a very fast little keyword that we're going to make use of right now, just to figure out how long a query actually takes. Just so you know, whenever you run a query right now, you do see query returned successfully in some number of milliseconds. That millisecond value right there is just a little bit misleading because it includes travel time for the query from essentially the PG admin interface over to the database and back. So in other words, it includes some network travel time that doesn't really reflect very nicely or is really relevant on the actual execution speed of the query itself. So even though this is some kind of benchmarking value right here, it's not a great metric to really focus on. All right, so we're going to first write out a query that we can use to just really test out how quick it is now to fetch a particular user based on their username. And then we're going to figure out how we can somehow benchmark it in a meaningful manner. So I'm going to get started by commenting out the create index at the top. I'm then going to do a just very typical query to fetch some particular user by their username. So I'll do a select star from users where username is equal to Emil30. Now notice that Emil right here has a capital E on it. All right, so I'm going to run that. And it looks like I was able to fetch one particular user. So the user with ID 1000. Okay, so that looks good, but now we need to figure out how long it actually took to execute this query inside the database. So to do so, we're going to add in a little special keyword or two right in front of our query. We are going to put in explain, analyze. Now explain, analyze, we're going to go into great detail on in a couple videos in the future. So we're going to go into really understand what these two little keywords here are doing for us in just a couple of videos ahead. But for right now, let's just run this again, and you're going to see that we get some very different output. Now we get back just one single column. We don't actually see any rows of data or any particular user, but we get back some information inside of here that kind of looks relevant from a benchmarking perspective. So for right now, there's really just one value I want to focus on, and that is this fourth row right here, execution time. That execution time is how long it took to actually run this query. So right now, it looks like it took about 0.3 milliseconds to run that query and find some particular user. Now, if I want to, I could run this a couple more times and maybe get a little bit more solid value, kind of like average these out. It looks like as I run it a couple more times, it's kind of stabilizing at around 0.05 milliseconds or so. Now, 0.05 milliseconds is really, really fast. Just to put that in perspective, that is extremely quick. So anytime that I see an execution time of 0.0 anything milliseconds, that's usually a query that I'm going to be pretty darn happy with. Now that is running the query with the index. So when we have the index in place, it looks like running this query or doing the select statement is just unbelievably fast. Okay, so I'm going to put just a little comment here and say with index, it took about 0.075 milliseconds. So now I'm going to drop the index. So I'm going to comment out the query. I'm going to drop the index, and then we'll do that same command and see how long it takes to run this query without the index in place. Okay, so let's drop it. Now the index is gone, and in theory, we can now no longer do any kind of fast lookup on our users table for queries that involve that username column. So I'm now going to uncomment the explain analyze. I'm going to run it again, and now we'll take a look at how long it took. We'll take a look at that. It is now up to about 1.2, 1.4, 1.5 milliseconds. Now, 1.5 or 1.2 milliseconds is still really fast. Just to be clear, that is a pretty darn quick query in the grand scheme of things. But on the flip side, it is way slower than how long it took to fetch a user when we had the index in place. As a matter of fact, we could just do a little bit of off-the-cuff math here. So I could take the 1.249, divide by 0.075, and we got a difference of about 16 times. We'll round up to 17. So having the index in place made our query run 17 times faster. That is a almost mind-blowing improvement in speed, significantly faster to run. So without a doubt, having an index around and using an index to actually execute our query has a huge, tremendous performance benefit. So right now, at the outset, it might seem like indexes are just the best thing around and we should use them all over the place. Well, maybe that's not always the case. There are many scenarios where an index is not super useful. There are even more scenarios where an index can actually ultimately slow down your database. So let's take a pause here. We're going to come back in the next video and go over a couple more notes around indexes just to give you a better idea of when we should and should not use them. We just saw that adding in an index adds a tremendous performance benefit to a very simple query. So at this point, it might seem like we should add an index to every column of every table, but that is definitely not what we do on any real database. Let me tell you why. So, quick reminder here, when we created the index, we were essentially creating some kind of tree data structure behind the scenes. And inside that tree data structure, for every row of our actual table, we extracted one piece of information along with a pointer over to some location inside of our heap file. So in other words, for every single row, we are now storing, in addition, inside of our index, some piece of information and a pointer. So that comes with some amount of storage cost. It takes some amount of hard drive space just to store this index. It doesn't just persist inside of memory. There's actually a file that is created on our hard drive to store all this index data. So anytime that you create an index, you are using some additional amount of storage space on your computer. Now we can very easily figure out how much space that actually is. So back inside of pgadmin, I'm going to delete the query that we had just a moment ago. I'm going to uncomment the create index and run it just to make sure that we actually have an index. So I definitely have an index now. And then we're going to run a little query to print out the size in kilobytes, in this case, or essentially the hard drive space used by our users table. So we're going to do a select, e.g. size pretty, and then inside of parentheses, e.g. relation size users. So again, this is going to print out the amount of space that is used by our users table. Okay, so it looks like we got 880 kilobytes. I'm now going to repeat the same, but this time I'm going to print out the size of our username index. So I'm going to change the string to users, username idx, and then run that. And we get 184 kilobytes. Now, is that a big deal? Well, definitely 880 kilobytes and 184 kilobytes is really no big deal at the end of the day. These are trivial amounts of space. But you can imagine that if you start to develop a database for a very large kind of application that stores a ton of data, then to create just one simple index for a table that is maybe, let's say, 80 kilobytes or 80 gigabytes large, we might be talking about 18 gigabytes worth of information just to store this additional index. Now, even 18 gigabytes might not seem like a big deal, but just so you know, anytime that you are using a hosted database solution, so in other words, if you are relying upon AWS to host a copy of Postgres for you, the amount of money that you pay on storage space is actually rather large. So in some cases, you can actually save a lot of money by not kind of stuffing a ton of extra information into your database. So even though these values might seem like they're not the biggest thing at the end of the day, every time you add in an index, you are ultimately paying some amount of money for it. Now, even paying some money is not the biggest deal if you actually are gaining some big performance benefit. In other words, if I'm building some really large application, if it only costs like $10 worth of storage space per month to hold some index, I might want to just go ahead and pay that $10. Totally realistic. However, there are other downsides associated with creating an index. So in particular, besides the fact that an index can be really large, because we're essentially storing all the data from one column, having an index around can also slow down the insert, update, and delete operations on that table. Because every single time that you make a change to that table now, Postgres also has to go and update the index. So if you decide to, say, insert 20 rows into your table, well, that means Postgres has to make 20 updates to the index as well. And that has some performance cost in its own right. So if you are creating an index for some table that is going to be updated very, very frequently, if you create an additional index, you might be paying for it in the insert, update, or delete speed. Now, in addition to both these big items, there's one other kind of big potential downside. It turns out that there are actually some scenarios where Postgres is not going to use an index to speed up a particular query. And I'll give you some really good practical examples of that. So just because an index exists doesn't guarantee that Postgres is going to actually use it. There are actually some queries that are going to run faster without using an index at all. So you need to really kind of ahead of time decide, okay, if I'm going to make an index here, do I actually expect it to be used by Postgres? Because if Postgres isn't going to use it, then you're just paying for the index and storage space, and it's slowing down your update speed, and you're not actually gaining any benefit from it whatsoever. So the point here is that we don't just go ahead and create an index on every column, because there are definite downsides to creating an index, and there's also not a guarantee that it's going to actually speed up anything about your database itself. Okay, so now we got that out of the way, I want to give you a couple more notes on indexes in the next video. Anytime that we run the create index command, we are creating a very specific type of index. So in Postgres, there are several different types of indices that we can create. The most common one, and the one that you want the vast majority of the time, is a B-tree index. So this kind of data structure that we just learned about right here, where we've got all of our information stored in the leaf nodes, and then the more parent nodes direct us to the leaf node that we want to visit, is referred to as a B-tree index. B-tree indices are what you want to create the vast majority of the time. In fact, I'm really only putting this video out inside of this course just to tell you that, hey, other indexes exist, but you probably don't need to worry about them the vast majority of the time. So beyond a B-tree index, there are several other kinds of indexes that you can create. Each one of these are only going to be used in some very specific scenarios. Each of these scenarios is actually kind of rather uncommon. So again, vast majority of the time, you just want to worry about B-tree unless you know that you are going to fall into one of these very specific use cases. Now, each of these use cases, or where you would use each of these different indices, are so kind of specialized and not very commonly used or ran into that we're not really going to cover them in this course, because I honestly will be surprised if you have to deal with any of these kinds of indexes on any practical application in your career. So I just want you to know that other indexes exist, and we only really worry about the B-tree type index. Okay, so that's it. Quick pause here. Move on to our next topic in just a moment. We only just created our first index manually a couple of videos ago, but it turns out that you've actually been working with indexes throughout this entire course. Let me show you what I mean. All right, so in this diagram, quick reminder, our Instagram database has a hashtags table. It has columns of ID, created at, and title. ID is the primary key column, and title is has a unique constraint on it. Title is the actual text of the hashtag itself. Anytime that you create a column that is a primary key column, or anytime you create a column that has a unique constraint on it, Postgres is going to automatically create an index for you for specifically that column. So in other words, our hashtags table already has an index tied to it called hashtags pkey. That is specifically on the ID column, and hashtags also has an index on the title column called hashtags title key. Now this is a unique constraint that serves as an index. Anytime these indexes are automatically created, they can be used for any kind of query, same as if we had created the index ourselves manually. So in other words, long story short, you never should have to create an index on a primary key column, and you should never have to create an index on a column that has a unique constraint on it, because indexes already exist. Now, the one thing that's really confusing about this is that these indexes don't actually get listed under the indexes section in pgadmin. Let me show you that right now. So back inside of pgadmin, we can take a look at our hashtags table. There's the indexes section, and it's definitely empty. No matter how many times I refresh it, there's nothing inside there. But again, there is an index on the ID column and the title column, and those can be used to speed up any query tied to those columns. Now you might be a little bit kind of like, hey, okay, so indexes exist, but I can't see them in pgadmin. That's kind of confusing, right? Well, it turns out there's actually a query that we can write to see what indexes actually exist inside this database. So I'm going to delete the select that we've got right there, and I'm going to replace it with select rel name and rel kind from pg_class, where rel kind equals I, and then run it. Okay, so this PG class table lists all the different objects that exist inside of our database. So all the different tables, indexes, sequences, and so on. A rel kind of I means that this object listed out inside of here is an index. So we are looking at all the different indexes that exist inside of our Instagram database right now. So we have an index of users pkey, post pkey, comments, likes. These are the primary key columns, or essentially the ID columns, for each of those different tables. So these are indexes. That means we never have to create an index for the ID column of any of those tables. We can then easily scroll down and see, okay, there's hashtags, pkey, so that is the ID column of hashtags, and there's our unique constraint on the title column. So rather than using pgadmin to really decide whether or not a particular table has an index, you could just as well run this query, inspect the result, and if you see an I right there, that means that some particular aspect of, say, likes has an index tied to it. Okay, so I know that's kind of a little bit nasty to have to remember that query right there, but really the rule of thumb is we don't have to create an index for any primary key column, and we don't have to create an index for any column that has a unique constraint on it. Okay, let's pause right here and move on. This is an optional video. In this video, we're going to take a look at a very low level at how indexes are stored on your hard drive and how they are actually used by Postgres. So 100% optional. I would almost recommend that you don't watch this video unless you've got kind of a natural interest in how this stuff works behind the scenes. So let's get to it. Okay, so when we create an index, an actual file is created on your hard drive. The file is assigned some kind of random number identifier, but we're essentially just going to say it is the index or some file representing our username index. the structure of this file internally has the same kind of structure that we had for those heap files, which we spoke about a little bit ago. So inside of this index file, we have 8 kilobyte pages. In the case of an index, each page has a very specific purpose, whereas back inside of a heap file, each page was essentially identical to another. The very first page is called the meta page. So this has some information about the overall index. We then might have some number of leaf pages, and then eventually one called the root page. So all the pages you see right here essentially represent the different nodes of our B tree. So at the very top is the meta page. That is information about the entire tree. We've then got the root block or the root page right here that has some directions inside of it to direct us to which page or which leaf has some particular records. And then the leaf pages themselves are where our actual information is stored for the index. So for example, this leaf right here might have some listing of usernames, and for each username there might be a pointer to where we could find the record corresponding to that username inside of our users heap file. Okay, so that's the internal structure of this index file. Now the index file or these individual pages are actually identical in nature to those heap file pages we had looked at previously. So inside of each of these pages there is a header, there's that item ID index array, there's then some free space, and then the actual items that are stored in each of these leaf pages. We are going to take a look at the internal structure of each of these leaf pages in just a little bit. Now, the next thing I want to do is kind of take a look at the raw data, or not raw data, but just some of the data that is actually stored in each of these pages. So to do so, rather than opening up our hex editor right away again, we're going to use an extension that's going to allow us to very easily view some of the data that is stored in each of those pages. The first thing we're going to do is run a command create extension page inspect. An extension is some piece of code that gives us some additional functionality inside of Postgres. In this case, the page inspect extension gives us some functions we can use to take a look at the data that is stored on different pages inside of either an index or a heap file. All we have to do is run this, and then we should see some result that says, "Hey, extension has been created." Now for me, I have already created this extension previously, so I get an error right here that says, "Hey, it already exists." So by just running that command, we now gain access to a couple of different functions that are going to allow us to inspect the data on each page of our index. So let me show you one right away. I'm going to do a select star from BT underscore meta P, and then users, username, IDX. So BT stands for B tree, and then meta P stands for meta page. So we are trying to retrieve information off the meta page of the user's username index right now. So let's run that and see what happens. And we get back a lot of information and a lot of columns that, well, don't really make a lot of sense. Who knows what these are all about? The only column in here that really makes a difference for right now, or the only one we really care about, is root. So root is the index of our root page inside of the index file. So we start off at page 0 right here, then page 1, 2, and 3. So inside the actual file on your hard drive, the root page is at index 3, using 0 index, of course. So now we can try to fetch the information off of that third page, and we'll see the data that is actually stored in the root node of our index. To do so, we're going to write out a slightly different command. We'll do a select star from BT page items, then users, username, IDX, and we want specifically page 3. So as you guessed, this stands for B tree, get all the items off of a specific page. Let's run that and see what happens. All right, now this is some very useful information right here. So it's a little bit challenging to read, but I'll walk you through it step by step. So first off, what exactly is the root node all about? Well, just a quick reminder, we discussed this a little bit ago. So here's a diagram we had previously looked at for our index. At the very top is our root node. The primary goal of the root node is to give you some directions on which leaf node you should go to. So that is what the root node is all about. And that's the information that we are being presented right here. We are being told that if we have some data matching some condition that is listed over here inside the data column, then we should go to the page index listed inside of the CTID column. So in other words, if we satisfy like some data criteria right here, we should go to page 1 inside this index. So in other words, page 1 is leaf node 1. If we satisfy some other data criteria, then we should go to page 2. And that's where we're going to find some information about the record we're going for. You'll notice that we do not see an index of 3 here. That is because index 3 is the actual root node itself. We are looking at the root node right now. So all the CT IDs right here, 1, 2, 4, 5, 6, 7, 8, those are the index of the different leaf nodes that we can go to. All right, so now, what about the data column? I said this is like the criteria that we're looking up. How do we actually interpret this stuff, and why is the first one totally empty? Well, to be honest, on this diagram where I said that there's some kind of comparison in the root node like this going on, I was kind of exaggerating just a little bit just to make things a little bit more clear. In reality, the comparison that we do here is a little bit more complicated. So to help you understand how this kind of comparison really works, we're going to diagram out the actual structure of our index. So we're going to fill in some values for our root node and then a couple of different leaf nodes just to get a better idea of how all this stuff works together. So first off, we are currently looking at page 3. That is our root node. So we can imagine that anytime we want to look up some particular value, like some username, we would go to the root node, and then we would go through some different comparisons listed right here. So what are those comparisons? Well, essentially, it's coming from these data values right here. We're going to ignore the first row for just a moment. So the first row would represent this box right here, pointing us to page 1 leaf node. And I know it's page 1 because, again, I've got the CTID right there of 1. So this is essentially a pointer to page 1. The next possible page that we could go to would be page 2 and then page 4. So I'm going to fill in those values right away. The next possible one we could go to is page 2 and then page 4. You can see that there are many different leaf nodes we can visit as we scroll through this. We're just going to worry about the first 3 for right now. Okay, so now back to that data column. What's really going on here? Well, again, we're going to ignore that first row and just focus on the second one. So we see some hex value inside of here. What does that data actually mean? I'm going to copy it really quickly. I'm then going to open up a new tab inside my browser and do a search for hex to string, and then just find some random one. I'm going to enter in that hex stuff from the data column, convert it, and I get back Allison14. So Allison14 is an actual username tied to one of our users. Allison14 is some value that is stored inside of our index. So what does it mean to have Allison14 right here at the second row? Well, what it really means is we go to that kind of box right here that represents that second row. We would say Allison14. We only want to go down to here, or maybe a better way of stating this would be all the different values inside of leaf node are guaranteed to be greater than or equal to, when alphabetically sorted, Allison14. That's what that data value really means. So we should only go into leaf node page number 2 right here if we are looking for some value that is greater than or equal to Allison14. So now we can kind of imagine what happens when we first come into this root node. We would go to the first cell right here. We would skip over it because it's empty, and we would say, okay, do we have a value that is greater than or equal to Allison14? If we do not, we would go back to the previous and go down to page 1, and that's where we would find the username we are looking for. Otherwise, if we are looking for some value that is greater than or equal to Allison14, we could possibly go down to page 2, but first we would probably want to check the next possible page over. So the next possible page over, we're going to take that data right there once again, do that same conversion, and we get Austin.Andrika96, which I'm going to abbreviate as just Austin.O. The next cell over is all greater than Austin.O. So now if we have a value that is greater than Allison14, we would go to the next one, say, do we have a value that is greater than or equal to Austin.O? If we do, then we would kind of continue on the comparison. Otherwise, if we have a value that is less than Austin.O, but greater than or equal to Allison14, that means we would go down into page 2. Okay, so I know that kind of process is a little bit confusing, but basically we start on the left-hand side and go over until we eventually kind of fail this comparison, and as soon as we do, that is a sign that we need to go kind of back one step and go down to the respective page. Okay, so now that we've got a slightly better idea of what's going on there, and I know that's a little bit confusing, but just bear with me for a moment. Now let's try going down to an individual page and see what information is actually inside there. So I'm going to go back over to pgadmin, and I'm going to try to fetch page 1 in this case. So I'm going to update the query to page 1, and let's see what data is actually inside there. Okay, so once again, this is all very useful stuff. For just a moment, we're going to skip over the first row. The first row on a leaf page has very special meaning, so we're just going to forget it for just a moment. We're going to go to 2. So 2 is going to be the first possible alphabetically sorted record out of our entire table. So if we take data right here, we take that hex value and convert that over, I can guarantee you this is going to be if we were to sort alphabetically, this would be very, very high on the list. So like probably username starting with like an A and then an A or something like that. So if I convert it, as a matter of fact, yeah, we get Aaliyah hints. So this is, if we consider sorting all of our different usernames, this would be at the very, very top of the list. So Aaliyah hints is the first user who is stored inside of this leaf node. So we'd say Aaliyah, and I'll abbreviate just as hints. Now, in addition to getting that username, we've also got the CTID right here. Now, previously, we saw the kind of first value inside the CTID was a page that we should go to kind of look up a leaf node. But when we were actually looking at a leaf node, the CTID takes on a slightly different meaning. When you are looking at a leaf node, the CTID represents the page and the index in that page of where we can find this record inside of our user heap file. So in other words, if we go into our user heap file right now, and we went to page 33, index 43, we would find the user corresponding with the username of Aaliyah hints. And I can prove that to you very easily. I'm going to write out a quick little query. I'm going to do a select CTID and star from users where username equals, I want that Aaliyah hints value. There we go. Now I'm going to make sure I clean up, there's that little extra red dot right there. I'm going to make sure I just delete that. So we're going to try to find some user with the username of Aaliyah hints. We're going to print out all the information about them, and then we're also going to print out their CTID. Now, you might recall that our users table does not have a CTID column inside of it. Well, it turns out that every row actually does have a CTID. It's just kind of invisible to us unless we specifically ask for it inside of our query. And that's what we're doing here. So when we run this query, I'm going to expect to see a CTID for Aaliyah hints of 3343. I'm going to run that, and sure enough, here is Aaliyah hints from our users table, and Aaliyah was found on page 33, index 43. So that is the actual kind of index operation in action right there. So we have very clearly identified. Let's go back to this diagram right here. We have very clearly identified that on a leaf node, we are storing some username along with an index or some kind of pointer of where to find the person with this username inside of our heap file. So rather than Alf, it was really Aaliyah H. And then it told us that we could find Aaliyah H inside of our users table at some particular block, at some particular index inside there. So that's really how the index is working. That's what it's all about. And I still want to go a little bit further, so let's keep going on here. So I'm going to redo the BT page items page 1. So Aaliyah hints is the first actual user that is stored inside this leaf node. And then we can find the very last user stored in leaf node by going down to the very bottom. And there's the last one right there. So I'm going to do another translation of data. I'm going to take that, turn it into a string. Looks like we get Allison.r. So let's update diagrams. We got Allison.r. And Allison.r can be found at CTID 8230. So I'll put in 8230. I'm also going to go back and fill in Aaliyah really quick. So Aaliyah was at 3343. There we go. And then there's definitely a ton of additional values here in the middle, but we're not going to worry about those for right now. Okay, so now the last big thing is, what's with that first row right there? What's that really all about? Well, this first row is not really saying that there's some user with this data at this particular CID inside of our user heap file. Instead, we can ignore the CTID for this very first row. This very first row is actually a pointer to the next user, or the first user inside of the next leaf node over. So it's kind of a pointer that allows us to jump directly from this page over to the next page. So if we ever wanted to find all of our users in alphabetical order, we could go all the way down to page 1 to start. We could go through all the users inside of here, and then we can use that little pointer to automatically jump over to page number 2. Now, if you're not coming from a real strong computer science background or something like that, if you're not familiar with trees or pointers and stuff, this might sound a little bit kind of weird or unimportant. Basically, this pointer thing, or this first row right here, is an efficiency thing. It is a performance thing. It allows us to iterate through all of our different users in a slightly more performant fashion. That's what this is all about. So again, this is for the first row inside of a leaf node that we see inside of specifically this extension. It's just a little pointer over to the next leaf node. Okay, so let's now take another look back at our root node. So that's at 4. Or excuse me, not 4, it's at 3. My mistake. So we just went through page 1. Let's now go on to page 2. So that's the next leaf node. So we're going to print out page 2. We once again get that first row that has some very special meaning tied to it. We're going to ignore it. So the actual first value that is stored inside of page 2 is at row 2 right here. So let's get that data. I'm going to do that same conversion. And you're going to see a little bit of a surprise here. When I convert it, it's Allison 14. Allison 14 was the first row that we just saw at page 1. So that pointer that we just looked at a second ago, it had a username of Allison 14. So really that was a pointer over to page 2, specifically the first record in page 2. So we can now see very plainly that Allison 14 actually has a CTID of 20 and 7. I'd put in the 20 and 7 right there. Then there's definitely some additional intermediate nodes there, or some intermediate values. That's all those additional rows. Eventually we can go down to the very last one to see what the very last user is inside this leaf node. So in this case, I'll do another quick copy paste, convert that. We've got austin.im. So over here, that's austin.im. And they've got a CTID of 7418. Where's my diagram? There we go, 7418. And then once again, we can take a look at the very first row. The very first row right here has a name of austin.andrika. So that very first row is a pointer over to the next page. And it's saying at that first page, the first entry is Austin Andrika. And so now once again, if we printed out page 4 and took a look at the first actual row inside there, I bet you anything that right there is going to be Austin.Andrika. So let's check page 4 very quickly. Here's page 4, print it out. I'm going to find the first actual record. So I'm going to find their username really quick, do the conversion, and I bet you anything it's going to be Austin Andrika. Yep, sure enough, it is. Okay, so at this point, I think we've gone through kind of enough iterations here. We have seen that there is the root node. We've got some directions inside the root node that we can use to do a comparison of deciding when we should kind of descend down to a leaf node. Each leaf node has the actual data that we're storing inside the index, so the actual username, along with the CTID, which is the pointer over to our user heap file. The first digit right there is the block that this user can be found in inside that user heap file, and the second is the index inside there. All the different usernames are sorted in alphabetical order, and then inside of each leaf node, we get that little pointer over to the next leaf node. And that's what allows us to iterate through all of our different users without having to do some kind of expensive iteration operation of kind of going back up to the parent, going over to the next node, going down to the child, and continuing on from there. Ooh, okay, so that's a lot. But we're not done. One last very quick thing. Last thing I want to show you really quickly is this actual structure, and just make sure it's really clear that this is the same structure that we saw back inside that user heap file. We're reusing the same structure for storing the index as well. So we're going to open up our hex editor again. We're going to take a look at some of the different pages and just very quickly say, yep, looks like it's the exact same structure. Okay, so to open up that index file inside of our hex editor, we first have to figure out where that file is on our hard drive. So I'm going to walk you through the steps for that very quickly. Kind of where we went through this previously when we were talking about opening up that heap file, but let's just do it again very quick. So I'm going to do a select OID dat name. Notice that's not data, it's just DAT from PG database. Okay, so that's going to give us the name or the identifier for our database itself. So for me, once again, it's 22442. I'm just going to keep that in mind really quick. I'm then going to print out where all the different database files are stored, or essentially my data directory on my machine, which I can do with a show data directory. So that's where all my database files are stored. So I'm going to open up that directory inside of a file inspector. Really quick here. Let me take that link. There we go. All right, I got it. Oh, it's on my second monitor. Let me drag it over. There we go. Okay, so remember, we're going to go into that base folder. Inside there, you should see a folder with the same identifier that we got from step number 1. So there's my folder 22442. I'm going to open that up, and here's all the individual files that represent all the different objects we have inside this database. So every one of these files represents either a table, an index, a sequence, and so on. Now we need to figure out which file actually represents our index itself. So for that, we're going to run one more command. We're going to do a select rel name, and what else do we want? Rel kind, I think, from PG underscore class, where rel kind equals I think we might need some additional identifiers here. Yeah, I think we also need a rel ID, I want to say. Let's just do a select star. Okay, that's better. So we're going to scroll through this list and find our user's username index. I'm going to scroll through. I might have to go down a little bit. And eventually, hopefully I didn't already scroll past it, because I glanced at my other monitor really quickly. Ah, there it is, right there, hiding at the bottom. So I got a user's username index. I can use the OID. Technically, the OID might be different from the file name. You can actually guarantee that you're looking at the right file by looking at rel file node. That's definitely the right name right there. Usually the OID and the rel file node are going to be identical unless you do some very specific commands. So I need to find file 22713 inside that directory. Okay, so I'm going to go down to the bottom. There's file 22713. So this file right here is what contains all of my index data for that user's table, specifically the username column. Okay, so now once again, we're going to open this up inside of our code editor, or really any hex editor you want to use. So I'm going to use Visual Studio Code. I'll do the drag and drop. I then get asked if I want to open this file anyways. Yeah, of course I do. And then right away, we're going to see a ton of different usernames. And we definitely only see usernames here. We don't see any other IDs created at. We don't see phone numbers, bios, anything like that, unlike the user heap file. So I'd say we are definitely looking at the correct index file right now. Now, there's a lot of weird looking symbols inside of here, so we're going to open this up in the hex editor mode. If you're using Visual Studio Code, just a reminder, you can do that with a Command-Shift-P or Control-Shift-P on Windows, and then search for hex editor. And once again, we get all these different hex values. All right, so right away, we are looking at page at index 0, which is our meta page. These first 24 bytes right here, just like the heap file we looked at previously, are the header for this particular page. Then there's a ton of other, well, I shouldn't say a ton of information. In this case, there's very little other information. We can pretty much just see meaningful data spanning from about right there to right there. And then everything else on this page is just zeros, which means there's no data whatsoever. So the meta page is, well, very small and stores just a little bit of information. So let's scroll on down, and we're going to try to find, where's our diagram? We're going to try to find leaf node for page 1. So essentially, just scroll down to page 1. So we're going to find that at the offset or row 2000. So we're going to scroll down, down, down a whole bunch until we get to 2000. Just about there. And here we go. So here's 2000. This is page number 1. So the data we're looking at right here is essentially the exact same data that we were looking at just a moment ago. If I rewrite that command very quickly, got to look it up really fast. I do not remember it off the top of my head. Select star from BT page items, and then our username IDX at index 1. So this data right here, that's what we are currently looking at inside of our hex editor, more or less. So again, this has the same exact structure of the heap file that we were looking at previously. So the first 24 bytes are the header. We can probably say that right there, you might remember, is the offset to the free space and the offset to our actual data. So then after those first 24 bytes of this page, we then have 4 bytes right there that probably specify the exact same thing that it did back inside the heap file. So that's probably the offset to the index of some particular item and then the length of the item as well. So we can scroll past all these different 4 bytes of identifiers. You'll notice we've got way more inside of this thing than we did on that user heap file we had looked at previously. So then right around here, we enter our free space. Here's the free space section. We can keep on going down a little bit more through all the free space, and eventually we get to where the actual records or pieces of data are stored for this index or for this particular page. So right away, we can start to see some values that look very familiar. There's Allison 14. That is essentially the pointer to our next page. Here's the last record on the first page of our index. That was Allison.r. I can go back to the diagram really quick just to prove that to you. So there's Allison.r. So with Allison.r, we should also see somewhere around here something that says exactly what Allison R CT ID is as well. So in the case of Allison R, she had a CT ID of 82 and 30. So some values around Allison, either immediately before or immediately after, should encode 8230 as well. So I'm going to find Allison R. I'm just going to kind of go back a little bit, maybe right there. Oh, that was a lucky guess. So you'll notice I clicked on that byte right there, and if I look at my int 16, there's the 82. So that is the actual encoding of the block where we can find Allison inside that user heap file. And if I go over another 2 bytes, 1E right there, there's the 30. So that's the actual identifier for Allison inside that particular block. Then we can repeat that same process for all these other user names as well. So there's all the information for Allison. Then I'll go down to the next little bit right there. That's probably the block number 5. And then ID or index 4 for Alicia 7. And then how about right here? Probably, I'm taking a guess, that's probably page 1. ID 41 for Alicia 73. And I think you get the idea. It just repeats over and over. So here's 89 and 50 for Alicia Prosacco 65, and just keeps on going. So here's all the different users stored in this index, along with the pointers to where they're stored inside the user heap file. And if we keep on going through all these different usernames, along with all their different pointers, eventually we will get onto page number 2. We'll keep going, and finally at row 4000, here's page at index 2. So there's the header, there's the 4-byte identifiers to each of the different items stored inside this page, and the process just repeats. So that's it. Okay, well that's probably way more information you ever wanted to have about indexes, but I just, like I said, want to show you how this stuff actually worked behind the scenes. So, I think that is it for right now. Let's take a pause here, and we'll continue on in just a moment. Oh, hold up. There's one last thing I want to mention very quickly. So we have been looking at an index that is for a collection that has about 4,000 or 5,000 rows or so. Eventually, we're going to have a ton of different leaf nodes. And there might be so many that the actual efficiency of this tree starts to suffer from it. at a certain point in time, once you have enough records inside of your index, Postgres is going to decide to add in another layer of leaf nodes underneath. Once that happens, we end up with a structure that looks a little bit closer to this right here. So in this scenario, we've got this kind of middle row right here of nodes. We would not refer to these as leaf nodes anymore. They'd be referred to as parent nodes. The actual data that's stored here is similar in nature to the same kind of comparisons we have up at the root node. So then the very children down here are still referred to as leaf nodes. And this is done just when we get to a certain number of records. It allows us to make sure we can still do reasonably fast lookups. So when does this actually happen? Well, the actual diagram you're looking at here is for our likes index. I went through the process of mapping out a rather sizable portion of the likes index. So that's what you're looking at here. We've got about 750,000 likes inside of our database. So if you take a look at an index over that table, where we have got a ton of additional records, that's where we start to get these additional layers in the middle put in. But when we have far fewer records, like in the case of users, where we have just about 4,000, we've got just that kind of one layer. So just the root and then directly to the leaf right after it. So I just wanted you to understand, or just know that if you try to repeat the same kind of mapping process for a much larger index, you might run into some intermediate parent nodes in between. Okay, that's it for real. Let's pause right here. At this point, we've spent a lot of time talking about indexes and understanding how they work. But we still don't really know when to use an index and how to really evaluate whether a given column should get an index at all. So we're going to start to change that in this section. We're going to start to focus a lot more on how to evaluate what makes a good query and what makes a bad query, and how we can fix a query or make it better at least a little bit by creating an index. The first thing we're going to do is better understand how Postgres handles queries that we hand off to it. So let's take a look. All right, so big diagram right here. I'm going to zoom in at the very top. So we're going to imagine what happens when we feed a query like this into Postgres. So select star from users where username is Allison14. This query is going to be fed into Postgres, and it's going to go through a series of processing steps. It's going to go through the parser, a rewriter, a planner, and an executor. Let's take a look at each of these steps in detail. Okay, so the first thing that happens is the parser. When you feed a query like this into Postgres, immediately Postgres is going to try to take all the different characters of that string and tear it apart one by one and figure out what the meaning of every character in every word is inside there. The parser is going to make sure that what you wrote out inside this query is actually valid SQL. So you have referred to actual keywords that actually exist. They're all spelt correctly. We've got appropriate punctuation and so on, all that kind of stuff. After evaluating this query, it's going to build up something called a query tree. The query tree is essentially a programmatic description of the query that you are trying to run. This is some sample output right here for this query. So I'm going to zoom in and we'll take a closer look at it. So in this query tree, we can see references to all the different parts of that query. So I can see very easily that we've got something here called the select statement. It looks like we are trying to refer to all the different columns that are going to come out. So we've got a reference to star right there. Here's our from clause, where we are trying to pull some information out of a user's relation, essentially the user's table. Here's the where clause. We're trying to do a comparison using equals. Oh, actually the equals is that part right there. And we are trying to compare between the username and the string Allison14. So again, this is referred to as the query tree, and it breaks apart the entire query that you feed in into these more kind of logical steps that can be understood by a computer program. Once the query tree has been written, it's then handed off to the rewriter. The rewriter is going to take a look at the query tree and possibly make little modifications to it if Postgres thinks that certain parts could be executed a little bit more efficiently. However, what happens much more frequently is it applies the idea of views to the query tree itself. Now, we're not going to worry about what views are just yet. We are going to cover views very shortly. But when we talk about views, we'll kind of come back to this topic and discuss what this little box right here really means. Essentially, the rewriter is going to take the query tree and just make a couple of small adjustments to it. After that, the query tree is going to move on to the planner. Now, the planner is what you and I really care about. This is the big thing that we're going to focus on. The goal of the planner is to take a look at the query tree, figure out what information you are trying to fetch, and then come up with a series of different plans or strategies that could be used to actually get that information. So in our case, the planner might realize that you're trying to get some information out of the users table based upon a username. So it might say, you know what, we could probably get that information very efficiently by using the user's username index, and then use the references or pointers inside there to go and fetch some appropriate users from the user heap file. The planner might also come up with a plan where it says, you know what, rather than using the index, we could just go into the user table directly, fetch all the different users, and do a one-by-one search through them. After coming up with all these different plans, the planner is going to evaluate which one it thinks is going to actually execute the fastest, and then choose that plan to actually run. Now, the actual strategy, or what actually goes on behind the scenes to figure out which of these different plans is the most efficient, is something that we're going to go into in great detail in the next couple of videos. After the planner decides on what the most efficient strategy is, it is handed off to the executor, which is going to actually run the query. The executor gets a number of rows, and that's it. That's the entire process. So again, out of all this, the planner is a thing that you and I have generally a lot of influence over. It's the thing that we're going to spend a lot of time on, because we're going to use the output of this planner quite a bit to really understand what makes a fast query and what makes a slow query. So let's start to go into more detail on this planner in the next video. Out of all the steps of this query processing pipeline, the most important one that we're going to take a look at is the planner stage. So let's take a look at one or two keywords that we can use to inspect the output of this planner step. All right. So explain and explain analyze. These are two keywords that you're going to become very, very familiar with. They are some of our best tools for understanding how a query is actually being executed and figuring out how to improve the performance of that query as well. We are going to place either explain or explain analyze in front of different queries that we run. If we write out just explain in front of a query, then Postgres is going to build up a query plan and then show us some information about it. It doesn't actually run the underlying query, however. If we put in explain analyze, Postgres is going to build up a query plan, it's going to execute the query plan, and then show us some information about the query plan and some statistics around how long it took to actually run it. So in other words, explain kind of tells us what Postgres plans to do, but doesn't actually do it. Explain analyze tells us what Postgres intends to do, and then actually executes it as well. Now, quick note, we are only ever going to use explain and explain analyze while we are trying to do some performance evaluation. We're never going to leave these in any kind of production application where we want to actually fetch some data. And the reason for that is that if you make use of explain or explain analyze, you do not actually get back the rows that are coming out of your query. Instead, you just get the query plan itself and possibly some information about it. All right, so let's take a look at how we would make use of explain and explain analyze. So we're going to first write out a very short query. We're going to try to do a little join this time around. Rather than just fetching some particular user, as we've been looking at so far, we're going to instead join together the users table and the comments table, and then print out all the comments that were created by some particular user. So I'm going to do a select username and contents from users. We will join comments on comments.userid equal to users.id. And we'll say that we only want to find the comments where they belong to someone with the username of Allison14. Okay, so let's just run that as it stands right now and make sure that we get some output that looks more or less correct. Well, yep, I'd say that looks pretty good. Okay, so let's now try applying the explain keyword. So notice that we put explain just directly in front of the query. I'm then going to run that, and you'll notice that we no longer get back any data. Instead, we get back just this one single column that contains something called the query plan. So this is the plan that Postgres plans to execute to actually get some information. We're going to take a look at what this query plan means in just a moment, but first, let's also do a explain analyze as well. So I'll run that, and you'll notice that now we get the exact same query plan, but we also get some information around how long it took to run it. We also get some information about how long it took to plan and execute the query plan down here as well. Now, one other thing I want to mention very quickly. If you are ever running SQL directly, so in other words, just writing out SQL by itself inside of some kind of arbitrary tool, you can always make use of explain analyze, as we are making use of it right here. But if you are making use of pgadmin, you can also use a feature to run explain analyze for you that is built into pgadmin. Let me show you what I mean. I'm going to delete explain analyze up here. I'm then going to find the play button. I'm going to go over just a little couple steps, and we'll see a step right here, or a little button. And if I hover over it, it says explain analyze. So if you just click that button, it's going to do that same kind of explain analyze step, but then also show you some kind of interface that is built into pgadmin to better explain the result of the query. So you get this nice kind of graphical view of what's going on. You get some more analysis and some statistics over here as well. Now, if you're going to use this feature as it's built into pgadmin, you're going to very frequently want to click that little down arrow next to that, and then enable pretty much all these different items. I'll then, after enabling all of them, click on the Explain Analyze button again. Now if I go to Analysis or Statistics, I start to get a lot more interesting information as well. Now we're going to use this feature built into pgadmin 1 or 2 times, but for the most part, I really just want to show you using Explain, Analyze by itself, and then interpreting this output right here, because you only get that kind of pretty print up when you're making use of pgadmin. And there are going to be many scenarios where you want to do an explain analyze when you are not using pgadmin at all. So you really have to understand how to run this manually and interpret the outputs rather than relying upon pgadmin to give you that kind of nice, pretty display. Okay, so with all that in mind, let's take a quick pause here. When we come back to the next video, we will start to understand what this entire query plan right here is really telling us. I've executed explain analyze, and I'm taking a look at the output right here. So again, refer to this as the query plan. Because I included the analyze keyword, we also have some information about how long it took to execute the overall query plan, along with some information about how long it took to execute individual steps. So let's now take a look at a couple of diagrams and really understand what this stuff is telling us. Okay, so I took that query plan and just put it into diagram format right here. Now out of all these different rows, I want you to notice how some of them have little arrows at the very start of the row. So I've got a little arrow right there, there's one right there, one right there. Each of the rows that have an arrow on them, we refer to as a query node. So this is essentially some step where we are trying to access some data that is stored inside the database, or we are trying to do some processing. So that is true of all the little arrows, or all the rows with an arrow. In addition, the very top line up here is technically also a query node as well. So even though it's not actually listed, you can kind of imagine that there's a little arrow up there. All right, so the way we read this is by going to the innermost rows. So in this case, it is this index scan on username index. Every single place where we see one of these little arrows, we imagine it is trying to access some data inside of our database or inside of an index, and then it is trying to emit that data or pass that data up next to the nearest parent that has an arrow on it. So for the index scan right here, the nearest parent that has an arrow is this hash line. So we imagine that the index scan is accessing some information on our hard disk. It is then passing that information up to the most parent or the nearest parent node, which in this case is the hash step, the purple one right here. The hash step is then doing some processing on that data. It is then emitting that data up to the nearest parent node, which in this case is the hash join. So information in total is going from index scan. We're then doing some processing on it on the hash step, and then the output of that is going to the hash join step. At the same time, we've also got a step inside of here, sequential scan on comments. You'll recall that a sequential scan means we're going to access all the different rows inside of a table. So we're taking everything inside a sequential scan, and we're going to also pass up all those rows up to hash join as well. So in this case, this hash join step is combining the output from the hash and the sequential scan nodes. Then finally, the output of the hash join step is our final result. So that's the actual rows that come back to us from the query. Okay, so in addition to telling us the individual steps and how they're kind of sharing information amongst each other, you'll notice that there are some other interesting numbers inside of here. Let's take a look at the hash join line by itself. So here's the hash join line. I first want to focus on just kind of the first set of numbers inside of here. So the term hash join is telling us exactly how this particular node, or this line right here, is either generating data or processing some data. In this case, we are doing a hash join operation, which, as you might guess, is going to implement some kind of join process, like the same kind of join that we put into our query that we wrote just a moment ago. We're going to eventually take a look at all the different kind of processing steps that there are between hash joins, hashes, index scans, sequential scans, and so on, and get a better idea of what they are all doing for us. So we'll take a look in more detail about this kind of node in just a moment. Immediately after that, we have something called the cost. Now we're also going to go into great detail on cost. So for right now, all I'm going to say is that the cost is kind of telling us the amount of processing power that is required for this step. Now for right now, what I want to really focus on are the two sets of numbers immediately after that. So we have rows of 11 and width of 81. So rows is an estimate or a guess at how many rows this step right here is going to produce. And then the width is an estimate of the average number of bytes for each of those rows. Now these two numbers right here are actually really interesting for one particular reason. Let me show you something interesting. I'm going to go back over to pgadmin. I'm going to find that analyze keyword and delete it. So now we've got just explain select blah blah blah. So I'm going to run that, and you'll notice that we no longer have any information about how long it took to execute any of these different steps. And the reason for that is that we did not actually execute any of these steps. So at this point, when we run this with just explain, in theory, we have not really accessed or gone through all the information in our users index or the users table or the comments table. We have not actually accessed any of that data. However, you'll notice that we still have a rows number and a width number on here. Now that's actually kind of a mystery. How does Postgres know, or how is it able to make a guess at the number of rows that we're going to get out and the average width of each of those rows if Postgres did not actually access the users table or comments or the users index and so on? So in other words, how is Postgres able to make these kinds of guesses at how long it's going to take to execute each of these steps when it just doesn't know about the data that actually exists inside of our tables? Well, it turns out that Postgres actually keeps some very detailed statistics about what is going on inside of each of your different tables. Let me show you. So we're going to write out another very quick query. So I'm going to comment that one out, and then we're going to replace it with, let me find my notes here. There we go. We're going to do a select star from pgstats where table name equals users. So pgstats is a table that is maintained by, you guessed it, Postgres. It has detailed statistics about all the different values and all the different columns of your different tables. So right now we are printing out only statistics about columns inside of our table of users. So let's take a look at what comes back. So we are being told that these are all rows concerning the users table. We're then being told that these are some statistics about the username column, the bio column, avatar, phone, email, status, and so on. We even have statistics about ID, created at, and updated at. So these statistics inside these tables is what allows Postgres to kind of make a guess at some of the different number of rows coming out of each of those steps of the query plan, and possibly the number of bytes for each of those rows as well. So take a look at some of the columns inside of here, and I bet you could guess what they're all about pretty quickly. So we've got, say, average width right here, which is the number of bytes on average for a biography. You'll notice that it's, in this case, say 45. We've got a username of 13. And you'll notice that this 13 right here doesn't quite line up to the width of 81 that we saw back over here. But remember, that's because the hash join step right here is showing us the average width of not only a username, but also the contents of a comment as well. So the average width of 81 might be 13 on average for the username, plus some amount also for the contents of each comment, which is, I would guess, probably about 68 or so. Now beyond that, we've also got some interesting other statistics in here as well. Let's take a look at, say, how about the status column? So remember, status right now has only values inside of it of online or offline. So there's a column inside of here, or this statistics table of most common values. So this records the most common values that are found inside of this column. So in other words, the status column most common values inside there are online and offline. We are also told that that's actually the number of distinct items inside there. We are also given the frequency of both those items as well. So on average, about 50.1% of rows have a status of offline, and about 49.8% have a status of offline. We also have some information for Instagram, or excuse me, a histogram, not an Instagram. A histogram, which in this case is kind of telling us the average distribution of items given some kind of sorting mechanism. So there's some other rows, some other columns inside of here as well, but you'll see that they are not actually being used. So this stats table is how that query planner is able to make a guess about the efficiency or kind of the cost or the outcome of each of those different steps without having to actually do any processing of those steps ahead of time. All right, so now that we've got a better idea on where some of these different values are coming from, let's start to dive a little bit more into the cost of these different steps in the next video. In this video, we're going to examine the idea of cost around each of these different lines. Now, I gotta be honest with you, this video is gonna be a little bit long. It might be a little bit boring, a little bit confusing, but at the very end, I'm pretty sure that you're gonna walk away with a good idea of what cost is all about. So I gotta beg you, please, just a little bit of patience, and we're gonna get through this as quickly as possible. All right, so we're gonna first begin with a working definition for what cost is referring to. For right now, in lieu of any kind of better definition, we're gonna say that cost is referring to the amount of time in, who knows, maybe seconds, maybe milliseconds, to execute some part of our query plan. Now, the reason I say that that is a working definition is that it's not technically 100% accurate, but it's a good enough definition for right now. It is good enough. So with that working definition, I now want to take a look at another diagram that we had looked at previously. Remember, this is our query pipeline. So we're going to think about this query for just a little bit. I want to forget the join statement that we were looking at in the last couple of videos. And I want to revisit this query again. In particular, I want to take that query and I want to really think about this planner step. So remember, in the planner step, the planner is going to take or generate a query plan, which is essentially a way to actually execute the query. Now, I had said that in this case, maybe the planner would decide to try to use the username index to look up the IDs of all the users with some particular username, and then use the pointers that it got out of the index to open up the user heap file and load up just the appropriate pages out there and fetch the appropriate users. And then alternatively, maybe the planner would decide that another valid way of executing this query would be to just take a look at all the users in our user heap file and search through all of them. Now, I made the assumption that probably using the index would be more efficient or faster, but let's actually revisit that decision. Let's try to figure out which of these two query plans actually would be more efficient using all the knowledge that we now have around how heap files work, how indexes work, and so on. At the end of the day, we're trying to figure out how the planner can really decide on which of these two operations is more efficient without actually running the query itself. That's what I want to try to do. Okay, so I sat down and put together kind of a series of steps on how I think, based on all of the knowledge we have around heap files, indexes, and so on, that each of these query plans might actually get executed. Let's walk through each of them very briefly. Okay, so first on the left-hand side, we're going to first take a look at the username index. So we're going to try to find some users with some very particular username by looking up that username inside the index, and then going over to our user heap file and loading up the appropriate users. So just really quick, let's walk through that process. So step number one, we're going to get our root node. Let's just kind of walk through it in this diagram over here. So we're going to go to our root node. We're then going to use some directions inside the root node to decide which leaf node we need to go to. So maybe in this case, it's this one over here. We then might find some appropriate user that we're looking for. Let's say that this actually says Allison. That would then give us a pointer right there into our heap file. It would say, go into the heap file. You can find Allison in block 1 at index 2. That would be go over to block 1, index 2. So that's kind of step number one. So we go into that root node, go to some random child page, take a look at all the values inside that page. Once we get that pointer, we would then open up the heap file. We would jump to some particular block that has the user that we're looking for and load up that user. And that's the entire process. That is what we are doing here. So that's if we are using the user ID, or excuse me, the username index. So now let's consider what would happen if we were not using the index at all. What would we have to do to find all the users with some particular username? Well, in this case, it's a lot more clear. We would open up the user heap file. We would load all the users from the first block, because remember, that's what we're really working with here. We got all the blocks inside that heap file, so we'd load up all these users. Then, user by user, we'd process each one and see if they contain the correct username. Then once we process all the users out of the first block, we'd move on to the next block, process all the users there, move on to the next block, and so on. So at the end of the day, that's really the work that we have to do for each of these options. Now, I want to go one step deeper. I want to try to assign some kind of some kind of cost per se, maybe a cost of sorts, or some kind of value to each of these. If we had to assign some kind of value to each of these steps or each of these operations, and if I had to say to you, oh yeah, I think that this way is 10 times more expensive than this way, how could we somehow get to some kind of numeric value to kind of evaluate or score which of the two are better? Well, if we had to kind of assign a score, maybe a good way of doing that would be to think about the number of different pages that we have to load up off the hard drive. So let's try that out. All right, so let's say that for our index over here, in order to first satisfy this index step, we maybe just have to load one random page off the hard drive. Because at the end of the day, you and I know that, well, we really only have one user with that username. So we just go to the root node, we then jump to some very specific child node and load up all the users out of there. That's probably it. That's the entire operation. So to go through this entire index stuff, we're just going to kind of forget the root node for just a moment. Technically, it would be 2 pages, but let's just forget that root node. So all we're really doing over here is fetching one random page off the hard drive that has all those pointer values inside of it. Then after that, we would open up the user heap file. We'd jump to some very specific block. So that means we're just fetching, again, one random page or one random block, and that's it. So in total, for the left-hand side over here, we are kind of just talking about fetching 2 random pages off the hard drive, and that's it. That's kind of the amount of work that we are doing. We're going to forget the fact that we kind of have to process any individual rows or stuff like that. At the end of the day, we're kind of just having to fetch 2 random pages. Now for the right-hand side over here, the amount of work that we are really doing, again, kind of neglecting the fact that we have to process each individual row, we just think about the amount of work we have to do involving the hard drive. We're talking about repeating this process right here for every page inside of our user heap file. So we're really talking about doing this amount of work for each page. So it's kind of like number of pages in user heap file. That's how many pages we have to load up. We have to load up the number of pages equal to the number of pages in the user heap file. Now, at this point in time, it might seem like a really straightforward calculation. Let's say that our user heap file has 100 pages in it. Then for this strategy, we're talking about loading up 100 pages. And for this strategy, we're talking about loading up just 2. So if we just think about this in terms of how many pages we have to load off the hard drive, at first glance, it's really obvious that this stuff on the left-hand side is more efficient because we are loading up 50 less, or by a factor of 50 less pages. It's 2 versus 100. Now, before we just kind of run away with that, there's one quick thing I want to throw out there. So for the index stuff, we are specifically talking about fetching random pages. And there's actually kind of a little bit of a difference here. Anytime that we are loading data off of random areas of our hard drive, there's usually actually a performance penalty associated with that. So if you are just randomly jumping all over your hard drive and loading up data from all over the place, that usually takes a lot longer to do than if you load up a bunch of data that's kind of all in one line. So in other words, if you're loading up a ton of data from one file, just kind of block by block throughout that file, that generally is a faster operation than jumping all over the place. And just to make sure that's really clear, let's just clarify that with a diagram really quickly. So in this diagram, if we load up block 0, and then block 1, and then block 2, we'd refer to that as a sequential load. We're loading up block by block in order. This typically occurs a little bit faster than if we do a random load. So if we were to jump directly to block 2, and then go back over to block 0 or something like that, usually there'd be many more blocks in between, but you kind of get the idea. If we're jumping all over the place, this usually takes a little bit longer to actually run. So with that in mind, we kind of have to take into account the fact that this over here is a sequential load, because we're essentially just loading up every page of users, block by block, page by page, throughout our entire user heap file, And over here, albeit only 2 pages, these are random loads, so they might take a little bit longer to actually run. So we should probably account for that in some way in our estimate. So here's my idea. How about we say we'll just make a total random assumption here. At the end of the day, it's a pretty big assumption and it's quite random, but let's just assume for a moment that loading up a random page of data takes 4 times longer than loading up pages sequentially. That's a really, really big assumption. But you know what? Let's just run with it. So now that we've made this assumption, we can now start to kind of quantify the actual work done by each of these different approaches. We could do it with a calculation like this. So on the left-hand side, we loaded up 2 pages in a random order. And then we said that anytime we are loading up a random page, we're going to say that costs 4 times as much processing power. So at the end of the day, we might say that it costs 8 for this index approach. Now, quick question for you. Does this 8 have any units associated with it? Is there some kind of like milliseconds units? Is there any kind of like seconds units? Well, no, not really. I guess technically there's like kind of units of 8 pages loaded in random order per sequential. There's essentially, at the end of the day, it's really hard to say that there's any kind of units whatsoever associated with this value. It's definitely a score of sorts. There's not really any unit associated with it. Just want to point that out really quickly. Then over here on the right-hand side, we said that, well, maybe there's about like 100. In reality, just, there's 110 pages in our user collection. So I've got the actual accurate value here, 110 pages. We did say that they were loaded sequentially. So we're going to say that sequential loads kind of get that like baseline value of 1. So it just means, hey, this is kind of like our baseline. So doing the random load order, 4 times more expensive. That implies that 110 pages loaded sequentially, we'd multiply it by 1 just to say this is kind of like our baseline value. So at the end of the day, we might give this a score of 110 and this a score of 8. Now, is this a scientific comparison? Yeah, probably not. But it's at least better than nothing, right? It's better than nothing at all. It's something that we can at least say, well, it looks like maybe there's a difference here of, I don't know, off the top of my head, maybe about 13, a factor of 13. So if I was a gambling person, if I was happy to gamble, I would probably bet that this is going to execute faster than doing this kind of sequential load over here on the right-hand side. So at the end of the day, if I had to make a choice based on the work we've done so far, I would say this is the plan I would go with. I would want to use my user name index, get some lookups, and then go over to our user collection or user table, and that's it. That's what I would do to execute this query. Now that we've finished this entire process up, we're going to take a quick pause and then relate this entire idea and how we just calculated these values back to the cost that we saw back on our query plan a little bit ago. In the last video, we took these 2 alternative ways of loading up some data. We then tried to guess at the actual steps that were going to be executed for each one, and then assign a score of sorts to each individual step. We then added them all together, and we eventually boiled everything down to one score, so to speak, or you might refer to that as a cost. We then used that to decide which of these 2 query plans would probably be more efficient. Now I want to repeat that same step, but this time we're going to repeat it for one specific line out of our query plan for that join statement that we were just looking at a moment ago. So in particular, I want to try to calculate some kind of cost or score for these sequential scan on comments. So we're going to make a guess at how this step is actually executed. We're then going to try to assign some kind of point value or something like that to each step that goes on behind the scenes. Now in this case, we're not really kind of debating between 2 alternative plans. I want to just take a guess at how we would load up all the comments from our comment heap file in isolation by itself. Okay, so here is my guess at how that is done. So in order to run just this one single line of our query plan, we're essentially talking about fetching all of our comments. And so here's my guess at what is going on behind the scenes. I think that we are probably opening up the comments heap file. We probably are going to load all the comments from the first block, process them in some way, and then repeat the process for the next block. And that's pretty much it. So let's see if we can't try to assign some kind of cost or score to how expensive this entire operation is. So we're definitely going to want to assign some kind of cost for loading up each individual page sequentially. But this time around, just a little bit different than the last video, I want to also try to assign some kind of cost to processing each comment in some way. processing a comment is probably not free. There's probably some kind of CPU time involved with it or something like that. So I just want to make some kind of real big guess or estimate at how long it takes to process each individual row. All right, so I'm going to first assign some actual numbers or quantities here. So I looked up these values ahead of time just before this video. Inside of our comments table, we have 60,410 rows and 985 distinct pages. Now that we know what these actual numbers are, or the quantity of these things we have to process, we have to try to score each of them in some way relative to each other. Well, without a doubt, loading up a page sequentially off the hard drive is definitely a lot more expensive than processing some row. If we're just processing a row, I'm talking about loading a row into the CPU, doing some kind of number crunching or turning bytes into a string or who knows what. We're just talking about a little bit of CPU time, which is probably a lot cheaper than fetching data off our hard disk. So to actually boil this all down to a score, we need to come up with some kind of formula. And here's a formula I want to try to use. I want to say that I want to look at the number of pages that we're loading and multiply that by 1. So we're going to kind of use that as our baseline and say 1.0, that is our baseline score for judging everything else. We're then going to take a look at the number of rows that we have. And I'm just going to go out on a limb here. I'm going to make a huge estimate, just once again, a total estimate. I'm going to say that processing one row is 1% as expensive as processing one page. So in other words, if we processed 100 rows, that would be equivalent to processing one page. Total guess here, but let's just run with it. So a 1% would be essentially 0.01. I'm going to say that's how we can kind of assign a estimate or kind of a cost of sorts to how expensive it would be to load up all the comments out of that comments table. So now using the values of 985 and 6410, let's actually sub those in here. So 985 times 1.0 plus 6410 times 0.01. And I'll do that calculation really quick. And we end up with 1589.1. So 1589.1. There we go. Okay, so now here's the big reveal. That's kind of an interesting number, right? Well, let's take a look at our query plan. Hey, wait a minute. Look at that. We just calculated the exact cost for loading up comments. That's pretty cool. I don't know. That's kind of neat. Good reveal, right? Okay, so what does this all mean? Well, throughout this entire process, we have made guesses at how information is being loaded up. So we tried to guess the number of pages, the number of rows, how many rows were being processed, how many pages were being loaded up sequentially versus random, and so on. We then tried to guess relative to loading up pages sequentially. We tried to guess or assign a factor at how expensive processing one row or loading up one random page was relative to loading up pages sequentially. So all these numbers here, these kind of cost factors, are all relative to loading up a page sequentially. So then we multiplied everything out and said, you know what? Processing one row is 1% as expensive as processing a page. So we calculated some kind of arbitrary value, probably not any units here. The number doesn't necessarily have any meaning. It's not something we could really bank on, but it's something that at least allows us to kind of assign a score to one distinct operation of our query plan. And that's what the cost is all about. It is about getting some kind of vague ballpark value of how expensive this step is relative to other steps of our query plan, or to be able to compare one query plan versus another. Now, just so you know, I did not make up that number right there. That's out of our actual query plan. And this is the actual calculation that is done by Postgres right here to figure out what the cost is for that particular line of the query plan. So now that I've kind of gone through this very long example and kind of led you through to the very end, let's take a pause right here. And I'm going to show you the actual concrete hard values and the actual real rules of this entire system in the next video. All right, so now that we've gone through this entire process, let's boil this all down to some real hard rules. So first, here's the actual full equation for calculating the cost of any arbitrary step of your query plan. So some of these different terms you're probably going to recognize right away. So we're talking about taking the number of pages read sequentially and multiplying it by some kind of cost factor of sorts. We then add to that the number of pages we read at random and multiply by that some kind of random page cost. you'll notice that just about every step inside this equation is really the number of doing something times some kind of cost factor. The first thing I want to do is show you where these different cost factors are coming from. So for that, we're going to take a look at the official documentation. I'm going to open up a new browser tab and go to that address right there. Okay, so here's browser. There we go. So we are on a page called Query Planning. Sounds pretty relevant. We're going to scroll down to a section called Query Cost Constants, or Planner Cost Constants. So inside of here, you're going to see a couple of different constant values. So these are values that are not going to change inside of your database unless you specifically change them manually. The first one listed out is sequential page cost. So this is an estimate. And by estimate, that's a really not great term here, but it's essentially some kind of arbitrary factor to use to gauge how expensive it is to load up one page sequentially out of a heap file. So notice that the default is 1.0. We've then got some kind of random page cost right here, which is relative to sequential page cost. I'll explain a little bit more on that in just a moment. The default value for random page cost is 4.0. That means that we are assuming that it costs or is 4 times as expensive to load up a page at random out of a heap file versus just loading up a bunch of pages sequentially. We then have some other cost factors down here. So the processing power required to essentially deal with one tuple by the CPU, processing one tuple out of an index, and evaluating one single operator. So an operator being like a multiply, a divide, a subtract, and so on. So for a CPU tuple cost, we have a default of 0.01, 0.005, 0.0025. Now, the one thing that I really want to point out here, and one of the big reasons that we just went through that very long example, is to just make it really clear that all those different constants are all based upon the sequential page cost. The sequential page cost is kind of our baseline value, and everything else is relative to the sequential page cost. So sequential page cost being at 1 means that's our baseline, and we are making the assumption that to fetch a random page out of our page file, or our heap file, is about 4 times as expensive as fetching pages in order. We are also assuming that processing a single row is about 1% as expensive, and then after that, we're assuming that processing a row out of an index is 50% as expensive as that, and then evaluating an operator is 50% as expensive as that. So at the end of the day, our sequential page cost is kind of like the baseline value, and we estimate the cost or the performance cost of all these other operations based upon sequential page cost. And just to be clear, if we change the default value here to like 2.0, nothing else updates automatically. I just mean to say that in theory, it is all based upon the sequential page cost as our baseline. Okay, so let's now go back to our formula. So now we are seeing where these values are coming from on the right-hand side. So they are all constant values. You can change them if you want to, but there are very reasonable defaults already set inside of Postgres for you. So you will not really be changing those default values unless you've got a really good reason for that. The documentation page we were just looking at actually has some reasonable notes around why you might do that. So like there's this green tip box right here. There's some really good discussion in random page cost as well about why you might want to change that. And there's definitely a lot of blog posts online on why you might want to modify these values as well. So that's the right-hand side of all these different terms. Now we got the left-hand side, and I think you're going to figure out what these are pretty quickly. So we've got the number of pages read sequentially, number of pages read at random, number of rows scanned or essentially processed, number of index entries scanned or essentially processed, and the number of times a function or an operator gets evaluated. So we can really take this equation right here and use it to calculate a lot of the different costs that we see back inside of our query plan. So we just did it to calculate the sequential scan on comments cost. We could, in theory, do the same thing to calculate some of these other values as well, but in a lot of other cases, doing the calculation really requires a lot more in-depth knowledge of what is going on. Even figuring out the cost of sequential scan on comments, you and I had to understand that a sequential scan loaded up a bunch of pages in sequence and then process the rows of all of those different pages. So to really evaluate these costs really requires you to have a deep understanding of what each of these different query plan nodes are really doing behind the scenes. So in other words, you might have a little bit of a hard time figuring out where, say, the hash join cost is coming from. Just throwing that out there. Now, last thing I want to mention really quickly about this equation right here, you're going to very frequently see this equation in blog posts and documentation abbreviated with just these two terms right here. And that's because a lot of the documentation and blog posts are showing you how to calculate the cost of a sequential read. So if we are doing a sequential read, think about what would happen to this equation. In a sequential read, we are reading no pages at random. That would go to 0. We are scanning no index entries. That goes to 0. And we are not, probably not anyways, doing any function or operator evaluation. So that goes to 0 as well. So this entire term would go to 0. That goes to 0, and that goes to 0. And we are left with just those two terms right there. And that's why you're going to see this entire big equation very frequently abbreviated as just these two terms. But again, in reality, there is all these other terms going on as well. But for a sequential scan, they go to 0. Now, even the equation I'm showing you is technically not the full story. There is such a thing as a parallel query read, and there is a cost associated with that as well. So you'll even see costs inside of here around parallel setup cost, parallel tuple cost, and so on. There's even like more costs inside of here beyond that. So technically, even the equation I'm showing you is not 100% the full story, but I think you're getting enough of an idea here that basically for every different data loading operation we do, there's going to be kind of a different variation of this equation based upon the different operations or steps that go into it. Let's take just a little bit more of a look at cost values. So in this video, we're going to focus on why every cost has two numbers inside of it. The first thing I want to clarify is that we are not seeing two numbers here because it is a range of estimated values or anything like that. So this is not a range of estimates. Instead, both numbers have a distinct purpose. So the first number that we see in every pair is the cost for this particular step, for the hash join in this case, to produce the very first row of output. And then the second number is the cost for this step to produce all expected rows. Now, even these descriptions are not very helpful, so let me kind of illustrate what's going on here with a diagram. All right, so we're back at this diagram. I've got my query plan on the right, and I've kind of organized all the different processing steps on the left-hand side. So remember, we start off first with the index scan. The output of that step is going to go to some kind of hashing process, who knows what that is. Then the output of that is going to go to some kind of hash join, where some data gets combined together with the sequential scan. So let's focus once again on the sequential scan. At this point, you and I have a pretty good idea of what is going on with a sequential scan. Remember, that means we're going to open up our heap file, read one page, process all the rows on it, go to the next page, process all the rows, and so on. Now, when we really think about that process, I want you to just kind of imagine that step of opening up a page and processing all those different rows. Once we process all the rows on one individual page, we then have some number of rows that are ready to be processed by the next step in our chain. So in other words, when the sequential scan opens up the very first page and starts to process all those rows, it generates some different rows, or in this case, I'm going to call them items, and we can immediately start to provide that first set of items off to the next processing step. So in this case, maybe the hash join. The sequential scan will then move on to the next page, open up the page, process the rows on that, and then we are able to start emitting those rows over to the hash join. So for a lot of these different processing steps, we are doing some kind of long-running processing operation where we are operating over a lot of different rows. In some cases, as soon as we process just one row, we can immediately take that row and emit it or send it off to the next processing step. And that next step might be able to immediately start doing something with that row while the original sequential scan is still running. So the lower bound cost that we're seeing here is what the cost is to just get the very first row, the very first little bit of information, and pass it along to the next processing step. Now, one thing I'm going to be totally honest with you about, in this case, our sequential scan has a cost lower bound of 0, which means it essentially is free, in theory, to start emitting the very first row for this processing step. Now, you and I know that in order for the sequential scan to emit the very first row, we have to open up a page, load all the records, process all those rows, and only then are we ready to start emitting those rows from the sequential scan step. So in theory, getting the first row has some cost associated with it, but the cost is indicated here as 0. And that's true of all sequential scans. All sequential scans are going to say that they have a cost of 0. To be honest with you, I don't really know why that is. If you know why it is, throw something into the QA of this video. Because again, in theory, a sequential scan, to get the very first row, we are doing some work, but the cost here of 0 seems to indicate that is not the case. So to me, doesn't quite make a lot of sense, but whatever, that's what it is. Now you'll notice that in some other cases, such as the hash step right here, the lower bound cost, or the startup cost is how we refer to it, is the same as the total cost, so 8.3 and 8.3. That indicates that for this hash step right here, it is not able to kind of start producing one row and pass it off to the next step. Instead, this indicates that the hashing process, whatever that thing is doing, has to process all rows before it can emit anything. So that means that the hash step is going to receive some information from the index scan. It's going to kind of collect all the records it gets out of the index scan. And then only after it has all these records, it's going to do all the processing on it in one big batch, and then send the absolute total result of all that down to the hash join. So that's why you're going to sometimes see a cost with the identical startup and identical total. Now, why do we care about these costs at all? Why do we care about the startup cost versus the overall cost? Shouldn't we just be looking at the overall in all scenarios? Well, the answer is that in some cases, in theory, we could speed up a query by trying to make use of processing steps where we can start doing some immediate work on some rows. In other words, imagine what would happen if we had a sequential scan that required us to load up all rows before we could do any work on them whatsoever. So if we had a startup cost of 1589.1, like so, that implies we would have to load up all of our comments before we can process them in any way, shape, or form. So in theory, that might take longer than if we were able to load up just a little bit of records and start processing them in some way immediately. So that's why we care about that kind of startup cost. All right, so now there's just one last thing I want to mention around cost in the next video. So we're almost done with cost. Just one more very quick thing. There's one last very quick thing I want to mention around cost. Now this is going to be a very quick little item. You might have already noticed it by taking a look at some of the different costs inside the query plan. I just wanted to have one standalone video just to make sure it is crystal clear what is going on. All right, so let's take a look at the cost of a hash join. So the hash join, in its own right, without really knowing a lot about what a hash join is, has a startup cost of 0. But if we take a look at the actual startup cost reflected inside the query plan, you'll notice that it has a startup cost of 8.31. So where is that coming from? Well, whenever we take a look at the cost of a parent node, so in this case, this is a parent node because it has some children. This is also a parent node because it has some children. We calculate the cost of that parent node as the sum of all child nodes. So the immediate children, in this case, the immediate children of the hash join is the hash and the sequential scan, plus the cost of this node in its own right. So if our hash join has an intrinsic cost of 0, we would also have to add in the cost of the immediate children, which would be 8.3 and 0. So the total startup cost for the hash join is 8.3. Now you'll notice that the actual cost inside the query plan is 8.31. That's because the intrinsic cost of the hash join is not exactly 0. It's technically just a little bit above 0. That's where the 0.01 is coming from. But the point here is that for every node that has a child, we have to take the startup cost and the total cost of that child and add it in to get the total cost of the parent itself. So long story short, costs kind of flow upwards. That's pretty much it. Okay, so that's just the last little thing I want to mention around cost. So let's now take a quick pause and move on to our next topic. There's one last very important lesson I want to take a look at around indexes. So we're going to write out a new query. We're going to do an explain analyze on it and just take some notes on it. All right, so we're going to do a select star from likes where the created at date of the like is before 2013-01-01. Remember, our likes table relates a user to a comment or a post that they have liked. All likes have a created at date on them. So this is going to get us a lot of different likes. In total, our likes table has 750,000 likes on it. So without a doubt, this will give us a lot of different rows. So I can run that and we see, hey, all right, there's our data. If we do a count star, we can very easily see that we get about 63,000 different rows. So definitely a sizable result. All right, so I'm going to go back to just a select star, and then let's put on an explain right before it. Let's take a look at what actually happened here. Well, naturally, our created at column currently has no index on it whatsoever. So we have to do a sequential scan and take a look at every like one by one, and eventually end up with a list of all the likes that were created before 2013. Let's now try to create an index on this created at column, just to speed up this query and see what happens. So I'm going to add in a create index, and remember, Postgres will automatically name an index for you, but I like to just apply the exact same name that it generates anyways, just to keep the name very clear in my head. We'll do a likes created at IDX on likes created at. I'm going to comment out the original query. It's actually okay if we continue to run it, but let's just go ahead and do the create index by itself. Okay, so there's the index. I'm going to comment out the index and then run the original query one more time. Okay, so now we can see very plainly that we have got some kind of index check here. We're seeing some new kind of analysis nodes here, where we're doing something called a bitmap index scan. We're then doing something called a bitmap heap scan as well. Now let's not worry exactly what those steps are really doing for right now. I just want to say, hey, it looks like we used the index successfully. So at this point, if we were to consider what is happening in diagram format, we are making use of this new index we just put together. Now in this case, because the likes table is so large, we get a multi-level index out of it. So in addition to the root node and leaf nodes, for further kind of division and efficiently looking up records inside this index, we also get something called parent nodes inserted inside of here as well. The parent nodes are very, very similar in nature to the root nodes in that they give us some direction on which leaf node we need to go to. So at this point, if we go into our index, saying that we are looking for likes created before 2013-01-01, our root node would say, okay, well, go this way if you want any likes created before perhaps 2011. So we would go down to this parent node. At that parent node, we would get some further level of division. That would send us down further. So we'd end up with this leaf node right here. We would start fetching all these different likes. Notice how they are all before 2013. So it'd start collecting all these different likes and getting all these different pointers to some actual likes stored inside of a heap file. Now, because we are getting so many likes, chances are we're going to be fetching a ton of different pages out of our heap file. After all, we fetch 63,000 likes. So we're definitely getting a lot of pages out of here right now. Regardless, it looks like the entire query we just wrote and executed is making use of the index, and it's running fairly quickly. So now let's make a very small change to this query that's going to have a very dramatic result on how it gets executed. So I'm going to take the created at less than 2013, and I'm just going to flip that from a less than to a greater than. So now this is saying give us all the likes created after 2013. Now I'm going to do a count on this. I'm going to take off the explain for just a moment, and let's take a look at how many records are fetched. So we were getting 63,000 before, now we're getting 688,000. All right, so let's now restore the explain and take a look at how the query is getting executed. Well, wait a minute, take a look at that. It's doing a sequential scan. We have created an index on the created at column, but it looks like Postgres decided to do a sequential scan anyways. Why is that? Well, it all comes down to the fact that we are fetching a tremendous amount of information out of our likes table. Think about what the index is all about. The index is really good for helping us find some very specific and usually small set of records. In this case, we are trying to find something like 90%, or I guess probably closer to 70% of all the records out of our likes table. We're trying to fetch a tremendous number of records. So because of that, if we were to make use of the index, we would end up having to fetch or probably end up visiting about 70% of all these different leaf nodes. And we would then have to take all those different pointers and open up a tremendous number of blocks out of our heap file. And when we are opening up these blocks, we're essentially probably going to be jumping around to each block randomly, which means that we have to pay that penalty for kind of random access in the heap file. So at a certain point, Postgres realized that rather than going through all the extra hassle of going through the index, having to do the random lookup for all these different leaf nodes and then random lookups inside the heap file, it decided, you know what, it's probably going to be a lot easier if we just open up the heap file directly, take a look at block 0, block 1, block 2, block 3, and just go through that file sequentially. So even though we have to visit every single record inside of the heap file, it saves us all that extra work of having to go through the index, get all these different pointers, and so on. The lesson here is that even if you have an index in place, you can easily write a query where Postgres decides, you know what, the index is too much trouble, I'm just going to fall back to doing a sequential scan anyways. So this is a scenario where adding in an index like this is not going to buy you any kind of performance benefit. And this is why being able to read and explain is so important, and why just being able to read it is really going to lead you to getting some better performance out of your database. Whenever you write out a query, just about any inside of your application, I really recommend you do an explain and make sure that it's actually making use of some kind of index you intend to be used. If you have a query that is never using an index, that is a sign that you should probably drop the index. So in this case, if we intended to write a query like this, where we always try to find all the likes created before, or created before 2013, created after 2013, there we go, I would probably want to drop the index tied to the created at column because it's not giving me any benefit in the scenario. Now, one common thing that you might do, and something that you'll see in a lot of kind of forum posts, specifically on Stack Overflow, you might see a lot of scenarios where people are saying, hey, why isn't Postgres using my index? How can I force it to use an index? Well, the answer here is that you don't want to force Postgres to use an index. Postgres has already done the math for you, and it realized that, you know what, it's going to be a lot more efficient to just ignore that index and do the sequential scan directly. Okay, so that is it for right now on indexes and thinking about explain statements and costs and whatnot. So let's take a pause here and continue in just a moment. We've been spending a lot of time talking about some very low-level topics in the world of Postgres. So stuff like indexes, how information is stored on the hard drive, and so on. In this section, we're going to start to take a step back and go back to the world of SQL. In particular, we're going to discuss something called common table expressions, which is a technique we can use to make a query a little bit easier to read. So let's get to it. We're going to first begin by writing out a query in a very normal, plain style, kind of the same style we're used to writing out throughout this entire course. So we're going to try to answer the following question. I want to show the username of users who were tagged in either a caption or a photo before January 7th, 2010. In addition to the username, I also want to show the date they were tagged as well. So to solve this, we're going to need a couple of tables out of our Instagram database, probably users, caption tags, and photo tags. Now, one way we could solve this is by making use of that union set keyword that we took a look at once or twice before. Remember, the union keyword allows us to take the results of two different queries and kind of join them together temporarily into one big set of rows. So to solve this query very easily, we could do a union between caption tags and photo tags. We could then call the result something like, I don't know, just plain tags. So that would be the result of joining together these two sets of rows. Once we've got that union, we could then do a join between the users table, specifically the ID column, and the user ID column of this temporary tags table. With that join, we could then select the username and created at, which would give us when the user was actually tagged. So I think this sounds like a reasonable strategy, good place for us to get started. So let's take a pause right here and then start to write out this query in the next video. Let's try out this solution back over inside of pgadmin. Okay, so back over here inside my query tool, I think we could do a select. I'm going to leave the select blank for just a moment. We'll then do a from users, and then we're going to try to join in the union of both our caption tags table and the photo tags table. Remember how we do a union, we're going to select some number of records. So I'll do a select of user ID and created at from caption tags. And then I'll do a union all with select user ID and created at from photo tags. Now, just two quick reminders here. Whenever we do a union, we have to join together two sets of rows that have identical columns. So in this case, they both have a user ID and created at. Second quick reminder, union all, specifically the all on there, is going to make sure that we do not remove any duplicate rows if there happen to be any duplicates. In this case, we are trying to print out all the tags that were created for users before January 7th of 2010. So even if there is some kind of duplicate, even though it's very unlikely, given that these created at dates have a very fine time resolution, they won't be removed. Okay, so after we find that union inside this subquery, I'm then going to give it just a little bit of a name here, or an alias. We'll just call that tags. And then we need to do the actual join criteria. So we'll do an on tags.userid equals users.id. So there's the actual join criteria. Then finally, we need to make sure that we also put in the date condition. So we only want to find tags or users who were tagged before that specific date. We'll do a where tags.createdAt is less than 2010 01 07. Okay, so that looks pretty good. Now the very last thing we need to do is fill out the select. So our original problem statement over here, or I guess the one over here, I've got slightly different description. We need the username and the date that they were tagged. So that will be the username of the user and then the createdAt of the tag row itself. So we should be able to do a users.username and a tags.createdAt. All right, so that's looking pretty good. There's just one little caveat here, one thing I want to mention. We technically do not need users right there because the username column is unique. We do need tags.createdAt because users also has a createdAt column. So if we put in just createdAt by itself, Postgres would not know if we were talking about the createdAt column of our tags or of users. Well, let's go ahead and run this and see how we're doing. Okay, so that looks pretty good. I've got a ton of different usernames. I've got some createdAts for all of them. And just by a visual inspection, it looks like these createdAts are all before January 7th of 2010. So I'd say that this is definitely the correct result. So we've got a query here that definitely solves the problem, but there's just one little small downside to it. And that is, we've got this big subquery right here. Now, is that really a big downside? Well, I just want to suggest that if you were to take a glance at this query right now, it might be just a little bit challenging to take just a very quick immediate glance and understand what is going on. So I'm kind of wondering whether or not we could somehow rewrite this query in some way just to make it more evident to other engineers what we are attempting to do here. So let's take a look at this common table expression thing. We're going to see how we can use it to rewrite this query in an easier way to understand in the next video. Let's try rewriting this query using a common table expression. So to do so, I'm going to go up to the very top of this file. I'm going to add in with tags as, and then a set of parentheses. I'm then going to cut the 3 lines out of our subquery and paste them into those parentheses. Then finally, down at our join statement, I'm going to replace the parentheses as tags with just tags by itself. And that's it. That's our common table expression. So the only thing we have really done here in rewriting this query is make it easier for you and I to read and understand what is going on. Making use of this common table expression doesn't actually change how this entire query gets executed. And we can even easily prove that by using the explain keyword that we just learned about a little bit ago. So behind the scenes, what we can kind of imagine is happening now is we're going to run that subquery. That's going to give us back some number of rows and columns. Those rows and columns can then be accessed through the tags identifier. So anywhere else inside the main query, we can refer to tags, and it's going to be essentially the result of that stuff right there. Okay, so let's run this again, and you'll notice that we get the exact same result we got before. All right, so let's go over a couple of quick notes. So common table expressions, we define them with a with keyword right before the main query. So this is our main query right here. There we go. And then we've got the common table expression right above it. So we're going to write a subquery into those parentheses. That's going to give us back a table, or kind of an imaginary temporary table that we can refer to anywhere from inside of the main query. Now, if you're looking at this whole thing right now, this whole common table expression thing, and saying, okay, great, we can rewrite the query, who cares? Like, what's the difference? Well, it turns out that there's actually two different uses, or kind of two different forms, of common table expressions. There's the simple form, which we are using right now, and this is used to make a query easier to understand, and that is pretty much it. Nothing else is really changing behind the scenes. It's just easier for you and I to read. But there is a second form of a common table expression referred to as a recursive form. A recursive common table expression allows you to write queries that are otherwise impossible to express with just plain SQL by itself. So simple CTEs, like what we have right here, kind of boring, kind of plain, just about making something easier to read. Recursive forms is where things start to get really interesting, and we can write out some very powerful queries that would otherwise be just about impossible to express with normal SQL. All right, so now the very last thing I'm going to do very quickly, I'm going to put an explain right above or right before the with, and then run it. And you'll notice that we get some kind of query plan right here. Okay, it looks like just about any other query plan we've looked at so far. I'm then going to undo all this CTE stuff and then do another explain. So I'm going to do some undos here. Okay, so here's the original query we had just a moment ago. I'm going to put an explain right before it. I'm going to run this and take a look at that. There is exactly zero change to the actual query plan. So with a very simple CTE, we're not modifying the underlying query in any way. It's the exact same steps being executed behind the scenes. Once again, it is just to make the query easier for you and I to read. Okay, so let's take a pause right here, and we're going to start to take a look at the much more interesting recursive form in the next video. In this video, we're going to take a look at recursive CTEs, which, as I mentioned, are much more interesting, but also a lot more challenging than a simple CTE. So first off, a couple of very quick notes here. So a recursive CTE is extremely different from a simple one. In my personal opinion, they shouldn't even really share the same term of common table expression, because these two things are just so incredibly different. You are going to want to use a recursive CTE anytime that you're working with a kind of tree or graph type data structure. Now, if you are not familiar with trees or graphs as data structures, just don't sweat this. Next thing I want you to understand, because you're going to see this in the query I'm about to show you, or the one we're going to write together, and it might be a little bit mysterious why it's there, every recursive CTE that you write is going to have a union keyword inside of it. So just keep that in mind for right now. And then finally, last thing and most important note, recursive CTEs are honestly probably one of the hardest concepts in all of SQL. Like out of everything, I would probably label recursive CTEs as the most challenging thing. So in this course, I really do not expect you to walk away from the following videos able to write out your own recursive CTEs. I don't expect it. What I do expect after the next couple of videos is just for you to be able to identify when you might want to use a recursive CTE. That's it. I just want you to be able to say, oh, here's a problem. Maybe I could solve it using a recursive CTE. And at that point in time, I would want you to do some research and maybe just get a quick reminder for yourself on how they work. All right, so with that all out of the way, let's take a look at a very quick example query. So we're just going to write out an example here very quickly, and we're going to run it and see what happens. So I'm going to do a with recursive. I'm then going to put in countdown, and then inside of a set of parentheses, val. Val here is short for value. Let's just say value, just to be really clear. Actually, val is actually a keyword, so let's not get a little bit confused. Let's just call it val, short for value. Then as parentheses, inside the parentheses, we're going to do select 3 as val union. So there's the union I mentioned. Every recursive CTE is going to have the union keyword inside of it. Then select val minus 1 from countdown where val is greater than 1. And then finally, after the parentheses, a select star from countdown. Okay, so there's our first recursive CTE. Let's now run this and just see what happens. So sure enough, we get out the values 3, 2, 1. If we want to, we could adjust that select 3 right there to how about select 10 instead. Then we're going to start off at 10 and count down to 1. And naturally, you could go up to, say, 50 or any arbitrary number, and you're going to get a countdown from that number all the way down to 1. So there's our recursive CTE. Now the question is, what's going on here and why would we ever use this? So let's try to answer that question in the next video. All right, so we've ran our first example of a recursive common table expression. So now we're going to take a look at a couple of diagrams and understand what is going on. The first thing I want you to understand are two pieces of terminology. So inside of the CTE itself, you'll notice that we've got that union keyword. As I mentioned, every recursive CTE is going to have a union inside of it, whether or not you think you need it. We then have onSelect immediately above. We refer to the select statement above the union as the initial or non-recursive query. So we refer to this select statement right here as either the initial query or the non-recursive query. They essentially are referring to the same thing. Then immediately after the union, we've got another select. We refer to this statement right here as the recursive query. Okay, so there's our two pieces of terminology. What's above the union is the initial or non-recursive. What's below the union is the recursive. Okay, so now let's go take a look at a diagram and start to break down what's going on here step by step. So in this diagram, we've got the query on the top left-hand side. We have the steps that are actually executed on the bottom left. And then the results of the query, or kind of what's occurring behind the scenes, we're going to diagram out step by step on the top right-hand side. Okay, so let's get to it. The first thing that occurs when we run this query, Postgres is going to define two tables behind the scenes, so you're not really going to see these immediately or really see them in any kind of output. We refer to these two temporary tables as a results table and the working table. So we're going to label those right now. So I'm going to say that this is my results table, and this is my working table. Both these tables are going to be given some number of columns. The columns that they get assigned are whatever you have inside of that set of parentheses right there. So we have with recursive, then some name, and then a set of parentheses. In this case, we have just one word inside of those parentheses of val, which again is short for value. That means that both of our tables are going to have one single column labeled val. If we had additional words inside of here, such as maybe created at, or who knows what else, count or something like that, that means that we would have additional columns inside of both these tables. So in addition to the val column, we would also have created at and count for both of them. But in this case, we've got just val by itself. So both tables have just the one column called val. All right, so that is step number one. We have defined the results and the working tables. Now we go on to step number two. In step number two, we run the initial or non-recursive statement. Remember, that is everything above, or really just the select statement directly above the union keyword. So we're going to run that, and then we're going to put the results from that statement into both the results table and the working table. So we can imagine that we're going to execute select3 as val by itself. If you're not sure what that would produce, well, we could always just do a quick copy and run that single line by itself just to see what it would give us. So when you do a select3 as val, you get back just one row, one column, and it has a column name of val. That's it. So we take that result and we put it into both the results table and working table. So I'm going to do that right now. I'm going to put in 3 right there and 3 right there. Okay, so that's step number 2, all done. Now we're going to move on to step number 3. And this is where things start to get a little bit trickier and a little bit more interesting. So in step number 3, we're going to now run our recursive statement. And here's the kind of little trick to understanding what's going on here. We're going to replace the table name of countdown in there with a reference to the working table instead. So you'll notice that inside of our recursive statement, we have from countdown. So I want you to imagine that instead of saying from countdown right there, we are instead kind of saying from working table. So working table being this thing right here. That is the key to really understanding what is going on. So now we can imagine what would happen if we ran this query right here. We are selecting all the different rows from the working table where val is greater than 1. So in that case, it gives us this one row right here. So I'm going to kind of pull that down as the intermediate result set. So that is the one row that we're getting back from the from working table where val is greater than 1. Then from that one row, we are saying take the value inside of the val column and subtract 1 from it. So in that case, we would take the 3 that's there, subtract 1 from it, and that gives us 2. So that is the output. Just 2 by itself is the output of running the recursive query. So that's step number 3. So we're now going to go down to the next step. In this case, so now we're going to ask ourselves if the recursive statement returned any rows, and yep, it definitely did. It gave us that right there. Then we're going to take that row and append it to the results table. So I'm going to make a copy of that and append it to the results table like so. I'm then going to throw away, this is not really in the step right here, but I'm going to throw away everything inside of the working table as it stands right now, and I'm going to replace it with the result of that recursive query that we just calculated. So essentially we run that thing right there, we then copy the result of it into the results table, and then we replace everything that's inside the working table with it as well. Because our recursive statement just returned some rows, we're then going to run our recursive statement again. So in this case, we return some rows. So we're going to go back up here to step number 3. So let's imagine what happens there again. So we're going to run the recursive statement. So pretty much this exact thing right here once again. So we're saying take all the rows from working table where the value is greater than 1. That would give us this row right here. Then out of all the rows we just found, we want to take the values inside of the val column and subtract 1 from them. Well, in this case, we've got just the 1 row. So we're going to take the 2, subtract 1. We're left with 1. So now we're going to go down to the next step once again. We're going to append the results of that query over into our results table. We're going to throw away everything inside the working table and put the stuff from the recursive query inside the working table as well. So now, because we just returned some rows, when we ran that recursive statement, we're going to recurse again. So once again, for a third time now, we will do a select from where. So we're going to take all the rows from the working table. Where val is greater than 1, well, this is not greater than 1. So we would throw that row out. So now in this case, when we executed this query right here, we did not get any rows back out of it. No rows whatsoever. So in this case, our recursive statement returned no rows, so we are going to immediately stop recursion. So we stop recursion. Then our results table will be taken. We're going to rename the results table to whatever we named our recursive CTE as. In this case, we called it countdown. So we're going to rename the results table to countdown. And now we're going to make this resulting table right here accessible to the rest of our query, or essentially the outer query. So in this case, we're doing a select star from countdown. That means take everything out of countdown and just print it out. So we should see, if we printed out the results of this table right here, we should see one column called val, and it should have values of 3, 2, and 1. And so if I rerun this recursive CTE one more time, sure enough, we got val with values 3, 2, and 1. That's it. That's how a recursive query works. Now, once again, this is definitely the most complicated topic in the world of SQL, in my opinion. Maybe it's not really, but I think it is. So if that entire process is confusing, don't sweat it whatsoever. Again, all I really want from you here is to just say, okay, I kind of have a vague idea of what's going on with the recursive CTE, and be able to say in the future where you might want to kind of research this and possibly make use of it. So to summarize very quickly, just a real quick recap here. With the recursive CTE, we've got the initial query and the recursive query. When we run the recursive CTE, we first begin by building up the working table and the results table. Both these tables are going to have the exact same columns that's listed out inside of these parentheses. We're then going to run the initial query. We're going to take the result of that and put it into both the results table and the working table. We're then going to start to run the recursive query again and again and again. Every time we run it, we're going to take the results and append them onto the end of the results table. We'll then throw away everything inside the working table and put the result of the recursive query in there as well. As soon as the recursive query does not return any rows, we stop recursion. and then we make this results table accessible to the rest of our query. So that's it. That is a summary. All right, so obviously doing a little countdown operation here, not really useful. You might be thinking, where would we ever actually use this? Especially if I'm saying, oh, I want you to know where to use this. Well, you need an example of that, of course. So let's take a pause here. In the next video, we're going to take a look at a definitely more complicated example that's going to give you a better idea of when you would use a recursive CTE. Let's take a look at a much more realistic example of a recursive common table expression using our Instagram database. All right, so we're going to first begin with a little screenshot. This is a screenshot of the Instagram app. This page is showing some suggestions of who I should follow. So Instagram is currently suggesting that I follow Justin Bieber. Yeah, I'm going to get right on that. Snoop Dogg and Jennifer Lopez. So I want to examine and figure out why these people are being recommended to me. Why should I follow them? Well, let's take a look at this kind of screen right here in a little bit more diagram format to help you understand where this data is coming from. So here's me at the very top. I am currently following The Rock and Kevin Hart. The Rock, in turn, is following Justin Bieber, and Kevin Hart is following Jennifer Lopez and Snoop Dogg. So Instagram makes the assumption, this is a really big assumption, if I am interested in these people, and those people are interested in these people, then I should be interested in Justin Bieber, Jennifer Lopez, and Snoop Dogg as well. Now that's a real big assumption. Who knows if I actually am interested in them, but that's what Instagram is assuming. So to get the list of suggestions for this page right here, we would have to write out a query to take a look at who some user is following, find those people, and then find who they are following in turn. So that seems like we could definitely figure it out. And we might even be able to write out a query like that using just a simple join statement. However, there's something else to keep in mind here. I'm currently looking on the screen at a big list of different users. So I might scroll down this list and eventually get to the bottom, and I might need to load up some additional number of users. Eventually, I might kind of exhaust all the different suggestions. I might take a look at all the different people that The Rock is following and Kevin Hart is following, and Instagram might eventually say, okay, clearly they're not interested in who The Rock is following and Kevin Hart is following, but I still need to be given some suggestions of who I should follow. So one way that we could kind of source some additional number of people or some additional number of suggestions after all these immediate ones have been exhausted is to take a look at who they are following. So if I kind of say, hey, I don't really care about Justin Bieber, Jennifer Lopez, or Snoop Dogg, maybe we could go one step further and say, because Justin Bieber is following Miley Cyrus, Jennifer Lopez is following Justin Timberlake, and Snoop Dogg is following Selena Gomez, maybe I should then be presented these people as some suggestions. And then in turn, naturally, I could say, you know what, I don't like any of these people. And then Instagram could go down one level deeper and show me who Miley Cyrus, Justin Timberlake, and Selena Gomez are following. And so you can imagine that this tree kind of grows in depth over and over and over. We're getting just additional layer upon layer. So even if we could figure out some way to write a join statement to get this kind of first unassociated layer, because I am already following these people, even if we could kind of figure out a join statement to get these, writing out a join statement to go down another level and then another and another would get really confusing and really nasty really quickly. So how can we fix this? How can we write out a query to find all these people? Well, as you guess, we're going to use a recursive common table expression to do this. Now, as I mentioned a little bit ago on one of these earlier diagrams, see, where is it? Right here. I'd said that you want to use a recursive CTE anytime you have a tree or a graph type data structure. So in this case, this diagram right here, it's definitely a tree. Technically, followers, people following other people, really forms a graph data structure. So in theory, I could follow Kevin Hart and Kevin Hart could follow me. And so that would constitute a graph rather than a directional tree. But for the purposes of this query and this exercise that we're about to go through, we're going to assume that it is strictly a tree. That's a really big assumption, and it doesn't really stand up in the world of following people, but we're just going to run with it for now because it's going to make the query that we're going to write just a little bit easier to understand. And that's what it's really all about right now. I just want you to understand this recursive CTE. Okay, so now that we've outlined the problem, we understand this kind of data that we're trying to find, and we understand that even though this is kind of not really a tree, we're going to treat it as though it is a tree. let's take a quick pause and then start to write out our recursive CTE in the next video. We now understand the goal of this query that we're trying to write. We are trying to give the user some suggestions. And one thing I want to point out here is that we are trying to give some suggestions to a very particular person. We're not generating suggestions for every person inside of our application, just for one person at a time. Let's first begin by taking a look at some of the different tables inside of our Instagram database and just think about which tables we're going to need to use to build up these different suggestions. Okay, so in total, I think that we really just need our users table and the followers table. So let's imagine the process of finding some suggestions for who user with ID 1 right here, or Haley, should be following. So I'm going to highlight Haley really quick. And then we'll take a look at the followers table and see how we could build up some suggestions for them. So the first thing we would do is take a look at the followers table and figure out who Haley is currently following. So we would find all the rows with a follower ID equal to 1. So that's right here and right here. So Haley is following the user with ID 5 and 4. I'm going to highlight those as well right away. So it looks like that is The Rock and Kevin Hart. Now, we don't really care about The Rock and Kevin Hart. Well, we kind of do in the real world, but in this instance, we don't care about them too much. Instead, we want to figure out who The Rock and Kevin Hart are actually following, because Haley is already following those two people. So we would take the IDs 4 and 5, take a look at all the other rows inside the followers table, and find the rows with a follower ID of 4 or 5. So here's one right here, and another right there. And then there's a 4 right there. So then we would take a look at who they are following. So that gives us the 6, 2, and 3. And then we can map those back over to the users table and see that they are references to Justin Bieber, Jennifer Lopez, and Snoop Dogg. Now, if giving these 3 people as suggestions is not enough, we could always go one level deeper. So we could try to figure out who Justin Bieber, Jennifer Lopez, and Snoop Dogg are following in turn. So for example, we would take a look and find all the different rows with a follower ID of 6, 2, or 3. In this case, there's just one of those. We got a row right here with 2. So we might do one level deeper inside that tree of suggestions, would be the user with ID 7. And I'm not actually reflecting that person inside the users table, but presumably they are inside the users table. All right, so that's the idea. That's how we would try to kind of walk through this entire process. So now we need to actually write out the recursive query. So let's do that to get started. All right, so I'm gonna be honest with you, trying to walk through in like a smooth and informative way on how to write this query is just really challenging. So we're just gonna basically write out the query together. We'll then take a look at a couple of diagrams to really understand what it's doing. I would love to try to be able to walk you through in a very natural fashion of how to write a query like this. But again, this is just a really tricky topic, and I really just want you to get kind of a flavor of what's going on here. All right, so we're going to do a with recursive, and then we're going to call this CTE suggestions, because we're essentially suggesting the different followers we want the user to try to follow, or excuse me, the different leaders we want the user to follow. Then we'll put in the different columns that the results table is going to have. We're going to have our results table show the leader ID, a follower ID, and another value that we're going to call depth. Now, this depth value is not a value that exists inside of either our users table or the followers table. This depth value instead is going to record at what depth we are finding a particular suggestion. So we're going to say that The Rock and Kevin Hart would be at depth 1. They are at the first level of our tree. Then these 3 people would be at depth 2, depth 3, and so on. So we're going to eventually be able to use this depth value to filter out the people at the first level, and then maybe kind of select or prioritize the people at depth 2, and then the people at depth 3, and so on. That's the goal of that depth column. We'll then put in as, and then first our initial query. So this is where we're going to do a pretty good amount of typing. We're going to say select leader ID, follower ID, and 1 as depth. So again, there's no actual depth column that we're pulling from. So we're just going to say that for the initial people that we're going to find, so like this initial level right here, we're just going to have a hard-coded depth value of 1. we're going to take these values from the followers table, and we want to find all the rows where the follower ID is equal to 1000. Oh, no semicolon there. So what's with the where follower ID equals 1000? Well, remember, we are following, or we're trying to get some suggestions for one individual person right now. So in this case, we're going to just assume that we are going to find some suggestions for the user with ID 1000. If you wanted to find some suggestions for a different user, you would replace that 1000 right there with the ID of whoever you want to find some suggestions for. We'll then put in our union keyword, and then after that, we'll do our recursive statement. So we're going to do a select followers.leader ID, followers.follower ID, and depth +1. Let's just keep typing for right now. So we'll do a from followers, and then we're going to join suggestions on suggestions.leader ID equals followers.follower ID. We're going to put in a where depth is less than 3, and then that is it for the recursive CTE. So this is going to essentially build up a big old table of suggested people to follow. I'm going to put in a couple of little bits of indentation here just to make it easier to read. We'll then write the outer query. Now remember, I'm going to tell you what all these lines are doing in just a moment, so just stick around for just a moment. We'll then do a select distinct users ID and users.username from suggestions. We're going to join in users on users ID equal to suggestions.leader ID, and then just two more lines, the where depth is greater than 1, and we're going to limit 30. All right, so really big query, a lot of stuff to figure out here. To get started, let's just run this thing and see what comes out. I'm going to run it, and you'll notice that this is going to take a little bit to actually run. If it takes your computer too long to run, then you can always click the stop button right there, and you can change the depth value from less than 3, or actually rather than changing the depth value from less than 3, you can change the limit. That's probably going to be the easiest way to increase the performance. You can take it down to maybe 5, and it'll be just a little bit faster to actually run. So after you run that, we'll then see some results like this right here. So in theory, these are some people that our user with ID 1000 should try following. Okay, so looks like we've got some data. Who knows if it's actually right? And now we need to figure out what this query is actually doing. So let's take a very quick pause right here, and then we're going to break this thing down line by line. Let's start to break down this query and understand what is going on piece by piece. So we're going to once again apply those same series of steps we saw before. We're going to try to imagine how that query would execute over just this very small table of users and this very small table of followers. And we're going to once again imagine finding some suggestions for user Haley right here, who has an ID of 1. So just to make sure that the actual query itself is consistent with our data set, I am going to manually change the where follower ID of 1000 right there, which means that we are trying to find some suggestions for the user with ID 1000 to 1, which would indicate or kind of mesh a little bit more nicely with our data set right here, saying that we're trying to find some suggestions for Haley. All right, so let's now go through our steps and imagine how this query is going to run. So step number 1, we're going to define the results and the working tables. So just to save a little bit of time, I went ahead and did that for us. Here's the results table and the working table. They're going to have 3 columns each of leader ID, follower ID, and depth. We have 3 columns with those very specific names because those are the 3 columns we listed right after the name of the CTE itself. So there's leader ID, follower ID, and depth. Okay, so that's step number 1. So I'm going to drag that off to the side. On to step number 2, where we are going to run the initial non-recursive statement. So here's our non-recursive statement. In the non-recursive statement, we're going to take a look at all the different rows of the followers table. We only want the rows where the follower ID is equal to 1, and for those rows, we're going to extract the leader ID, the follower ID, and we're going to also get a column called depth and give it a constant value of 1 for every row. So let's imagine how that would actually play out. Okay, so we're going to go to our followers table, we're going to find all the rows with a follower ID of 1. So there's one right there. And for those rows, we're going to extract only the leader ID and the follower ID. So I'm going to pull out that row right there. And we're also going to give it that fixed constant value of depth of 1 as well. So then we've got one other row with a follower ID of 1. There it is right there. We will pull that to the working table and give it a depth of 1 as well. So we've added those rows, or the result of the initial query, to the working table. We also add that to our results table as well. And that's it. That is the result of our non-recursive statement. Now we're going to move on to our recursive statement. Then remember the little trick that we use for understanding the recursive statement. The trick is to find the reference to the name of the CTE itself, and we're going to replace that with working table. Now this is just a trick that I recommend that you do in your mind. You're never going to actually write out working table inside the query. It is just a trick to help you understand what is going on. Again, do not write out working table in here. So now we can imagine how this query would be executed. So we would select everything from our followers table. We're going to join in the working table where the leader ID of the working table is equal to the follower ID of the followers table. So long story short, we're going to find the rows where this column is equal to this column. To illustrate this join, we're going to kind of diagrammatically, or I guess visually, just to put it very simply, show the matching or the merge tables in this temporary table over here. So I'm going to call this followers working table. So then it would have all the different columns from followers and all the different columns from the working table as well. So it'd be ID, leader ID, follower ID. So these three columns are coming from the follower side, and then leader ID, follower ID, and depth, all coming from the working table side. So let's now do the join. So we will first begin with the working table down here. We're going to find all the different follower IDs with a ID of 5 or a value of 5. So there's one right here and one right here. So I'm going to copy out both those rows. And they would get merged together with copies of that row. Then we'll do the join for the leader ID of 4. So we'll find all the different rows with a follower ID of 4. Looks like there's just one. So I'll put it right there, and that would be joined with that row like so. Okay, so now that we've got the join table put together, we would then execute the where statement. Now you'll notice that between the last video and this one, I adjusted the depth from a 3 down to 2. And that's just to make this example go a little bit faster. You can change yours to 2 as well. It's totally up to you. So we would execute that where, and we'd make sure that we've only got rows inside of here with a depth that is less than 1. Well, in this case, they are all less than 1, so everything looks fine to me. So then we would select out of those remaining rows just the follower side leader ID, the follower side follower ID, and we get a depth and add 1 to it. So we'd take the follower side leader, the follower side follower, take depth and add 1 as well. That would give us all these different values. We then take the depths, add them in, and add 1 to them. And that right there is the result of our recursive query. So now we will take that result, copy it into our results table. We would dump everything inside of our working table and put the result of the recursive statement in there as well. All right, so we've gone through one example of the recursive statement. So our recursive statement did return some rows, and because it did return some rows, we're going to run the recursive statement once again. So I'm going to very quickly empty out the join table. So now we're going to run our recursive statement again. That means we have to do the join a second time around. So we're going to take a look at all these different working table values, and we will join them with a followers table follower ID column. So we'll start off first with a value of 6. It looks like we don't have any follower IDs with a value of 6, so no joins. Then a leader ID of 2. It looks like we've got one row with a leader ID of 2. So that would be joined over here, like so. And then on to 3, we do not have any rows with a follower ID of 3. So that is the output of the join. So then we would apply the where clause to it. So we'd make sure that we've only got rows with a depth less than 2. Well, in this case, we have a depth of 2. That is not less than 2. 2 is not less than 2. So we would dump this row because it failed the where clause. And that's it. That is the result of our recursive query. There are no rows to actually select any columns from. So in this case, our recursive statement did not return any rows. We have nothing to merge into the results table. So we stop recursion, and this results table right here, we can imagine gets renamed automatically to the name of our CTE itself, which was suggestions. So we would call this thing suggestions, and then the rest of our query would start to operate on it. So in other words, everything down here would start to work on it. So it looks like the first thing we do is we select everything out of suggestions. We find only the rows where the depth is greater than 1, because remember, a depth of 1 means that these are people that our user with ID 1 is already following directly. So we would dump those rows. We would then take the remaining rows and join it with the users table. Our join criteria is the leader ID with the user ID. So we would match the leader ID of 6, 2, and 3 with the users. So that would give us matches with Snoop Dogg, Justin Bieber, and Jennifer Lopez. We then, out of those remaining values, select just the user ID and the user usernames. So we'd end up with, essentially, I'm just going to kind of abbreviate right here, we'd end up with just the rows of Justin Bieber, Jennifer Lopez, and Snoop Dogg. And that's it. Okay, so that is a recursive query in action. Again, I'm going to repeat it for the third time. You do not need to be able to reproduce this entire query on your own. Absolutely not. All I want you to understand is that we can use a recursive CTE to somehow fetch data out of a kind of tree or graph structure. That's it. So in the future, if you're ever working on some kind of database where you need to find maybe all the employees who are managed by one kind of person, find all the different states that are in some kind of country, or find all the, who knows, all the municipalities or something like that. Essentially any kind of hierarchy. That's the term you really want to be thinking about. Anytime that you're working with some kind of hierarchy and you need to write a query around it, you might want to think about a recursive CTE. Okay, so that's it on this stuff. Let's take a pause here and move on in just a moment. In this video, we're going to take a look at another query that we're going to solve. And once again, we're going to run into an issue or two with this query. We're going to make use of another advanced feature inside of Postgres to solve it in a more elegant fashion. So let's take a look at the query that we're going to try to solve. All right, so this query is going to be somewhat similar to the last couple we've put together. So we're going to take our table of users, caption tags, and photo tags. The goal here is to find the most popular users. So we're going to define the most popular users as being the users who are tagged the most across all the different posts on our platform. So let's first imagine how we might solve this using these 3 different tables. Well, first off, I think that once again, we don't really need to have these 2 separate tables of tags. We really just need one collection of all the different tags. So we could do another union, as we've done before, between caption tags and photo tags. So if we do a union, we would take all the different rows, put them all together inside of one table, and then call the result maybe something like tags. Once we've got this put together, we could then do a join between users and tags. We would join on the user's ID column and the tag's user ID column. Let's take a look at what that would get us. So we're going to imagine the join process here. So this is the table that's going to be created after we do our join. So we're going to take a look at each individual user ID, and then for each user ID, we're going to move them over to that table and join it with each user ID out of the tags table. So we'll start off first with Haley. So it looks like we've got a user ID of 1 right there. And then we've got another user ID of 1 and another user ID of 1. So we would have in total 3 rows for Haley. So that means that Haley has essentially 3 tags. We'd then move on to Eldon. we'd find all the different 2s. So there's one right there. We've got another set of 2s down here as well. And these would also be Eldon. And then we could repeat the process for user IDs of 3 and 4 as well. You can imagine how that table would start to fill out. So once we get to this point of this user tags table, or this join table of sorts, we could then do a group by operation. We could group by username. So we would have Haley as our group by and Eldon as our group by. And then we could count the number of rows for each of those different groups. In the case of Haley, we would have a count of 3. And for Eldon, we would have a count of 3 as well. Once we get those counts, we can then do some kind of order operation or a sorting operation to make sure that we get the most popular users at the top of the list. So that's it. That's the general idea. Let's go and write the SQL for this right away. Okay, so back over here, I'm going to put in my select. I'm going to leave select empty for right now until we have a better idea of some of the data we are working with. I'll then do a from users, and then we're going to join in the result of a union between photo tags and caption tags. And when we join or take the union of these two tables, the only column that we really care about is that user ID column. We didn't actually make use of the ID column at all. We only made use of user ID. So that's the only column we really need to care about for the purposes of the union. So I'll do a select user ID from photo tags, union all, and notice that we're making use of the all here because we do not want to remove any duplicates. We'll then do a select user ID from caption tags. Then remember, anytime that we do a subquery like this inside of a join or a from, we always have to apply an alias to it. So we'll apply an alias of tags. We'll then provide the join criteria. So we'll say join on tags.userid, and we want to match up those user IDs to the users.id. Okay, so that looks pretty good. So now we can do our grouping operation. So I'm going to group by users.id, or excuse me, users.username. And because that is a unique column out of all this, we could put down just a username by itself. We can then do our ordering operation. So we'll do an order by count star. And we want to make sure that we get the greatest counts on top. So we'll make sure that's descending. And then finally, I think we could do our select at the very top here. And we're going to select just the username for each of these groups and the number of rows in each group, which we'll do a count star for as well. All right, so we went through this rather quickly. That's just because, well, the query itself is not really the interesting part here. Let's run this, make sure it works, and I want to point out something that's just a little bit awkward about this. Okay, so I'm going to run it, and I would say that looks pretty reasonable. So I've got Bonita96 on top. Looks like they've got 21 unique likes, or excuse me, tags. Emilio Moore has 17, 16, and so on. Yep, that's looking pretty good. So in theory, Bonita96 is our most popular user. They have the most tags across all the different photos and captions. All right, so it looks like this works, but what is the awkward part? Well, without a doubt, the awkward part here is that we are in yet again a scenario where we have had to take the union between our photo tags and caption tags tables. This is a topic that we've brought up several times now. Maybe it was kind of a mistake when we were doing our initial database design to create these two separate tables, because we just have to keep on having to take the union of them again and again and again. And we have not yet really gotten into any kind of situation where it was advantageous at all to have those two separate tables. So I'm starting to think that this might have been a mistake in our design. And maybe there's some way that we could fix this up or somehow improve the situation. And that's what we're going to focus on in this section. How can we kind of fix up this mistake right here? The fact that we made two separate tables when maybe we should have just made one. So let's take a pause and dive into this topic a little bit more deeper in the next video. At this point, I think that we can come to the conclusion that having the separate tables of caption tags and photo tags is probably a design mistake. We have had to find the union between these two tables several times to execute some pretty basic queries, and we've not really found any benefit to having these two tables be separate. So I think that we probably maybe did make a mistake in our design here. So how are we going to fix this? Well, there's two general ways we can solve this issue where we have two tables, but we probably only want one. So in this video, we're going to take a look at the first possible solution. All right, so for our first possible solution here, this is kind of the obvious solution. we could take these two tables and merge them together into one table and then delete the originals. So in other words, we could create a new table called tags, and would have all the different columns that are common between the caption tags and the photo tags tables. So for example, it would have the ID, created at, updated at, user ID, post ID, X, and Y. We could then copy over all the different rows from photo tags and all the different rows from caption tags. Just in case you're curious about what that would look like, you can insert rows from another table by doing an insert into, and then right after that, without any semicolon at the end of that line or anything like that, we can select some number of rows using a very typical select and from statement. So in this case, we're going to insert some number of rows from photo tags into this new tags table. Same thing down here for caption tags. So after we do these copy operations, we could then delete the original photo tags and caption tags. And we are left with just the one single tags table. So this might seem like a pretty obvious solution, something that would be pretty straightforward. I've even got all the SQL written out for it right here, but there are some big downsides to this approach. So two big downsides to this first solution. The first really big issue is that we cannot copy over the IDs of all the different photo tags and caption tags to this new tags table. And the reason for that is that these photo tags and caption tags tables, they might have rows that already have duplicate IDs inside them. Remember, we're using that serial data type for all of our IDs. And that means that every single table is probably going to have an ID of 1, 2, 3, 4, 5, 6, 7, and so on, unless we eventually delete some of those rows. So it is very likely that photo tags and caption tags are going to have some identical IDs. And that means that we just can't copy these IDs over to the new tags table. That means that if there are any other records inside of our database that are pointing to those different ID values, then all of a sudden we can have some foreign keys breaking. Because if there was some other resource that are pointing at, say, photo tags or caption tags, no longer will those IDs match up to whatever records we are adding to the tags table. The other big issue here is that if we had a lot of other queries already written out inside of our application that made reference to specifically the photo tags or caption tags tables, now all of a sudden they break because we're talking about deleting those tables. So not only do we run into this kind of referential integrity issue where we can't pull over these very meaningful pieces of data, in this case the IDs, but we also run into these really big issues where, well, we have to go and rewrite possibly some big portions of our code base just to make sure that we refer to this new tags table. So although solution number one is something that we could definitely do, I think there are some tremendously large downsides to it. So as you could guess, we're not going to use solution number one. Instead, we're going to take a look at another possible solution in the next video. And as you can guess, yep, that's going to be the solution that we're going to end up using. So quick pause. We'll take a look at a better way of merging these tables together in the next video. Let's take a look at solution number two. So in solution number two, we're going to create something called a view. You can think of a view as being like a fake table that has a reference to rows or data from other tables inside of our database. When we create a view, we can essentially wrap up some other information or present it in a cleaner form that already exists inside of our database. Ultimately, you can think of a view as being very similar in nature to a common table expression. The only issue with a common table expression, you might recall, is that we attach them to some other query. So in this case, we've got a common table expression up here at the top, and we can only refer to this tags, CTE, inside of the query that it is directly attached to. The nice thing about a view is that we get this very similar behavior where we can kind of wrap up some existing query, but we can create a view ahead of time and then refer to it at any future point in time in any other query. And we don't have to rewrite the view or anything like that. So you should really think of a view as being very similar to a common table expression. The big difference is that we create a view ahead of time, and then we can refer to it at any point in time after that. Now, a couple more notes on views. A view can wrap up data from other tables. Essentially, we're taking some existing query that we might have written, and we just wrap it up inside of a view. That's all it's really about. So when I say that we can have a reference to rows or data from other tables, I'm really saying we could put any logic into a view that we want to have. We are going to use a view in our case to take the union between two different tables, in our case, caption tags and photo tags. But we do not have to use a view for only a union. We can put any kind of query into a view. Once we put this first view together to create some kind of new fake table of sorts that we're going to call tags, we'll take a look at a couple other examples of views just to make sure it's really clear that we can kind of wrap up any query inside them. Okay, so in our case, we're going to create a view right away. I'm going to go back over to pgadmin. I'm going to find our existing query and comment it out. And then down here at the bottom, we're going to write out a little bit of SQL to create a new view. So we're going to write create view. We're going to call it tags, and then put in as in a set of parentheses. We're then going to write out our query inside of these parentheses. So this is where we are going to kind of generate some data that's going to be accessible through the view. In our case, we're going to take all the different rows from photo tags and take the union with all the different rows from caption tags. Just remember that when we take a union, we need to make sure that the columns and the type of data inside these columns match up between the two tables that we're doing the union between. So we're only going to select just a couple of different columns from both photo tags and caption tags. Let me show you what I mean. So inside of here, we'll do a select ID created at user ID, post ID, and then I'm also going to put in a string of photo tag in a column that I'm going to call type. So I'll say as type like so. And I'm going to get all those from photo tags. I'll then do a union all with a select ID created at user ID, post ID, and caption underscore tag. Also as type from caption tags. The only goal of this as type column right here is so that we can actually distinguish between a row that is supposed to represent a photo tag and a row that is supposed to represent a caption tag. That's the only reason type is in here. Okay, so now we can create the view by running this. You'll notice it says create view successful. We can now do a select star from tags. And if I run that, we'll see a concatenated or essentially union between all of our different photo tags and caption tags inside this list. Now, of course, there are many different photo tags, so if you scroll down really far, you're probably only going to continue to see photo tags. But just to confirm that we've actually got some caption tags in here, we could also do a where type is caption tag. And if we run that, yep, there we go. Now we can see that we've got both of those sets of rows inside of here. So with this view, we've essentially solved this issue of having two separate tables. We've kind of merged them together, but it's not any permanent change whatsoever. We can always remove this view if we want to, and none of the underlying data is going to go anywhere. All the underlying data inside of the two separate tables still exists. So if we have any queries that refer to those two separate tables of caption tags or photo tags, those existing queries are going to work just fine. But now we've got a very convenient way of referring to the union between caption tags and photo tags by using the view that we just put together. All right, so let's now delete that little temporary thing right there. I'm going to uncomment our big query. So now we can remove the subquery inside there. And now we can just refer directly to tags. So we're going to join tags on tags.userid equal to users.id. So if I now run this, I'll see that I get the exact same result I had before, but now we don't have to have that big, nasty subquery inside of here. Okay, so that is views, but still a lot for us to learn about them. So let's take a pause right here and learn a little bit more about views, why we use them, and so on in the next video. Let's take a look at another possible use case of a view. So I'm going to show you another list of queries we might want to try to run. So let's say that maybe the 10 most recent posts inside of our application are really important. Maybe every single day, whenever a user logs in, we want to show them the 10 most recent posts on our entire platform. And maybe we want to show who created those posts, the number of likes each one received, who were tagged in them, the hashtags they used, the average number of hashtags used in each of them, and the number of comments for each of them. So in all these different queries here, notice how the 10 most recent posts are very, very important. So if we wanted to run these 6 different queries, we could write out some kind of subquery in each of them that finds the 10 most recent posts, or alternatively, we could create a view that will find the 10 most recent posts. We could then reuse that view in all 6 of these different queries and not have to rewrite the logic to find the 10 most recent posts again and again and again. So let's take a look at how we would create a view to find the 10 most recent posts. So I'm going to go back over to pgadmin. I'm going to delete everything inside there, and then we'll do a create view and we'll call it recent underscore posts as, and then inside of here, we'll write out our query to find the 10 most recent posts. So for that, we could do a select star from posts. I'll do a order by created at, and I want to be descending. So the most recent post will be at the very top. And then we will limit 10. So only give us 10 results back. So we can now run that. That will create the view. We can then do a select star from recent underscore posts. And if we execute that, we'll then see a list of the 10 most recent posts. Just so you know, the data set that we're making use of here, posts can span anywhere from years of 2010 all the way up to 2019. And so we're taking a look at only posts here that are in 2019, which means these are probably the 10 most recent posts. You'll notice that it's also descending dates, so it does look like this is the correct data. So now that we've got this view put together, we can much more easily start to write out all 6 of these different queries without having to repeat that same logic around doing that order by and the limit 10 over and over and over again. So for example, if we wanted to now show the users who created the 10 most recent posts, we could very easily do a join on recent posts. Just as a quick example, that might look something like join in posts, or excuse me, join in users on users.id equal to recent underscore posts dot user ID. Because we are working with a post here, that's what this recent post thing is. And remember, a post has a user ID foreign key column. We're going to join that stuff together. And then maybe in this case, we want to find just the username for the people who created these 10 posts. So now if we run that, we can see those usernames very easily. We could very easily do these other 5 queries, but I think you get the idea rather quickly. Let's take a look at just one other example of views in the next video. In this video, we're going to take a look at how to change the definition of a view and delete a view as well. So let's say that we are working with our recent post view that we just put together. Remember, it finds the 10 most recent posts. And maybe we've now got a new requirement. Maybe we need to find the 15 most recent posts. So we need to go back and change some configuration of the view itself. To do so, we would write out create or replace. That's the magic part right there, the or replace part. So create or replace view. We'll then put in the name of the view that we want to make some changes to. So in this case, it is recent posts. We'll then put in the as, and then write out our new query that we want to run anytime someone tries to access this view. So now we'll do a select star from posts, order by, created at descending, and now we'll do a limit of 15. So in this case, we already have a view with the name of recent posts. So rather than creating, we're going to replace the existing view. So if we run this, well, let me do that again. There we go. Looks like it was successful. And now if we do a select star from recent posts and run that, we'll see that we get back 15 different results. Yep, there we go, 15 right there. In addition to changing a view, we can also delete a view. So at some point in time, you might realize, you know what, I actually didn't need that view at all. So to delete a view, very simple and straightforward, we can do a drop view and then the name of the view itself. So in this case, recent posts. We can then run that, and that's it. The view is now gone. If we try to refer to this view now, we'll end up with an error. Now, if at any point in time you want to see all the different views that exist inside of your database, you can open up your database inside of pgadmin, go to schemas, open up public, go down to views, and there are our views right there. You'll notice that in my case, it still says that recent post is around. You can right-click on views, click on refresh, expand that again, and then you'll see, yeah, it did in fact get deleted. Okay, so now we are left with just the tags view. All right, just 1 or 2 more notes on views. Let's discuss that in the next video. We've now had a good look at views, so we're now going to take a look at a variation on a view. All right. So at this point, we've been talking about views, which are essentially queries that we kind of wrap up and refer back to at some point in time in the future. Whenever we refer to a view, we are ultimately executing the underlying query kind of stored within it. So we're now going to take a look at a variation on a view called a materialized view. A materialized view is a query that we're going to kind of wrap up or kind of package, but the query is only going to be executed at very specific times. However, every time that we do actually execute the query, Postgres is going to take the results and save them, and we can then refer back to those results without rerunning the query itself. So we make use of materialized views anytime that we have a very expensive query. In other words, a query that might take many seconds, minutes, or even hours to actually execute. We can run a materialized view just one time and then hang on to the result set and refer back to the results without having to go and rerun the very expensive query. Now, there's kind of an interesting parallel between views and materialized views that's kind of similar to the world of common table expressions. So remember, with common table expressions, we had simple and recursive. With a simple common table expression, we were making use of a tool that really just made it a little bit easier to read a query. And the recursive common table expression was a tool that allowed us to actually run kinds of queries that we could otherwise just plain not express. So there's kind of a parallel between simple common table expressions and views, and recursive common table expressions and materialized views. For the simple CTEs and views, these are just kind of like convenience tools that make it a little bit easier for us to refer back to some kind of query, or just kind of clean up a query and make them easier to understand. On the other hand, recursive common table expressions and materialized views, these add in some major functionality and allow us to do things that we would otherwise just plain not be able to do. So just a kind of interesting point I wanted to throw out there. All right, so to get a better idea of what materialized views are all about, we're going to once again write a query, take a look at the results, kind of do a little bit of analysis, and then add in the idea of a materialized view. So let's take a pause right here and discuss the query we're going to write in the next video. So here's the query that we're going to try to solve. This query is going to ultimately take a pretty good amount of time to actually execute. This might be a good place to make use of a materialized view, but we'll talk about why that is in just a moment. For right now, let's just understand the query we're trying to solve. So we've got our table of posts, likes, and comments. Remember, likes have either a defined value for post ID or a comment ID, because you can like either a post or a comment. I want to try to show every week of our application, or kind of every week, starting from the date of the very first post all the way to the very last post. And for each week, I want to show the number of likes that posts and comments received. Now, very critically, rather than using the date of the like, or essentially when the like was added to a post or a comment, I want to kind of assign all these different posts and comments to the week they were created, and then show the total number of likes that each one received. Now, to really kind of clarify that, let's just take a look at a diagram of what we're really trying to do here. Okay, so I've got down here at the very bottom a little timeline of sorts. So we're going to start off right here on the left-hand side, and we're going to say that our starting date for all these different posts and comments appears to be 2010, January 1st. So that's kind of our starting time. So that's 2010, 01, 01. 1 week later, or 1 week in the future from that, would be 2010, 01, 08. We now have kind of a 2-week span right here. Here's week 1, and then week 2. So now we would want to take all of our different posts and comments and assign them to one of these 2 weeks. So for posts, I'm going to reflect all the posts right above the line. So I'm going to show above this kind of arrow right here where each of these different posts was created. So it looks like all the different posts were created during the first week. So I'm going to copy their IDs and just stick them down there like so. Then for comments, it looks like the first comment was created during the first week. So I'll put one of the comment IDs right there. And then it looks like the other 2 comments were created during the second week. So right there and right there. So that's how we want to kind of bucket or group all these different posts and comments together. Then we're going to go back through and count out the number of likes that all the different posts during this week got, and all the different comments during this week got, and then same thing for the next week, and so on. So it looks like we can go through each of these likes row by row. The first one is a like for post with ID 2. So just to kind of reflect the like, I'm going to just put that right there and say, okay, post with ID 2 got a like. The next one says that the comment with ID 3 got a like. So I'm going to put a little marker right here. Then the comment with ID 2 got a like. Then the post with ID 2 got another one, and another one. And then finally, the comment with ID 1 got a like as well. Now we can take this diagram right here and kind of tabulate it into a result table. So for our final output that we're looking for, I want to see 3 different columns. I want to see each week. I want to see the number of likes that the posts inside that week got, and the number of likes that the comments inside that week got as well. So our first week would be 2010-01-01. The second week is 2010-01-08. And then it appears that during that first week, the posts got 3 likes. So I'd put in a 3 right there. And it appears that the comments got 1 like. Then during the second week, it looks like there are no posts that got any likes whatsoever. So I'd put a 0 right there. And it appears that the comments got 2 likes. So that is the results that we're looking for. So essentially just group all the different posts and comments into these kind of week-long buckets, and then count the number of likes that each of them got. Okay, so now that we understand what we're trying to do here, let's write out a query to solve this in the next video. Before we write out this query, there's one other very quick reminder I want to give you. Now throughout this course, we've been doing a lot of join statements. And remember, anytime that we write out just the join keyword by itself, that implies that we want to do by default an inner join. But there are some other kinds of joins available to us. There are left joins and right joins. To solve this query, we're going to have to make use of a left join. So I just want to very quickly get a quick reminder on how a left join works and why we need it to solve this particular problem. So in total, we're going to do a 3-way join, and we're going to make all those left joins. So we're going to start off with a base table of likes. We're then going to do a left join of posts, and then we're going to do a left join with comments as well. So we're going to kind of diagram out this entire process and really just get a quick reminder on how left joins work in general. All right, so we're going to first begin by joining together likes and posts. We're going to join them based upon this post ID and ID columns. So we'll go through it row by row. First is the first row right here. So I've got a like with a post ID of 2. So I'm going to pull that row down, and that would match up with this post right here. So I'll pull it down like so. Then we're going to take a look at the next row right here. Now notice how we have a value of null. If we were doing an inner join, we would throw this value away because it doesn't actually match up with any rows inside of our post table. However, because we are doing a left join, remember the left join means we want to keep all the rows out of our likes table no matter what. So we are going to include that row, even though normally with an inner join we would throw it away. Because we don't have any matching values for our posts, we are going to throw in null and null to say, hey, there's not actually any value here for us to join up to. Then we'll go on to the next row. So once again, we've got a post ID of null. So again, we're going to put in values of null and null where the post would normally be. We then get 2 rows with a post ID of 2 in a row. So I'm going to pull both those down, and those would line up with the post with ID 2 and 2. And then finally, one more like with a null value. So we would bring that down, and that would be given some null values as well. So that is the output of joining together likes and posts. So now we're going to also do a further join. So kind of the second join, that's what makes this a 3-way join between likes and comments. And this time around, we're going to be joining on post ID with the ID of the comment. So when we do this, we're going to essentially be filling in more or less kind of all these null values. That's what's really going on here. So all the different likes where we originally had a null for the post ID, we're going to go back through, find the comment ID, and pull down the value from the comments table. So in this case, we got a comment ID of 3 right here. We'd pull down that comment, put it right there. Comment ID of 2, put that right there. And then finally a comment ID of 1. Put that right there. Then all the remaining rows where we had already matched up to a post would get values of null. So right there will be null and null. And right there and right there. Okay, so that's it. So that's what we get out of doing a 3-way left join. For every single row, we've got a post ID with a defined post, or we have a comment ID with a defined comment. If we don't have a post ID, then all the post columns are null, and if we do not have a comment ID, all the comment IDs are null. Now, if we had done a normal left join, all these different rows where we have a null value would have been thrown away because they didn't line up with anything from either posts or comments. So if we wrote out this query that we're about to do with just a normal inner join, then the resulting table would be 100% empty. So even if you did an inner join here in this case, you would learn pretty quickly once you start to look at your result set that you were probably not getting the data you expected. All right, so now that we got this reminder on how left joins work and why we have to use one in this case, let's go ahead and write the query in the next video, this time for real. All right, my friends, let's start to write out this query. So we're going to begin with a select star. We're going to start off from the likes table. We'll then do a left join with posts on post.id equal to likes.postid. We'll then do a second left join with comments, and we're going to join on the comments ID equal to likes comment ID. There we go. Let's run this by itself and just see what we get. This query is going to take a couple of seconds to run. It might take you all the way up to 20 or 30 seconds, so just give it time to actually execute. Now, I want to take a close look at the set of columns we get back. The first set of columns we have right here are for each individual like. So we have ID, created at, user ID, post ID, comment ID. Those are all about one single like. In this case, it is a like for a post because the post ID column or value is defined and comment ID is null. Then the next set of columns are all about the post that was liked. So we've got the ID of the post that was liked, created at, blah, 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 all the stuff for the post itself. And then finally, if we go all the way to the right, we'll see the last set of columns over here are all about the comment, in this case, that was not liked because it was a like for a post and not a comment. So all the comment values are set to null. So you'll see that this has the exact same structure as the diagram we were looking at a moment ago. Every single row has information about a comment, a post, and a like. And in every single case, either the comment or the post has null values inside of it because every like is either for a post or a comment. Now, one thing I mentioned in the last video is that it might be just a little bit kind of intimidating to understand that, hey, we had to do a left join here. You might be sitting there and thinking, hey, how would I ever know to do a left join? Well, let's try running this query without the left keywords on here at all. So I'm going to take out left really quick and then run this. So you'll see right away that we get a completely empty result set. So this right here, this would be the sign that you are probably not doing the correct kind of join. The fact that you're getting no records whatsoever means, hey, maybe I should not do an inner join. Maybe I should do some other kind of join. So just wanted to throw that out there really quickly. All right. So now we have the entire kind of structured data, or really all the different values we need. So now the next thing we need to do is take the created at value of all these different either posts or comments, and we need to somehow round them down to the nearest week. Because remember, we're trying to essentially group all these values by each sequential week. So for that, we're going to use a function that is built directly into Postgres called dateTrunc. The dateTrunc function allows you to pull one piece of information out of a timestamp. In this case, we're going to pull out the week from all the different created at values that we have. The dateTrunc function is then going to automatically round down that information or that little part of the timestamp that you pull out to kind of like the nearest unit. So in this case, it's going to automatically round down the created at of all these different posts and comments to the nearest week. So even if, say, this post right here was created on January, say, 5th, it will be automatically rounded down to January 1st. Let's take a look at how it works. I'm going to delete the star at the select statement. Then I'm going to give myself a little bit of space. We'll put in a dateTrunc week, because that is the piece of information we want to pull out of a timestamp. And then we want to specify either the created at of the post or the created at of the comment. So our created at of the post will be defined, or the created at of the comment over here will be defined. One of them is going to be null. So we need to make sure that we try to pull out the week from the value that is not null. So for that, we can make use of that coalesce function that we've taken a look at several times. Remember the coalesce function? Sounds really fancy. All it's going to do is take a look at all the different arguments we provided and then return the first argument that is not null. So to the coalesce function, we will put in posts created at and comments dot created at. So out of these two values, one of them is going to be null. Just give us the first one that is not null. All right, then finally, I'm going to take this entire date trunk line and apply an alias to it. I'm going to call it as week. Okay, so let's run this now and see how we're doing. Well, it looks like we definitely got some values here. And if you look very closely, you'll notice that all the times are now down to 0. So in theory, these are all created at values that are rounded down to the nearest week. But it's kind of hard for us to really verify that. So one thing we could do is to now sort all these different values. So at the very end of my query, I'm going to remove the semicolon and put in an order by week. So let's run that. And now we can see that we're starting off with January 11th, because that's really the first post or the first comment that we get inside of our data set. So these are all likes right here, or they are all in reality, well, they represent a like for either a post or a comment, and the post or the comment was created during the week of January 11th, 2010. So then we can scroll through and you'll see that the next date value is going to be January 18th. So it's very clear now that I think all these different values have been rounded down to the nearest week. So we can keep going. There's 25 and so on. Okay, so that looks good. So now the last thing we need to do is kind of summarize all these values. We don't want to see every single week. We don't want to see every single post or comment or like. We want to essentially group them all together. So we can do a group by with that week value, and then we can start to add in some counts. So right before the order by, we'll do a group by week. Let's run that. And now we just see each unique date or each week by itself. So now finally, last step, we're going to add in the counts. So we're going to count up the number of posts inside this bucket and the number of comments inside that bucket. So for that, back up at the select statement, I'll put a comma right after our alias of as week. And then we will do a count on posts.id as num posts and count comments.id as num comments. Remember that with the count function, it does not count null values. So out of this entire first week bucket right here, any likes that were for a post that had an ID of null will not be counted. Same thing for comments. So this will just count up the number of likes for posts and the number of likes for comments inside of that particular week. Okay, let's go ahead and run that. And we should, yeah, there we go. That's it. Now we can see that during this first week, it looks like there were 29 likes for posts and 0 likes for comments. Then we had 31 likes for posts, 3 for comments, and so on. This actually kind of lines up with reality because during this first week, there's not really any posts for anyone to add comments to. So a lot of posts were created, but we didn't actually get any comments created for them yet. So then we can scroll through and compare all these different values. Now, I do want to mention maybe my column titles here are a little bit misleading because these are not the number of posts or comments that were created, it's the number of likes that were assigned to either posts or comments. Maybe a better alias for both these would be like num likes for posts and likes for comments. That might be just a little bit more descriptive. Okay, so that looks good. All right, so we have our result at long last. But there's something I want to mention about all this. Right now, on my computer, which is pretty darn modern and definitely some good equipment in my machine right now, it takes me about 2 or 3 seconds to actually run this query. And for you, if you're on an older machine, it might take all the way up to 10, 15, or even 30 seconds to run. If we need to run this query all the time, then 10 or 20 or 30 seconds is way too frequent or way too long. We don't want to be running this query all day long or repeatedly if it's going to take quite such a long time. So in this case, we really need to figure out some more efficient way of running this query. We need to somehow improve its performance. And that's why we are going to be using a materialized view. So let's take a pause right here, come back to the next video, and figure out why a materialized view will allow us to increase the performance of this query. We've now got a query here that takes a rather long time for us to execute. So there are definitely a variety of different ways that we could improve the performance, we could definitely create an index on, say, the post ID column or the comment ID column of the likes table, and that would increase our performance by quite a bit. Well, let's say that for whatever reason, we just don't want to do that. So one possible solution would be to create a materialized view out of this query. As we mentioned just a moment ago, a materialized view is going to run this query at only very specific times. After the query is actually executed, Postgres is going to hold on to the results of the query, and then we can refer back to those results anytime we want, and there's going to be a huge performance increase because we are not rerunning the expensive query again and again and again. So let's take a look at how we create a materialized view. To make a materialized view, we take some query that we essentially want to kind of persist or hold on to the results from. Then right before the query, we will write out create materialized view. We'll put in a name for the materialized view. In this case, I'm going to call it weekly likes, and then as a set of parentheses, and we're going to put that whole query inside the parentheses, like so. Now notice that I've got a semicolon only at the other side of the closing paren there. I don't have any semicolons inside of the parentheses. Then finally, after the parentheses, we're going to write with data. So with data right here means that when we first create the materialized view, we want Postgres to automatically run this query one time and hold on to all the results. Let's now run this and see what happens. Okay, so it looks like it has been executed. So now Postgres is holding on to the results of this query right now. So now we can refer back to those results or run any query we want to on the results by taking a look at weekly likes. So for example, if I comment this out and do a select star from weekly likes, we'll see the results of that query and take a look at that. It ran amazingly fast. For me, it was 59 milliseconds, and again, that includes travel time to the server, so in reality, it was probably a lot faster than that. So we cut down on the execution speed, or kind of taking a look at the result of this query, from, for me, about 2 or 3 seconds, all the way down to a fraction of a second, just a handful of milliseconds. Now we can take a look at weekly likes as often as we wish, and do anything that we want to with them. We could further sort these values, we could take a look at only specific columns, or anything else we want to do. Now the one downside to a materialized view, even though it's very clear that we get this very big performance benefit, is that if we now modify any of this underlying data, in other words, if we modify our likes table or posts or comments, that is not going to modify those kind of cached results that are currently stored inside of Postgres. Instead, we have to manually tell Postgres that it needs to go back and update the materialized view. It needs to rerun this query, take the results from it, and hold on to those results. So let's take a look at how that works. Now, really quick, I want you to take a look and notice how for the very first week right here, or the really first 2 weeks, I've got 29 posts and then 31 posts. So those are, I should say, likes for posts. So these are likes for posts that were created during the month of January. So we're going to run a delete statement. We're going to delete all the different posts inside of our January month. So in theory, this number, or these numbers right here really, should all go down to 0 because we don't have any posts inside that first month of January anymore. So let's try to write out something that's going to delete those lines. So I'm going to do a delete from posts where the created at is less than 2010-02-01. That is February 1st right there. So I'm going to run that. Okay, looks like we deleted some stuff. Now I'm going to comment out that delete statement. I'm going to uncomment that same select from weekly likes, and we're going to see that we still have some posts inside there. Or once again, I should say likes. So in reality, these likes don't really exist anymore. So now Postgres is referring to some data that is just plain out of date. So to fix this, we have to tell Postgres to update the materialized view. It needs to rerun this query and then hold on to the results that come out of it. So for that, I'm going to recomment select star from weekly likes. And to update the data that is being held by materialized view, we write out refresh materialized view weekly likes. So in other words, go to weekly likes, rerun that underlying query. We'll do that. And now if I comment that and uncomment the select star from weekly likes, we will see that we don't have any values for that week of January anymore. Okay. So this is looking pretty reasonable. So we've now got a tool that we can use to dramatically speed up the results of making some kind of query or kind of getting access to the results of some query very quickly. Now, as you can guess, the one big downside to a materialized view is that we have to very manually tell Postgres that we want it to rerun the query inside the materialized view. That is the one big downside here. So in general, we only like to make use of materialized views whenever we are trying to calculate some values that are not going to be changing very often. This example of finding all the number of likes for posts and comments on a week-by-week basis is a really good example, because we probably do not need to rerun this query right here too often. Once we do it one time and we've got that kind of big list, we probably don't need to rerun this until, say, next week, when we can take a look at the previous week's number of likes for posts and comments. This would be a really good example of where we don't have to rerun or refresh the materialized view again and again and again. We might only have to do it, say, once a day, or once an hour, or once a week, or something like that. Okay, so that's materialized views. Let's take a pause here and continue in just a moment. In this section, we're going to discuss transactions. Just about every single article, blog post, piece of documentation, and so on around transactions always explain them using the exact same example. And there's actually a really good reason for that. The example that is used is really effective at helping you understand what transactions are all about. So even though we are currently working with our Instagram database, we're going to go through pretty much the same kind of example. We're going to set out a new table inside of our Instagram database, not really related to any of the other tables. We're doing it just to better understand what transactions are all about, how to use them, and what they're for. Okay, so let's get started. Okay, so I want to imagine for just a moment that instead of working on our Instagram database, we are instead developing a database for some kind of bank. So maybe for this bank, we need a table of accounts. And every account might have the name of the person who owns the account and its balance, or the amount of money currently stored inside that account. One thing that we might need to do in a banking kind of application is transfer money from one account to another. Let's imagine that we need to transfer $50 from one account belonging to Allison to another account belonging to Gia. So how would we do that? Well, if we were in the real world to do a transaction or a transfer of sorts, we might just have Allison hand off $50 to Gia. But obviously we can't do that in the database world. So we have to break this down into a series of steps that are actually compatible with what we can do inside of a database. So to do a transfer like this, we might break it down into one step where we subtract or withdraw $50 from Allison's account. And we could do that with a statement like this right here. So we could say that we want to update a table called accounts. We could find an account belonging to Allison, and then take whatever the current balance is and subtract $50 from it. Then separately from that update statement, we could run a second update statement where we add $50 to Gia's account. And there's a SQL that we'd run for that right there. So this seems simple enough, but it turns out, especially when we start talking about money, that there's actually some really big issues that can start causing us trouble. Let's take a look at one very simple issue that we might run into with these two separate queries or two separate updates right here. Okay, so maybe we are running some application server on, who knows, AWS or DigitalOcean, or even just on your computer. And maybe, unfortunately, in between your server running this first query right here, or this first update, and the second update, maybe, unfortunately, you have some kind of crash. Now, when you crash, you might have already ran the statement that would subtract $50 from Allison's account, but you were never able to actually run the statement that would add $50 to Gia's account. Eventually, your server might come back online, but you might not have any infrastructure or any code in place to detect any of these kind of half-executed steps. If that was the case, then you will have withdrawn $50 from Allison's account, and you've essentially got no accounting for it whatsoever. Nothing to say that you still need to add $50 into Gia's account, nothing to say that Allison has $50 less than she should have, and so on. So this would definitely be a scenario that would be really bad and hard for us to recover from. So this scenario is what transactions are all about. we're going to use a transaction to solve this kind of problem, where we want to run some kind of updates in series, and we need to make sure that all the different updates are always executed, or none of them are executed. So in other words, we need both these statements to be successfully executed, or if only one is able to be executed and not the other, we need to roll them all back and undo all the changes we have made. Okay, so now that we understand vaguely what transactions are going to be used for, let's actually start to walk through a little scenario in the next video. Back inside of pgadmin, let's go ahead and create that accounts table that we were just talking about. We'll then try to experiment around with the table a little bit and better understand what transactions are all about. So I'm going to first get started by creating a table called accounts. I'm going to give this table 3 different columns. So I'll give it an ID that will be of type serial. I'll say it's going to be the primary key. I'll then also give it a name column that will be a varchar 20. And we can of course say that it can't be null. And then maybe we will also give an account a balance, which is the amount of money currently in the account. I'll make that an integer. I'll say that it cannot be null. And of course, if you want to, you can also put on a check here to make sure that the balance never goes negative, for example. You might also want to give it a default, perhaps of 0 or something like that. Totally up to you. Okay, so let's create that table. And then once we create it, I'll then go ahead and insert 2 rows into it. So I'm going to make 2 accounts, one for a user that I'll call Allison and another that I'll call Gia. And we'll give them both $100 to get started with. So we'll do an insert into accounts. We will specify the name and the balance. We'll then provide the different sets of values. So first we'll do Gia with $100, and then Allison with $100 as well. Okay, I'm going to run that. Looks like it was successful. So finally, I'm going to delete the insert and do a select star from accounts just to make sure everything was created successfully. Yep, looks good to me. All right, so now that we've got some data to work with, we're going to take a quick pause. I apologize for the super short video, but the next one's going to be just a little bit long, so I want to make sure that we've got a lot of time to focus on exactly what all this transaction stuff is all about. We've now created that accounts table, so now we're going to take a look at how we created transaction and manage it. We're going to first begin by taking a look at a couple of different diagrams. So inside this diagram, we've got our Postgres database. We are connecting to a Postgres database by creating something called a connection. Every query tool window that you open up inside of pgadmin, or anytime that you connect to your database from some other kind of application, or even some code that you might write, you are creating a different and unique connection. So if I go over to my left-hand nav right now, right-click on Instagram, and click on Query Tool, that opens up a second Query Tool window. I now have 2 separate windows open. Each of these windows are issuing or connecting to Postgres with a separate and unique connection. So we can now imagine that this first window is like connection number 1 right here. And the second window is like connection number 2 right there. So in this case, I don't actually have a connection 3 or 4, but we can imagine that I could very easily open up additional query tool windows and those connections would exist. Whenever you open up a connection to your database, you are connecting to your, well, database. And you have access to all the data inside that database, such as the accounts table, users table, posts, and so on. The data that you are looking at is the exact same data that all the other connections are looking at as well. So we might refer to this as kind of like being our main pool of data. Now that's not a technical term, I just have it in here for the purposes of this diagram. And I just mean to say all these connections see the exact same data. Okay, so now that we've established that, we're going to start to walk through this process right here and how we would run these 2 separate statements by using a transaction. And along the way, we're going to be taking a look at a couple of other diagrams that are just like this. Okay, so back inside of my first window, I'm going to open up a transaction. That's how we refer to it. You can say that we open a transaction, we create a transaction, or we begin a transaction by running just the keyword begin by itself. Now, before I do, I want you to take note that in this solid gray bar right here, there's a little plug icon. And if I click on it, it says there is no current transaction. So just take a look at that icon for a moment. I'm going to click on the play button to run begin. And I'll now be told, okay, well, query returned, but what does that mean? Well, you might notice that the little icon right there has changed. And if I click on it again, it says that the session is idle in a valid transaction block. So this connection, this window that I'm currently looking at, connection number 1, is now in a special or different state than connection number 2 over here. You'll notice that if I click on connection number 2, it still has that normal icon. So connection number 1 is now in a special state. But what does that mean? Well, as soon as we open up a transaction, we can imagine that this is what occurs. When you execute begin, you can picture in your mind that our database is creating a separate workspace of data just for connection number 1. And we can further imagine that we are taking a copy of all the different tables, all of our different rows, everything out of our main database and making a copy into this separate isolated workspace. Now, very important, behind the scenes, we are not actually copying any data whatsoever. Just by opening a transaction, we are not copying any tables, any rows, anything like that. This is just a very convenient way to imagine what is going on behind the scenes. So now connection number 1 is the only connection that can access any data inside this workspace. So now we can start to freely make changes to this accounts table, and no other connections are going to see those changes whatsoever. So let's try that right away. Let's try withdrawing $50 from Allison's account, and then see if we can detect those changes from any other connection we have. So inside of my first query tool window, I'm going to delete the begin statement and then replace it with a update accounts. We're going to set the balance to balance minus 50, where the name is Allison. So we are subtracting $50 from Allison's account. That is the first query of this 2-query process. So let's now run this. Okay, looks like it was successful. I'm going to comment that query out for just a moment, and let's do a select star from accounts. So if I run that, we'll then see very easily, just plain as day right here, Allison now has $50 in their account. But that is from the perspective of connection number 1, which is currently running inside this little isolated environment that has a separate copy of all the data inside the accounts table. So we can now change over to connection number 2. We can issue the exact same query, and we're going to get a different result because connection number 2 is still looking at our primary source of data. So let's try that out. Over inside of my second query tool window, I will do a select star from accounts. And then take a look at that. Allison in this world still has $100. So here's one result where it says Allison has 50 and another where Allison has 100. So clearly, connection number 1 is somehow isolated or separate from all the other connections. So now we can continue to make some additional adjustments to our data inside of connection number 1. So back inside of connection number 1, I'm going to comment out select star from accounts. I will uncomment this first update. Let's now add in $50, this time to Gia. So I will run that. There we go, update successful. Going to recomment, going to uncomment. We'll do a select star from accounts once again. And now we have Allison with $50 and Gia with $150. If we go to that separate connection once again and rerun this, in this world, Gia still has 100 and Allison still has 100 as well. So we have now made some number of changes to all the data inside of this separate little workspace. So now the big question is, how do we take those changes and somehow merge them back in to the main data pool? Well, we have a couple of different options for that. So first, after making some number of updates, if we want to merge those changes back into the main data pool and allow everyone else to see that data, we can run the commit keyword by itself. So if we just run commit, that means take all those changes, merge them back in. Alternatively, if we decide for any reason that we don't want to save those changes, if we don't want to merge them back in, then we can run the rollback keyword. So if we run rollback, that is going to delete the separate workspace. We're not going to save any changes, and connection number 1 will continue to take a look at the main data pool. There's two other little scenarios I want to mention very quickly. Another scenario that we can fall into, if connection number 1 runs some kind of query that results in an error. So for example, if we do a select star from some table that doesn't exist, that would result in an error. Whenever you have this separate workspace and get an error inside of it, The workspace, or really the transaction is what we're referring to here, enters an aborted state. You have to manually run a command of rollback to get out of that aborted state. Until you run rollback, you will not be able to issue any other queries or statements inside of that transaction. So in other words, if you have some kind of error, you got to run rollback. You're going to delete everything inside there. And connection number 1 falls back to looking at the main data pool again. So then the very last scenario I want to mention, because this one is very relevant for us, if we ever, for some reason, lose this connection, so if the connection is just suddenly terminated because the process that is making the connection crashes, so like our server or something like that, if we crash, then Postgres will detect that, and it's going to automatically clean up that transaction and delete all that stuff. And so we will not commit any of those changes back to our main data pool. So we're going to take a look at all 4 of these different scenarios, but for right now, let's just try doing the very basic commit. We have some changes inside this transaction number 1, and I want to commit them back to the main accounts table. So for that, I'm going to go to my first query tool window, and we should be able to see that little clock icon right there. I'll then run commit by itself. So it looks like the commit was successful. And now we should be able to do a select star from accounts inside of query tool number 1 and see Allison with 50, Gia with 150. And we should be able to go over to the second window, rerun that query, and also see Allison with 50 and Gia with 150 as well. So that's it. Okay, so we've taken a look at how to open up a transaction, or we might refer to it as a workspace. We then saw 4 possible ways of essentially closing out or finishing the transaction. We can commit it. We can roll it back if we just decide that we don't want to deal with any of the stuff. If we have an error in one of the statements we run, we can close this thing out with a rollback. And then finally, if there's any kind of error in the connection itself, if the connection just crashes, then Postgres is going to automatically just clean everything up for us. So now that we understand all 4 scenarios, like I said, we're going to walk through a couple of different scenarios with this accounts table in the next video. Now that we've seen some of the basics of transactions, let's try to simulate this scenario right here. So I want to try to open up a transaction. We're then going to subtract $50 from Allison's account. We're then going to simulate a crash. And remember, whenever a crash occurs during a transaction, Postgres should automatically delete that transaction and not commit any of the changed data back to our main data pool. So that everything should just blow away and we should not see any subtraction from Allison's account or anything like that. So let's go ahead and give this a shot. To get started, I'm going to first reset both rows inside of my accounts table. I'm going to make sure that both Gia and Allison have $100 once again. So I will do a update accounts, and we will set balance to 100. We do not need any where here because this is just going to take a look at all the different rows inside of accounts and set the balance of every one of them to $100. We should now be able to do a select star from accounts and just verify, yep, they both have $100. So now let's open up a transaction. Remember, we do that with begin. When we run begin, we should then be able to see that icon change into that little clock, and it says we are in a valid transaction. So now we can start to simulate this flow. We're going to withdraw $50 from Allison's account. So for that, we will do a update accounts. We will set balance to balance minus 50, where the name is Allison. So I will run that. Okay, the update was definitely made inside this transaction. And inside the same window, we can very easily do a select star from accounts and verify that Allison now has $50 less. So now we are in this in-between stage. We have done the withdrawal, but we haven't added in $50 yet. Now we're going to simulate a crash. To simulate the crash, I'm going to go over to the dashboard tab on the top left-hand side. I'm then going to go down to the bottom right. I will click on the refresh button, and then I should see 2 items on here with the name of pgadmin-con. If you only see 1 item, that's totally fine. These 2 rows that say con represent the 2 query tool windows that I have open right now. So I'm going to manually terminate both those windows. So click that red X right there, and the red X right there. So now those connections have been terminated, just 100% stopped. So in theory, we no longer have any transactions running. Postgres should have automatically recognized that that connection has died and cleaned up the transaction tied to it. So let's now try to verify that by opening up another window. I'm going to open up a third window right now. I'll do a select star from accounts, and we will see that both Allison and Gia still have $100. If you want to, you can take that exact same statement and go to the other two query tool windows we had open, do the same thing. When you run that query, it's going to ask you to restore the connection, so essentially establish a new connection. So I'll do that. Yep, still have 100. And then back to the window where we were actually doing the subtraction there. And if we do that same thing, we are told $100. So the transaction that had been tied to this connection or this window just automatically got swept away. And so that is how we're going to make sure that we never fall into this kind of scenario. We're going to make sure that if we ever need to run some number of queries in sequence and they all have to be executed or none of them be executed, we're just going to wrap them all inside of a transaction. Okay, so that's pretty much it. Now I want to take a look at one or two other scenarios in the next video. So quick pause right here and let's get back to it. There's just one other scenario that I want you to see very quickly. So recall that if you ever open a transaction and then run a query that results in an error, then the transaction is going to enter into an aborted state, and you have to manually roll back the transaction. So I just want to show you a very quick example of this, because anytime you start working with transactions, you're going to see some error messages that essentially result from the same thing, and I just want you to know how to interpret those error messages. Okay, so back over here, you can reuse any of the existing query tool windows you have open, or just create a new one. I'm going to go ahead and do a begin to open a transaction. I'll then do a select star from something that just doesn't exist. So that is definitely going to result in an error. I'm going to run that, and sure enough, we got an error. So now if we try to do absolutely anything else inside this transaction, so a select star from accounts, for example, even if it is valid, we are going to be told, and this is the error text right here that I want you to recall. This is the text that you need to remember because you will run into this in the future. It says current transaction is aborted. Everything's going to be ignored until the end of the transaction block. So to end the transaction block, or essentially close the transaction out, we're going to do a rollback. And that's it. So we'll do a rollback. The transaction is now closed. And now we can once again do some normal queries like select star from accounts. And everything works as expected. So again, anytime you see those magic words, something about an aborted transaction, remember, you just got to do a rollback, and then you can start using that connection as you would normally once again. I'm really excited about this section because we're going to be talking about a very important topic, and that topic is schema migrations. Schema migrations are all about making very careful and well-planned changes to the structure of your database. So we are talking about adding columns to a table, removing columns, changing the name of a column, adding tables, removing tables, and so on. Schema migrations are exceptionally important whenever you start working with other engineers. So to help you understand what schema migrations are all about, we're going to spend this video to walk through a little story. I'm going to give you a little story, or tell you a little story, about one day that you might have working as an engineer over at Instagram. So we're going to pretend that you are an engineer working at Instagram in charge of managing their database. And maybe on this one particular day that you are working at Instagram, you have to make a couple of changes to the structure of the database. So we're going to imagine that you make some changes, and well, if you just make those changes directly to the database, we're going to see that some really big issues start to arise very quickly. Now, the reason that I'm going to tell you about all this stuff in kind of a story format is because these are issues that I can just about guarantee that you are going to run into at some point in time in your database career. So I really want you to see the kind of series of steps that lead to these issues and how you should solve them. Because we are going to be going through all this in kind of a story format, this video is going to end up being a little bit long. So if you don't really care about my story that I have to tell you, totally fine. If you just want to kind of skip ahead, go to the next video and get a summary, that's totally fine. Otherwise, stick around and let's get to it. All right, so here is the story. We are pretending that you are an engineer working at Instagram. You are in charge of specifically the comments table. That is it. That's all you have to do. That is your whole job. Your job is to manage this table, and that is it. In order to make changes to the comments table, you are working with two separate copies of Postgres. One copy of Postgres is hosted on your local machine. Another copy of Postgres is hosted on Amazon Web Services. There are two copies of this database for you to work with so that you can make changes to the copy of Postgres on your local machine and just test out that these changes are working as expected. So you essentially have a development environment on your computer. Once all those changes are working the way you expect on your local machine, you then make those changes to the production database hosted on AWS. So all of your actual user data lives inside of this database over here. This entire flow of having a local development environment separate from a production environment is extremely common. So this whole setup is totally fine, totally reasonable. So let's imagine that you show up to work one day and you get some feedback from some other developers. And these other developers tell you that on the comments table, there is that contents column. And the feedback is the name of this column is not good. Contents and comments already sound very similar. The name of the table is very similar to this column name. In addition, it's really challenging to remember if this is contents or content. So the feedback that you are getting from other developers is that this column name needs to change. So you say, okay, well, that's a simple change. You and I in this course haven't really discussed how to rename columns yet, but just so you know, it's a very simple and easy process. So you decide that all you should have to do is rename that column. Very simple, very straightforward change. So on your local machine, you would take that comments table, you would run a statement like this right here, which will rename that column from contents to body. That is your solution. You say we're going to have a new column called body. Now you're not actually moving any data around here or anything like that. You are just renaming the column. This is a very inexpensive, very fast, very easy operation inside of Postgres. So this is, in theory, a very low-risk change. So again, you go ahead and make this change on your local machine. When you run that statement, you don't get any errors or anything like that, and so you figure, hey, everything looks good. Let's go ahead and make this change to our production database hosted on Amazon Web Services. So you go ahead and open up pgadmin, you connect to your production database hosted on AWS, and run that same kind of statement right there. Now just so you know, doing something like this, connecting to your production database and making a change to the structure of that database using pgadmin, that is something that's going to get you into trouble for reasons that we're going to see very quickly. So you go ahead and make this change to your production database. And lo and behold, about 0.001 seconds after you make that change, sirens start going off in your office. Alarm bells are going off. And you start getting emails saying that there are some critical errors coming out of your application. And so chances are it's all tied to that rename of that column of contents over to body. But what happened? Why are there errors at all? Well, let's think about the overall structure of your application, some kind of like Instagram-like application. Okay, so for some kind of Instagram-like application, you might have some kind of request coming in to an API server. This request might be issued whenever some user tries to create a comment. That request will go to some kind of API server. The API server will then try to extract some comment text from the request itself, use that text to build up some kind of SQL statement to insert or create a comment, and then send that off to the database. Just one little issue. You just renamed that contents column over to body, but you never made any changes to the API server itself. So whenever the API server builds up some statement to insert a new comment, it might still be referring to that contents column, and it is not referring to that new body column. So as soon as you run some statement like this right here, Postgres might throw an error and say, hey, there is no contents column. We have a body column, but there's definitely not a column called contents. And so your API server would start to throw some errors because you are trying to run some invalid SQL statement. Okay, so we're going to take a very brief breather right here and reflect on big lesson number 1. Big lesson number 1 is that anytime that we make a change to our database structure, we have to synchronize that and deploy it at the same time that we change our clients as well. So in other words, if we change that contents column over to body inside of our comments table, we need to make sure that at just about the same time we make that change, all of our different clients, such as an API server, are told, hey, you need to run this new version of code that is going to refer to a body column and not contents anymore. We can kind of imagine this entire scenario in a sort of time diagram like this right here. So in this diagram, we've got 3 columns, one for the database, one for some kind of change that we need to make to our API, and then one for the existing running API. So on the top left-hand side is the change that we need to make to our database. You are trying to run a command that's going to rename the contents column over to body. That operation is going to be very quick and very inexpensive. You are able to rename a column in just a fraction of a second. So in theory, what you really want to do here is try to make that change at just about the same time that you start to deploy a new version of your API code. A version of that code that's going to refer to the body column instead of contents. Now, even if you try to make these 2 changes at the same time, you can still run into a little trouble. Doing a deployment of some kind of application server might take many seconds or even several minutes. So there could potentially be some kind of window in time here where you rename that column and you are still in the process of doing a deployment of your API. In the meantime, you still have the old version of the API running with some code that is still referring to the contents column. So the instant that the rename of the column is complete, the existing running API would start throwing errors every time a user tried to insert a new comment, because there is no contents column anymore. It's only after that deploy finishes with some new version of your application code that is referring to the body column correctly that the API error would start to go away. So again, there's a kind of window in here during which any request where you are trying to create a comment would fail. Now, anytime that you see some kind of company ever send you an email that says, hey, our service is going to be down from maybe 2 a.m. to 3 a.m. on Wednesday morning or something like that, anytime that you hear about some big company with some planned or scheduled downtime, changes to the database structure, this is frequently what they are doing during those downtimes. One way to address this whole situation is to just say, hey, you know what, we're going to take down our entire application, we're going to stop the API running, we're going to make some changes, planned changes to the database, and then once those changes are completed, they will deploy a new version of their application code, bring everything back up and online, and ta-da, everything is working as expected. However, there are many companies, many scenarios where you need to make changes to the database and you just plain cannot take the application down. You might be working for a company that has some kind of service level agreement, or SLA is what it's referred to, and in an SLA you might be required to keep your application online for a vast majority of time out of the year. So in some scenarios, having a window like this just cannot happen. So we're going to take a look at a couple of different techniques to understand how we can minimize this scheduled downtime, or this window right here, and make sure that we don't have any scenario where some kind of change to the database is going to result in some kind of errors. Okay, so that is kind of part 1 of our story. Let's now go into part 2. Oh, one other very quick item I want to mention here. If you are starting to work at a very large company, one other thing I want to mention here is that if you are planning on making a change to the database and a change to your API server at the same time, those might be 2 different teams of engineers. So there might be one team of engineers dedicated to maintaining the database and another dedicated to just handling deployments. So if you are trying to make these 2 changes at the same time, that kind of assumes that you're going to have these 2 different teams of engineers working very closely together to kind of schedule this downtime and so on. And that in its own right is challenging as well, because you have these different teams of engineers that might not even know each other, who have to kind of do this coordination on some very important operation. Okay, so like I said, that is part number 1. So let's now go into part number 2. So part number 2, let's say that you made that change to the database, you renamed that column, you saw all those errors, and so you very quickly hop back onto pgadmin and rename that body column back to contents. So now all the errors went away, but you still need to make this change. I'm sure you can imagine that your manager might be really angry that you broke the application. So they might say that moving forward, in order to avoid any issues like this again in the future, you are going to be responsible for the comments table and any related changes to the API that are trying to access the database, or specifically that comments table. So in other words, you are now responsible for this entire series of actions. You have to make the change to the database and the code on the application server as well. And then to make sure that you are doing everything correctly, all the changes you make need to be reviewed by another engineer. So to make sure that this entire new flow is working as expected, your manager tells you, okay, go ahead, try to change contents to body again, but follow these new procedures. So you say, okay, no problem, I can do this. So you go ahead and make that change on your local machine, once again, to the comments table. You change contents over to body, and you also change some API server code as well. We don't really have to worry too much about the code here, but you can definitely take notice that we have references to the body column inside of here now. So you test out all these changes locally on your machine, you confirm that they work, and you say, okay, time to get a review, time to actually deploy this stuff. So maybe you post on GitHub, or whatever version control you are using, a request for a code review. And you say, all right, here's the changes I made. We've got some new version of our API code where we are now referencing the body column. So on GitHub, you have created a code review request, and it contains all the changed code specifically for the API. Now I say for the API here because throughout this entire course, you and I haven't really focused too much on how to kind of codify changes to a database inside of any saved file. In other words, we've really been opening up pgadmin at all times and then manually running statements to add tables, remove tables, add columns, and so on. So you can kind of imagine that if we took our same level of knowledge right now and created a code review request like the one we have right here, we might not have anything inside of this code review request that says, hey, here's the actual SQL to be reviewed as well. So I want you to think about the impact of that. We have a code review here where we are asking someone to check these changes out, but inside the code review are only changes to the API. So let's imagine what would happen. Okay, so we can imagine that maybe your boss decides to take a look at this first code review themselves. So at this point in time, on your machine, so that's on the left-hand side over here, you have the body column inside the database, and you have some API code that refers to that body column as well. So for you, everything is working A-OK. But for your boss, they check out your code to do a review on it. All of the code on the API is referring to that body column, but your boss has not done anything whatsoever because there's nothing inside the code review to mention this, that the body column needs to be renamed over to contents. So as soon as your boss checks out all this code and tries to test it out locally, whenever they try to insert a new comment, they would get an error that says, hey, there is no column body, because inside the database, they still have the contents column. So what would happen here? Well, chances are your boss would come back and say, hey, I tried to test out your code, but got an error of column body not found. What is going on here? Fix this. Well, I'm sure you could figure out what was going on really quickly. So maybe you would put up a note that says, just open up pgadmin and run this statement right here. That will rename the column to body and everything should work as expected. After making that change, your boss could then test everything out locally, and chances are everything would work as expected. They've now got a version of the database that has a body column, and they've got a version of the API that refers to that body column as well. So everything works as expected. Your boss would probably say, okay, looks good, go ahead and merge this stuff and deploy it to production, and your code review is complete. Almost. So let's imagine that maybe you go ahead and do the deployment, everything works as expected, but in the meantime, your boss says, I don't want to look at this version of the code anymore on my local machine. So they might go ahead and revert all the changes that you had made to the API on their machine. But they might forget to make any of the changes or revert any of the changes to their copy of the database. So they are once again in a conflicted state. They now have a version of the API on their machine that refers to the contents column, but they've got a version of the database that has the body column. So once again, they could try to create a comment, get an error of something like, hey, column contents does not exist, and they fail to ever insert a comment. So what would happen here? Well, chances are your boss would come back and say, you just broke everything on my computer. I'm not even running your code anymore, and everything is broken. I can't create any comments. And so maybe at that point you would get fired. Who knows? Okay, so at this point in time, big lesson number 2 here, whenever you are working with other engineers, it is extremely important that you have a very easy way to tie the structure of your database or changes to the structure of your database to your code as well. So whenever someone checks out or kind of looks at a particular version of your code or your application server, they need to somehow make sure that they've got the correct structure of the database as well. So at this point in time, out of this video, out of this entire story that we just walked through, we really have these two big lessons. So let's kind of take these lessons into the next video, and we're going to start to take a look at schema migrations and understand how they solve both these big issues. In the last video, we ended up with two big lessons. Lesson number one was that whenever we changed the structure of our database, we needed to make sure that we changed our clients that were connecting to that database at the same time. Big lesson number two was that whenever we were working with other engineers, we really need a way to tie the structure of our database to some specific version of our code. So in this video, we're going to start to take a look at a way that we can solve both these big lessons. All right, here we go. So at this point in the course, we have been making changes to the structure of our database by opening up pgadmin, accessing some database, and then writing out some command that changes the structure of our database. So in other words, all changes were made directly inside of pgadmin. Moving forward, wherever possible, we're going to instead author something called a schema migration file. Schema migration files are files that contain some amount of code that describe a very precise and very detailed change that we want to make to our database. So for example, if we wanted to take our comments table and rename the contents column over to body, we are going to write out a schema migration file. That migration file is going to contain some code that says, I want to rename contents over to body. So what's going on inside these schema migration files? Well, a migration file can be written in any programming language you want. This entire idea of schema migrations is not tied to any particular language. So you can author a migration file with Python, Java, JavaScript, C++, anything you want to write it with. In general, a schema migration file is going to contain two different sections inside of it. We refer to one section as up or upgrade, and the other we might refer to as down or rollback or downgrade. The up section will contain some SQL that is going to somehow advance or upgrade the structure or change the structure of our database. So in our example that we walked through in the last video, we might have an up section inside of a migration file where we rename our contents column over to body. The down section is also going to contain some SQL that is going to exactly undo whatever the up command did. So if our up command renamed contents to body, our down would do the exact opposite. We would rename body back to contents. Once we author a migration file, we then apply it to our database. So inside of this example, we might start off with an empty database right here. If we wanted to then create some kind of table inside of it, we could write a migration file where the up section described or had some command that would create maybe a comments table. The down section would do the exact opposite of that, which would drop the comments table. If we wanted to change the structure of our database, we would apply migration file number one. That's the term we use. We apply a migration. And then if we decided for any reason that we wanted to undo that change, we would revert or undo migration number one. So we use the terms apply to describe taking a migration file and making a change to the database. We use the term revert to describe undoing that change. So every migration file contains everything you need to make a change and undo a change. Any single project can have many different migration files inside of it. So you might start off a project with a totally empty database. Rather than opening up pgadmin and writing out some SQL that would create some tables for you, you could instead create a migration file that describes setting up the initial structure of that database. So you might write out a migration file number one. Inside of it, you would describe creating maybe a comments table. You could then apply it to that empty database, and now you would have a database with a comments table inside of it. If you then wanted to rename, say, that contents column over to body, you could write out a second migration file that described renaming contents to body and apply that to this database, and you would end up with this right here. You've got the same table, but now it has the body column. Now, the very nice thing about migration files is that you can take a project with a bunch of migration files inside of it and hand it off to any brand new engineer working at your company. That brand new engineer could then run all the migration files, and they would be guaranteed that they've got the most up-to-date, perfect and exact structure of the database. The other nice thing about migration files is that if you ever write a migration and then decide that it's not quite right, you could run the down migration tied to it. So you would undo that migration, make some change, fix everything up, and then reapply the up. Okay, so now we've kind of described this idea very briefly of migration files. Let's go a little bit deeper into what problems this solves in the next video. Now that we've got a better idea of what these migration files are all about, let's see how they address big lesson number 1 and big lesson number 2. So first off, big lesson number 1, where we found that we needed to make changes to the structure of our database at the same time that we changed all the clients connecting to that database. So when we start making use of migration files, we can address this very easily. We can say that whenever we do a deployment of our API, we might start to deploy our code, and again, that process might take several minutes. Then, at some point in time, as soon as this new version of our API is ready to start receiving traffic, we can then automatically run all available migrations inside of our project. So we can write a script that will do that for us. So when we run those migrations, we're going to automatically change the structure of our database. And then the very instant that our database structure is changed, we can then start receiving traffic on this new version of the API. So in theory, this could shrink down that window of time where we have a differing version of our API and a different version of our database structure down to a very small period of time. Now, the other big lesson that we ran into was whenever we were running or working with other engineers, we had to make sure that we could very easily tie the version of our code for our API or whatever else it is to the structure of our database. So with migration files, we can do that very easily. Inside of any given code review request, we can say that we have some new version of some code that needs to be reviewed, and we can pair along with that a migration file that describes the exact changes to the structure that need to be made to our database in order to safely execute this new API code. So then, in theory, another engineer could take all the code for this code review request, they could apply the migration, which would give them the correct structure of the database to run this new version of the API. The other engineer could then evaluate and test all this code. And then finally, once they were complete with the review, that engineer could then revert this migration. And that would take them back to the current structure of the database. That would allow them to run whatever current code base or version of the code or the version of the API is really out there. Well, I think it's pretty clear that making use of migration files pretty well solves this whole kind of code review problem and making sure that we've got a synced version of the API and a synced version of the database. And it at least better addresses some of these issues around deploying a new version of our code as well. It doesn't solve all issues here. We'll talk about some other big issues that start to come up with this process, but it definitely gives us a better solution than what we had before. All right, so last thing we need to really take a look at is how we actually write a migration. So let's start to write out some code in the next video. Let's start to get a better idea of how to create and run a schema migration. Now, as I mentioned, you can write schema migrations in just about any different language. In this diagram right here, I did about a 5-minute Google search and found a list of libraries that are going to help you create or run a schema migration for JavaScript, Python, Java, Go. So as I said, any language you want, all these different libraries more or less work the same way at the end of the day. So we could pretty much pull up, say, a random link right here about from Go. And if we take a look at the documentation for this Go PG migrations package, you'll see that it works more or less the same way that I just described inside the last video. Same thing for the Python ones, same thing for the JavaScript ones. So to get a better idea of how at least one of these works, we're going to try to write out a migration using the Node.js package, node pg migrate. So we're going to be writing a little bit of JavaScript to do a migration. Now, the fact that we're using JavaScript in this course, that might be a little bit disappointing. You might be wanting to write this stuff out using Python or Java or Go or anything but JavaScript. Honestly, we are going to be writing such little JavaScript, you won't believe it. A very small amount of JavaScript, really honestly not a lot whatsoever. So even if you are not a fan of JavaScript or have very little knowledge on it, I still really recommend you follow along because again, at the end of the day, all these packages mostly work the same. Okay, so let's take a look at the documentation for this package very quickly. So I'm going to open up a new browser tab. and I'm going to navigate to npmjs.com. So this is a repository of a lot of different packages you can very easily install into a JavaScript-based Node project. Once here, we're going to search for node pg migrate, and we should see the first result right there. Then once here, if you want to, feel free to take a look at the documentation. There's also a link to a documentation page a little bit towards the bottom. So here's docs right here. Now, when you start looking at the documentation, you will see a little bit of JavaScript code, and you'll notice that although it seems like they are creating a table of users and maybe creating a table of posts, and they are wrapping that all up inside of a function right here called up, so that's very closely following what we discussed in the last couple of videos, you'll notice that you do not see a lot of SQL in general. So one quick note on all these different packages. A lot of these different packages have tools inside them that can automatically generate either an entire migration for you or generate SQL for you automatically. I highly, highly recommend, very highly recommend you write all migrations manually yourself using plain SQL. You have enough knowledge now throughout this entire course to understand how to do this. You understand how to create tables, how to drop tables. You understand how to create columns. You understand different options around columns. You have enough experience now to write out migrations manually. It's always advantageous to write out migrations manually as opposed to letting a library do it for you, because a lot of times libraries are going to make some intrinsic assumptions around some different options that you might want to apply to a column. So for example, they might apply some default value for you. They might say that a column can have null inside of it. They might say that they want to create an index with some particular option. And you might not know all the different specifics of what is going on behind the scenes when you're using these libraries. So if you write out the migrations manually, you're going to have a perfect understanding of what is going on behind the scenes every single time, as opposed to relying on the migration tool to do it for you. So I just want to throw that out there very quickly. There are many packages, and actually I'd say a majority of these kind of let you get away with having a migration being generated for you. And again, we really do not want to do that. So as we start to look at that documentation, even for this library that we're going to use, they are making use of some functions right here that essentially generate SQL for you. We are not going to do that. We're just going to use kind of the scaffolding or kind of the framework here of this migration stuff where we can define an up function, have it be executed for us manually and all that kind of stuff. But as far as actually making true changes to the database, we are going to write out some raw SQL. So just a quick note on that. All right, so let's take a pause right here. Now we understand what we're going to do. We're going to generate a project in the next video. We're then going to install this module and start authoring a migration. Let's get some practical experience generating and running migrations. So at our terminal, we're going to first begin by creating a new Node.js project. We're then going to install that node pg migrate module that we just looked at, and we'll use it to then generate and execute a migration. So to get started, inside of my terminal, I'm going to make a new folder that's going to hold all the code for all this migration related stuff. So I'm going to make a new folder called IG, short for just Instagram. I'll then change into that directory. And then inside there, I'm going to run npm init-y. This will generate a package.json file, which will allow us to install some different modules into this project. So I'm going to run that command. After that, we'll then run an npm install command that's going to actually install the node pg migrate module. So I will execute npm install node pg migrate, and then before you run that, we're also going to install a second module called pg. pg is short for Postgres. This is a Node.js module that allows us to connect and work with Postgres directly. Okay, so once we've got both these modules written inside of here, we'll run that and let it do its thing. Both these modules are rather small, so they should only take a moment or two to actually be installed. After I have installed them, I'm then going to open up my code editor inside that directory. All right. So inside of here, I should see a node modules directory. That's where all those packages are installed that we just added. We've then got a package.json file and a package lock file. Now, before we start changing anything inside this project, let me describe very briefly what we're going to try to do. Currently, inside of our local Postgres database, we've got that Instagram database with a ton of data inside of it. I don't really want to delete any of the data inside there because we might eventually want it later on inside the course. And you might eventually want it if you want to go practice a couple of different queries or whatnot. So rather than making any permanent changes to that Instagram database, we're going to instead generate a new database, which we will call simply social network. So we're going to make a new database called social network. We're then going to write out 2 migrations for it. The first migration is going to do exactly what you see right here. We're going to try to create a new table called comments. After that, we're going to create a second migration file, which will rename the contents column of comments to body. So we're not going to be directly working with any data. For this example, we are just focused on creating an empty database and then creating some different objects and changing objects inside of it using some different migration files. So with that in mind, let's take a pause right here and then start to put this example together in the next video. All right, my friends, let's first begin by using pgadmin to create a new empty database. Once again, we're going to call it simply social network. So I'm going to go back over to pgadmin. Once there, I'll do a right click on localhost and then go to create database. We'll then give this a name of social network and then click on save. So there's our empty database. Naturally, we can click on it, open up schemas, go to public, and then tables, and there's nothing inside of here right now. So let's now start to create a new migration file. This migration file will describe the process of creating a new table. It's going to have both an up section and a down section. And so in this case, the down is going to be the exact opposite of up, which means that the down section is going to drop a table called comments. To create a new empty migration file, we have to do a little bit of one-time setup back inside of our code editor. We'll then run a command at our terminal. So the one-time setup we're going to do is to open up our package.json file. We are going to find the scripts section inside of here. At present, there's one default script inside. I'm going to delete that entirely, and then we will replace it with migrate node pg migrate, like so. All this line does is allow us to access the node pg migrate CLI from our terminal. That's it. We only have to do that step one time. So now we can go over to our terminal and run a command that will create a new migration file for us. So back at my terminal, I'm going to make sure that I'm inside of my IG project directory, and then I'm going to generate a new migration file by running npm run migrate create, and then after that, we're going to put in a name for this migration file. The migration file name should be descriptive and pretty much at a glance tell us exactly what the migration is going to do. So in this case, I'm going to put in create table comments. So we can read this very easily as create a migration called table comments. So if I run that, we'll then be told that a new migration file with that name right there has been created inside the migrations directory of our project. So we can now go back over to our code editor. You'll see that there is a new migrations folder inside of here, and inside there is a file called table comments. The number at the very start of this is a timestamp. So that is the time at which this migration was created. That timestamp is going to tell this migration library later on, so node pg migrate, what order these different migrations should be executed in. Because we would want to make sure that we always run this migration file first. In other words, the migration file that actually creates the table before we ever try to run a migration that would try to change it in some way. Then inside this file, we can see very easily that there is a function right here called up and a function called down. So these two functions do exactly what we described before. They are going to contain or produce some amount of SQL or run some command or do whatever to either advance the structure of our database in some way, and then down is going to contain some SQL or run some command or do whatever that is going to revert or do the exact opposite of whatever we did with up. Now, if you had looked at the documentation, you might have noticed that this pgm argument right here is essentially an object that we can use to create tables or change tables, add columns, all that kind of stuff. But as I had mentioned previously, we are not going to rely upon any kind of automatic migration generation or anything like that, anything to automate the process of making changes to our different tables. So instead, you and I are going to write out pgm.sql. We're then going to put in a multi-line string, which in JavaScript we indicate with a set of backticks. That is a character to the left of the 1 on your keyboard. And then we are going to write out some raw SQL inside of here that we want to execute. So this is where you and I are going to write out some raw SQL that is going to generate this new comments table. We'll make sure that we designate a couple of different columns for it and so on. So again, we are not relying upon any kind of built-in function that is going to create the table for us. Okay, so in our case, I want to create a table called comments. And all I really want to have inside there is an ID, a created at timestamp, updated at, and contents. That's pretty much it. Let's throw some of those things in right away. So I will do a create table comments, and then a set of parentheses. Inside of here, we will do our ID of type serial, and we'll say it's going to be our primary key. Next up, we will do our 2 timestamps of created at and updated at. So we'll do a created at timestamp with time zone. And remember, we will provide a default for this. So the default is going to be current timestamp. We'll then do the same thing for updated at. So timestamp with time zone, default current timestamp. And then finally, we'll do our contents column as well. So contents can be a varchar 240. And let's say that you always have to provide a contents for a comment. It doesn't really make any sense to have a comment without any text for it. So we'll say not null. Okay, so that is our up statement. It generates the comments table, and that's all it does. So then inside of down, we're going to do the exact opposite. So I will do a pgm.sql, another multi-line string, and inside of here we could do a drop table comments. So again, the down is the exact opposite of whatever we did inside of up. Okay, so I know that there's a decent amount of JavaScript inside of here. You might be curious what this export stuff is, what this pgm argument is. At the end of the day, all that stuff is just plain not important. Again, all these different libraries work the exact same way, and after reading the documentation for a couple of minutes, you will understand what these different migration libraries are doing. At the end of the day, you get some place to write in some SQL to advance the structure of your database, and you get some other location where you can write in something to revert that change. Okay, so now we've written our migration. The last thing we have to do is actually execute it or apply it to our database. So for that, we are going to have to do a little bit of platform. So in other words, Mac OS versus Windows versus Linux setup. So quick pause right here, and then we'll figure out exactly how you're going to run this migration depending upon your operating system in the next video. We've got our first migration put together, and now it's time to actually execute it. So to execute the migration, it's going to be a little bit different depending upon your operating system. So let me first give you a quick little guide. Okay, so we're going to eventually run a command to actually execute the migration. The first thing we have to do is set up an environment variable called database_URL. This is going to be a string that tells the node pg migrate module that we're using exactly how to connect to our database running on our local machine. To set this environment variable, we first need to figure out the actual value that we want to set it to. The general format is going to be this string right here. So you're going to put in Postgres : then your username to connect to your Postgres instance, a colon, a password, so that's going to be the password that is used to connect to your instance, and then at localhost 5432/social network, with social network being the name of the database in particular that we want to connect to. Now, I only put the spaces in here for clarity. So when you eventually write out this full URL, you are not going to put in any of these extra spaces. So it's going to eventually look something a lot closer to this right here. If you installed Postgres on Mac OS with the Postgres app, then your username is going to be whatever your username is on your computer. If you need a quick reminder on what that is, you can go over to your terminal and type out "who am I?" and that's going to be your username right there. Then on Mac OS with Postgres app, there is no password. So if you are on Mac OS, you're going to not put in any password and you're going to remove that colon as well. So for me personally, because I'm on Mac OS, running Postgres app, I would put in exactly that string right there. If you're on Windows, on the other hand, your username is going to be Postgres, and your password is whatever you entered when you initially installed Postgres. So recall many videos ago when we did that initial installation, in that little setup wizard, you had to enter in a master password. That's what your password is. If you don't remember it, I would really recommend you first start off by just trying something like password, because during that video, that's what I told you that you might want to use. So once you've got that entire string put together, we're then going to run a very specific command while also setting this database URL environment variable. So depending upon your operating system and which terminal you are running, you're going to end up entering a slightly different command. So if you're on macOS with Postgres app, it'll be database_URL equals, and then your Postgres URL, and then a space, and then npm run migrate up. If you're on Git Bash, it will be the database URL, same thing right there. If you're on CMD, it'll be set database URL, and then notice and right there without any spaces on the other side. And then finally an example with Windows PowerShell as well. Now, if you're on Windows, don't forget we do need the password in there. Make sure you get the password in there as well. Like so. Okay, so once you've kind of picked your flavor out here, let's go and try this out. So we're going to go back over to our terminal. For me, because I'm on macOS, using Postgres app, I'm going to put in database_URL equals Postgres : / I'm going to connect as my username with PG, and then at localhost : 5432 / social network. And then after that, I'll put in a space, and then the actual command I want to run here is npm run migrate up. So that is going to advance the structure of our database by running the migration file that we just put together. So I'm going to run that, and I should see something like this right here. Now right away, if you get any error messages, chances are either I listed out one of the Windows commands here incorrectly, or alternatively, you might have entered in an invalid username or password. That's pretty much what is happening if you're getting any error. Either one of these commands is incorrect, or you put in the incorrect username or password. Now, once you do run this stuff successfully, you're going to see a message that says migrating files. We are running the table comments migration file. We ran this migration, so we applied that command right there, and it looks like the migration is now complete. So if we now go back over to pgadmin, I'm looking at my social network database. I can scroll down to tables, refresh that, and I will see that I've created that comments table. We can then take a look at the different columns inside there, and it looks like we do in fact have ID, created at, updated at, and contents. You'll also notice that there is another table inside of here called PG migrations. This table was created for you automatically by the Node PG migrate module. If you do a right click on there and then go to View Edit Data, All Rows, you'll see that this table essentially just lists out the name of a migration that has been executed and when it was actually executed. So that table is used by many different migration frameworks, or a table very similar to it, I should say, is used by many different migration frameworks just to keep track of what migrations have actually been executed and make sure that you don't run that same migration again. So we would not want to try to run this same migration again a second time. Technically, nothing bad would happen, but we would definitely get an error if we tried to run the exact same statement. If you go and run the same command, once again, back at our terminal, and try to do that same migration again, it'll just say, okay, there's no migrations to run because our module has detected that we already ran the one migration that we needed to execute. Now, here's the really interesting part. If for any reason we decided that this migration was not written correctly, or if we did something wrong, or if we just don't want to have our database in this structure anymore, we could run the same exact command, but at the very end, instead of up, we'll put in down. So down is going to undo the most recent migration. So I can run that, and you'll see that it does the down command out of our migration file. So we just dropped table comments. So now if we go back over to pgadmin yet again and refresh tables, now table is gone. And we've only got PG migrations, which again just keeps track of which migrations we have actually executed. If you refresh that table now, PG migrations, you'll see that there are no rows inside there, and that indicates that we have not actually executed any migrations. Okay, so that is pretty much the basics of running a migration and then eventually undoing it. So now let's take a look at just authoring one more very quick migration. Where's our diagram? Here it is right here. And all I really want to do here, where's that darn migration or diagram? Here we go. So I just want to run one other migration where we are going to attempt to change the name of a column on that comments table. And that's it. So let's try that out in the next video. Let's now generate and run a second migration file. The goal of this one is to change the contents column to the name of body. So for that, we'll go back over to our terminal. Once again, inside of our project directory, we can do an npm run migrate, create, and then a name for the migration. So once again, we generally want to be as descriptive as possible. So we might say something in this case, something like contents, or how about rename contents to body. Okay, so it looks like the file was created. Now we can open that file up inside of our editor. Inside the migrations directory, we'll see the new file has been generated. And then once again, we've got the up and the down. So we'll fill out the up first. We'll do a pgm.sql. And we can alter table comments, rename column contents to body. That's it. That's how we rename a column. Then we'll fill out the down, which once again is going to be the exact opposite of whatever we did in the up. So in this case, a pgm.sql, alter table comments, and we want to rename column body to contents. And that's it. So let's save this, and then once again we can go back over to our terminal and run that up command. So it's going to be that same database URL, the really long one that we just put together a moment ago, then npm run migrate up. So I'm going to go up. It looks like that created first the comments table for me, and then went ahead and applied that renaming step. So whenever we did the up, we got two different upgrades. We got the creation, and then we got the change to the column title. So now once again, if we go back over to pgadmin, we can do a refresh on tables, take a look at comments, look at the columns, and we no longer have a contents column. Instead, we've got body. Okay. So once again, if we wanted to, for whatever reason whatsoever, we could rerun that same command, and instead of doing an up, we can change it back to down. Now when we do a down, it's only going to revert one step at a time. So in this case, we renamed body back to contents, but we still have the entire comments table. So if we wanted to reapply that migration, we can do it up again. And there we go. We are back to having contents be body. Okay, so that is it for schema migrations. Now, in all this discussion about schema migrations, we've said very distinctly that we're really talking about changing the structure of our database. We haven't really discussed too much about how we might do a migration, but also change possibly some data as well. For example, we might want to take two different columns and merge them down into one. We also might want to, say, change the data type of a column. And if we did something like that, we might have to actually massage some data as well. That's definitely an open point that we need to think about. The other thing I want to think about is whether or not we can use this kind of migration process to achieve a zero downtime change to our database. In other words, can we change the structure of our database in any way we can think of and not have any downtime or any errors with our server associated with that? So still a couple of things for us to figure out. Let's take a look at all that in just a moment. We've now written out two migrations, but before we move on, there's one last big topic I want to take a look at in the world of schema migrations. So a couple of quick diagrams just to lay out a little scenario for you. Okay, so we now have a social network database that looks like this right here. I want to write out a third migration. And in this third migration, we're going to create another table that we'll call posts. Posts is going to be very similar to the post table back on our Instagram database. So we will give it a column of ID, URL, and latitude and longitude. Once again, latitude and longitude is going to represent where in the real world this photo was actually taken. Now we're going to imagine that at some point in time, maybe years down the road, after we have created this post table, we decide to take the latitude and longitude columns and merge them down into one single column of type point. Now, we have not discussed data type of point in Postgres yet inside this course. A column with a data type of point is used to represent a coordinate or a point on a 2D plane. So one single column of type point actually stores two different values inside of it, an x value and a y value. So we want to take latitude and longitude and combine them together down into this location column. This one column can safely store the values of latitude and longitude inside of it. Now, why would we do this? Who knows, but let's just say we want to do it. So we might write out a fourth migration to take those two columns and merge them down into this one single one. Now, as I mentioned just a couple of seconds ago, we're going to imagine that between migrations number 3 and number 4, several months or even years might have passed. So in other words, in between the time of us originally creating this post table and now us wanting to take latitude and longitude and merge it down into location by itself, maybe in that time, we have gotten many millions of rows added into our post table. So we might have millions of different posts here. So we need to take millions of different latitude and longitude pairs and merge them down into this one single location column. All right, so now that we kind of understand our goal here, there's a couple of things I want to just mention. So first, we need to kind of devise a strategy on how we're going to merge these columns together. What we might do is break it down into a series of steps that look like this right here. We could first add in an empty column called location that had type point. We could then somehow copy all these different latitude and longitude values over to this new column. And then once we have safely copied all those values over, we could then drop the original columns of latitude and longitude. So these 3 steps right here could be used to break this entire process up into 3 manageable distinct steps. But even though I make it seem like this would be an easy process, it turns out that one of these steps is actually a little bit more complicated than it might seem at first glance. So, quick reminder. At this point in this section, I've been using the term schema migration many times. And every time I said a schema migration is all about adding columns, removing columns, adding tables, removing tables, and so on. Step number 1 and step number 3 are definitely schema migration steps. We are adding a column, we are removing columns. But the middle step is just a little bit different. This middle step is not really about changing the structure of our database in any way. Instead, we are talking about moving data around between very different columns. We would refer to this not as a schema migration, but a data migration. It is a data migration because we are moving moving values between different columns. It turns out that handling data migrations and where we actually write the code out or the SQL for this, and whether or not we place it alongside our schema migrations, is a very controversial topic in the database community. So let's take a quick pause right here. In the next video, I'm going to outline exactly why data migrations are a little bit different and why they are controversial. I just made the claim that there's some kind of difference between a schema migration and a data migration. So once again, remember, schema migrations, we're changing structure. Data migration, we are moving data around. So in this video, we're going to start to take a look at why it is not a good idea to try to do a schema migration and a data migration at the same time, or essentially all in one step. Now, there are several reasons to not mix and match schema and data migrations together. In this video, we're going to focus on just one reason by itself. But again, there are more reasons than what I'm going to show you in just this video. All right. So what this all really comes down to is a question of, for these 3 steps, are we going to write them all out inside of one single migration file and try to execute them all at the same exact time? Or are we going to split them out into separate migrations where we can run them all in separate steps, or essentially at different points in time? So if we try to do everything inside of a single migration, then in one file, we would have a SQL statement in the up function that would add our column, another SQL statement that would copy some data around, and then another SQL statement that would drop some columns. If we split everything over multiple migrations, we would have one migration file dedicated to just adding this column location. We would have maybe another migration file or maybe some other kind of operation, we could figure this out, that would do the actual data copying step. And then finally, one more migration file that would actually drop the columns latitude and longitude. So why would we prefer one way versus another? Well, as I'm going to show you, if we try to do everything inside of one step, we can very easily get into trouble really quickly. So let me show you what's going on. Okay, so I want to really take this one single migration step right here, and I want to really break it down and think about what is going on behind the scenes. So in this diagram, we've got kind of a series of steps we'd go through if we are trying to run a migration file like this. So we'd first begin by running some SQL statement to add a location column. Whenever we add a column to a table, that is generally just about instantaneous in nature. So we could add this column location, and a millisecond later, the column would be in place, everything is good to go. Then the next thing we would do is start to copy data. Now, as I mentioned in the last couple of videos, we are assuming that our post table might have several million records inside of it. Copying millions of different values around is going to take some amount of time. It might take only a couple minutes, but it could very well take 30 minutes or even an hour to copy all this data around. So after waiting for all this copying stuff to be done, eventually the copy is complete. After that, we would then drop columns latitude and longitude, and just like adding a column, dropping a column is just about instantaneous in nature. When you drop a column, Postgres does not go back into your different heap files and delete any data. It just says, hey, this column is dead. And then over time, it's going to clean up all the values inside the column that you dropped automatically. But it's not something that takes any immediate amount of time. Okay, so now that we understand the series of steps, I want to mention one other very quick thing on the side. Whenever we run a migration, it is very common to place a migration or execute it inside of a transaction. That's to make sure that if we ever start to do some amount of work, say up here, like adding a column, removing a column, then copying some data around, and then get down to, say, dropping a column down here, if anything goes wrong with dropping the column, we probably want to undo all the work that we had previously done during the migration. So we really do not want to ever have a migration in a kind of half-executed state. And to prevent that, well, we just run it inside of a transaction. So if at any point in time, any one of these steps fail, we're going to roll back the entire transaction and the entire thing gets canceled, no changes actually made to our database. So it's a really good idea and just about required. There are some cases where you are not going to run a migration inside of a transaction, but those are very rare. So in general, we really make the assumption that we are running migrations inside of transactions, and that is almost a hard requirement. However, once we start running a migration inside of a transaction and simultaneously start copying data around inside that transaction or that migration, stuff starts to get really interesting really quickly. Let me show you what I mean by that. Okay. So remember, whenever we open up a transaction, we can imagine that we're kind of opening up a separate workspace for some number of operations. And when we imagine that we're opening up that separate workspace, it's kind of like we can kind of imagine, again, this is not what really goes on behind the scenes, but we can imagine that we're kind of creating a copy of all the data inside of our database and putting it into that separate workspace. We then do some amount of work inside that separate workspace, and then if there are no errors, we commit the transaction, which essentially merges all the changes we made back into the real world of our database. So, the really important thing to understand here is that the instant we open up that separate workspace, we are getting a copy of all the data inside of our post table at that instant in time. Like this instant in time right here, or really, I guess it'd really be at we'll say at the very top is when we are really opening our transaction. So we could say that we are really just getting a copy of the post table at this instant in time. And then it's going to take us some amount of time to actually do that copy operation. Now, in that meantime, while we are doing the copy operation, we still might have our API server up and running, like the actual application up and running, and we are still accepting requests and possibly also creating posts. So this diagram right here is kind of hard to read. Let me kind of walk you through it step by step. So we are assuming that we are running our migration inside of a transaction. When we open up that transaction, we are getting kind of a copy of that post table. Let's assume for just a moment that our post table has just two rows inside of it, row 1 and row 2. So during this very long running step right here, all we are really doing is copying the latitude and longitude values over to the new location column. So we can imagine that it's going to do the 50, 30, and 10, negative 46. And even though it's only the two rows right there, we'll just assume that this takes 30 minutes or an hour or something like that. So this is all occurring inside the transaction. And inside the transaction, we essentially have the snapshot of the post table. But in the real world, outside the transaction, we might still have our API server that is receiving requests to create posts. And so our API server might be sending some create requests off to our database and saying, hey, let's create a new post, let's create another new post, and so on. And so while we are doing that copy operation inside the transaction, we may have added in 2 additional posts down here. These 2 additional posts are not going to magically show up inside the transaction. Again, we created a snapshot of the post table when we created the transaction or when we opened it up. So inside the transaction, this copy of the post table is never going to see rows with ID 3 and 4. So then eventually the transaction will complete. We're going to take all the data inside of here. So eventually we delete latitude and longitude, like so. And we have just location, like so. Then we take this copy of the post table and we essentially merge that back into the real world. When we merge it back into the real world, we would have the same ID and the same URLs. It would bring down that location column, and the latitude and longitude columns would get dropped. Well, we never did any work to calculate the location column for these new rows of 3 and 4. And so by default, they'd probably just end up with values of null. So by doing all this work inside the transaction and then merging it back into our post table, not only did we lose some data related to rows 3 and 4, but we also now have kind of an erroneous state here where this location column has some null values inside of it. So this is all because we tried to do some kind of data migration step during a migration. So this is one of the big downsides of trying to do a data migration and a schema migration at the same time. If you're doing everything inside of a transaction, and you probably really want to do it inside of a transaction, you can end up in this really weird state where any additional records that you added into a table while that transaction was running might accidentally get deleted. You might have some data loss. You might otherwise lose some values. So definitely kind of some awkwardness around all this. All right, so this is just one reason that we might want to not try to run a schema migration and a data migration at the same time. As I mentioned, there are some other reasons for this, but this is one very good reason to be aware of. So let's take a pause right here and continue in just a moment. We just saw one possible issue that you could run into whenever you try to run a schema migration and a data migration together at the exact same time. So now we're going to take a look at how to solve that by taking those 3 different steps and executing them all separately and allowing for some amount of time to pass in between each step. So let's take a look at the solution. Okay, so in this diagram, we're going to take a look at some different number of steps we're going to go through, and we're going to imagine all the different changes that we're making to the post table along the way. So step number 1, up here, we're going to run a schema migration that is going to add a column called location or loc to our post table. So simple and straightforward. Basic schema migration that adds a column. So we can imagine that we would add in a new column, and we would have all the values inside that column by default be null. So a very obvious initial requirement is that this column must allow us to put in null values to get started. We will eventually allow for setting that column to be not null. So we will eventually allow you to say, hey, you can't put any null values in here, but at the very start, we do have to allow for null values. After that, we'll then move on to step 2. Now, in between step 2 and step 1, we can allow for just about any period of time. We could run step 1 on a Friday, take the weekend off, come back on Monday, and then run this next step. We can even allow a month to pass in between. The nice thing about this entire approach or this entire flow that we're going through is that you can allow just about any amount of time to pass in between each step. It's not super time dependent. So in step number 2, we're going to deploy a new version of our API, or essentially our application server, and it's going to make sure that anytime that we create a new post or possibly update a post, we're going to write new values to both the columns latitude, longitude, and location. So in other words, if we came into our post table and we tried to create a new post right here, let's say number 3, we would make sure that we put in some appropriate latitude, longitude, and the appropriate location as well. So let's say we had a latitude of 25, a longitude of 25. We would also make sure that we fill out that point value as well for location. We would then repeat that process for any number of posts that are created during this step. So if we create another post in here, say post with ID 4, and this one is at 3535, we would just make sure we fill out location as well. So essentially, after this step right here, every new post that we create or any post that we update is going to have both the latitude and longitude and location defined for it. So now on to step number 3. In step number 3, we're going to go back and backfill all the previous rows we had ever created. Now this step does not have to be in the form of some kind of schema migration file. We could very easily write a separate script authored in maybe Java or Python or JavaScript, some kind of separate little program that can go and take a look at all the rows inside this table, calculate the new location value, and update that column. Essentially, we're going to go back and do that copy operation, and it does not necessarily have to be in the form of a schema migration file. So we would go back to every row that has a null location, and we would put in 50, 30, 10, negative 46. So now at this point in time, we have a location for all of our different rows. Now we're going to move on to the next step. So the next step, we're going to update our code once again. So this is updating our API or our application server. And we're going to make sure that we write only to our location column. So we're going to say that for any newly created post, no longer are we going to worry about putting in any values for latitude and longitude. We're only going to worry about filling out that location column. So maybe 6141, and latitude and longitude at this point could be null or essentially whatever else. And then finally, very last step, because our application no longer really cares about the latitude, longitude columns, because we are not writing to them anymore, and presumably we would also not be reading from them, we can finally drop those columns. So we can drop latitude and longitude like so. And so now, at the very end, we are left with our post table that has ID, URL, and location. All of our different rows have a defined value for location, and at no point in time were we ever in a scenario where we kind of missed out on copying some different values over or ran into any kind of issues like that we saw previously back on that other approach. So this is the process that I recommend you taking a look at anytime that you have to do a schema migration and a data migration together. You're going to break it up into a series of different operations. You're going to do some initial change. You'll make a change to your client that's going to try to write to both the old column and the new column. You'll manually copy over all the data from the old columns to the new one to backfill all the records, update your code again to only make use of the new column, and then finally drop the old column. Now this is an approach that's generally going to serve you pretty well. There will be some scenarios where this doesn't quite work out, but in the vast majority of the time, this is the style that you really want to be thinking about. Okay, so now that we've got a better idea of how to properly do a data and schema migration together, quick pause right here. We've now spent a lot of time talking about the differences between a schema migration and a data migration. But just talking about this stuff really isn't enough. You've got to actually kind of walk through this process yourself to understand what is going on and some of the challenges that come up along the way. And so that's what we're going to be doing in the remainder of this section. All right, so here's what we are going to do. In this video and the next one, we're going to do a little bit of setup. We're going to first write out a migration to add an initial version of our post table. This initial version of the post table will have the latitude and longitude columns inside of it. Then in the next video, we're going to create a very small web application. This web application is going to allow users to just view all the different posts inside of our database and create new posts as well. So that is to kind of just get ourselves set up and imagine that that is some kind of running web application that we want to make some changes to. Once we do all that initial setup, we'll then go through this 5-step flow. So we will add in a location column using a migration. We'll then make a new version, or essentially make a little changes to this web application. We'll then write out a script to copy those values around. We'll then make another change to that web application, and then finally write one more migration. Now, this little web application we're going to be building is going to be written entirely in JavaScript. If you do not want to write JavaScript, again, that is totally okay. The web app itself, we're going to build entirely inside of one video. So if you want to, you can skip that video without any issue whatsoever. I will give you all the code that you need to run that little web application. So if you want to skip all the web app stuff because you don't want to write JavaScript, again, no problem whatsoever. Okay, so now that we understand what we're trying to do here, let's begin right away by writing out a migration to create an initial version of this post table. So to create a migration, once again, we will go back over to our terminal. Inside of our project directory, we can run npm run migrate, create, and then a name for our migration. I'm going to call our migration add posts table. Okay, so it looks like the migration was created. Let's open up that file and implement the up and down functions right away. So inside my editor, here's migrations. There's the new file we just generated. Let's define the up function first. For up, we'll do a pgm.sql, then a multi-line string, which remember is written out using backticks. We'll then put in here create table posts. We'll give it an ID, a URL, and then a latitude and a longitude, like so. We're not really going to use the URL column inside of here at all. I'm just putting it in to say, hey, yeah, this is a table of posts. Let's make sure that we also put the down function together. That will be pgm SQL. And remember, we're going to do the exact opposite of whatever we did inside the up step. So in this case, we'll do a drop table posts. Okay, so that looks good. So I'm going to save this. And then let's immediately go back over to our terminal and run this migration. So back at our terminal. As a quick reminder, you're going to make sure you define one of these environment variables before you run the npm run migrate command. So if you're on Mac OS, you'll do database URL, blah, blah, blah. Here's git bash, cmd, PowerShell, and so on. So in my case, I'm going to take that command right there. Go back over to my terminal. I'm going to make sure I update that username to whatever my username is. In this case, it is SG. And then I will run the migration. Cool. So it looks like I just created that table of posts. I should now be able to go over to pgadmin and take a look at my social network database. If I right-click on it and refresh, I can then go down to schemas, tables, and I will see my post table that was just created right there. Looks good. Okay, so we've got step 1 complete. So now we're going to take a brief pause. When we come back in the next video, we're going to start to create this web application. As a reminder, totally optional. You don't have to do it if you don't want to. Once again, inside this video, we're going to be creating a very small web application using JavaScript. 100% optional. I just want to repeat that for the 5th time. So if you do not want to write any JavaScript, no problem whatsoever. Skip this video, go to the next one. I'll give you all the code you need. Otherwise, stick around and let's get to it. So for this very small web application, we're going to write out a small Express.js server. This Express.js server is going to send down some HTML to a user that is going to show a list of posts to them on the screen. We'll also make sure that we can show a form that a user can use to create a new post. Now, I'm going to assume that you have a little bit of background in Express. If you do not, I would recommend you skip over this video, because this is a course about databases, not quite so much about web servers. Okay, so let's get to it. To get started, back at my terminal, I'm going to first install 2 dependencies. One is going to be Express itself, and the other will be a library that we can use to connect to Postgres directly from a Node application. So I'm going to do npm install, Express, and PG. PG being the module that we're going to use to connect to Postgres. Okay, so I'm going to install that. Looks good. Then back inside my code editor, inside my root project directory, I'll make a new file called index.js. We're going to write out all the code for this very small application directly into this file. To get started, at the very top, I'm going to require in Express. I will also require in Postgres, or PG. I'll then immediately use this PG module to create a connection over to our Postgres server. So I'm going to write out const pool is new pg.pool. I'll then provide an object, and then inside of here, we're going to provide a couple of connection details to tell this PG thing how to connect to our local Postgres server. We will first put in a host of localhost, a port of 5432, the name of our database, which in this case is social network, And then the last two options here are going to be slightly different depending upon your operating system. The last two options are going to be a username, which is called simply user, and a password. So you are going to use the same username and password that you just provided to that db migrate command. Let me go back to that diagram very quickly. So you'll notice that inside of each of these db migrate commands, you listed out a username and a password. So you're going to take whatever username and password you just used to do the migration and stick it in for those two options inside that PG pool object. So if you are on Mac OS, you're going to use whatever your username is and then an empty string for the password. If you're on Windows, you're probably going to use a username of Postgres and a password of whatever password you set when you initially installed Postgres itself. So for me, because I am on Mac OS, I'm going to put in a user of SG, because that is my username, and an empty string for the password. If you are on Windows, once again, you will probably put in something like Postgres, and then whatever your password was. After that, I'm then just going to run a very quick query to verify and make sure that this connection to Postgres is working as expected. So I'm going to put in pool.query, and then select 1 + 1. I'll then do a .then. I'll take some res argument and do a console.log of res, like so. Never mind what all this stuff over here is doing. It's just going to run a query and then print out the result of it. So let's save this and then run this file as it stands right now from our terminal, just to make sure that we are connecting to Postgres successfully. So to run that file back inside of my IG project directory, I will do a node index.js. Okay, so I see a lot of information being printed up here. As long as you see something like this, you are good to go. If you see something that says, hey, could not connect to Postgres or something like that, that means that you likely have a mistake inside of one of these options. Now, we are going to talk a lot more about what is going on with this PG module inside of a future video. So for right now, just understand that this PG thing is being used to connect to our Postgres server, and that's all we really need to understand for right now. We can use this pool thing to run a query, like what you see right there, and that's pretty much it. So we will understand exactly what a pool is, how to use this module, and so on in much greater detail later on. All right, so let's continue on with our application. So after creating that pool, I'm then going to create an Express app. I'm going to wire up one middleware to use with the Express application that is going to allow us to receive form submissions from a browser. So I'll say app.use and then put in express.url encoded and provide an object with extended true. Then after that, we'll put together two route handlers. One route handler is going to show a user a list of all of our different posts and a form to create a new post. The other route handler is going to receive a form submission and create a new post inside the database. So let's do the route handler that will show a list of posts first. We'll write out app.get/posts, async rec and res. We're then going to use this pool object up here to run a query to get a list of all the different posts that are currently inside of our database. So we will write out const, and then inside of a set of curly braces, rows, await pool.query, and then once again, a multi-line string. Inside of here, we're going to write out a little bit of SQL to just get a list of all of our different posts out of the database. So very simply, it will be select star from posts. That's going to run the query and then give us back a list of all the posts that exist. Then after that, we're going to send back a response to whoever just sent us this request, and we're going to print out inside of a table a list of all of our different rows that we just got back from that query. So we will once again do a multi-line string. Inside of here, we're going to write out a table. So we're going to write out a pretty good amount of HTML. Should be quick, don't worry. I'm going to put in a table element. I'll give it a t head. And then inside there, a tr. And inside the tr, we'll do a table heading of ID. We'll then print out the longitude of the post and the latitude of the post as well. Then after that, right after the T head, I'll put in a T body. We're going to iterate over all the different rows we just got back from our query and build out a separate row for the table for each individual one. So for that, inside this T body element, I'm going to do $ curly brace. We will take a look at rows. We'll do a mapping statement. And for every single row, we're going to run an arrow function. So for every single row, I'm going to return another multi-line string. And inside there, we'll place a tr that's going to show a couple of different TDs. The first one will show the ID of the row that we just retrieved, so row.id. We'll then show the longitude, and then finally the latitude as well. Now, one last very small step. I'm going to find our row statement. I'll find the closing parenthesis for it. And then right there at the end, I'm going to do a dot join with an empty string like so. Okay, so this right here is going to take all the rows we just got back from that query that we executed and just build up a very simple table. So nothing at this point is really that crazy so far. Now the last thing we're going to do, right after creating the table inside this big string, we're going to show a form that can be used to create a brand new post. So I'm going to, right after that table, put in a form element. I'm going to give it a method of post that is related to how the form is going to be submitted to our server, not related to the fact that we are creating a post or anything like that. Then inside the form, I'll put in a nice little header, about an H3, that says create post, just so user understands what's going on here. We'll then do a div with a label of longitude and an input with a name of LNG. I'm then going to repeat that same exact structure. So we'll do a div with a label of lat, an input with a name of lat, and close off the input. And then finally, right after that closing div, we'll put in a button with a type of submit, and we'll give it some text of create. Okay, so that is a lot of typing. So at this point, let's just save this, do a very quick test, and make sure that we can see something inside the browser without any kind of errors. So I'm going to go back over to my terminal, and we're going to run our project. So to run the project, we're going to run the command. Oh, sorry, we forgot one last little statement down at the very bottom of the file. Never actually told the Express application to listen on any port. Let's make sure we do that very quickly. So down here at the bottom, we'll do an app.listen, about 3005. And I'll just put in a quick console log and say listening on port 3005. Okay, now we're ready to test. So back over at the terminal, we can do node index.js. And it looks like I've got a little issue here. I've got some other process that is already listening on that port. My mistake. I'm going to run that command again. That's better. Now inside the browser, we should be able to navigate to, inside of a new tab, localhost 3005/posts. And there we go. So here's the table. It looks a little bit plain right now, but that's totally fine. And we've got a form to create a post as well. So now the very last thing we have to do is make sure we put together a route handler to deal with a form submission. And whenever we get a form submission, we're going to create a new post inside of our database. Don't worry, this is going to be a lot faster than all that HTML we just put together. Back inside of the index.js file, we will do an app.post. We're going to watch for a post request to /posts. We'll then put in an async function with rec and res. Then inside of here, we're going to take a look at whatever data the user just submitted to us. So we're going to pull off a longitude and latitude from rec.body. we're then going to run a query that is going to create a new post and save a new post into the database with this longitude and latitude. So for that, we will do await bool.query, and then inside of a string, insert into posts. We're going to say that we're going to save a latitude and longitude, then values, and then we're going to write out something that's going to look a little bit strange here. Once again, we're going to have a big discussion about what this pool thing is in just a little bit, so bear with me on this next little part. Right after values, we're going to put in a set of parentheses, and then $1, comma, $2, like so. So don't worry about what those are all about for just right now. Then as a second argument to this function, and I'm going to put in a new line here just to give myself a little bit of space, I'm going to put in an array and then provide the latitude and the longitude. Then finally, after running that query, I'm going to redirect the user back over to our post route, which is that first route we put together at the top of this file. Okay, so that should be it. I'm going to save this, flip back over, and we are now ready for a test. Now, one last little thing here, we do need to restart our server because we just made a change to it. So I'm going to do a Control-C and then run node index.js again. Now we're ready for a quick test. So inside the browser, I'm going to enter in a post with about a longitude of 1 and a latitude of 1. I'll click on create, and there we go. So we can see a new post was created with an ID of 1, a longitude of 1, and a latitude of 1. I'll do another with a longitude of 1.234 and a latitude of 4.321. Okay, looks like that works as well. Okay, so that's it. We've now got a running web server. And more importantly, this running web server, or this version of the application, is going to take a post that we submit to it. It's going to pull out the longitude and latitude and save those values into the longitude and latitude column. So now that we've got this entire initial thing working as we expect, we're now going to take a quick pause, come back in the next video. We're going to write out a migration to add this column location and then immediately modify this web server to make sure that we write values to both the latitude, longitude, and location columns. So let's start this entire process in the next video. If you skipped over to the video where we went through the setup of all this web server stuff, then make sure you take a look at that text lecture and follow all the setup directions inside of it. By the very end, you should be able to go to localhost:3005/posts and see something like this on the screen. Go ahead and create 1 or 2 different posts inside this little form. You can enter in any longitude or latitude that is a valid number, and then you should automatically see it up here inside this little table. So now that we've got this little web application put together, and we've got a little bit of sample data inside of our database, we're going to start to go through this flow. So we are going to imagine that we want to add in the new column location, and we want to take all the values from the latitude and longitude columns and merge them into that column. So we're going to go through this 5-step flow. Every step along the way, we're going to have 2 very critical requirements. For every step, we should still be able to add a post using that form inside the browser, and at every step, we should always make sure that we're not losing any data. So those are the 2 big requirements. The other kind of little requirement that's going to be a little bit more challenging to test, just because we're a little bit constrained on time in this video format, but should still hold up, we should be able to allow any arbitrary amount of time to pass between these different steps. So after we say add that column right there, we should be able to wait a day or a couple of days or even a week. And as long as we are not otherwise modifying any of the stuff around that column or our API, we should still be able to come back in a week later time and add in or kind of execute that step right there and still have everything work as expected. Okay, so let's get to it. Step number 1, we're going to generate a migration that we're going to use to add a new column called loc or location to our post table. So at our terminal, I'm going to press Control-C to end that process, and then do an npm run migrate create, and we will call this migration add loc to posts. We'll then open up that migration file inside of our editor. So here's the migration. Let's do the up first. So we'll do a pgm.sql. Inside of here, we want to add a new column. For that, we will write out alter table posts, add column LOC, and we want it to be of type point. We'll then once again do the exact opposite inside of down, so pgm.sql, and we'll do an alter table posts, drop column LOC. There we go. Okay, so I'm going to save that. And then we will run this migration. So as usual, back at our terminal, we're going to run that really long command. So it'll be that database URL with your connection credentials inside there, and then npm run migrate up. So I'm going to run that, and I should see that we've got the new column added. Naturally, we can also go over to pgadmin, take a look at the post table. If I right-click on it and do a view edit data all rows, we should now be able to see very plainly URL, latitude, longitude, and location. And of course, location has values of all null right now. So that is step number 1. Let's start our server back up. So back at the terminal, I'll do another node index.js. And now with this new structure to our database, we should still be able to add posts without any kind of errors or anything like that. So let's test that out very quickly. Back inside of our browser at localhost 3005/posts, I'm going to add in another longitude and latitude here. So I'll do, how about 4.001 and latitude of 4.001. And yep, everything looks good. Okay, so that's step number 1. So quick pause, come back to the next video, and move on to step number 2. All right, so step number 2, we're going to make a little change to our server code. We're going to make sure that whenever someone tries to create a new post, we're going to add a new row with a value for latitude, longitude, and that location column as well. So let's get to it. We're going to be making a little change to the code inside of our node server. Now, even if you don't want to write any JavaScript, hey, don't sweat it. We're not actually writing any JavaScript here. We're actually going to be writing some SQL. We're going to be modifying a query where we actually create a post. So you don't need to know any JavaScript whatsoever for this step. So inside the index.js file, I'm going to scroll on down, and I'm going to find line 58 or so. Right after that, on line 61, is the query where we are actually inserting a new post into our post table. So this is where we are going to make sure that in addition to inserting a post with a latitude and longitude, we also insert location as well. So for that, I'm going to first turn this into a multi-line string just so we can split it out into separate lines and read it more easily. Or alternatively, you know what? We can just put in a new line. That'll work as well. So I'm going to first update the query itself, and I'm going to say that in addition to inserting columns latitude, longitude, we're also going to put in LOC. Right after the $2, I'm going to put in a comma and then $3. And again, we'll talk about why we are putting the $sign values inside of here in just a little bit. And then finally, inside this array, right after LNG, we'll put in a comma, and then we're going to put in a value that will be used for the point or the location. So for that, we're going to put in inside of a string, template string, so backticks, we're going to put in a set of parentheses, then $, curly braces, LNG, comma, outside the curly braces, $, curly brace, LAT, and that is it. So this little bit right there, that little string is just a little bit tricky. Just double check, make sure you've got the same thing as I. This is how we insert a point in Postgres. A point is defined as a set of parentheses, and then we put two numbers separated by a comma. So at the end of the day, the longitude and latitude will be replaced inside there, and so we might end up with something like 4.001, 4.001. Okay, so let's save this. We'll then go back over to our terminal, and we're going to restart our server. So here's the terminal. I'll press Ctrl-C, and then restart the server with node index.js. And then let's go and try to create a new post inside the browser, and we're going to verify inside of pgadmin that we added in a longitude, latitude, and a point as well. So back inside the browser, I'll put in a longitude of 5.001 and a latitude of 5.123. So I'll create that. Well, it looks like the insert worked as expected, so I don't have any syntax errors or anything like that. Now we'll go back over to pgadmin and make sure that we see a location value for this particular row as well. So inside of pgadmin, I'm looking at the view all view for the table of posts. Just as a reminder of how you get here, you'll take a look at table section, posts, right click on that, and then go to all rows. Okay, so there's the value that we just added in. So I've got my latitude, longitude, and location as well. And so you'll notice that this is stored in point syntax. So we have essentially two values inside of one column. So this is definitely looking good. So now anytime that we add a post in the future, we're going to get all three different rows populated. Okay, so that is it for step number 2. Then we'll take one more pause and move on to step number 3. We have to write out some kind of script that is going to go back and copy all the latitude, longitude values for all those previous rows over to the column of location. So let's take a look at that in the next video. On to step number 3, where we are going to copy over all the values of latitude and longitude to location. Now this step is going to be a little bit more nuanced than you might think. It turns out there's actually a lot of different considerations here and how we implement this. We're going to take a look at 2 possible solutions and then highlight some of the pros and cons around each of them. Okay, so first option, for updating or copying all those values from latitude and longitude over to the location column. For the first option, we can use some JavaScript code to do all these updates for us. So in this option, we would write out some JavaScript file. It would then execute a query like this right here, where we would take a look at the post table and find all the posts that have a location of null. Remember, we really only care about posts with a location of null. If the location is not null, it means that this is a row that is already using this kind of new schema. So we could load up all those posts. We could then do the update, so essentially calculate what the point or the location value should be. We could also optionally do some other complicated business logic or validation during this step. And then finally, we can formulate another query down here to update that given post back inside the database. So we got one query to pull information out. We're going to get a lot of posts with that, calculate all the updates, and then run some number of updates and send them back over to the database. This approach has a couple of different downsides tied to it. First off, remember our post table might have a ton of different records inside of it. Let's imagine for a second that we have 1 million different records or 1 million different posts. Well, if we wrote some kind of query like that and executed it, we could accidentally load up 1 million different records into our JavaScript server. And in that case, chances are we would eventually run out of memory and our node server would just crash entirely. So in general, we probably don't want to write a query like this that's going to attempt to load all of our posts in one go. Another way we could approach this is to use something called batching. So if we make use of batching, we would try to load up just a set of all of our records at once. So we could do that with something as simple as limit 5,000 or something similar to that. That means give us the first 5,000 posts where location is null. We can then do the update for those 5,000 records and then save the updates back over to the database. That makes sure that we're not going to load up too many records in one go. There are some downsides to this batching stuff, however. When we start doing batching, this kind of implies that we're going to kind of have multiple different batches running, and each batch will be running sequentially. So in other words, we'll do one batch, process everything, save it back to the database, open up another batch, do all the processing, save it back over, and so on. It's entirely possible that by the time we get to the very last batch, there could be some kind of error in our logic in how we do the update or how we calculate it. We might only see that error when we get to that very last batch. So if we only see that error at the very end and that error crashes our program, now we're kind of left in a halfway between state where some number of rows have been updated and the other rows have not. Now we could solve that by making use of a transaction, but that has its own set of challenges that we'll talk about at the end of this video. The other downside to this is that it requires us to manually connect to our database from a JavaScript environment. This is sometimes a little bit challenging. As you're going to see a little bit later on in this course, if you provision a database, for example, on AWS or Amazon Web Services, that database will frequently be very locked down, and it will be challenging to connect to it from any arbitrary location with any kind of arbitrary JavaScript file or something like that. And so there might be scenarios where just trying to connect to your database from a node environment will be a little bit challenging. The one very big upside to this approach, however, is that we can very easily run really complex business logic or do some kind of complex validation on all these records before we process the update. So in our case, calculating this new location value is very simple and straightforward, but it's entirely possible that we might want to do an update like this that requires a lot more validation. In just about every scenario, doing validation is a lot easier from your application code, or in other words, from a JavaScript world, than trying to implement that validation in SQL. So this is one very big upside to this approach. Okay, let's take a look at a second solution. So solution number 2 is to just rely upon SQL. So we could write out some kind of JavaScript file that would once again connect to our database and just send in a very simple update statement like the one you see right here. Or we could just write out that statement directly inside of pgadmin and execute it. So this statement in particular is going to take a look at the post table, find all the posts where the location is null, and then calculate the update. And that's pretty much it. So this is a very simple and straightforward way of doing this update, by just relying 100% on the update being done inside the database itself. One very big upside is that we are not moving any information or records between the database and the JavaScript world. That means that this update is, in theory, going to run a lot faster than if we were trying to load up all these rows into our JavaScript world. One very big downside to this approach is that it's, of course, a lot harder to implement any kind of complex validation. Because again, we don't really have the ability to execute any kind of JavaScript or inspect any of the individual rows that are being updated in any way. There's one other issue I want to mention very briefly around both option number 1 and option number 2. This is an issue that only starts to come up once you have many records inside of a given table. So we're talking about on the realm of hundreds of thousands of records or millions of records. If you only have a couple thousand or tens of thousands, this is definitely not a big issue you need to worry about. So whenever we do an update with either approach, we might want to run the entire update inside of one single transaction. There's a really good reason for doing that. It means that if we start to process all these rows and we get to that very last row, if something goes wrong with updating that last row, it might mean that there's some kind of bug or issue in our update logic. So if we threw an error on the update of that very last row, then the transaction would automatically cancel, we'd roll back the whole transaction, and none of the updates would actually be saved into our post table. So doing the update inside of a transaction, generally probably a good idea, and it's probably something we want to do. But there's a little issue around a long-running transaction that you need to be aware of. Let me show you the potential issue. Let's imagine that we open up a transaction, and inside of our transaction, we start to take a look at all of our different rows that need to be updated. So we might see row 3 right here. We would see that it has a location of null, so that means we need to do an update. So we would say, okay, our new location is going to be 25, 24. So we would put in 25, 24 right there. And then internally, Postgres says, hey, this value right here has been updated. Whenever a transaction is going to update a value, that entire row is going to get locked. I'll tell you what it means to be locked in just a moment. We can kind of imagine that transaction number 1 updated row 3. And after that, it's then going to move on to row 4, and then 5, and so on. But for just a second, we'll just leave it right here at row 4. So at this point in time, this row has been locked. This row is going to be locked, and essentially it cannot be updated by any other transaction until transaction number 1 has either committed or rolled back. So in other words, no other transaction can update that value right there until transaction number 1 has processed all the other rows inside this table. So if in this period of time, some user makes a request to our application and they say, hey, I'm trying to update the location of post with ID 3. So they're trying to update that one right there. Well, unfortunately, that value is locked. And so this transaction number 2 is not allowed to update any value inside this row until transaction number 1 is completed. Now, transaction number 2 is not going to fail entirely. It's just going to sit around and wait until transaction number 1 is either committed or rolled back. So eventually, transaction number 1 will finish processing 4 and 5 and so on, and then eventually say, okay, that's it. I've done all my updates. I'm going to commit them. And so then all those rows that have been updated are then unlocked. And now finally, transaction number 2 can finally do the update to that row right there. So this is going to be an issue if transaction number 1, essentially our update process, is going to be running for a very long time. It means that during that period, no other transaction or essentially any other attempt to modify these same rows is going to succeed. They're all going to wait around until transaction number 1 is completed. And we can very easily test this out inside of pgadmin. Let's do it right away just to make sure this whole idea is crystal clear. So inside of pgadmin, I'm going to open up 2 query tool windows, both inside of our social network database. So here's window 1, and here's window 2. Inside of window number 1, I'm going to do a select star from posts, and we'll see that we have a post with ID 1 that has a latitude of 1. I want to try to open up a transaction that is going to modify that value. We're then going to try to modify the value from the other window that is not running the transaction, and we're going to see this kind of phenomenon in action. So inside of my first window, I'm going to comment out the select. I'm going to do a begin to open up a transaction. I'm then going to attempt to modify the row with ID 1. So I'll do an update posts. I'm going to set the latitude to 2, where ID is 1. That's the update. So I've now updated inside the transaction that row. So now the row with ID 1 is locked, and it cannot be modified by any other transaction until this transaction is closed out. So either completed or committed or rolled back. So I'm now going to go over to the second terminal window. So this one is not in the same transaction. I will do a select star from posts, and we'll see that the row with ID 1 still has a latitude of 1, which is what we would expect, because inside the other terminal window or the other query tool window, this is still running inside of a pending transaction. No values have actually been saved back into the real table. Now let's go ahead and try to update that same latitude value right there from the query tool window that is not in the transaction. So I'll comment out the select and do a update posts, set latitude. In this case, we'll try to set latitude to 10, where ID equals 1. Now take a look at this. When I run this, it's just going to sit. So this update right now is just sitting around and waiting for the first transaction to be completed, either committed or rolled back. So in this scenario, the query tool window number 1 is like our bulk update. We're just waiting for it to process all these different rows and eventually commit or roll back. The second query tool window is like transaction number 2. We're trying to do a very small, very targeted update to one row, but that row has been locked because it's been modified by transaction number 1. So on query tool window number 2, well, we're still just sitting here, and we're going to continue sitting here until we eventually commit the transaction or roll back the one inside of query tool number 1. So let's go ahead and commit this one. I'm going to comment out the update. I'll then commit it. I'm going to run commit. And the instant I commit this, if we go back over to query tool number 2, the update over here has been processed because transaction number 1 got resolved. Now, if we comment out that update and do a select star from posts, you'll see that the 10 is what we ended up with, because inside the transaction, we had done the update to a latitude of 2. That transaction then got committed, so latitude for a very small period of time was updated to 2, but then the pending query that we had over here actually processed, and we end up finally updating the latitude value to 10. Okay, so long story short, whenever we are doing this really big update of a ton of different rows, there will be some period of time where nothing else can update those rows until our update has been completed. There is a very easy way to kind of get around this, and that would be to do the same kind of batched update system. So a batched update might be whenever we do, let's do it right here. Okay, yeah, we spoke about this right here. So if we do the batched update where we're only trying to process some number of rows at a time, then we would process 5,000, commit the result, process the next 5,000, commit the result, and repeat that process over and over until we have not done any other updates. As soon as we do no updates, that's a sign that we've updated all the different rows and placed a location value inside of each one. The downside to this is that, well, we can't do the entire update inside of one single transaction. It will instead be a series of different transactions. So there's definitely still a big downside to it. Okay, so enough talking in this video. Let's take a pause right here and then implement either solution number 1 or number 2 in the next video. We are going to update all of our values inside the post table by using option number 2. So we are going to write out a very simple JavaScript file that's essentially just going to put together a SQL statement and execute it. And that's pretty much it. We could, of course, do this directly inside of pgadmin. The reason that we are doing it inside of a JavaScript file is so that we can commit this file to version control eventually and share this file with other engineers, because there might be other engineers working on our project who need to make this update as well. In addition, we're going to eventually have to run this update for our production instance or our production database, in theory. And so we would probably want to commit this file just to make it easier to run this query for the production instance in the future. So in this video, we are going to write out just a little bit of JavaScript. As usual, if you don't want to write out any JavaScript at all, no problem. Pause the video here and continue to the next one. Otherwise, stick around and let's get to it. I'm going to first get started by going back over to my code editor. Inside of my migrations directory, I'm going to make a new folder called simply data. And then inside there, I'll make a new file called 01. And then I'm going to give it a name of lng lat to loc.js. So the idea behind the 01 right here is to just provide an index for this file, the order in which it should be executed in case we ever have any other data migration files. The migration framework that we are using, the node pgmigrate module, is only about managing or running the files directly inside of the migrations directory. So by placing this file inside of a nested data directory, this is a sign that is a data migration. So now inside this file, all we have to do is connect to our database, run a query to do the update for us, and that's it. So to connect to the database, we're going to use some of the same code that we wrote out inside the index.js file. I'm going to open up index.js. I'm going to find where we required in PG and where we defined the pool as well. I'm going to copy all that, take it back over to that file we just created, and paste it in. Then immediately after creating the pool, we are going to execute a query to do the update for us. So I'm going to put in a pool.query. I'm going to add a multi-line string, and then inside there, update posts, set loc equal to point lng lat, where loc is null. So this is how we can create a point value out of two different columns. We call point, and then provide a longitude and a latitude. Whenever we run pool.query, that's going to return a promise, so we can chain on a .then statement. Inside of the .then, I'll first do a little console log that just says update complete. And then we're going to close out the pool that we created and disconnect from our database by writing out pool.end, like so. And then if anything goes wrong with executing this update, I'll add in a .catch. I'll receive an error, and we'll do a console.error of error.message, like so. And that should be it. So let's save this file. We'll then go back over to our terminal and try running it. So back at my terminal, I'm going to stop our running server with a Control-C. I'm going to change into the migrations data directory. So there's our file right there, and we can execute it manually with a node 01 long lat to location. I can run that and update complete. So now in theory, all the different rows inside of our table have the update applied. Let's go take a look at pgadmin and just confirm that's the case. So back inside of pgadmin, if I do a select star from posts, it looks like we've got all of our different location values. Awesome. Okay, well that is the update. That is step number 3. So we still have 2 more steps to go through, but they are much quicker. All we have to do is do a very small update to our code and then write out that one other migration. So let's get to it in just a moment. For step number 4, we're going to go back into our server code and we're going to update it so that we're only writing to the location column. We're also going to make sure that we are only reading from that column as well. So let's get to it. All right, so back inside my editor, I've opened up my index.js file. I'm going to scroll down a little bit and find our first route handler where we are getting our list of posts out of the database. Now, just to understand how we can access that location column out of this list of rows we get back, let's just do a console log of rows for right now and just see how that location thing actually shows up inside of our code. After putting in that console log and saving the file, I'm going to go and start my server back up. So at the terminal, I'll change back to my root project directory and then run node index.js. Then to make that console log get triggered, we'll go and refresh our application inside the browser. I'll go back over to my terminal, and there's our console log. So you'll notice that this location column is going to be an object that has values of X and Y. That's how we are going to read all these different locations. So now we can go back into our editor. We can take a look, or how about first we'll remove that console log. Then inside of our table, we can either just print out the entire location column by itself, or we can continue to print it out as separate longitude and latitude values. Let's do that, because as far as the user is concerned, these are still longitude, latitude values. We only changed how they are being stored inside the database. So down inside of our rows mapping statement right here, rather than printing out row.lng and row.lat, we will instead make it row.location.x and row.location.y, like so. Before testing this out, let's also go down to the very bottom and update how we save information into the database as well. So down at the route handler all the way at the bottom, where we are creating a new post, we can remove all the references inside the post table to latitude and longitude. So inside the query itself, I'm going to remove the latitude and longitude. I'm also going to remove the $2 and $3. And then finally, in this array that we are providing as the second argument, I will remove latitude and longitude. Now we are just inserting a location point by using the longitude and latitude that show up to this request handler. Now, the question that you might have is, should we change the form that is being submitted to create a new post? In other words, should we try to receive out of the request body a point or kind of like a location instead of the separate longitude and latitude? Well, remember, everything we're doing here is really changing how we are storing information inside the database. And we don't necessarily need to change how we are receiving information into our server. So we can continue receiving a longitude and latitude and then kind of coercing that into a point for us to actually store it inside the database. So this right here is totally appropriate. All right, so let's save this again. I'm then going to go back over to my terminal and restart my server. So we'll do a Control-C and then another node index.js. And let's go and do a test. So I should now be able to refresh the page and still see the same kind of content on the screen. You might notice that you get a different longitude and latitude value just in case you were kind of playing around with any of the values inside the database. I definitely was. And now we should be able to create a new post as well. I'm going to put in a longitude of about 60 and a latitude of 65. And it looks like that works as well. Let's go take a look at pgadmin just to make sure that information is being stored correctly. So back inside of pgadmin, if I do another select star from posts, yep, there's the 6065. And you'll now notice that latitude and longitude are showing up as null. Okay, so I'd say this looks pretty good. So let's take a pause right here, and then we'll come back and do our very last step, which is to finally drop the latitude and longitude columns. All right, very last step, we're going to drop those two columns. So once again, this takes the form of just generating another migration and running it. So it should be really straightforward. Back at my terminal, we'll do a npm run migrate. We're going to create a new migration, and we're going to drop lng and lat. We can also, if we want to, we could say from posts, just to be a little bit more descriptive. Okay, let's go open up that file and make sure we drop those columns. So we'll find our migrations directory yet again, open up the new migration file. So inside of our up, we'll do a pgm.sql. And very interestingly, this time around, we're actually dropping a column inside the up as opposed to creating a column. In all other cases, we've been adding stuff inside of our up statement. This time it's kind of reversed. So we can do an alter table posts, and then we can drop two columns with one statement by doing drop column lat, comma, drop column lng. That's going to drop both columns with one statement. Then we can, once again, do the exact opposite of that inside of our down. So we can do a pgm.sql, alter table posts, and in this case, we will add a column of lat that will be of type numeric, and add column long of type numeric as well. Don't forget the comma at the end of that second line. So that should be it. So we'll save this file. Let's go back over to our terminal. We're going to rerun that migration command. Let's find it. I know it's in my history. There we go, right there. So we're going to do one last up. And so we have dropped lat and long. And now we should be able to start our server back up one last time and still have everything working as expected. Yep, still good. Okay, so that is it from start to finish. We have seen how we can make a drastic change inside the structure of our database and not only do a sequence of schema migrations, but also do a data migration as well. However, along the way, we saw a lot of code written inside of JavaScript that was kind of mysterious. So, for example, what was inside of our index.js file this entire PG thing all about? What's the pool all about? And perhaps most importantly, out of all of this, what is down inside of our post request handler towards the bottom? What were we with those $1, $2, $3, and so on items as well? So although we've kind of gone through a rather advanced process here, we still don't have a lot of information about working with a database from a JavaScript environment. So we're going to start to change that in the next section. So quick pause and let's get to it. In this section, we're going to start to take a lot of what we've learned and apply it to an actual application. So we're going to build out a very small Node API. We're then going to connect to a database that we're going to call Social Network. Inside of that database, we're going to have a users table that has just a couple of different columns inside of it. We're then going to focus on interacting in some way with this table from our Node API. Once we've got this all put together, we're then going to add some tests on top of this project as well. Along the entire way, we're really focused on how we work with a database from a real application. So we're going to be really focusing much more on how we actually interface with the database as opposed to putting together an API or anything like that. So I'm going to generally assume that you're vaguely familiar with what an API is and how to write some JavaScript code to implement one. So let's take a pause right here and get started on this project in the next video. Let's do a little bit of project setup for our first API. So I'm inside of a workspace directory of sorts. Inside of here, I'm going to make a new folder that's going to house all 3 different versions of our API. I'm going to call this overall folder simply API. And then inside that API directory, I'm going to make a folder for our first API version. I'm going to call this one Social Repo. So the name of our project is essentially social app or social database, whatever you want to call it. And this first version of our API is focused on this repository pattern. I'm then going to change into that directory. I'm going to generate a new package.json file inside there with npm init-y. And then after that, we're going to install a couple of dependencies right away. So we're going to install several different things here, so bear with me with just a little bit of typing. We're going to get a package called ddent. We're going to get express. We're going to get jest, node, pg, migrate. We're going to get nodemon. We're going to get pg, pg-format, and then, format, there we go. And then finally, super test. So a couple different dependencies, but this is all we're going to need in total. So once you're very sure that you've got all these different dependencies typed in correctly, we'll run that command. Installing these dependencies is going to take just a couple of moments, so we'll take a very brief pause right here and come back when this is all complete. Looks like the initial installation is all complete. Between the last video and this one, I opened up my code editor inside this new social repo directory. I would encourage you to do the same as well. Once you've got this project open inside of your editor, we'll take a look at the package.json file. We're going to first begin by adding in a couple of scripts to the script section. I'm going to delete the initial test script that's inside there, and then replace it with a migrate script. So this is the same migrate script that we wrote out previously around node pg migrate. I'm also going to create another script called start that will be used to actually start our project up. Whenever we start up our project, we're going to run nodemon index.js. So eventually we will have an index.js file inside the root directory of our project. We don't right now, so if you run this as is, naturally something bad will happen. Okay, so that's it for our package.json file right now. Now the next thing we're going to do is generate a new migration to create that users table inside of our social networking database. So remember, the social networking one is the same one that we've been working with for the last couple of sections. This users table is going to have just a couple of different columns inside of it. So we're really just going to give it, we take a look at the diagram right here, just the ID, a created at, an updated at, a username, and a bio. That's it. We're not going to really worry about any validations or any checks or anything like that. Instead, we are really much more focused with how we're going to treat this data from our JavaScript application. So let's generate a new migration. Back at our terminal, we can do so by running npm run migrate, create, and then we're going to call this migration, how about add users table. Once we've got that generated, we'll then open up that file inside of our editor. We've done many migrations at this point in time, so I think you understand what's going to come next. Inside of here, we'll do a pgm.sql. We will create a table of users. I will give it columns of ID, serial primary key. I'm going to give it a created at with type timestamp with time zone. And we will give it a default as well of current time. Oh, current timestamp, excuse me. We'll then do the same for updated at. And then a bio. Make that a varchar, how about 400? And then finally, one other column, and its name escapes me. Username, of course. We'll do a username. We'll make that a 30. And I'm going to mark this as not null, because I definitely really want every user to have a username defined. Okay, so that looks good to create our users table. So now we will implement the down function as well. We'll do a pgm SQL. And in this case, we will drop table users. Before we run this migration, I would like to use a fresh database rather than reuse the same social network database that we've been using throughout the last couple of sections. So I'm going to go back over to pgadmin, where I still have my database open. I'm going to find our social network database. Here it is right here. I'm going to make sure I close all the different query tool windows I have open. And once those are all closed, I'm then going to drop this social network database. So I'll right-click on it and then go to delete/drop. After that, I'm going to recreate it. So I will right-click on databases, go to create database, and I will make a new one called social network once again. Okay, so there is our brand new, empty, fresh, clean database. So now we can run the migration we just put together. As a quick reminder, to run the migration, you're going to run one of these different commands depending upon your environment and how you are running your terminal. So in my case, I'm on Mac OS with Postgres app, so I'm going to run that right there. So I'm going to go back over to my terminal. I'm going to change that username to SG. And then after that entire environment variable, I will make sure I've got npm run migrate up. Okay, so I'm going to run that, and looks good. So we should now have our users table. I'm going to verify that just very quickly by going back over to pgadmin. Take a look at schemas for our social network database. Go down to tables, and there's our new users table right there. So looks good. Looks like we got a good start. Let's take a quick pause right here and then continue with our API development in just a moment. Let's continue doing a little bit of initial setup in this video. So we're going to start to set up our Express server, which is going to handle all incoming requests. And we need to make sure that it's just very clear about what different routes we're going to define for this server and what each route is going to do. So we're going to follow some different RESTful conventions. We're going to have the listed routes you see right here. If anyone makes a request to them with a given method, we're going to do whatever is listed inside of the goal column. So in general, like I said, we're really just following RESTful conventions, nothing too unusual here. So let's start to set up the Express side of our application, and we're going to start to scaffold out each of these different routes. All right, so back inside my editor, I'm going to create a new folder inside my root project directory called src. Inside there, I'm going to make a new file called app.js. Then inside this app file, we'll first require an Express. I'm then going to export a function And this function is going to create a new Express application and then return it. So we will do a const app is Express. We're then going to wire up a single middleware to parse any incoming JSON. And then finally, we will return the app. Now, this right away might look a little bit different than what you're used to around Express applications. You might be really used to seeing just an Express app created, and then maybe a couple of different middlewares, and then finally an app.listen something something at the very bottom. But in this case, we're taking a little different approach. There's a very good reason for this, and it's tied to our testing strategy, which we're going to take a look at a little bit later on. Okay, so this looks good for right now. Next thing we're going to do is create a routes file. This file is going to have all the different route definitions tied to our different users resource. So inside of my src directory, I'm going to make a new folder called routes. And then inside there, I'll make a new file called users.js. At the very top, we're going to import Express once again. We're then going to create an object called a router. The router allows us to associate a lot of different routes with this object right here. We can then export that router and then associate it with the Express application that we just created back inside the app.js file. If I'm going a little bit quickly here, please recall that in general, I'm kind of assuming that you've got a background in Express and are more or less aware of what we're doing here. This is, of course, a course about databases and not quite so much Express, which is why I'm kind of going over these parts a little bit more quickly. All right, so this is where we're going to scaffold out all those different routes. So we need a router.get on /users. I'll then put in an async request handler and just leave it collapsed right now. We'll then do a router.get users /:ID. We'll then do a post, so router.post /users. Then an update, so that will be router.put users. And then I think finally, last one is our delete. The router.delete users /:ID. And sorry, a little typo here. On the put, there should be a route param of :ID, like so. So we now have get, post, put, delete. Then we have users, users ID, users, users ID, users ID. Okay, so once we've got this all put together, we will then export the router we created at the very bottom. So a module.exports of router. I'm then going to save this file. I will go back over to the app.js file we just created. I'll then import that router, and I'll call it users router. I'll get that from the routes users file. And then I'm going to associate that router with our Express application. And technically, if we are following correct capitalization, that really should be a lowercase u. So I'm just going to update that very quickly. Then finally, app.use users router like so. Okay, so that looks pretty good, at least enough to get us started. So now, quick pause right here, a little bit more of setup, and then we're going to start implementing our first repository right after that. We've now finished a little bit of setup with Express, so now we're going to start to set up our connection to our Postgres database. To do so, we're going to be using a module called PG. The PG module is used to specifically set up a connection to Postgres and run some SQL. That's it. The PG module does not do any query building, so it doesn't help you write any SQL. It doesn't do any validation. It doesn't do any kind of checking. It does absolutely nothing whatsoever but run some SQL. PG is a very popular module in the Node community, so much so that many other Postgres-themed modules internally make use of PG. So for example, that actual migrate module that we're using, the one that we already used inside this project, internally that migrate module makes use of PG. The ORM that we're going to use a little bit later on also makes use of this PG module. So behind the scenes, PG is powering just about everything. So it's definitely worth your time to get a better idea of how it works internally. And that's what we're doing with this first version of this API. Now internally, the PG module can be used to create something called a client. We usually do not make use of a client directly. And the reason for that is very simple. when you create a client, it can only execute one query at a time. That is definitely a very big issue anytime that we're trying to build something like an API. Because if we ever get multiple requests coming into our API and we need to run multiple queries at the same time, with a client, we would only be able to run one of those queries at a time. So rather than using a client directly, we generally make use of something instead called a pool. A pool internally maintains a list of different clients. Then anytime that you need to run a query, you essentially ask the pool to run a query for you. The pool will take your query, hand it off to one of the clients that is free internally, and that client will then execute the query over to Postgres. So rather than creating clients directly, we instead create a pool which automatically maintains this list of clients for us. There is one scenario in which you will make use of a client directly, and that is whenever you need to write or run a transaction. We will see an example of that later on, so just keep in mind, if you need to run a transaction, you need to use a client. At the end of the day, making use of a client and a pool is just about identical in nature. All the different methods between the two are almost identical. So don't get too bogged down with the differences between a client and a pool. Okay, so let's go back over to our code editor. We're going to create a new file and then create a pool inside of it. So I'm going to find my src directory. I'm going to make a new file inside there, and I will name it pool.js. Then at the very top, I'm going to require in the PG module. Now, quick note here, and I really apologize ahead of time for a little bit of confusion that is probably going to arise right away. So normally, we would create a pool like this. We would do something like const pool is a new pg dot, not what I wanted, thank you autocomplete, pg dot pool. We would then provide some configuration options, or really connection options, to tell this pool how to connect to our database. So we might provide a host of localhost, a port, and so on. And then finally, we would export that pool so it can be used by the rest of our application. So this is normally what you would do, and this is what you're going to see inside of documentation, blog posts, articles, and so on. However, you and I are not going to do this for an extremely important reason. This reason is tied to some of the testing stuff that we're going to go over later on. It turns out that if you create a pool in this style right here, then it makes it really, really challenging to connect to multiple different databases. You might be curious about why you would ever want to do that. Well, trust me, once we start to take a look at our testing setup, we're going to be in a scenario where from one application, we want to connect to multiple different databases. So this approach does not work very well for that. So instead, we're going to take a slightly different approach. We're going to essentially create a pool, but we're going to wrap it up inside of a class instead. If it sounds really confusing, don't sweat it. It's going to be at the end of the day, a very, very small change. And all the code that we're going to write for this slightly different implementation is still 100% compatible with every use of a pool that you would otherwise have. So we're making just a very, very small change here at the end of the day. Again, I apologize for the confusion, but it is a change that we have to make. So I'm going to delete what we would normally do and replace what we're going to do on this project specifically to get a really nice test set up instead. So we're going to write out class pool. So we're going to essentially kind of wrap up a pool ourselves. Our class, or an instance of this class, is going to have a single instance variable called _pool. We will default it to be null. Then for right now, we are going to give this one single method called create. And actually instead of create, let's call it connect. Maybe that makes a little bit more sense. Inside of connect, we are going to receive some connection options. So that's going to be like the host name and the port and all that kind of good stuff. So we're going to take those connection options. We're going to use them to create a new actual pool and pass in those options. And then after creating that pool, we're going to assign that to _pool. Then at the very bottom of the file, we will do a module.exports new pool, like so. So you can see that this code is very similar in nature. We are still creating some kind of pool thing, ultimately, right here, and then exporting it. The only difference here is that we are wrapping up this pool inside of another class so that we can very easily tell our pool to connect to some different database at some point in time. So if we ever want to connect to a different pool, we'll be able to call connect, provide the configuration options or the connection options, and we get a brand new pool connected to that different database. That's the only difference here. We're just making it a little bit easier to tell our pool to reconnect somewhere else very, very easily. Okay, so again, I apologize for that confusion, but at the end of the day, this is a really, really small change. We are going to eventually come back and add in a couple other methods to this class. So there's a lot more that's going to be going on than just this connect method, but for right now, that's good enough. So let's take a quick pause right here and continue on with a little bit more setup around this pool in the next video. This pool is looking pretty good. Now, one of the last things we're going to do for some initial setup, we're going to add in a new file to our root project directory called index.js. Inside that index.js file, we're going to accomplish two things. First, we're going to start up our Express application, which we had defined inside this app.js file. And we're also going to tell our pool to connect to our local database. So inside of our root project directory, I'll make a new file called index.js. Inside there, I'm going to first require in our app function. Because remember, this is a function that's going to build an instance of our Express app. I'm also going to require in that pool that we just created as well. Then inside of here, we need to tell our app to start listening to some given port for traffic. We also need to make sure we tell our pool to connect to some given database. We should probably make sure that we try to connect to our database first, because if we have some invalid connection credentials like a bad username or a bad password, we would want to throw an error and stop our application from ever starting up or listening for any traffic. So ideally, we would do something like pool.connect and then put our configuration options in here. We would then want to make sure that we connect successfully before we ever start listening. So let's do that right away. So this object is going to be very similar to that object we put together around our data migration a little bit ago. It's going to have a couple of different properties that tell our pool how to connect to our local database. So we are going to put in a host of localhost, a port of 5432, the name of our database, which is social network, and then your username and password. So user, for me, it is my username on my computer, SG. Again, if you're on Windows, it's probably Postgres, and then your password as well. So this is your password for the database. If you're on Windows, it's going to be the password you set up during the initial Postgres installation. If you're on macOS, it is probably a plain empty string. So then, in theory, right after that, we could create an instance of our app that will create our app using that app function we had previously built out inside the app.js file. And then we can use that to start to listen for some incoming traffic. And I'm going to have my app listen on port 3005 once again. And I'll just do a console log and say, listening on port 3005. Now, normally you would think this would work out as expected. You'd think that this would actually connect to our database. And if anything went wrong with that, you would think that would throw an error and then start listening for traffic. Well, here's kind of lesson number 1 around the PG module. Remember, we just spoke about how a pool wraps up some different clients. It turns out that when you first create a pool, it does not actually make any contact with Postgres whatsoever. It is only when a client is created that we make any contact with Postgres. So in other words, when you first create a pool, no contact with Postgres is made. And that means that all these connection credentials right here are not actually used or evaluated in any way. So if we want to make sure that these are the correct credentials and throw an error if they are not, we need to somehow tell the pool to immediately create a client and try to connect to Postgres. The easiest way to do that is to simply run a query. So one way we could do this very easily is go back over to our pool.js file. Inside of connect, right after creating our new pool, we can use that pool to make a very simple, very basic query. When we make that query, it's going to force the pool to connect to our Postgres database, and that therefore is going to test out those connection credentials we just provided. So to run a very simple and very basic query, we are going to do return this._pool.query, and we are going to run the query select 1 + 1. Now, this right here is not as funny or as janky as it might seem. It turns out that there are actually many other libraries in the Node ecosystem that do something just about identical to this, to test out your connection to the database when you first create a pool. As a matter of fact, the ORM that we're going to use in version 3 of this API does this exact same query when you first initialize the ORM to make sure that it has some valid connection to the database. So this right here, not as weird or silly as it might seem. So now we will save the pool.js file. I'm going to go back over to index.js. So we are now returning a promise from that connect function. That's what this return right here is doing. So it is a promise that is only going to resolve when that query is executed successfully. If the promise that is returned gets thrown or rejected, then the promise that gets thrown or we receive back over here is going to be thrown as well. So to make sure that we only start up our application after we successfully connect, I'm going to remove the semicolon at the end of that line. I will chain on a .then, and inside there is where we are going to do our actual application setup. And then if for some reason anything goes wrong with that connection, we will put on a catch. We'll receive the error that occurred while we were trying to make that connection and do a console.error of that error object, like so. We could, of course, also use the async await syntax right here, optionally if you want to, but that would also require us to define a separate function and then place all this code inside of it just so we could use async await. So if you want to do that, totally fine, up to you. Okay, so I'm going to save this. And I'm going to go back over to my terminal and run this file and make sure that it all works as expected. So back inside of my project directory, I'll do a node index.js. And sure enough, that means that we just ran that select statement and everything worked as expected. We can very easily see what happens if we provide some invalid connection credentials. So for example, if I put in a host right here of a bunch of gibberish and save this, we can then go back over, and now we are told very simply, okay, something went wrong, and our actual Express server did not start up. We got kicked directly back to the command line, which is probably what we want. Okay, so this looks pretty good. So we now are initializing our connection. We're making sure that the connection is actually valid, and only after that do we start up our Express app. So we have a pretty solid base for our application at this point. Let's take a pause right here, and we're going to start to implement a couple of our different routes starting inside the next video. We've got a good start to our pool class. We're now going to add in two other methods to it besides connect. Right after connect, we're going to add in a method called close. The goal of close is to close out the pool, or essentially disconnect from our Postgres database entirely. Once again, we're going to eventually use this method inside of our testing setup. For right now, we're just going to throw it in and use it a little bit later on. To actually disconnect from our Postgres database, we'll call this ._pool.end. We're also going to return the result of that. Then finally, one other method. This is our primary method for actually running some kind of query or sending a SQL statement off to our database. We're going to define a method called query. Inside of here, we're going to accept one argument for right now. So this is going to be some little bit of SQL that we want to execute. And then we will return this _pool.query and pass in that SQL that we want to execute. Now, I want you to know right away that there's a really big security issue here. So we're going to eventually come back to this method and discuss a really big security issue around it. This is going to be part of a larger discussion around security inside of our database. So for right now, just understand that this code right here, this function, is not exactly perfect, and we do need to revisit it and just have a little further discussion in a little bit. Okay, so that is it for our pool class for right now. And once again, I know that it looks like we're just kind of arbitrarily wrapping up this pool, the actual pool that we are creating right here inside of the connect function. But again, this is all being done to kind of make it a lot easier to do our testing setup in just a little bit, and also to make connecting to multiple different databases from the same application a little bit easier as well. Now that we are in a good spot with this pool, let's continue on to our first repository that we need to create in the next video. Well, we've got our pool created, which will allow us to run some arbitrary queries. We've also got a couple of different routes scaffolded out. Now we can start to really think about how we're going to build out each of these different route handlers. We'll start off first with our /users route handler. If anyone makes a GET type request to this, then we want to get a list of all the different users in our users table and return it. So in theory, whenever we receive a request right here, we really need to do two things. We need to run a query to get all users, and then send the result back to the person who made this request. The real question here that I want to focus on is what we are doing for this step right here. How are we going to run a query? Well, we could do so very easily by requiring in that pool object that we just created and then running a SQL statement from right here. But there's going to be a slightly different way that we're going to do this. We're going to use what is called the repository pattern. So let's talk about exactly what a repository is and why we are going to use one at all. All right. So we are going to create an object called a user repository. This object is going to have a couple of different functions tied to it that are all about somehow accessing, updating, inserting, or deleting different rows inside of our user table. So our user repository will have a couple of functions like find by ID, insert, update, and delete. And each one is going to do pretty much what you would guess. Find will get an array of different users. Find by ID will find some particular user, and so on. This user repository is going to be our central access point for somehow reaching into the user's table and fetching data, updating data, or whatever else it is that we need to do around our user's table. Each of these different methods inside of our user repository is really designed to be used by one of our different route handlers. So for example, our /users route that we're about to work on is going to make use of this find method. Same thing for say /users/ID, that will probably use a method like find by ID to find some particular user with the given ID. Now, our user repository doesn't necessarily have to have a one-to-one lineup that's going to just exactly serve these different route handlers. Our user repository could also have several other methods attached to it as well. So we might have a find one method that is going to find a user given some kind of filtering criteria. We might have some kind of count function to get the number of users in the user table. We might also have some kind of validate function as well. So we can have as many functions tied to the user repository as we want. The only thing to keep in mind is that this user repository object is going to be our central point for interacting with the user table. Now, when we think about how we're going to actually build the user repository, there's a huge variety of different ways that we can implement this. So we can make this a plain object that has some functions declared on it. We can make this an instance of a class. We can make this a class that has some static methods tied to it. We can build up this user repository in any way, shape, or form we want. The only real big idea behind this repository pattern is that we've got one single object that is essentially governing access to some aspect of our database, in this case, our user table. And that's it. So the user repository pattern, or the really repository pattern, is pretty straightforward. Just remember one central point for accessing a type of resource inside the database. Okay, now that we've got a little review or overview on what this repository thing is all about, let's start to implement it in just a moment. Let's start creating our first repository inside of our project. Inside the src directory, I'm going to create a new folder called repos, and then inside there, I'll make a new file called user-repo.js. So we're going to define our first repository inside of here. Technically, it's going to be our only repository because our project is only working with a table of users. So our repository is eventually going to need to somehow reach out to our Postgres database and execute a query of some kind. In order to access our database, we created that pool.js file. So this is the object or the instance, really, that we are exporting down here at the bottom, that we're going to eventually use to run some kind of query. So we need to require that pool into our user repo file. So at the very top, we will add in const pool is require up1 directory pool. Then after that, we can start to define our repository right away. As I mentioned, there are many different ways that we can define this repository. So I'm going to show you 3 different ways that we can very easily make use of. All 3 different ways are, at the end of the day, pretty much equivalent, and there's not really a great reason to use one way over the other. It really comes down to kind of your personal preference as a developer. So one way that we could define our user repository would be to export a plain object that has a couple of functions defined inside of it. So it could have a find function, and it could have a find by ID, and maybe an insert, and so on. And so each of these functions might take some kind of argument. It might then run some kind of query by using our pool, and then return the result. That's pretty much it. So this is option 1. Option number 2, I'm going to delete this really quick, would be to create some kind of user repo class, which would then have a couple of different instance methods defined on it. So it might have an instance method, such as find, a find by ID, and an insert. And then at the very bottom, we could create an instance of this class and export it. So that would be something like module.exports new user repo. That's option number 2. And then finally, option number 3 is going to be very similar, but rather than defining all these different functions as instance functions, so to access these functions, we have to create an instance of the class first, we could instead mark each of them as being static methods that allow us to access each of these functions without first creating an instance of the class. So we could do static find by ID, static insert, and so on. Now, to access each of these methods, we would not have to create an instance as we are doing right here. We can instead just export user repo. And then inside of another file, just as a very quick example, we could do something like user repo.insert or user repo.find, and so on. So again, at the end of the day, all 3 different methods, 100% equivalent more or less, and there's really not a great reason to use one approach over the other, outside of your own personal preference as a developer. I personally rather like this static method approach because it makes this class just very easy to read. In general, just looks kind of clean to me, but it's totally up to you. If you want to take another approach, that is totally fine. So this is the style that I'm going to be working with. So now we're going to define a couple more functions on this instance, or excuse me, on this class. So we're going to also define our update and delete functions as well. I'm going to add in static update and static delete. So inside of each of these different functions, we might accept some argument. We're then going to make use of our pool to run some kind of query against our database and then return the result of that query. That's pretty much it for every one of these functions. So all these functions are going to look rather similar in nature. Accept some argument, run a query, return the result, and that's it. Whenever we run a query using this pool object, it is always an asynchronous operation. It takes some amount of time for the pool object to reach out to Postgres, execute that query, and get a result back. That means that in just about all these different methods, we are going to want to make use of this async await syntax. So right away, we should probably go around to each of these different functions and mark them with the async keyword. So I'm going to go around to each one, and right after the static keyword, I will put in async. Okay, so that looks good. Now finally, let's start to put together some implementation for our very first function. So whenever we call find, our ultimate goal is to just reach into that user table, get a list of all of our different users, and return the result. So the query that we need for that is going to be very simple and straightforward, something like select star from users. So we can use our pool to execute that query. So we're going to say const result is await pool.query. Remember, that's the function we put together to actually run some SQL statement. And then we will put our actual SQL that we want to run in there as an argument. So we want to run select star from users. Notice that we have the await keyword right here to allow the query to actually be executed. So we should be getting back some kind of result object. Now the result object right here is not going to be the actual array of rows, or essentially array of objects representing all those different rows. Instead, the result object has a lot of additional information about the query that was issued, some other statistics about it, some other settings, and so on. So the actual data that we really care about on that result object is on the rows property. So result.rows, that's the data we care about. That's going to be the array of objects we get back where each object represents one distinct user. So we don't really care about the overall result object, we really just care about the rows property. So to save ourselves a little bit of time, we could just destructure off that rows property by itself, because again, that's the only thing we really care about. Then, once we got that rows object, we might want to do some kind of parsing on it. Who knows? We'll see if we need to do any further kind of processing on it in any way. But for right now, let's just return rows. So I'll do a return rows like so. Okay, so there's our first static function. So we've got our find function, go and get all the users, just return them. and that's pretty much it. Now that we've got this one function put together, we can make use of it from our router file. I'm going to go back over to my users.js file. I'm going to go up to the very top and require in our user repo. From the repos directory, user repo. And then finally, inside of our route handler right here, we can call that function we just put together on the user repo to get the list of all of our different users and then send them all back to whoever just made this request. So we could do const users is await user repo.find, and then take that list of users and send it back. So that would be a normal res.send users like so. Okay, so that looks pretty good. Now, I got to tell you, there are a little bit of holes in our logic here. You're going to see that maybe we can't just directly return this rows object right here. Maybe we have to do some further processing on it. In addition, like I mentioned just a little bit ago, inside of our pool.js file, we still have a really big security issue in here. So at this point, we've got some solid code, but it would be really nice if we did just a little bit of testing to confirm that everything is really working the way we expect. So let's take a pause right here, and then we're going to figure out how we can somehow manually test out all the code that we've written in the next video. We've got a little bit of code put together, and now we need to somehow test it out. To get started, we first need to start our server up inside of our terminal. So back at our terminal, I'm going to make sure I'm inside my root project directory, and then run npm run start. So that should start our server up, and we are now listening on port 3005. Now to test out this API, we need to somehow make a request to it. There are two methods that we're going to use inside this course to make some kind of arbitrary request to our server. So it's totally up to you which one you want to use. You can either download a standalone client called Postman. Postman is a standalone application that you can use to make arbitrary requests to some given endpoint. If you want to make use of Postman, you can go to postman.com inside of your browser. You might have to sign up for a new account. You'll then be prompted to download an installer. So go ahead and run it, and eventually when you get Postman installed, you will get a little screen like this right here. Once you have Postman open, we'll then open up a little new tab right here. This will allow us to make some kind of arbitrary request. In our case, we want to make a GET request to http://localhost:3005/users. We can then click on send, and that will make a request to our running application. In this case, I get back a response of empty array right here, which means that currently we don't have any users inside of our users table. So if you want to use Postman, that's totally fine. If you don't want to download that additional application or do any additional sign up, well, if you're making use of Visual Studio Code, you can download a little extension that will allow you to make requests directly from your editor by downloading and running an extension called REST Client. Let me very quickly show you how this tool works as well. Back inside my editor, I'm going to find my View menu at the very top and go to Extensions. Inside this Extensions tab, I'll then search for REST Client, and I should see the very first result right here. Go ahead and install this. Once you've got it installed, we'll then close this window. And then back inside of my file folder structure over here on the left-hand side, I'm going to make a new file inside of my root directory, and I'll call it request.http. Then to make a request to our running server, we're going to write out the URL that we want to make the request to. So in our case, it's http://localhost:3005/users. Then to execute that request, we can right-click on it and click on Send Request. That extension is then going to issue the request, and we'll see the result appear on the right-hand side. So once again, we get an empty array right there because we currently do not have any users. The nice thing about this request extension is that you can easily write out multiple different requests and then execute any one at any given time. So let's say, for example, that we eventually want to write out a second request. We could put down ###, and then on the other side, we can write out some totally different URL. So because we've only got one route right now, I'm just going to write out the same route. Now we can right-click on that one and click on Send Request. And it's going to send that request as well. So the nice thing, again, about this extension is that we can eventually have all of our different requests inside of one file and test them all out very easily. So it's totally up to you which client you use. I'm going to be using REST Client moving forward, but if you are not using Visual Studio Code, feel free to use Postman instead. Okay, so now that we've got some ability to test here, let's go ahead and actually rerun this request in the next video. We're going to, of course, notice that we don't have any users inside of our users table right now. Then we'll get started on actually adding in some users to our database and then testing again. At this point, we can send a request off to our API using either this extension inside of Visual Studio Code or Postman. So if you send the request off now, we get back, of course, an empty array because we have no users in that users table. Just to make sure all of our code is working as expected, let's go over to pgadmin and manually insert 1 or 2 users into our users table and then repeat this request again. Over in pgadmin, I'm going to find my social network database. I'm going to open up the query tool, and then we'll do a manual insert into users. We will specify a bio and a username for each user. We'll then put in 2 users by putting in values. For my first user, I'm going to give a biography of this is my bio, and I'll give them a username of Allison14. And then for the second user, we'll say this is about me, and I'll give them a username of Gia67. I'm going to run this, and it looks like it was successful. Now I'm going to print out everything from my users table, and we've got those 2 users. Now, one thing I want you to notice very quickly is that we also have those created at and updated at columns as well. Just keep that in mind for a moment. Okay, so now back inside of whatever API client you're using, Postman or this extension, we'll send the request again. And sure enough, everything works as expected. So we've got our actual users here. There's just one little thing I want to mention, a very small nitpick. Notice how created at is created underscore at, and update at is updated underscore at. Is that a big deal? Well, I just want to point out one thing really quickly. We might eventually need to do some kind of filtering or something like that, maybe on this find function, or we might need to try to find users created before a certain date or updated after a certain date, or whatever it is, we might need to eventually access that updated at and created at property. If we were to try to access those properties right now, we would have to do something like, say, users at 0 to get our first user, because that is an array of users, dot created underscore at. Now this right here is using some naming convention inside of JavaScript code that is not standard in JavaScript. Standard casing inside of JavaScript is camel casing, where we would do something like created at with a capital AT and no underscore. So this is kind of a small nitpick, but it's something that really you kind of want to keep consistent inside of your code base. If we are using JavaScript and we are following camel casing, we really want to be able to access created at and not have to do something like created underscore at. Otherwise, you're going to have very inconsistent casing across your entire application. So there are really 2 options, or maybe 3 options available to us here. We could say, well, this is what it's stored as inside the database. We're going to have to just deal with this everywhere. And in some cases, we will have properties that we are accessing that have an underscore in them. That's option number 1. Option number 2 would be to go back over to our database and just rename these columns. However, if we rename these columns, we're no longer really following proper naming convention in the world of SQL, because proper naming convention would be to use these underscores. That's option number 2. We could change the database, but there's definitely a big downside to it. Option number 3, which, as you'd guess, is what we're going to do, whenever we execute a query and get back some results, we could do some processing or parsing on those results. We could try to find every instance where we've got a property name with an underscore inside of it and automatically convert it into a capital letter instead and remove that underscore. So that's what we're going to do. Whenever we make a request off to our database and we get back some result, we're going to iterate over that result. We're going to take a look at all the different properties and all the objects we get back. And if any of them have an underscore, we're going to automatically fix the casing. And that's going to make sure that we've got 100% consistent casing between our database, and we still can have consistent casing inside of our application code as well. So let's take a look at how we're going to fix up all this casing stuff with some actual code in the next video. I'm inside of my user repo file looking at the find function. So when we run our query, we get back that array of objects right here that we refer to as rows. We're going to write in a little bit of code right underneath that to iterate over that array of objects. For every object, we're going to take a look at the object and take a look at all of its different keys. If any of those keys have an underscore inside them, as updated at and created at do, then we're going to remove that underscore and capitalize the next character. Let's take a look at how we would write this code directly inside this function, and then eventually we're going to extract this code and make it a little bit more reusable, because we're probably going to run into the same issue when we start implementing stuff like find by ID, insert, update, delete, and so on. Okay, so right after we get rows, we're going to do a parsed rows, be the result of rows.map. We're going to take a look at each individual row. For each row, we're then going to create a new object called replaced. This object is eventually going to hold all the different keys inside, or all the different updated keys inside of each individual row. We're going to iterate over all the different keys of the row object itself. And then we will decide whether or not we need to somehow parse or fix the casing of that key. So for this, we're going to say camel case will be the key dot replace. We're going to use a regular expression here. So I'm going to put in 2 forward slashes, a GI right after, and then inside those forward slashes, we're going to write out our regular expression. I'm going to put in a set of parentheses. I'm going to put in a square bracket, a dash underscore, and then inside of another set of square brackets, a dash z. Then right after the GI, we'll put in $1, then an arrow function. Inside the arrow function, we're going to take $1 to uppercase. We're then going to replace any underscore that we found with an empty string. So what's going on here with this regular expression? Well, essentially, we're going to take a look at every single location where we see either a dash or an underscore, followed by some single character. Anytime that we find exactly that, we're then going to be provided that match, so the dash or the underscore, and then the following character inside of this function right here as an argument called $1. So we're going to take $1, we're going to convert the entire string into uppercase. We're then going to find the underscore inside there and replace it with an empty string, effectively removing it entirely. So this will give us the camel case version of our entire key. So we're going to iterate over every key inside of an individual row. So we're going to iterate over ID, created at, updated at, bio, and username. We're going to create that updated key with the correct casing. And then once we get that updated key, we're going to place that updated key inside of replaced, along with the original value from the row itself. So we're going to say replaced camel case is row at key. And then finally, outside of the for statement, we're going to return the replaced object. Okay, so that's going to build up our parsed rows array. So that array of objects should have only all the correctly cased keys inside of it. So now we are going to return parsed rows instead of just the normal rows. So let's save this, and we'll test it out right away. Back inside of our request.http file, or inside of Postman, we'll send the request again. And now we can see very easily that we correctly have created at, updated at, created at, and updated at. So now, whenever we get that response back from the server or from our database, we automatically parse all those keys and replace them with the correct JavaScript cased or camel cased keys instead. Now I know some of the code inside of here is a little bit nasty. Hopefully we can just understand, hey, that's just going to fix up some casing for us, and that's pretty much it. Okay, so let's now take this code that we just wrote out. We're probably going to have to reuse this in several different locations inside of our repository, and maybe even other files or other repos in the future as well. So we might want to extract that code into some kind of additional file so we can reuse it in the future. Inside of my repos directory, I'm going to make a new folder called utils. And then inside there, I'll make a new file called 2camelcase.js. Inside of here, I'll do a module.exports. I'm going to export a function. This is going to take some number of rows that we want to fix up all the casing for. And I'm going to go back over to our user repo. I'm going to take that entire parsed rows statement. I'm going to cut it and then move it over to the function that we just created. We don't really need any parsed rows variable anymore. We can just return the result of the mapping statement itself, like so. Okay, so that should be it. So now we've got a very reusable function that can automatically rename or fix all the casing in all these different objects for us. So I'm going to save that file. I'm going to go back over to user repo. At the very top, we will require in to camel case from utils to camel case. And then finally, at parsed rows right here, we're going to take out parsed rows. We're going to put in to camel case and parse all the rows that we got back from the query itself. And that should be it. So let's save this one more time and then do one more additional test. So I'm going to send that request off again. And yep, looks like it still is working as expected. Now, at all times, whenever we get back any kind of result from our database, we should be able to always easily parse that data, fix all the casing, and never inside of any of our JavaScript code should we ever have to use that kind of underscore casing at any point in time. So I'd say this looks pretty good, reasonable solution. Let's take a pause right here and continue on to our next function, find by ID, in just a moment. Let's move on to our find by ID function. The goal of this function is to take some ID and try to find a user inside of our users table with that ID. This function is going to be used from our user router file. So here's the user router. We're going to call that function specifically from the second route handler right here. So whenever someone makes a request to users/ID, we're going to take the ID out of the URL and then pass it off to that find by ID function. Let's put together the route handler first and then go build out the actual find by ID function. So inside of here, we first need to get access to that ID. To do so, we can destructure the ID property off of rec.params. So that's going to automatically give us whatever ID is right there inside the incoming request. We'll then get some user out of our user repo by making use of the find by ID function and pass in the ID. Notice that we've got the await on there as well. Whenever we try to find a very particular user, we always might end up in the case where someone asks for a user that doesn't actually exist. So we should probably make sure that we actually have a user right here. Make sure that we actually have some value and we didn't get back undefined or null or something like that. If we got back null or undefined, we should probably respond to the incoming request with a 404 to say, sorry, but we were not able to find a user with that ID. So we'll do something like, if we do have a user, then we'll send back that user. Otherwise, if we do not have a user, then we'll send back a status of 404. Okay, so this request handler right here, it looks pretty reasonable. So let's save this, and we'll go back over to our user repo and start to implement find by ID. So here's our user repo. Here's find by ID. As we just mentioned, this function is probably going to take in an argument of the ID of the user that we're trying to find. Then inside of here, we can do something very similar to what we did up here. We can run a query and try to find a user with a particular ID, get back some result, parse it in some way, and then return it. Now, the one thing I want you to be aware of is that the first version of our code is going to have a really big security issue. And that's what we're really going to focus on here. So I first want to write out some kind of naive code or not good code that you might accidentally write on your own project. I then want you to see exactly what the security issue is, and then we're going to come back and fix it up and make sure that you really understand what the security issue is. So let's go ahead and write out some bad code to get started. So we will put in something like const rows. We'll then run a query. So that will be an await bool.query. I'm then going to put in a multi-line string by using a set of backticks. And then inside of here, we're going to put in a select star from users. And of course, we only want to find a user with a very particular ID. So we'll put in a where ID equals, and we'll put the ID into the string. So again, this query right here, very big security issue. I'm going to tell you exactly what is wrong with that. I just want to repeat one more time. Please do not write code like this at any point in time. Okay, so then after that, we might want to make sure that we only get back one particular user. Now, in theory, all of our IDs are going to be unique, so we should never get back multiple users. But if you wanted to, if for some reason you weren't sure if you were going to get back one user or multiple, you could always put on a limit 1. And that will guarantee, of course, that you get back just one user. But in our case, because the ID column is unique, we don't really have to worry about that at all. So we're going to get back rows once again, which will be an array of all the different rows we found while executing this query. So rows should probably contain either no values, so empty array, or it should have one value inside of it. Either way, we do need to make sure that we convert all the different objects inside that array to camel case. So we're going to do a return to camel case. We'll put in rows, and then we're going to take the first entry inside that array. If this array is empty, then this is going to give us back undefined. Otherwise, if there is one user inside there, well, we're going to get back that one single user. Okay, so let's save this. We're then going to run this as it stands right now. We'll then take a quick pause, and then we'll take a look at what this security issue is. So back inside of our request file or Postman, we're going to modify our request URL right here. I'm going to say that I want to find the user with an ID of 1. So I'll put on the /1 like so. I'm then going to send this request. And there we go. I got back that one single user. If I try to put in a user with an ID that definitely doesn't exist and send that off, I then get back a 404. So I can ask for a user with ID 1, and I can ask for a user with ID 2. And if I go up to 3, we don't have a third user, or at least I don't, so I get that 404. So let's say this looks pretty good. But as I mentioned 4 or 5 times now, very big security issue. So let's take a pause right here and figure out what is going on in just a moment. So what is this really big security issue all about? Well, let's go run one more request. And when we do so, we're going to modify the request we make just a little bit. Okay, so I'm going to take my request URL right here. I'm going to find the 1 right there. And then right after the 1, I'm going to put in a semicolon and then drop table users and another semicolon. Now, I don't know about you, but this doesn't really look like a valid request to me. But whatever, let's just go ahead and run it. So I'm going to send the request. And it looks like nothing happens at all. Well, let's go back over to our terminal and see what our server is doing. It looks like the server threw some kind of error. Well, okay, maybe that was just a bad URL to try to make a request to. So let's just go ahead and revert that URL and make a request to a URL that we once again knows actually works correctly. So I'm going to delete all that stuff after the 1, and let's try sending this off again. I'm going to send it, and still nothing happens at all. Well, let's go back over to our terminal once again and see what's happening now. Well, now there's a lot of error information inside of here, but notice that there's one error right here that says relation users does not exist. What does that error mean? Well, let's go back over to pgadmin, take a look at our database, and just figure out what is going on. So back inside of pgadmin, I'm going to try doing this select star from users once again. And hey, wait a minute, same error. What does this mean? Let's take a look at our actual table definitions inside of Social Network. So I'm going to refresh this thing. I'm going to go down to our tables listing, and inside of tables, wait a minute, once again, we've only got one table inside there. What is going on right now? Well, this is an example of the security issue that I just mentioned in action. So let's take a look at a couple diagrams and understand what just occurred and what happened to our users table. So here we go. Okay. So at present, we are making requests to our application. Our application is taking that little 1 right there on the very end of our URL. We extract that number 1 as a plain string. It doesn't actually get extracted as a number, even though it looks like a number to you and I. It gets extracted as a plain string with the number 1 inside of it. We then take that string, we hand it off to our getUserById function inside of our user repo. We then use plain string concatenation to insert that string of 1 into the very end of our query. So we can kind of imagine that at the very end, we take that string of 1, put it right there like so, and that is the query that we execute. So we take that query and send it off to our database. So what happened with that other query that we just wrote a moment ago where we put in that drop table users? Well, let's walk through this same exact flow. So we wrote out 1 semicolon drop table users semicolon. So we can imagine that we took that 1 and everything after it. It was extracted as a parameter of the URL. We then put it onto the very end of our SQL statement right here, and we ended up with what you see down here at the very bottom. And we sent that off to our database and executed that statement. So we ended up running inside of our database select star from users where ID equals 1 and then drop table users. Drop table users is, of course, how we delete a table and all the information inside of it. So by just modifying that URL very slightly, we were able to make a drastic change to our database. And as you can imagine, this is extraordinarily bad. It is incredibly bad. This means if we kind of deployed this code into a production environment, that any arbitrary user could run arbitrary statements inside of our database by just modifying the URL. This is indescribably just the worst scenario, the worst thing that can possibly happen inside of a deployed web application. We refer to this scenario as a SQL injection exploit. A SQL injection exploit is when you take some user-provided input, either inside of a form post, like a user submits a form, or in the form of taking some part of a URL, or just about any other value that is provided directly from a user. If you take that value that is provided from a user and just plainly execute it inside of a SQL query, the user can modify that value that they provide and do any kind of arbitrary operation inside of your database that they want. So they can read information off of tables that they shouldn't. They can try to make changes to your database. They can even try to delete tables or records as well. So we never, ever, under any scenario, ever directly take user-provided input and use some kind of direct string concatenation stuff to join that user-provided value into a query. So in other words, we are not going to be writing any code that looks like this right here. This is very bad, and we do not want to write this at all. I can't state that enough. If you ever write some code like this right here, and you end up introducing a SQL injection exploit into an application, that is a very bad thing, and it's definitely grounds for kind of getting fired from a job. I'll be totally honest with you. You really don't want to do this in any production application. Now, of course, in some scenarios, we do want to take some kind of user-provided value and supply it to a query. So there are a variety of different safe ways to take user-provided values and somehow get it into a query. This can be done safely, but we absolutely do not do it by taking a normal template string, like what we have right here, and just interpolating the value indirectly. We also would never write out something like, say, just a very quick refactor here. I'll just copy this entire query down. So we would never also do something like, come on, you. Like that right there. So we are still taking some kind of user-provided value and just putting it directly into a query as well. This would suffer from the same kind of issue. Okay, so again, we refer to this as a SQL injection exploit, and I hope all my strong language in this video makes it really clear how bad this is. So at this point, you might be able to say, okay, like I understand, Stephen, I get it, it's bad, we don't want to do this, but what is the solution? Well, there's a very clear solution to this problem, and it's going to be very easy for you to identify when that solution is being used. In other words, it's going to be really easy at the end of the day for you to identify in code when there is a SQL injection exploit and when there is not. Let's take a look at how we're going to solve this problem in the next video. Now that we understand the SQL injection exploit, let's take a look at how we can solve this and still make use of some kind of user-provided values inside of a query. All right, so there's really two big solutions we can possibly use. So if we ever want to get a user-provided value into a query, which inevitably is going to happen at some point in time, we can either add some code to sanitize a user-provided value into our application itself. So this would take the form of you and I writing out some code to make sure that whatever that query parameter is that's coming inside that URL doesn't somehow contain some SQL statement embedded inside of it or anything like that. So we would have to write out some pretty complicated code to make sure nothing nasty is actually going on. That's option number one. Option number two is generally preferable by a huge margin. In option number two, we can instead rely on Postgres to sanitize some user-provided values for us. So in general, we want to always try to go with option number two right here, but there are some scenarios where option number two doesn't quite work out, and I'll show you what those are. So let's take a look at how we would make use of option number two. How would we somehow rely on Postgres to sanitize values for us? Okay, so really quick, I want to give you a reminder on what is going on inside of our application right now with that PG module that we're making use of. So the PG module is in charge of taking some statement, running that statement, sending it off to the database, and getting a response back. So right now, we're just taking some SQL statement with values already inside of it and handing that off to PG. So PG is just taking that entire statement and throwing it off to the database. So we're going to change this approach just a little bit. Rather than giving PG just the completed statement by itself, we're going to kind of break this into a two-step process. We're going to instead give the PG module two separate things. We're going to give it a statement that is kind of like a template of sorts. So notice that now inside the SQL query, where we previously had an ID, I now have a $1. $1 right there you can think of as kind of an identifier that says, hey, we should take some kind of value and stick it in for this spot right here. Then separately, we're going to provide an array of values to be substituted into that statement. So in this array, at the very first index is a string of 127. So when we eventually execute this statement, we want something, be it PG or Postgres or whatever else, to essentially take a look at that $1 right there and say, oh, I need the first value out of that values index or that values array. So it's going to go into that values array, find the very first value because it's $1, and it's going to replace that $1 with 127 like so. If we ever have, for some reason, multiple values that we need to substitute in here, so maybe we also have an and username equals something, we would put in a $2, and then the value that would be substituted in there would be the second value out of this array. So maybe in this case, we would have username of Gia67 or something like that. So $1 would get replaced with 127, $2 would get replaced with Gia67. So how is this actually used by PG and Postgres? Well, the statement is used by PG first. PG is going to take that statement and create what is called a prepared statement. It's going to reach out to our database and say, hey, I want you to get ready to run a query that looks like this right here. So just get ready to run it. When it does so, it's going to use a very special keyword called prepare. That tells Postgres that it needs to start to plan to run this query, but don't run it just yet. Whenever we prepare a statement ahead of time, we have to provide an identifier for it. This identifier is randomly generated by the PG module. So PG is essentially going to say, create a prepared statement with some random name. It then says that this prepared statement is eventually going to take a string as a single argument. So that's the string that we're going to put in right there for the ID. Now you might be thinking to yourself, hey Stephen, wait, we're not actually dealing with an ID that's a string, it's actually an integer. Totally fine. We could say just as well, hey, this is going to be an integer, totally fine, works the same way. I'm only saying that this is a string right here because technically, remember, when we pull this number out of the URL, it is a string. It's not actually a number. Just trying to stay a little bit consistent from that standpoint. So the PG module is going to create that prepared statement that tells Postgres that, hey, you're going to have to run this thing at some point in time very soon. Immediately after that, the PG module then says, okay, time to execute that prepared statement. So go and execute prepared statement with this name, and we want to substitute that value of $1 right there with a number 127 or the string 127, whatever. So your database is then going to substitute in, let's zoom in here. It's going to take that prepared statement. So we'll imagine it kind of gets copied over here. It's going to take that 127, substitute it in for the $1, and then execute this right here. So how does this actually solve any issues? Well, Postgres is 100% aware of what you are trying to do with a prepared statement. It 100% understands that when you call execute and you provide some values right here, these are values that should be placed into a query. They are not queries in their own right. So if you ever try to put in something like, say, drop table users right here, that will not be executed as a query. Instead, we can imagine that it would be placed inside of here as a string like drop table users, and that would not actually get executed in any way. Instead, you would run a query where Postgres literally tries to find a user with an ID of drop table users. And naturally, there's not going to be any user with that ID, and so this is a harmless query to actually execute. So this is option number one. We are essentially relying upon Postgres and this idea of a prepared statement. That's what this is called. We are relying upon a prepared statement and how that prepared statement gets executed to deal with sanitizing the value for us. We're relying on the fact that Postgres is 100% aware that when we actually execute the statement, we're going to provide values and not some further additional query to run or anything like that. Okay, so that's kind of the behind the scenes on what's going on with the PG module and how we can write out some query and still make use of user-provided values. Now, like I said, this is just one option out of two possible options. So the downside to this approach is that we can only use a prepared statement when we are trying to substitute in a value to a query. There are eventually going to be some scenarios where you might want to specify that maybe the table that you're pulling data from, or maybe the column that you're pulling from. So like ID, username, and what else we have? Bio. You might want to substitute in users, ID, username, or bio on the fly. In this case, these are all identifiers. We cannot specify identifiers on the fly with a prepared statement. We can only specify values, like literal values, such as numbers and strings and so on, with a prepared statement. So if you are ever in a scenario where you want to, on the fly, specify some given column that you want to select, or select what table it's from, or whatnot, you cannot use a prepared statement for that. And that's where this entire approach starts to come up short. Okay, so now that we've seen what's kind of going on behind the scenes, we understand one little limitation to this. Let's take a pause right here and then go and refactor our code to make use of this prepared statement approach to safely execute a query with some user-provided stuff inside of it. Let's start to fix up our code and make sure that we can run some kind of query that has user-provided values inside of it without leaving ourselves open to a SQL injection exploit. Before we modify any code, however, we do need to make sure that we reset our database and make sure that we've once again got a users table. Because when we ran that SQL injection request just a little bit ago, we accidentally dropped our users table. It doesn't exist anymore. So to recreate that table, I'm going to go over to pgadmin. I'm going to just drop my entire social network database. That's just the fastest way to do this. I'll then recreate the database. I'm going to again call it social network. Okay, so there's our database. We now need to run our migration inside there and recreate the users table. So to run our migration, we can go over to our terminal. I'm going to rerun the migration. So here's my database URL with npm run migrate up. So that recreated my users table. And now I'm going to go back over to pgadmin very quickly and once again create 1 or 2 users. I'll open up a query tool for social network, and then we'll do an insert into users. We will specify a bio and a username, and I want to insert values of, this is my bio for Allison14, and a little bit about me for Gia67. So let's insert those 2 users, and I'll do a select star from users just to make sure everything is looking as I expect. Yep, looks good. Okay, so now our database is back in a good state. So let's now go back over to our code editor, and we're going to start to modify a little bit of our code to make sure that we can run a query that has some user-provided values inside of it without exposing ourselves to any kind of SQL injection exploit. We'll first begin inside of our user repo file. So inside of user repo, we're going to modify our call to pool.query. We're going to break this up into 2 separate sets of values. The first argument will be a query or an actual SQL statement, and instead of any kind of identifier inside of here, not identifier, but instead of any kind of value inside of here, we'll place that $1 or $2 or whatever value we want to eventually substitute in. So in this case, we want to substitute in a value right here. So I'm going to delete that and place in $1. Then as a second argument, I'm going to put in an array that contains all the different values that we eventually want to substitute into this statement. In this case, we want to substitute in this ID right here. So I'm going to put in ID like so. So now when we pass this thing off to PG or the PG module, it's going to first build that prepared statement out of just that part right there. And then after the prepared statement has been created, it will then execute it with this array of values. As a reminder, once again, if you ever want to provide multiple different values to be substituted in, you would add them to this array. So let's say maybe a username. And then we would put in an and username equals, and then we put in a $sign with a number after to refer to which index inside this array we want to substitute in. So in this case, I want to take a look at the second value inside the array, username, and put it right there. We could very easily rearrange these values right here. So now username is the first element inside this array. So to refer to username, we would have to change that to $1, and we would have to change the ID right here to $2. just a for example. Okay, so I'm going to undo those changes because we don't actually care about finding user by username right now. Okay, so we have now solved the security issue right here. So I'm going to take out that comment and save this file. And then before we actually run this, remember the pool.query function that we are running right here is a function that you and I defined inside of our pool.js file. So we need to take these two arguments and just make sure that we pass them through to the actual query function inside of the PG module. So long story short, we have to go back over to pool.js. We're going to accept that second argument right here of values. We frequently refer to this as parameters or params for the query. And then we're just going to pass that directly through to params. So once again, we have solved the really big security issue. So I'm going to take that comment out. Okay, so that should be it. So now we should be ready to test everything. And we should be able to make some kind of query with even some kind of SQL statement inside of it and not have it actually be executed inside of our database. So I'm going to pull open my API request client. I'm going to try to make a regular query, or you know what, first, let's make sure our server is actually running. Forgot that step. So back at our terminal, let's do our npm start. Okay, now we're ready for a test. So I'm going to do a very normal request right here and try to find a user with ID 1. We're going to send that off. Looks good. Find a user with ID 2. Looks good. Try to find a user with ID 3. Doesn't exist, and so we get a 404. So let's now change that back to 1. And I'm going to put in a semicolon and then drop table users. So now we can try to run this. When we try to run it, nothing happens whatsoever. Well, let's go back over to our terminal and see if our server is throwing an error. So back at my terminal, I can see very easily there's an error right here, and it says invalid input syntax for type integer. So 1 semicolon drop table users. So it's very clear at this point that we are essentially trying to substitute in or put in some kind of value and compare it against an integer. So in this case, we're trying to compare against this string of 1 semicolon drop table users. So that entire string right there is being treated as a string and not as a separate SQL statement, which is exactly what we want to have happen. So this is a perfect solution, or a very good solution, to this entire SQL injection exploit. It's going to make sure that we can put in some kind of user input into a query, as we're doing right here, and not have to worry about any kind of security issue. So a little bit ago, like 1 or 2 videos, I had said to you, oh yeah, you're going to be able to identify very easily whenever you are addressing this exploit or you are not. So whenever you are trying to make use of some kind of value, any kind of value, be it user provided or some kind of value that you are generating yourself with your own code, you are always going to want to put that into a SQL statement that looks like this right here. So we always want to see some kind of SQL statement with maybe a $1, $2, $3, and then an array of values right after that. That is what we want to see. Okay, so as long as you see this, you know, okay, chances are we're good on SQL exploits for this statement. Okay, so this is looking pretty good. Last thing I'm going to do here inside of find by ID, my code formatter broke this out into separate lines, which is really, really annoying. So I'm just going to collapse it down to one single line manually, like so. So it's not quite so ugly anymore. All right, so this looks good. So let's take a pause right here and continue in just a moment. Let's move on to our next request handler. So that's going to be post/users inside of our routes users file. We're going to make sure that we can use this route handler to create a new user. The first thing we should probably do is just make sure that we can receive some kind of data inside of a post request. Let's just get a quick reminder on how we do that in general. So inside this request handler, I'm going to add in a console log of rec.body. And then after that, I'll do a res.send of empty string, like so. So whenever we make a post request, we are going to include a body to the request. Inside of Express, we can access that data that is sent along with the request as rec.body. So let's test this out inside of Postman and inside of the built-in request handler inside of our editor really quickly. So if you are making use of Postman, you can select this drop-down right here and change it over to post. You'll make sure that you are making a request to 3005/users. There should not be any ID on there, so just users. We'll then go to the body tab. We will select raw. I'm going to make sure that in this dropdown, I have JSON selected. And then inside of here, I'm going to enter in an object with a key inside of double quotes of username. and I'll give it a username of, how about cookie123, and a bio, also in double quotes, of I am a cookie. So now if I send this, I should be able to go over to my terminal and see username right there and bio right there. If you are making use of the request sender inside of Visual Studio Code, then we'll open up that request.http file. We can specify multiple requests inside of here if we want to. So I'm going to put in a hash, and we'll put in a little template right here to make a post request. So I'm going to put in post in all capitals, http :/localhost 3005/users, and then a space and http:/1.1. We'll then specify a content type of application/JSON. And then right after that, we'll put in the JSON that we want to send along. So it might be, once again, a username of cookie123 and a bio of I am a cookie. So now we can send this request off. We got back an empty response. That's totally fine. I'm going to go take a look at my terminal once again, and there's that same console log. Okay, so just a quick review on how we receive the body of a post request inside of Express, and how we can send a post request with Postman and that request sender. Now that we've got this quick review out of the way, let's start to put in some implementation here in just a moment. Let's continue working on this request handler. So we've now got our request body. We probably want to take that request body, pull out the username and the bio from it, and then send it off to some method inside of our user repo, probably this insert method right here. So we are going to destructure out the username and bio from rec.body. We'll then do an await user repo insert, and we will just pass along directly the username and the bio. And whenever we create a user, we generally want to take the user that was created inside the database and send it back to whoever made this request. So we're going to assume that our insert function is going to return some information about the actual user record that was created, such as the ID, the created at, the updated at, and the username and the bio as well. And we're going to take that all and send it back to whoever made the request. So we're going to assume that we will get back a user and send it back like so. So now let's go back over to our user repo file and put together some implementation inside of insert. So we're going to first receive that username and the bio. We're then going to use our PG or our pool.query method, just like we did up here, to insert a new user. So once again, we are running a query that has some user-provided values inside of it. So we need to use the same kind of parameterized query, like what we have right here, with the array as the second argument. So inside of insert, we will do a await pool.query. We want to do an insert into users. We're going to provide values for the username and the bio, and the actual values for that will be placed inside of a set of parentheses as usual. And we're going to say that we want to do some substitution from $1 and $2. Then, as a second argument to this function, we can put in our array of substitute values, and that will contain the username and the bio. So once again, we're going to take username, substitute it right there, and bio, and substitute it right there. Now there's one little gotcha here. Remember I said just a moment ago that whenever we create a user, we probably want to get some information about the user that was created. By default, whenever we do an insert statement, we don't actually get any information about the user that was created back. If we do want to get information about that user, then after the value statement down here, or at the very far right-hand side, we have to put in a returning star, like so. That means that after we insert this user, then go ahead and take all the different columns for that user and return them. So then, as a result from this entire query, we should get the information about the user that was created. So we can once again receive that as rows like so. So this will be an array of objects as usual. That array of objects might have that created at and the updated at properties inside of it with the improper casing. So we do still have to send it through that toCamel case stuff once again. So we'll do a return toCamel case with rows. And then if we inserted a user successfully, chances are we are only going to get back one single user. So So we really just want the first element out of this array. So once again, we'll do a @0 like so. All right, so let's save this. And I think that we are ready to do a test. So once again, you can go over to your request client of choice, either Postman or this built-in one. I'll go ahead and send the request, and maybe I'll put in a different username here really quickly. How about, I don't know, Minty3. I'll give it I am a mint. I'm going to send that request, and there we go. We have inserted a new user. We've got the bio, the username, and all the columns associated with that user. So this looks pretty good. Okay, so I think that you're probably starting to get the idea that a lot of this stuff is going to get a little bit repetitive. So we can go through update and delete rather quickly now. So let's start to tackle those in just a moment. I'm inside my routes file. Let's move on to the put statement right here, which is going to be used to update a user. So in this case, we need to pull some information out of the request body. So that's going to be the new username and bio that we want to assign to a user. We also need to do something very similar to this right here, where we get the ID of the user that we want to update out of the URL. So back down inside of put, we can first get our ID from rec.params. We can then get the new username and bio from rec.body. So then we will update our user and do an await user repo.update. We're going to pass in the ID that we want to update, and then the username and the bio as well. And then finally, we'll do a res.send for user. Okay, so let's save this. We'll then go back over to our user repo file. I'm going to go down to the update function, and we will receive the ID, the username, and the bio. Then inside of here, we'll once again get our rows that comes out of doing this update. That'll be an await pool.query. And to do the actual update itself, we just need to make sure that we use the appropriate update syntax. Remember, for that, we can do a update and then the table name. So update users. And let's make this a multi-line string, or can we get away without it? Let's try going without it first. So we'll say that we want to update users. We want to set username to $1, and we want to set the bio to $2. And we only want to update the rows where the ID is equal to about $3. And then finally, very similar to when we do an insert, when we do an update, we don't actually get any information back about the rows that were actually updated. So if we want to get some information back about the user that was updated at the very end, we have to put in a returning star again. So that's our query. Then as the second argument to the query function, we'll put in the values to use for substitution. So this will be username first, then bio, then the ID. The username, bio, ID. Okay, so then once again, we're going to get back this array of objects right here, even though we probably only updated one user. So we will return to camel case rows, and we'll pull out just the one entry that's probably going to be in there. There's one other thing to be aware of. Right now, we are really assuming that we are going to find a user with the ID that the person who made the request provided. So back inside of our user router file, we are really assuming that we're going to find a user with that ID. It might be entirely possible that a user tries to tell us to update an ID that doesn't actually exist. So to make sure that we actually updated something, we can take a look at this user variable. If it is defined, that means that we actually did find a user and we updated it. Otherwise, if it is undefined, it means that we were not able to find a user to update. So very similar to what we did inside of our get right here, we can check for the existence of the user variable. And if that is defined, then we'll send back the user. Otherwise, we'll send back a status of 404 to say, sorry, but we did not find someone with that ID. Okay, so let's save this. I'll go back over to my built-in editor. I'm going to copy our post right there. I'm going to put some hashes underneath it and then paste that post. And we'll just make a couple of updates to this thing. I'm going to change it to a put. I'm going to try to update a user with an ID of 1. And I'm going to update their username. I think user with ID 1 is Allison14. So I'm going to change it to Allison156. And I will give Allison a new bio as well of Allison, I am Allison. How about that? So I'm going to send that request. Okay, looks like we've got the new bio and the new username. Let's verify that by sending our request to get a list of all users. So I'll go back up to this very top one. I'll send that request. And it looks like right there, yep, there we go. I am Allison, Allison156. Okay, so that is our update statement. Now just one more we'll take care of rather quickly in the next video around deletion. All right, our last route handler. So let's get to it. All we have to do is handle a delete. The code for this is going to look very similar to the put we just did right here, almost identical in nature. So let's just get right to it. We're going to first pull out the ID from rec.params. We'll then try to find a user and delete it. Now, when we find a user and delete it, as a convenience, we're also going to return the user who was deleted. So we're going to do an await user repo.delete and then pass in the ID. If we were not able to find a user to delete, then we can assume that user right here is going to be undefined. So once again, we'll say if user, then we will send back the user who was deleted. Otherwise, if we did not find a user, we'll send back a status of 404. Let's go to our user repo and implement that delete method. So here's delete. We will receive that ID. And then once again, very similar to what we just did for the update statement, we'll get some rows as a result of await pool.query. We want to run delete from users. And we only want to delete the users where the ID is equal to $1. So we'll again put in our substitution array, or the parameters array as we sometimes call it. So in this case, it'll have just one element inside of it, and that will be the ID. Oh, it looks like I'm forgetting a semicolon right there. I'm going to put it right in. Okay, so then once again, we can return to camel case rows, and we'll get the first element out of that array. Okay, so that looks good. So let's save this, and once again, we'll do a very quick test. So to test this, I'm going to copy the put that we just did, throw it down below. I'll do a delete this time. I'm going to try to delete the user with ID 1. There is not going to be any body for this request. I'm going to delete that, and we can go ahead and send the request itself. And it looks like I got an error. Do I not have a user with ID of 1? I think I might not. Let me do this once again. Let me send the overall request. Oh, okay. So I forgot the returning statement, unfortunately. So once again, just like even though I said very proudly when I was mentioning this just a moment ago, back inside of our user repo, I said that this delete is going to be very similar to the update. Well, yeah, it really is. So when we do the delete, we don't actually get any information about the users who were deleted back. So if we want to, we need to add on that returning star once again at the very end. So that's why I got back that 404 error. I got back a 404 because we did delete the user, but we didn't return anything from the query about the fact that the user was deleted. So we got back an empty set of rows. We eventually returned undefined, and our user's route right here for delete got back undefined, and so we fell into the send status of 404 case. My bad. So now that we've got the returning star statement on there, everything should work as expected. So let's once again try to run this request. We don't have a user with an ID of 1 anymore, but I do have a user with ID 2, I think. So I'll update it to that, send the request. There we go. So there's the user who was deleted. And now if I try to do a get all users, I should not see a user with an ID of 2. And I definitely don't. Okay, so that is pretty much it. We have put together a first initial version of this API using the repository pattern, where you and I wrote out all the SQL for it manually. So now we're going to start to write out a couple of tests around this API, because doing testing around a database is actually kind of an interesting little problem. You actually need to have more understanding of the database and how you're connecting to it than you might think. So we are going to learn a little bit more about Postgres itself when we do our testing setup. So let's take a pause right here and start to implement some automated testing in the next video. Our entire application is put together, and I'd say it's working fairly well. But I would really like to add in a couple of automated tests to our project just to make sure that it's working as expected at all times. Now, just so you know, to get through the coming videos, you really don't need to know very much about testing at all. Instead, the goal of all this discussion is really to learn about 2 additional features inside of Postgres itself. So again, really not a lot of testing stuff per se, really a lot more about Postgres. So let me show you the primary issue that we're going to run into. I want to be just really upfront and forward about what is going to be challenging here. All right. So we are going to eventually write a couple of different test files. In total, we're going to write out 3 files, and each of them is going to have some code inside that is going to try to execute some tests and make sure that our application is working as expected. To run these test files, we're going to be using a test runner called Jest. Jest is a program that's going to execute these 3 files all at the exact same time. This is a little bit atypical. A lot of other test runners out there in the JavaScript world try to run test files sequentially. So it will run all the tests in one file, then all the tests in another, and then all the tests in another. But in order to save a little bit of time while running tests, Jest runs tests in parallel. So that means that we're going to have code inside of test file number 1 running at the same time as test file 2, running at the same time as test file number 3. Now here is the big challenge. Here's what we're going to have to figure out, and this is where we're going to have to do a little bit deeper dive into some internals of Postgres to really solve this problem. All 3 of these test files are going to be trying to work with the same exact database. They're all going to be connecting to our social networking database and making changes to data inside there. We can very easily get into scenarios where these 3 different test files have little conflicts going on between them, just because of the nature of how we write out tests. So there might be some scenario where test file 1 might try to create a user, and then maybe try to get the most recent user that was created out of the users table. And that might be part of a very normal test. Create a user, get the most recently created user, make sure that user has some certain attributes. If test file 1 creates a user, and then in the very next microsecond, test file number 3 creates a user as well, we could potentially break that test inside of test file number 1. So in other words, because these tests are being executed in parallel, they might interfere with each other and cause some tests to fail erroneously. And that's what we need to solve. So this is going to be a good little bit of fun. Like I said, you really don't need to know a lot about testing to do this. We're going to write a rather small amount of testing code overall, and it's really a lot more about understanding Postgres. So let's take a pause right here and then start to implement this testing setup in the next video. All right, my friends, let's get to it. Let's start to write out a couple of tests. Inside of my src directory, I'm going to make a new folder called test. Inside of there, I'm going to create a directory called routes. And then inside of that new folder, I'm going to make a file called users.test.js. So the goal of this file right here is to test some code that we wrote out inside of our users route file. We're going to eventually be making a couple of different requests and just verifying that a user is fetched correctly, created correctly, or whatever else. Again, at the end of the day, we don't really care about the test we're writing here quite so much. So inside of this users.test.js file, we're going to write out our first test rather quickly. We are going to require in one module at the very top. We're going to get request from supertest. This is a module that we installed at the very start of our project. It is all about helping you test an Express application. We are also going to require in the app.js file. Remember, inside that app.js file, we exported a function to build a copy of our Express app, wire up some stuff, and then return it. So I'm going to get app from require up one directory, up another directory, app. Now just to avoid any possible naming conflicts, we might want to call this thing, rather than app, because it's not really an app, it's actually a function to create an app, we might call it build app instead. Not required, just maybe a little bit better. Okay, so then after that, we will just go ahead and directly define our first test. So for our very first test, I'm going to say that we can create a user. That's what I want to test first. This autocomplete is giving me a really tough time today. Okay, there we go. So now to test out our application, we're going to use this build app function to build a copy of our Express app. We're then going to pass that app off to this request thing right here. This request thing is then going to allow us to make some kind of imaginary or fake request to the Express application and just test out how it behaves. So we are going to do a await request. We're going to pass in the result of build app. We're then going to try to make a post request to the endpoint of /users. We're going to send along some information about a user that we want to create. So I'm going to try to create a user with the username of test user and a bio of test bio. I'm then going to expect that the result of this request is a 200, like so. Technically, it should be a 201, but doesn't really matter. All right, so that's going to go ahead and make the request, make sure that we get back a 200. Now, to make sure that we really, truly created a user, we might also write a little follow-up test inside of here. We might try to, say, reach into our users table using our user repo, fetch some particular user, and just say, hey, this person actually exists, or what have you. Another very common pattern that you might see in some applications is to make an assertion at the very top about the number of users that we have at the start of our test, run this request, and then take the count of users inside of our table once again, and just make sure that the number of users increased by 1. So there's a lot of different approaches for this. Let's take a very simple and basic, straightforward approach and make sure that we start off with maybe 0 users inside of our user table, and then after running this request, we should have a total of 1 user. So for that, up here, we're going to need to make use of our user repo, and we're going to need to use the user repo to get a count of all of our users. We don't really have that functionality just yet, so let's go add it into our user repo very quickly. Inside the user repo.js file, I'll go down to the very bottom. Down here, I'm going to do a static async. We will just call it count because it's going to give us the count of users inside of that user table. And then we'll do a const rows is await query or pool.query. And we want to run a query of select count star from users. That's pretty much it. Now in the result that we get back right here, this rows in this case, because we are getting a count as opposed to some kind of record or row or something like that, just so you know, the result of rows right here is going to look like this. It's going to be something like count is whatever our count is. That's going to be what the rows object looks like in this case. So if we want to return really just the number by itself, we would return rows at 0.count, like so. So I think that this would definitely work out for our test code. So I'm going to save this. I'll close the user repo file. Back inside of our test file at the very top, I'm going to require in our user repo because we now definitely need it. We'll go up one directory, up another, I think. Yep, repos, user repo. So then at the very top, we can do a const users, or how about const starting count? Maybe that's more descriptive. That will be an await user repo.count. We can then maybe just do a starting assertion and say, you know what, our test is going to start out with 0 users. Because in theory, that's what we want to have, right? We are, in theory, inside of some kind of clean testing environment. And we want to start off with 0 users inside of our table. So I'm going to expect that starting count is going to equal 0. Then we will do our request and repeat that same process afterwards. So we'll say finish count is user repo.count. And I will expect that finish count is going to equal the number 1. That's how many users we should have after making that request. Okay, so this test right here might look a little bit atypical from a testing perspective. If you have a background in testing, you might look at this and say, Steven, this is a ridiculous test that we would never, ever write. Well, it turns out that people do write tests like this. It is a very low-level test that just says, you know what, we can make a request. Something is changed inside the database. It is not outside the realm of possibility of writing something like this. And even if you were not to write a test like this, at the end of the day, we're kind of writing this test just to prove a point here, so to speak. I just want to show you very clearly that when we start writing tests or running tests in parallel, we can get into a lot of trouble really quickly. All right, so now that we've got our first test put together, take a quick pause right here. We're going to try to run this test, and naturally, we're going to start to see a lot of big problems start to crop up. So quick pause, and we will run this in just a moment. We've got an initial test file put together, and to be honest with you, a lot of the code inside of here looks pretty reasonable. If I ran these tests, I would kind of assume that they would work as expected. Naturally, that is not what is going to happen. We're going to start to try to run these tests, and we're going to start to see a whole barrel of different errors. So we're going to spend the next couple of videos just doing a lot of troubleshooting to figure out how to get these tests running as expected. I apologize in advance that these videos are going to be painful, The reason that I'm showing you all this kind of painful stuff, rather than just having you put the solution directly in, is that I can just about guarantee you will run into these issues on your own projects as well. So better for you to see all these problems inside of a course where I can give you really nice solutions and explanations immediately, as opposed to you having to troubleshoot all this stuff on your own. Okay, so that out of the way, let's try to run our tests and see what happens. To run our tests, we're going to first open up our package.json file. We will find our script section, and I'm going to add in a new script here of test. Whenever we run the test script, we're going to execute the command jest, which will find all the different test files inside of our project and automatically execute them. So I'm going to save that file and close it. I'm then going to go over to my terminal. I'm going to stop my running server, and I will execute npm run test. Okay, so it looks like it's starting up. Looks like we are running some tests, and sure enough, we end up getting an error really quickly. So here's our first error. So it looks like this error is coming from our pool.js file. Let's open up that file right away and try to figure out what is going on. So I'll find pool.js. The error that we got was coming from this line right here. It said cannot read property query of null. So that is implying that this dot_pool is being evaluated to null. That's why we were seeing the error that we just saw. So why would that happen? Well, remember, this dot_pool only gets defined, or reassigned from null, I should say, whenever we call connect. Right now, this connect function is only being executed inside of our index.js file. So here's index.js. This is the file that we'd run to start up our entire application in development mode. When we run our tests, this file does not get executed. So in our test suite or in our test environment, we are never telling our pool to connect to anything at all. So we probably have to fix this up somehow. To fix this up, we can go back over to our users test.js file, and we can add in what is called a before all statement. A before all statement is going to take a function. That function will then be executed, and we're going to wait for that function to be executed before we run any of the tests inside this file. So we could use this before all function right here as a very convenient location to set up a connection to our database and just make sure that we are actually connected to it. So to connect to our database, let's require in our pool as well. And then inside of here, I'm going to return pool.connect, and then we'll provide some connection settings to that function. For right now, we'll just use the exact same connection settings that we put into our index.js file. So I will take these exact same settings, I'm going to copy them, and then paste them inside of pool connect right here. Whenever we call pool.connect, it's going to return a promise that resolves after we successfully connect to that database and run that initial select 1+1 query that you might recall. Because we are returning a promise right here, Jest is going to wait for that promise to be resolved before starting to run any tests. So in theory, this code should work pretty well. Let's save this, back over to our terminal, and we're going to run npm run test once again. Okay, so here we go. And, well, it looks like stuff started to run, but it looks like we ended up with a failed test. In this case, we tried to run the test, create a user. We got that starting count. We then expected that the starting count would equal 0. But instead of getting a value of 0, which is what we expected, we instead got a string of 1. So it looks like this initial expectation right here is not quite working as expected. There's one other little issue inside of here as well. At the very bottom, we've got a little warning message. It says, Jest did not exit 1 second after the test run has completed. That pretty much means that after running all the tests, our code did not naturally quit as it should. So we are now kind of stuck here in a pending state inside of our terminal, and we can't really do anything at all until we press Control-C to get kicked back to the command line. So it looks like at this point, we've got two distinct issues. Number one, we were expecting to see 0 users inside of our user table. Didn't work. Number two, after running our tests, our program kept on running. So let's do a little bit more troubleshooting in the next video. In this video, we're going to very quickly troubleshoot this little warning message down here and figure out why our test suite did not naturally exit. So for this, luckily, there's a very easy solution. Remember, inside of our test file right now, we are setting up a connection to our database. Whenever we open up a connection, we're essentially saying, hey, e.g., make a connection to the Postgres database and just hold that connection open. As long as the PG module is holding open a connection to Postgres, our program is never going to naturally exit. It's only if we tell our pool to actually disconnect from that database that we can exit naturally from our program, because essentially our node program no longer has any work for it to do. It doesn't have an open connection, it has no other task queued up, so it says, well, I've ran out of things to do, I'm just going to naturally exit. So to make sure that we sever our connection, or we might say that we would close our connection to Postgres, you might recall that inside of our pool.js file, we had defined a method called close. When we call close, that is going to terminate our pool, or essentially disconnect all of our clients from Postgres. So this close function is exactly, or this error that we're getting is exactly why we added in this close function earlier. So to fix this little issue back inside of our test file, I'm going to define an after all function. As you might guess, this function is going to be invoked after all of our different tests inside this file have been executed. And then inside of here, we will return pool dot, what do we call it? Was it end? Nope, close. Pool.close. So this says after running all tests, disconnect from Postgres, that's going to return a promise. And once again, Jest is going to wait for that promise to be resolved before moving on from this step. Because we are disconnecting from our Postgres instance, now Jest can say, oh, looks like our program is no longer doing anything. Let's just naturally exit. Okay, let's save this. Go back over to our terminal. I'm going to again do a Control-C and then run my test once again. Of course, we're still going to get a failed test, but now notice that we get kicked back naturally to our terminal, which is definitely what we want in this scenario. Now, this might seem like a very small thing, but it turns out that stuff like this starts to get really important if you ever start to wire up your test suite to a CI pipeline, or essentially some kind of pipeline that's going to automatically run your tests for you. A lot of pipelines like that are going to run your tests and expect them to naturally exit after some period. So if you ever have a test suite that does not naturally exit at some point in time, your tests are just going to be forever pending. So this is definitely an important improvement to have in place. Now that we've got this fixed up, another quick pause, and we'll start to troubleshoot this other issue in just a moment. The next thing we're going to troubleshoot is the failing test. So once again, we've got a test here that is expecting that we start out with 0 users, but instead we ended up with 1 user inside of our database. So let's figure out why that is. All right, so quick little diagram right here. So right now we have Postgres running on your computer, and inside there we've got a database called social networking. Right now we are trying to execute our application in 2 different modes, either in development mode, which is where we are trying to essentially run our application as usual, and then try to access it from Postman or that built-in API client. We are also trying to execute our application in test mode. So that's when we try to run our app and do some automated tests using Jest. Right now, our application in both modes is connecting to this exact same database. So when we start up our application in test mode, we're connecting to our existing social networking database. We are then trying to get a count inside that test that is failing of all the users inside of our users table. And naturally, right now that table has 1 user inside of it. So our tests are failing because we are connecting to a database that we are using for development purposes. Now, there's a couple of different ways we could solve this. We could say that whenever we are about to start up our tests, maybe inside of some kind of before all statement, like right here, we could try to take a look at all of our different tables and delete all the data inside them, or something like that. But that would be a pretty bad approach, because that means that as we are naturally testing our application and doing development, we might be creating users just to make sure that everything works as expected, and then all of a sudden, whenever we run our tests, we would dump all of our data. That's very inconvenient, and we definitely would not want to do something like that. So instead, we're going to take a much more straightforward solution. We're going to instead just create a second database. So our application will continue in development mode to connect to our primary social networking database. And whenever we launch our application in test mode, or essentially through Jest, we're going to instead have it connect to a totally different database that we'll just call something like social networking-test. That database name makes it really clear that this is a test database, and it might have some data inside of it that's going to get deleted very frequently at some particular time. So I think this is a pretty reasonable solution. So let's go over to pgadmin. We will manually create a new database called social networking-test. We'll then update our application to connect to that database inside of test mode. So back inside of pgadmin, I will create a new database. I will call it social networking-test. Okay, there's our database. Oh, I call that social networking. It should be just social network. Let me just recreate that really quickly. So social network-test. That's better. Okay, so there's our database right there. Now we can go back to our test suite and tell it to connect to this database instead. Inside of our users.test.js file, we've got the before all statement where we are connecting to our database for specifically running our tests. So we'll just change the name of the database right there. We'll say instead of connecting to social network, connect to social network-test, like so. Okay, so that should be it. So now we are connecting to a totally different database, which in theory should start off nice and clean, nice and empty. And so when we get this initial starting count, we should definitely have 0 users inside of our user table. So let's go back over to our terminal once again and see how we're doing. Back over here, I'll do an npm run test. And I bet you can guess what's going to happen. Yep, we get a nasty error. So in this case, the error says relation users does not exist. So we saw that error a little bit ago when we were talking about SQL injection exploits. This error right here means that there is no users table. Well, okay, this one's kind of a gimme. I bet you can understand why this is. We just created a database and we didn't actually run any migrations or inside of it. We didn't manually create any tables or anything like that. So even though now our test suite can connect to this database, it doesn't have our expected structure inside of it. So we need to make sure that at least one time, perhaps, we run all of our migrations inside there. All right, let's take a quick pause, execute those migrations inside of that database in the next video, and then move on to our next issue. Let's try running all of our migrations against the social network-test database and then try running our tests again. So to do the migration, we'll go back over to our terminal and run that same kind of long command once again. But this time around, we'll make sure that we change the database name from social network to social network-test instead. So we'll run that, and there we go. We have created the users table inside of our test database. Now let's try to run our tests once again, because now our tests are going to be running against an empty database that does have the correct structure inside of it. So we will do another npm run test. We are going to see a very small error here that's not really relevant. It was just one little step that I kind of forgot when we were writing out a little bit of code. So in this case, we are comparing the result of that count query to 0. And the result of the count query came back as 0 inside of a string. That was my mistake. Whenever we got that count back, it comes back as a string. We just need to parse an integer out of it. So let's go back to our user repo very quickly and make that change. So inside of my user repo, I will find the count function we added just a little bit ago, and we will wrap that count in a parse int. So it's just going to take that string and pull an integer out. Okay, so I'll save that, and we'll go and run our tests again. Hey, there we go. That's what I like to see. Finally, our test passed. So this is great. It's a good step forward. But you know what? Just out of an abundance of caution, let's try running our tests again and just make sure they pass a second time. So I'm going to run my tests again. And uh-oh, they failed this time. Well, that's kind of strange. Let's try running them again. If we run the tests again, it looks like they are still failing. So what's going on here? Well, this time around, you might be able to guess what is happening. The very first time that we ran our test successfully and we got that one test passing, that meant that we took our count. It was in fact 0. We then created a brand new user and saved them into our users table. We then took our count again, and at that point in time, there was in fact one user inside of our users table. We then tried to run our tests again after that. But between the first run of our test suite and the second run, we never deleted that user that we had created inside of our users table. So we still had some leftover data inside the users table from a previous run of our tests. So the second time we tried to run our tests, we once again took the starting count, but at that point in time, there was one user. The one user that had been created during the previous run. And so, of course, this test right here failed. So what are we going to do now? Well, there's a couple of different things we can do. First, we can make the assumption that maybe our database isn't completely empty and clean for every single test. That's what this block right here is really doing, or specifically this expectation. It's really making the assumption that our entire users table 100% is empty, no rows inside of it whatsoever, when this test is executed. We could say, you know what, maybe that's not a hard requirement. So we could just delete that line and take a starting count. And then later on, when we get our finish count, rather than expecting finish count to equal 1, we could take a look at finish count minus starting count and expect that to equal 1. So this is going to just say, you know what, during this small period of time right here, we had some starting initial count of users. We created one user, we took in a new count, and the difference between the starting and the finish should equal 1. So this style of test will allow us to run against a database that already has some rows inside of it. Let's try saving this, going back over, and running our test again. Hey, now it's passing. And we can run this test as many times as we want. So it looks like assuming that our database is not empty and that there might be some other existing rows inside of it is a better assumption to make. But maybe that assumption is not really going to stand the test of time. Maybe there are going to be some other issues we run into that's going to make this entire situation a little bit more tricky. So at this point in time, let's just say, you know what, it looks like we've got something that works. At the end of the day, it works, right? Where our tests are running, we can create a user and verify that the user is created. So now we're going to start to create some additional test files. So these are going to be some additional test files. Remember, when we are making use of jest, additional test files are executed in parallel. So we're going to be executing test file 1, 2, and 3 all at the exact same time. So let's start to duplicate some test files or create some other ones. We're going to run them all in parallel and then see what happens then. Our one test is now working perfectly. So now we're going to start to duplicate this test file. We're going to duplicate it twice. Then we're going to run all 3 test files at the exact same time. And we're going to start to see that we get back some, well, interesting results. Before we duplicate this test file, however, we're going to open our package.json file. We'll find our test command. And then right after jest, I'm going to add in --no--cache, like so. The reason we are adding in this option right here is just to make sure that jest is going to run all 3 of our different test files in parallel. There are some scenarios where jest will decide to run each file sequentially, or essentially one at a time. And that's not what you and I really want in this case. We want to force jest to run everything in parallel because it is going to more closely simulate how you would really run tests in a rather large project. Okay, so let's save that. I'm then going to find my test directory. I'll find the routes folder. And then there is our users.test.js file. So again, we're going to duplicate that file 2 times. I'm going to copy it and then paste it into routes once and again. I'll then rename the copies. I'm going to rename the first one to users-2.test.js and then users-3.test.js. Make sure that the file extension on all 3 of these files right now is test.js, so .test.js. All right, so now we've got the same exact test duplicated 3 times. And we can imagine that we're going to run this test right here 3 times at the same time. So let's go back over to our terminal, run this, and just see what happens. Okay, so back at my terminal, I'll do an npm run test. And sure enough, they all failed. Now, you may not see a failure immediately. You might only see 2 failures. You might only see 1 failure. You might see all 3. Essentially, it's kind of random what result you get. If I rerun my test again, I might only see 2 failing. Yep, okay, that's actually totally by chance right there. I now have 2 failing. If I do it again, I might be back to 3. I might be down to 1. Who knows? But you can tell right away that we're now starting to get some really unpredictable results. The first thing we have to do is figure out why this is. Why are we starting to see some tests fail? Well, let's take a look at a quick diagram. Here we go. Okay. So we had written out a test file that looked like this right here. So this is the first test file that we started off with. Inside there, we got the current count of users. We then created a user. We got a new count. We took the new value of count, subtracted the old, and we were expecting that to be exactly equal to 1. So this is when we just had one test file by itself. But we now are starting to add in multiple different test files. So we can imagine that the same exact operation is really occurring 3 times in a row. If we ran all of our different test files sequentially, or essentially one at a time, we would be in this kind of scenario. We would get our initial count, create a user, get a new count, make sure that the difference is 1. We'd then get the current count, create a new user, blah, 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 and so on. So if we were running all of our test files sequentially, all of our tests would probably work as we expect. But as soon as we start to run them at the same time, we start to get some overlapping operations, like what you see right here. So in the current scenario we are in, let's kind of imagine these 2 and 3 files over here. We can imagine that we are first getting the count, and then in parallel, at just about the same instance, over in the third test file, we're getting the count over there as well. So maybe the initial count right here is, say, 1 user. And at the same exact time over here, it is 1 user as well. Then in both test files, at essentially the same time, we create a new user. So now, in theory, there are 3 users inside the database. So then when we get back down here to our actual assertion, we do a check and we try to see if 3 minus the 1 that we got during the initial step right there. So is 3 minus 1 equal to 1? Well, no, that's actually equal to 2. So it's all coming down to the fact that we are getting the count at probably the same exact time between these multiple different files, then creating users at more or less the exact same time, and then trying to get some count as well. So you can start to see that, well, yeah, we're going to get some really unpredictable results when we start to run these test files in parallel. So I think it's pretty clear that we need to figure out some way to deal with this. Let's take a pause right here and try to think of some strategy to handle this and make sure that each of our different test files can essentially run in its own little isolated environment. At this point in time, I think it's pretty clear that when we try to run our 3 different test files in parallel, or essentially at the same time, they are all trying to access the same users table inside of our social network-test database. And because these different test files are accessing the same exact table, we start to get some conflicts really quickly, and we start to get some mysterious test failures. So we need to figure out some way to work around this. We need to make sure we can run all of our tests in parallel still, without any kind of conflict between these different test files. So let's take a look at 2 possible solutions for doing that. The first possible solution, we could make sure that every single test file gets its own database. So for this, we could say, hey, we've got 3 different test files. Before we ever run our tests, maybe we go into our database or our Postgres instance locally and create 3 separate test databases. So A, B, and C. Then inside of our code editor, where we tell inside of our test file to connect to some particular database, we could say for this first test file, connect to social network-test-A, and then the next file could be B, and the last file could be C. So we would be making updates to these pool.connect statements inside of each different test file. Now, the upside to this is that each different test file would have its own independent copy of a database. So each one would have its own users table to work with, and each test file can make as many changes to that users table as it wishes. And we would not have any conflict between these different test files. The downside to this approach, however, is that if we have many different test files, we would have to create many different test databases inside of our local Postgres instance. And that would get really tedious really quickly. That would mean that every single time we create a new test file, we would also have to go off to pgadmin, create a new database, and then run some schema migration inside of it to set up our users table. So option number 1 is definitely feasible, but, well, there's definitely a big downside to it. So we're going to go with a second option, option number 2. Option number 2 is kind of in theory very similar, but it's going to get some isolation between our different test files by using a little bit more complex mechanism inside of Postgres. So we're going to make sure that every test file gets its own schema. So the obvious question that comes up right away is, what is a schema? Well, a schema you can think of, a little quick side note here, you can think of a schema as being very similar to a folder on your hard drive. So on your hard drive or on your local file system, you have a folder or a number of different folders to organize different files. You could think of schemas as being very similar in nature. We can create multiple schemas inside of one single database and then use these different schemas to organize our different tables, indexes, and all the other kind of objects we might create inside of our database. Whenever you create a database, by default, it gets one schema created called the public schema. And you can actually see that very easily inside of pgadmin right now. If you go back over to pgadmin and take a look at our social network test database, and you can find schemas right there, you'll see that we've got public right now. So we are currently working out of the public schema. And the nice thing about creating these schemas is that every single schema can have its own separate copy of a given table. So each of these different schemas that we might create, schema A, B, and C, can have its own users table. We can then tell each of our different test files, so our first test file, the second one, and the third one, which schema it should connect to. So for the first test file, we could say, hey, you need to connect to schema A and make use of the users table inside there. For the second one, connect to schema B and schema C. We essentially get that same kind of isolation that we have with multiple databases, but rather than creating multiple databases, we are creating separate folders inside of one single database. Let's take a pause right here, digest this a little bit, and go into more detail in the next video. Let's have a little bit more side discussion on schemas and understand how they really work behind the scenes. To do so, we're going to start to run a couple of different commands inside of pgadmin to create a schema and then create a table or two inside of it. Let me show you what I eventually want to do. I want to create a new schema inside of our social network-test database called test. And then inside there, we're going to create another users table. This users table is just going to have one or two columns inside of it, maybe just an ID and a username. So ultimately, we're going to have two schemas, and we're going to have two very similar tables. We're then going to run a couple of different commands and figure out how we can access objects, such as a table, inside of one schema or another. So to get started, I'm going to go back over to pgadmin. I'm going to make sure I'm connected to my social network-test database, and then I will open up a query tool inside there. So the first thing we will do is create that new schema. To do so, very simple, very straightforward. We just write out create schema, and then the name of our schema, which in this case will be simply test. So I'm going to run that, and that's pretty much it. We can now see the new schema on the left-hand nav if I right-click on schemas, click on refresh, and now there's my public, and down here towards the bottom, there's test. So I now have two different schemas. So now that we've created this test schema, I want to try to create a users table inside of it. There's just going to be one little difference here compared to how we normally create a table. All we have to do when we create this users table is be very explicit and very clear that we want to create this new table inside the test schema instead of the default public schema. So let me show you how we do that. We'll do a very normal create table, and then rather than just writing the name of the table by itself, I'm going to first write out the name of the schema that we want to create this table in. So in this case, I want to create the table inside the test schema. I'll then put a dot, and then the actual name of the table that I want to create. So users. So this means I want to create a new table inside of the test schema, and I want its name to be users. So now inside of here, as usual, we can define a couple of different columns. I'll give it an ID and just a username. So I'm going to run that, and the table has been created. So now if I go down to my test schema and expand tables, or refresh it if you've already opened it, you should now see the users table that we just created inside there. If you leave off the test dot right there, so if you don't include it at all, then by default, Postgres is going to try to create a table inside of the public schema. So if we run this like that right now, we're going to get an error message because we already have a users table inside of our public schema that already exists. Let's now also try to take a look at creating or inserting new rows into a table inside of a schema as well. So let's try to insert maybe just one or two users into the users table inside the test schema. To do so, we'll do an insert into, then once again, we'll put down test.users. So that means we want to insert some new rows into the users table in the test schema. So I bet you're starting to notice a pattern here. Whenever we make use of a schema, if you want to specify some schema to access, right before it a reference to a table or a index or anything else that belongs inside that schema, we'll just write the name of the schema and then a dot. That's pretty much it. If you leave off that thing entirely, that means just by default, use the default schema. So I'll do an insert into test.users. I want to provide just a username. And I'll put in, how about just Alex and whatever, just some gibberish. So I'll run that. And now if we open up or right-click inside of our test schema, tables, users, I'll right-click that, go to View, Edit Data, look at all rows, and now inside there, I can see very easily I've got Alex and whoever's else name that is. If we want to revert back to adding in some users into our public schema, or the default one, then all we have to do is take off that test dot. And that would add some users into our public schema instead. So finally, one last quick example here. If we do a select star from users by itself, that will give us all the users inside of our public schema. So if I run that, I'll see the results from our public schema users table. And if we do a test.users, once again, that's going to show us the results from the users table inside of our test schema instead. Okay, so at this point, all we've really covered is how we can create a new schema, how we can create some objects inside of it, and then run some queries against those objects. So all we really have to do in general, whenever we refer to a table or anything like that, put the name of the schema right in front of it. And that's pretty much it. So now that we've got that kind of baseline understanding of schemas, let's start to expand upon this a little bit more in the next video. In the last video, we made it really crystal clear that if we ever want to access a table inside of another schema besides public, we put the name of the schema, then a dot, and then the object or the table that we're trying to access. So at this point, that is crystal clear. It turns out that we can actually modify that behavior a little bit. We can change which schema Postgres is going to try to access by default. Let's take a look at a diagram or two and understand what I mean by that. Okay. So right now we have our schema public and our schema test, and they both have a users table. So I want to imagine what really goes on behind the scenes whenever we run a statement like this right here, select star from users. When you run a statement like that, Postgres is going to first start to say, hey, wait a minute, we've got more than one schema inside this database, and each of these different schemas might have a users table. So Postgres has to make a decision about which schema to use when it tries to execute this command, if we do not specifically specify a schema in there. And in this case, we did not. So rather than just always 100% of the time defaulting to using the schema of public, as I kind of made it sound like in the last video, it turns out that we can actually customize how this question gets answered by Postgres. We can customize which schema gets accessed if we do not specifically designate it when we write out our statement. So to do so, Postgres uses a little setting internally called the search path. The search path controls which schema Postgres is going to access by default if we do not specifically designate it inside of our query. We can print out this search path variable very easily over inside of pgadmin. But let's do it right now. Back over here, we're going to do a show search_path. So you'll notice that it says $user and then public. Let's ignore the $user for just a moment. So ignoring that little variable or that little part of the string right there, focusing just on public, that means that if we ever run some kind of query or some kind of statement, and we mention a table without designating a specific schema, then Postgres is going to default to trying to find that object inside the public schema. So that's what this search path really means. So what does the $user, what is that talking about? Well, remember, whenever you connect to your Postgres instance, you're connecting as a specific user. So if you are on Windows, chances are you are connecting with the username of Postgres. And if you are on macOS, you are connecting probably with the username of whatever your username is on your local machine. In other words, I'm really talking about inside of our test file, the user right there. So whenever you connect to Postgres, you're connecting with a very specific username. In my case, it is simply SG. The $user right here means that if we have a schema inside of our database with the exact same name as the user that we are logged in with, then we should try to access that schema first. So in other words, taking my example of having a user of SG, if I ran a command like this right here, or a statement like that right there, that means first, if we have a schema called SG, let's imagine this one is called SG, then we should prefer to try to find the users table inside of schema SG. So that's what the $user is really talking about. It is just making sure that if there's a schema named after yourself, let's prefer and try to use objects inside that schema before accessing public. Now, it might seem like I'm going into a lot of detail on what this $user means, but it turns out that's actually going to be a very relevant setting for us very quickly. Let's now try to play around with search path just a little bit. We're going to change our search path manually so that rather than always defaulting to looking for a schema named after ourselves and then public, let's first instead try to get Postgres to prefer to connect to the test schema whenever we do not otherwise specify a schema to use. So to do so, I'm going to update my search path. I'll do a set search path to test and then public. So I'm going to run that. I'm going to comment that out because we're going to undo that setting here very quickly. I ask you, please watch this video to the end because we are going to undo that command we just issued here in just a moment. So now if we do a select star from users, rather than defaulting to finding the users table inside of our public schema, we're going to first try to find the users table inside the test schema first. So I'm going to run that, and now we see results from our test schema instead. Okay, so that is the search path. It controls which schema we're going to find an object in if we do not otherwise designate it inside of our SQL statement. Naturally, if we want to, we can still designate which schema to use. So if I put in public users, that means go into the public schema, find the users table there. So if I run that, I get results from the public table, or excuse me, the public schema. Okay, so that is the search path setting. So now we're going to undo that change here very quickly. So we're going to do a set search path to double quotes $user, like so. That reverts our search path to the default setting. Okay, so now that we understand how schemas are searched by Postgres, it all comes down to this search path setting. Let's now start to take all this knowledge around schemas and whatnot and put it together in the next video to really understand how we're going to make sure that all of our different test files somehow connect or use a different schema. We've now got some fundamental knowledge around schemas. Now that we've got that all under our belt, we're going to go back to our test setup and figure out how to make sure that every test file is somehow isolated from our other tests. Now, I got to tell you right away that there's going to be a little bit of complex code and understanding that's going to be needed to really put this stuff together. So I want to first outline a really big issue that we're going to run into as we start to try to tell each of our different test files to use our different schema. Okay, so I'm inside my users test.js file right now. I'm going to scroll down to the test we have written inside of here. So remember, inside of this test file, we've got a userrepo.count and a userrepo.count. So we are trying to get the count out of our user table at some point in time. Let's go take a look at the user repo implementation really quick and just take a look at what that count method really does. So inside of our src repos folder, I'll find user repo. Here it is right here. I'll then go down to the very bottom. And there's our count method right there. Remember, our count function is going to run select count star from users. So when we run this query right here, we did not designate some schema to make use of. So by default, we're going to use either the schema that is named after the current user connected to the database. So in my case, it would be SG. For you, it might be Postgres or whatever your username is. And if that doesn't exist, then it's going to fall back to using the schema of public. So right now, for all of our different test files, when they run that query or this userrepo.count, here's what's going to go on behind the scenes. So we've got user test file right here. It's going to run that statement, send it off to the database. And because we did not designate some schema, we were not specific, even if we have some other schemas available for these test files to connect to, this query by default is going to be executed against our public schema. And that's true of all of our different test files. Because we were not specific, because we did not designate which schema to use, they're all going to fall back to using the public schema. And so that makes we didn't gain anything here by creating some additional schemas. We still have all of our different test files still trying to access the users table or the same users table, and so we're still going to run into these exact same conflicts. So by just creating these schemas, we're not really doing anything. We need to somehow make sure that all the different queries that are somehow being executed from this test file, and this test file are being executed against some different schemas so that we get that isolation we are looking for. Turns out that is actually rather hard to do. How do we somehow tell this test file to use this schema, this one to use this schema, and so on? if you tried to take a kind of a naive approach here, you might say, okay, Stephen, well, we can do this. Maybe we can say that whenever we call user repo.count, we will pass in the name of the schema to use. So maybe I want to use schema A, or how about like test schema A or something like that. And then inside of our user repo, maybe we could somehow accept that as an argument to count, and then somehow just reference that inside of our query itself. We can do some string interpolation or something like that and put in schema dot, like so. Yeah, this could technically work. You could definitely do this, but this would get really tedious really quickly to always have to worry about which schema we are somehow running this query against. So there's got to be a better solution here. I'm going to undo all of those changes very quickly. That was just a quick example. So that is definitely a naive way we could approach this, but definitely not ideal. There's got to be a somehow better way of doing this. So naturally, there is. Let's take a pause right here and take a look at the strategy that we're going to use to make sure that each of our different test files are going to run all of its queries against different schemas without having to modify the queries themselves. So how are we going to make sure that each test file somehow uses a very specific and unique schema? Well, in this video, I'm going to show you exactly how we're going to do that. Now, just so you know, the steps I'm going to explain here are going to sound really complex and confusing, but it all boils down to just a couple of lines of code. And even if it is confusing, remember what I said at the start of this application? The whole goal was to show you some really complicated setup in a course where I can answer all of your questions very easily, as opposed to you having to discover all this stuff on your own. So, how are we going to make sure that each test file connects to its own distinct and unique schema? All right, here we go. So we've got a series of steps we're going to go through on the left-hand side. Let's walk through these one by one. The first thing we're going to do for each test file, we're going to connect to our Postgres instance as normal. So in other words, we're going to connect as our current user. So again, on Windows, that's as your current user of Postgres. And on Mac OS, you're going to connect as your current username of probably whatever your username is on your machine. After that, we're then going to generate a random string of characters. For this example, I'm going to imagine that I'm going to generate a random string of characters as ASDF. We're then going to create a new user, or what we refer to as a role, on our Postgres server. And we're going to name it after whatever string of characters we just generated in the previous step. So in this case, I would generate a new role of ASDF. After that, I'm then going to create a new schema with that same name of ASDF. So I've now got a schema called ASDF over here. And then finally, we're going to tell our test file to connect to our database with that same name of ASDF. Now remember, one of the rules around deciding which schema is going to be used whenever we start to execute a query, like this one right here. The first rule that is actually applied by default is not run against the public schema. Instead, the first rule is if there is a schema named after the exact same username that we are connected to the database as, then use that schema. So inside of our users test.js file, we're going to say we want to connect to Postgres as user ASDF. So now we have a connection to our Postgres database. It has a connection with a username of ASDF, which is identical to one of the schemas inside of our database. So whenever we write out a query like the one you see right here, and we do not specifically designate a schema to use, we're going to get that first default rule of checking to see if there's a schema named after the user we are connected as. So by default, rather than connecting to the public schema and running this query against it, the query is going to be instead executed against that schema, the one with the same exact name as we are connected to our database as. So that's how we're going to make sure that this user test file is going to run all of its different statements again against schema ASDF. We're then going to repeat this exact same process for all of our other test files as well. So maybe for the second file right here, maybe we generate a random string of characters as ZXCV. Then we'll create a new role or user with ZXCV. We'll create a new schema, and then make sure we tell our test file to connect to the database with that username. This will be connect to EG as user ZXCV. We'll have a schema ZXCV. And so inside of this test file, when we run some statement like this, that users reference right there will be automatically expanded to, behind the scenes, zxcv.users. In other words, look at the users table inside of that schema. And so we can start to see right away that we get this isolation between all of our different tests. They're all going to be taking a look at different schemas and executing all these queries against these different schemas. So that's pretty much it. That is our strategy. Now again, I want to repeat, I'm sure this sounds pretty confusing. You might especially be confused by this idea of connecting to Postgres as a specific user, especially since we've been talking about having a users table. The actual users table inside of our database is a different kind of user than what we're connecting to our Postgres database as. So I know there's still probably some big confusion here, but don't sweat it. We're going to walk through every step along the way and really understand what is going on. Okay, so let's take a pause right here and continue with this implementation in just a moment. Now that we understand our general flow, let's go back over to our users test.js file, and we're going to make sure that we write out all these steps right here before we start to run any tests inside that file. So we're going to write out a lot of code inside that file, and then eventually we're going to extract that and make use of it inside of our other two test files as well. Okay, so back inside my editor, I'm going to find the before all statement. So that's where we're going to do all this setup. I'm going to put in a couple of comments inside of here just to guide myself. And just so you know, we're going to do some of the steps, so we're going to write out some of the code in a slightly different order than the order that I showed you on the diagram back over here. So this order of steps, slightly different order, but at the end of the day, everything is just about identical. Okay, so we're going to first begin by randomly generating a role name to connect to PG as. That's going to be essentially our randomly generated username or role name that we're going to use to connect to our database. We're then going to connect to PG as usual. So in other words, using these existing credentials that we already have down here. We're then going to create a new role using the role name we generated up here. We'll then create a schema with the same name. After we've created the schema, we're then going to disconnect entirely from Postgres. And then one more step inside of here that I didn't show back inside the diagram, but as soon as I mention it, I think it'll make a lot of sense. We have to actually run our migrations inside of that schema. So whenever we create a schema, it starts off totally empty, no tables inside of it whatsoever. The tests inside this file and other files that we eventually put together are going to expect that things like our users table actually exists. So we need to make sure that all those schema migrations we had put together actually get executed. As a quick side note, the term schema migration and the kind of schema thing that we're working with right here, these are two very different kinds of schemas. They just happen to use the same name. So we're going to run our migrations in the new schema. And then finally, we're going to connect to PG as the newly created role. And because we are connecting under that role that has a name identical to the schema we had created earlier, all the following queries that we execute inside this test file, so any query that refers to any table whatsoever, they're always going to be kind of redirected to that newly created schema. Okay, so that's the general idea. Now, before we write out any code inside the before all, we're going to add in a couple of import statements at the very top. So I'm going to import a function called random bytes from crypto. I'm going to get default as migrate from node pg migrate. So that's the library that we're using to actually run our migrations. And then we're also going to get something called format from pg format. The random bytes function we're using to randomly generate a series of numbers and letters. So this is essentially going to be used to generate our role name. So let's get started with the random bytes function right away. So I'm going to make a new variable called role name. That will be random bytes. We'll pass in 4 and then do a toString of hex. So again, just giving us back a random string of numbers and letters. There's one little side note around this. Whenever we create a role inside of Postgres, it must always have a name associated with it that starts with a letter. Can't have a role name that starts with a number. This random bytes function is going to generate a random string of numbers and letters. And so there is a chance of this generating a string that starts with a number. And that would lead to an error inside of Postgres when we try to create a role using this role name. So to make sure that this string always starts off with a letter, we're just going to do something really simple here. We're just going to say take the letter A and then join on that random string right after it. So that's going to make sure that we always start off with a letter at the very start of our role name. Okay, so then after that, we're going to connect to Postgres as usual. That's going to be essentially the exact same thing we have down here. So I'm going to cut that and delete the return statement. I'll then paste that right underneath the comment. We'll make sure we put the await on there. And because we are now making use of the await keyword, I'll make sure that I mark the enclosing function as async. Next up, we're going to create our role. To create a role, we just run a very simple query. So we're going to do an await pool.query. And we will run create role. We're going to put in our role name with login password, role name. And around this second role name right here, I'm going to make sure that on the left-hand side and the right-hand side of that interpolation, I put in a set of single quotes. Very important to make sure you get those in there. So this is how we create a new role that we can use to connect to our database. Pretty simple and straightforward. Very similar to how we have a role such as whatever you have right here that you use to connect to the database as well. That's going to make a role with the given role name, and we can connect using that password. After that, we'll then create our schema. So we'll do an await pool.query, create schema, we'll put in role name, and we're going to also add in authorization with role name as well. That just makes it very clear that this role that we just created can access this schema that we're making. So in other words, make a schema, and we want this role that we just made to have access to it. Do double check and make sure you've got the spelling of authorization correct right there. As a quick side note, you'll notice that I'm doing some direct string interpolation for a query that we're about to send off to our database. And I told you earlier when we were talking about SQL injection exploits that we never want to have something that looks like this right here. In this case, we are running tests, so we're not working with any user-supplied data. So technically, no risk of SQL injection here. However, nonetheless, we will come back to this code in just a little bit and refactor it so we don't have this kind of string interpolation stuff, which can be very easily confused with having a weakness for SQL injection. So if you're worried about that exploit, we'll come back and fix this up in just a moment. Okay, so next up, we're going to disconnect entirely from Postgres. So that's going to be await pool.close. Remember, when we put our pool class together, we gave it a close method that we can use to disconnect from Postgres. Next up, we're going to make sure we run our migrations in that schema. And we're going to do so using this migrate function. So we're still using the same node pg migrate module to run our migrations. At this point, we have only used that module from the command line. This time around, we're going to run our migrations programmatically. So we run them programmatically by using this migrate function. So we'll do an await migrate. We're going to have to pass in a couple of different options. First, we're going to designate the schema that the migrations are going to be executed in. The name of our schema is role name. We're going to designate which direction we want to run our migrations. So remember, our migrations can be used to advance forward the design and structure of our database or roll it back. In this case, we want to advance forward. We want to apply all of our migrations. So we're going to go in the direction of up. We're going to put in log and provide it an empty function. Normally, whenever we run migrations, this migrate function generates a ton of log statements and dumps them out at the terminal. Because we are running tests here, we don't really care about any of these log statements. And if we printed out all these logs, it would make it really hard to interpret our test results. So we're just going to say don't do any logging whatsoever. By providing this empty function, the migrate library is going to try to call that function with all the log statements that are generated. So we're essentially saying just take this empty function, provide all the logs to it, but we're not going to actually do anything with them. Next up, we're going to provide a no lock of true. By default, we are supposed to only be running one set of migrations at a time. But because we are trying to run multiple different test files in parallel here, we might be in a scenario where we are trying to run multiple different migrations simultaneously. usually that would result in an error. So we're going to override that behavior by providing no lock true, which essentially means don't lock up the database when we are running these migrations. Next up, we'll provide dir, short for directory. This is going to be the folder inside of our project where all the migration files are stored. Our migration files are stored inside the migrations directory. We'll put in simply migrations like so. And then finally, we're going to specify how to connect to our database to actually run the migrations. So we're going to provide a database URL. We can provide some connection settings either as a string or an object. We're going to do an object. So inside of here, we're going to use the same exact host, port, and database from our earlier connect statement. But our user and password are going to be different because we're going to run these migrations under this newly created role that we made just a moment ago. So we're going to put into this database URL, the host, port, and database. Make sure on URL right there you have capital U, lowercase r, and L. And we'll provide the user as role name, and the password for that is role name. Then finally, after running our migrations, we're going to actually connect back to Postgres as the newly created role. So we'll do another await pool.connect. We will provide once again the same exact host, port, and database. And then our user will be role name, and our password will be role name. And that should be it. Okay, very long video here. I apologize for that. But let's run our tests very quickly, and we're going to really just hope that our user's test.js file passes all of its tests. But we still might have some failures inside of our other two test files. That's because they're still trying to contend over the user's table inside of our public schema. But the user's test.js file should be creating its own private schema now and running all the tests using that schema. So I'm going to make sure I save this file. I'll go back over to my terminal and do an npm run test. All right, so we might get two failures. Yep, looks like I got two here. But I should have at least one passing. And the passing test should be the user's test.js file. And it looks like it is. Well, I'd say this looks pretty good. Now that we've got some kind of early confirmation that this approach is going to work as expected, let's take a pause right here. We're then going to start to extract all this logic and make use of it inside of our other test files as well. Our test file is now working, but there's definitely some improvements we can make. So the first thing I want to take a look at are the two queries that we wrote right here to first create a role and then create a schema associated with it. So you'll notice that we are doing some direct string interpolation here. And I said earlier on inside the course that this is definitely something we do not want to do because it leads to SQL injection exploits. Now in this case, there's zero chance of us having any kind of SQL injection stuff going on here because we're not working with any user supplied data whatsoever. In addition, I would never expect to see these lines of code executed against a development or production database. These are solely related to test databases. Nonetheless, I totally understand if you don't want to have code that looks like this inside your project. So let's try to refactor this stuff. Now, one way we could refactor this, or one way you would think we could refactor it, is to use that same kind of parameterized query approach, where we put in, say, role name, and then replace our usages of those variables with $1 and $2. You would think that would work. And based on the way that I am saying this, as you guess, yeah, it turns out it actually doesn't work at all. Why is that? Well, just a little note here from the Node Postgres documentation, which is the library we're actually using here to run these queries. So it turns out we can only use this parameterized approach when we are trying to put in literal values into a query. So whenever we're trying to substitute in, say, some kind of where clause or something like that. But we cannot use this approach for injecting parameters that are supposed to be identifiers. And an example of an identifier is something that's going to be, say, the name of a schema, a table, a column name, etc. So we cannot use this parameterized style if we are trying to designate the name of a schema, the name of a role, and so on. So in other words, we cannot use this approach to substitute in the name of our role right there, or the name of our schema. If we still want to do some kind of SQL injection prevention, we can instead use a package called pg format, which is basically going to do a very similar thing to what you see here. So we already required in EG format at the very top, so we're going to use that to handle this SQL injection stuff. Okay. So I'm going to find the pool.query. I'm going to just go ahead and delete that entire thing, and we'll replace it with our escaped version of the query. So we're going to put inside of here, format. I'm going to call it, we're going to provide a normal string. Inside there, we're going to put in create role, and then %i with login password %l. And notice that the I and the L are capital letters. Then after that query, we're going to put in a comma, and then we're going to list out the two values we want to have substituted in for that %i and that %l. So we want to substitute in role name and role name. The %i means that we want to substitute in something that's going to be an identifier. %l means we're going to substitute in something that's going to be a literal value. So this is how we use the format module to still do some kind of escaping when it involves a literal, or excuse me, an identifier. Now let's do the same thing for creating the schema as well. So I'm going to delete the whole query and replace it with format. And then, what was this one? Create schema, %i, authorization, %i. And then role name and role name. Okay, so let's save that and go run our tests again. Okay, looks like our test is passing still. So, very good. But now we have definitely no chance whatsoever of any kind of SQL injection here. Again, wasn't really an issue to begin with, but now we're 100% sure of that. Okay, so good improvement. Quick pause right here. Couple more improvements in the next couple of videos. Well, our user test file is looking pretty good, and we've now got a ton of logic inside of here that we probably want to make use of inside of our other test files. So in other words, we probably want to have an identical before all statement inside of our users2 test file and users3 as well. We could definitely just copy paste this entire before all, but then we would have some duplicated code between our different test files. So rather than just copying the entire before all, let's make a helper file that will have some code inside of it related to setting up our database to be ready for some different tests. So inside of my test directory, I'm going to make a new file called context.js. The idea of this file is it's going to make some kind of instance of a class that will serve as the context, or essentially as a place where we can store a lot of different helpers and whatnot for all of our different test files. Inside of here, I'm going to make a class called context, and then export that class at the bottom right away. Now, I'm going to be totally honest with you. This class context is going to have some slightly advanced code inside of it that is really not at all related to Postgres in any way, shape, or form. It's really more related to how we set up a test suite and run tests and stuff like that. So we're going to go through the implementation of this class very, very quickly. We're essentially going to copy paste some code around and reorganize it. And by the end, we're going to have something that works really well. And I'm just going to kind of leave it up to you to figure out how this thing works. At the end of the day, it's going to be really simple in its functionality. But just because there's going to be a lot of code that we're moving around really quickly, that's the reason it's going to be just a little bit complicated. So having said that, let's get to it. The first thing we're going to do, we're going to add in a static method to this class with async that we're going to call build. Inside of here, we're going to place all the code that we just wrote out inside of that before all statement back inside of our test file. So I'm going to go back to my test file. I'll find the before all. I'm going to take everything from that first comment down to the very bottom of that function. I'm going to cut all of that, go back over to my context.js file, and paste all of it inside of build. And then fix up the indentation just a little bit. Next up, at the very bottom of the build function, so here's the very bottom of the build function right here, I'm going to return a new instance of context, and I'm going to provide the role name that we had randomly generated to it. Then outside the build function, we're going to define a constructor. This will accept that role name, it will assign the role name to the role name property, like so. And then finally, at the very top of the file, we're going to add in a couple of different require statements. So at the very top, we will add in all the different require statements we need to make this build function work as expected. So we definitely need the random bytes function from crypto. We definitely need format from PG format, and then default migrate from node PG migrate. We also are making use of pool inside of here as well, so let's make sure we require in our pool too. Now back inside of our users test.js file, I'm going to clean up those 3 require statements that we don't need anymore. I'm going to require in the context class that we just created. And then inside the before all, we're going to create an instance of context by using context.build. And I think that should be enough to actually get us started and run the test successfully at least one time. I think so anyways. We'll see if I'm actually right or not. So let's save this as it stands right now. I'm going to go back over to my terminal and run my tests. So I should see at least that one test file of users test.js passing, and yep, it looks like it is. Looks like everything is still working as expected. So now you might be kind of curious, why did we create context at all? Why does it have the build function? Why is any of this going on? Well, remember, as we start to create all these different test files and run our tests, every single time we run a test, we are creating a different schema inside of our database. So over time, as we start to run our test suite many, many times, we're going to be creating many different schemas and many different roles inside there as well. So we probably want to make sure that we do some cleanup after ourselves when all these tests are complete. We probably want to make sure that we go into our test database, delete the schema we had created, and delete the role as well. So we can do that very easily by now adding a method to this context class. We can let's take a pause right here, and I'll show you how to do that in the next video. Let's add in a method to our context class that's going to automatically clean up after ourselves. So in other words, we want to delete the role that we had created and the schema that goes along with it, so that we don't just keep accumulating roles and schemas every single time that we run a test. So back inside of my context.js file, I'm going to go down to the very bottom, and I'm going to add in a new method called close. So inside of here, we're going to do a couple of different things. We're going to first disconnect from PG. We will then reconnect as our root user. We'll then delete the role and schema that we had created. And then finally, we will disconnect again. So why are we doing the first disconnect and reconnect? Well, remember, the entire goal here is to clean up after ourselves. We want to delete that role and the schema we had just created. Whenever we call close, we will probably already be connected as that role that we're trying to delete. As you'd guess, we can't delete a role that we are currently connected as. That doesn't really make a lot of sense. If we try to delete a role that is currently in use, because we are connected to the database as that role, we would end up with an error message. That's why we are doing the initial disconnect and then reconnect as our root user. Okay, let's put in some implementation. So I will do an await pool.close. We'll then do a await pool.connect. And we're going to connect as our root credentials. So the root credentials, we can really just do a copy paste from earlier on up here. So it will be whatever your root user and password are. And you'll notice that we are starting to reuse these credentials quite a bit. So I'm going to cut those out and then make a variable at the very top called default ops or default options. Now we can more easily make use of these connection settings all over the place without having to paste them again and again and again. So I'll then put in default ops right there from where I just pasted it or cut it. And I'll make use of it down inside of our connect statement as well. Like so. Okay, so next up, we'll write out a query that will delete the role in the schema we just created. So we'll do an await pool.query. We will again make use of that format function just to avoid any possibility whatsoever of any kind of SQL injection. So the actual query that we're going to run in this case will be drop schema %i and then cascade. And don't forget, we're going to put in some argument for that %i right there. So the schema that we want to delete is this .role name. And then we'll do another query to delete the role itself. So drop role %i and put in this .role name as well. And then finally, after we've done that cleanup, we can then disconnect altogether. So we'll do an await pool.close, like so. Okay, so that should be it. So let's now go back over to our users test.js file again. So we've now got context, and we want to call that cleanup function after all of our test files inside of here, or all of our tests inside the single file have been executed. So in other words, we need access to this context variable inside of after all. Remember, after all gets executed after all of our tests inside of here have been ran. So to get access to that variable, we're going to define a variable outside just to get the scope put together. That before all, rather than declaring a new variable called context, we're going to assign the context we just built to context. And then finally, inside of after all, we'll return context.close like so. Okay, so now let's save this. Let's go back over to pgadmin really quickly. I'm going to refresh my schemas category right here, and you'll notice that I now have 9 schemas because I've ran all my tests about 9 times or so. So if I now run my tests again, I should not see an additional schema created. It will be created, but then it'll be almost instantly deleted after our test file has ran. Let's go and run our tests. Okay, looks like the test passed. So hopefully we did call that close function. So I'll go back over to pgadmin. I'm going to refresh schemas again, and I still only have 9 schemas. Perfect. So that means we are now correctly doing all that cleanup. Now, if you want to, you can manually delete the remaining extra schemas we have inside of here beyond just the public one. So for each of these randomly generated ones, we can right-click them, and then in this case, we're going to do a drop cascade as opposed to just a delete/drop. So we can go through. This is totally optional. I'm just assuming you might want to clean up. I'm going to delete all the rest of these very quickly. And one more. And I'm also going to delete the test one down here that we had created a little bit ago as well. Okay, so now we're back to just one schema. So this is looking pretty good. Okay, so now that we've got this nice context thing put together that will automatically set up this entire kind of connection and all this infrastructure around the database and then clean up after ourselves, we can now start to make use of all this stuff inside of our other 2 test files. So let's start to do that in the next video. All right, my friends, let's take this entire same context stuff out of our users test file, and we're pretty much just going to copy paste it over into our other 2 test files. So I'm going to take everything from the const context require statement right there, all the way down to the bottom of our after all. I'm going to copy all that. I'll then take it over to my users test2 file, and I'm going to replace the existing before all and after all with it. I'll then do the same thing inside of the users3 test file as well. So there's the after all and the before all. I'm going to delete it and do a paste. After making both those updates, let's now go run our tests again, and we're going to expect to see all 3 tests passing now. Because now they are all running totally isolated in their own separate schemas. And it looks like everything worked as expected. And now we can run these tests as many times as we want, and everything passes. Awesome. Okay, we should also be able to go back over to pgadmin, refresh schemas, and see that the schemas that were created automatically got cleaned up as well. So I would say that this is a pretty good success. There is one other quick improvement I want to make, however. This is totally optional. It is not actually required for what we're doing right here. One thing that we might want to do is to make sure that after every individual test inside of a file, we might want to delete all the data inside of our database. To do so, we could just do a very simple drop all records, or essentially delete all records out of all of our different tables. That will make sure that if we create any records inside this test file and then this test right here, and then run some other test right after it, we'll be operating out of a totally clean, fresh slate. We could definitely just recreate our context entirely, but it's slightly faster if we just delete all the data out of our different tables. So we'll just do the slightly faster approach. So to do so, back inside my context.js file, I'm going to add in another method that I'll call reset. And inside of here, I will return a pool.query, and we'll do a delete from users. So essentially, just take a look at our users table, delete every row inside there. If you eventually have additional tables inside of your database, you could just add in more delete statements. So maybe you also want to, say, delete posts and comments and, who knows, images, whatever else as well. But for right now, you and I just have users, so we'll leave it just like that. So now to make use of this, back inside of our users test file, we can add in a before each. And inside of here, we can do an await context.reset. So that will make sure that we delete all the different rows in our different tables before each test inside of this file. Let's just do a quick another run with that. And yep, looks like everything still works. Okay, so this is definitely a pretty good test setup. We've now got some infrastructure put together that allows us to run as many test files in parallel as we want, and they're all going to be running in total isolation. So not only are we going to run our tests very, very quickly, but we're also going to make sure that one test does not interfere with another. So this is a really great setup we've put together.